Welcome. Functional programming is becoming increasingly important in industry, and Scala is one of the most popular functional languages out there. To give you a number, about 500,000 people have already registered for the predecessor of the Scala course on Coursera. Scala is special since it fuses functional and object-oriented programming in a practical package. It interoperates seamlessly with both Java and JavaScript. Scala is the implementation language of many important frameworks, including Apache Spark, Kafka, and Akka. It provides core infrastructure for sites such as Twitter, Netflix, Spotify, and also Coursera. In this course, you'll discover the elements of the functional programming style and learn how to apply them usefully in your daily programming tasks. You'll also develop a solid foundation for reasoning about functional programs by touching upon proofs of invariance and the symbolic tracing of execution. The course is hands-on. Most units introduce short programs that serve as illustrations of important concepts and invite you to play with them, modify, and improve them. The course is also complemented by a series of programming projects as homework assignments. What about the recommended background? Well, you should have at least 1 year of programming experience. Proficiency with Java or C# is ideal, but if you're experienced with other languages such as C, C++, Python, JavaScript, or Ruby, that's also sufficient. You also should have some familiarity using the command line. Welcome to my course on functional programming principles in Scala. As the name implies, we're going to do quite a bit of Scala programming, but that's not the primary objective of the course. The primary objective is to teach you functional programming from first principles. You're going to see functional programs, methods to construct them, and ways to reason about them. You're going to find that functional programming is a paradigm that's quite different from the classical imperative paradigm that you know from languages such as Java or C. In fact, you can combine the two paradigms, and it's one of Scala's strengths that it provides a gradual migration path from a more concise Java-like language to full functional programming. But in this course, we're not going to be gradual. We're going to take a clean break. I'd like you to suspend for the time being most of what you know about programming and look at programs with fresh eyes. That way, I believe you'll be better placed to absorb the new way of thinking promoted by functional programming, and once you've done that, you'll also be able to integrate what you have learned back into your daily programming practice. A couple of remarks on the organization of the course. It will consist of a sequence of videos which will introduce the elements of the course one by one. We'll typically have 5 or 6 videos per week. The videos will often have quizzes where you're asked to fill in some questions. Those questions could be multiple choice, or I might ask you to code something. After the quizzes, you will always see the answer in the videos. Beside the quizzes, there are also assignments. The assignments you have to hand in, and you're going to be graded on them. And if you pass the assignments, then you will get a certificate at the end of the course. The quizzes, by contrast, they're just for your own education. There are no grades for these. So, let's get started. Welcome to this first hands-on lecture on how to do functional programming with Scala. In this lecture, we are going to look at the most fundamental elements of programming. In fact, every non-trivial programming language provides primitive expressions that represent the simplest elements of the language. So that would be something like a number or a string. Then it combines ways to combine expressions like add 2 numbers, concatenate 2 strings, and finally it will provide ways to abstract expressions. Abstracting means we introduce a name for an expression, and then afterwards we can refer to the expression by its name. So a good way to approach functional programming is to think of it as a very powerful calculator. In fact, most programming languages, Scala included, have an interactive shell which is often called a REPL. REPL stands for read, eval, print loop. The REPL lets you write expressions and it responds with the value of those expressions. If you want to start the Scala REPL, you can simply type Scala at the command prompt. So let's do that. We type Scala and we get a REPL. It says here starting .erepl because at the time I record this lecture, we are still having a pre-release of Scala 3 called .e. So we have the Scala prompt, and now we can type expressions like this one here. And the REPL will respond with the value, 232, and also its type, which is int in this case. We'll learn more about types later. But functional programming languages, of course, are stronger than REPLs. For a starter, they also let you define values and functions, and you can give them names. So, for instance, you can write def size equals 2. And now you have defined size, and you can use it in another expression like this one. So how are expressions in a functional language evaluated? In the end, it's of course the computer, but a good high-level way to think about it is in very much the same way you would simplify an expression with a pen and paper. So you would typically take the leftmost operator, evaluate the operands going left to right, and then apply the operator to the operands. If you have a name like size, then you evaluate that by replacing the name with the right-hand side of its definition. So size would be 2 in the example that you saw previously. And the evaluation process stops once the result is a value, and a value for now is just a number. Later on we'll see also other kinds of values. So let's just illustrate that with another arithmetic expressions, 2 times pi times radius, where pi and radius are defined like you see here. So that would evaluate like this. You first take the name pi and replace it by its definition. You perform the multiplication. You take the name radius and replace it by its definition. You perform the multiplication and you arrive at the result. Now let's do something a little bit more interesting. We can also define functions that take parameters. For instance, here's one. Now the REPL responds with a def, the name of the function, its parameter, and its result value. You can write then square of 2. You get 4, you can write square of 5 plus 4, and you get 81. Or you write square of 4, and you always get the result. Of course, we can push this further and now define a function that in turn calls square. So let's call it sum of squares. And we have defined a function that takes 2 double parameters and a double result. So let's look at the syntax of what we've done here. So we can have function parameters. They are given by a name and a colon and a type. And functions can also have result types, in which case also we have a colon at the end and its type. Types for now are basically just primitive types, and those are as in Java, but they all start with a capital letter. So we have int for the usual integers, long for 64-bit integers, float double for floating point values, char for characters, short and byte for shorter integers, and booleans for the boolean values true and false. So let's look at evaluation again. How would we evaluate an application of a parameterized functions? In fact, it's done in a similar way to what we already know from operators. We evaluate all the function arguments from left to right. We replace the function application by the right-hand side, and at the same time, we replace the formal parameters of the function by the actual arguments. So let's do this for the sum of squares example. Let's say we start with sum of squares 3 and 2 plus 2. We simplify the arguments, that simplifies 2 plus 2 to 4. We replace it with the body of the function, and at the same time we replace the formal parameters of sum of squares, which were x and y, by the actual arguments, which were 3 for x and 4 for y. Now we're left with square of 3 plus square of 4. We simplify in turn square of 3, that gives the body of square, 3 times 3, plus square of 4. After simplification, we take the right operand call that expands to 4 times 4. Now we get the result 25. Now this will probably seem completely trivial to you, and you might wonder why I insist so much of the details of evaluation. In fact, it turns out that this evaluation model, which we also call the substitution model, simple as it is universally powerful. That means we can express every algorithm with that model. The idea underlying the model is that all an evaluation does is reduce an expression to a value. It can be applied to all expressions as long as those expressions have no side effects, which means that those expressions are functional or purely functional. The substitution model has been formalized in the lambda calculus, which gives a foundation for functional programming and for programming in general. In fact, the lambda calculus is older than computers are. It was first invented by Alonzo Church, and it was intended as a foundation of mathematics. In fact, a couple of years later, another logician, Kurt Gödel, showed that a complete formalization of mathematics is impossible, so lambda calculus was left as a model more for computable mathematics and for computing. So now that we know what evaluation is, we can ask interesting questions. One interesting question is, does every expression reduce to a value in a finite number of steps? Does every evaluation terminate? So let's think a little bit. Can we find an expression whose evaluation would not terminate? In fact, yes, here is one. So we can write an expression loop. It's of type int, say, and its body is loop. So if we reference loop in an expression, then by our rule, the reference would be replaced by the body, which is again loop. So we get a beautiful and very tight loop of an expression that only evaluates to itself, and therefore evaluation of that expression will never terminate. Another interesting question to ask is whether the evaluation strategy we've seen is the only possible one, or whether there are other possibilities. One particular detail is that our interpreter reduces function arguments to values before rewriting the function application. Can we change that? In fact, yes, we could alternatively apply the function to unreduced arguments. So for instance, if we start with the same expression as before, 3 sum of squares 3, 2 plus 2, then we would get square of 3 plus square 2 plus 2. So I haven't evaluated 2 plus 2, I just pass it like this. And then we would continue as before on the left, and on the right we would now replace square of 2 plus 2 by 2 plus 2 times 2 plus 2. So the parameter of square x gets replaced by the expression, not its value. And now finally I have to reduce the 2 plus 2 here and the 2 plus 2 here, and arrive at the same result. So that alternative evaluation strategy is known as call by name, whereas the one we saw previously is called call by value, because we evaluate things before we pass them, so we pass only values and not full expressions. In fact, it was no accident that both reduction sequences reduce to the same value 25. That's always the case, so both strategies reduce to the same final values as long as the reduced expressions consist of pure functions, no side effects, and both evaluations terminate. So which one is better, call by value or call by name? So you might think that call by value is better because it evaluates every function argument only once. If you go back to the sequence that you saw here, you notice that the evaluation of 2 plus 2 is done twice, because we passed it to square here and here. Now we have duplicate work to simplify 2 plus 2 to 4. Now that's of course in this case completely trivial, but instead of 2 plus 2 you could have an arbitrary complicated expression, and then it starts to matter. So call by value definitely has the advantage that it evaluates every function argument only once. But call by name also has an advantage, which is that, well, if a parameter is completely unused in the evaluation of a function, then the function argument is not evaluated at all. So call by name can evaluate function arguments 0 times, 1 times, or multiple times, whereas call by value always evaluates them exactly once. And sometimes when it's 0, then call by name has an advantage. So let's make a little quiz about that. Let's say you have the following function definition. Def test takes two parameters x and y, and its body is x times x, so y is unused. So for each of those function applications that you see here, indicate which evaluation strategy is fastest. That means has the fewest reduction steps. Call by value, call by name, or maybe sometimes they have the same number of steps. So let's see what the answers will be. If we write test 2, 3, then, well, you have in both cases the evaluation 2 times 2, so they're the same. If we write test 3 plus 4, 8, then call by value is better because the expression 3 plus 4 will be evaluated only once before it is passed into test. If you write test 7 2 times 4, then call by name is faster because the evaluation of 2 times 4 is omitted altogether. And finally, if you write test 3 plus 4 2 times 4, then essentially call by value has an advantage for the first parameter, call by name for the second parameter, and the two cancel each other out. So you will have again the same evaluation complexity. In the last session, you've seen a formal model of evaluation, which we called the substitution model. And you've also seen that there was more than one way to evaluate an expression. We identified two evaluation strategies, which were called call by name and call by values. In this session, we are going to go into a bit more detail about these strategies, in particular with a view on termination. So what we've learned in the last session is that the call by name and call by value evaluation strategies reduce an expression to the same value as long as both evaluations terminate. But what if termination is not guaranteed? In this case, there's an important theorem to remember. The theorem says that if a call by value evaluation of an expression terminates, then the call by name evaluation of the same expression terminates as well. But the other direction is not true. So there are expressions that terminate under call by name and that do not terminate under call by value. So let's try to find such an expression that terminates under call by name but not under call by value. What could there be? Think a little bit. Well, here's a candidate expression. Let's define first. It takes two integers, x and y, and just returns the first one. And now we consider the expression first of 1 and loop. So under call by name, we have that the arguments 1 and loop are passed as they are. So we immediately replace first by its body x, which in this case would be 1 because 1 is the argument that's passed to x. So we evaluate in one step to 1. Under call by value, on the other hand, we evaluate the two arguments first, so 1 evaluates to 1, no problem there. But loop, as we've seen, evaluates to loop. So we get stuck literally in this loop that first one loop always evaluates to itself and evaluation does not terminate in this case. So if you just look at termination, it might seem that call by name is a better evaluation strategy than call by value. But Scala, like most languages, actually uses call by value by default. There are two reasons for this. One reason is that a call by value can avoid sometimes exponentially many reduction steps because it avoids duplication of evaluations. And the second reason is that as long as a language has some imperative side effects, which is the case for Scala, call by value is actually much more predictable than call by name. That means it's much easier to tell when the effects of an expression actually happen if the evaluation strategy is call by value than if it is call by name. So for both of these reasons, Scala uses call by value. But it gives you the choice to choose call by name explicitly, and you do that by adding an arrow in front of a function parameter, as you can see in this example here. So here we have a function const1. It takes a call by value parameter x and a call by name parameter y, because you have the arrow here, and it just evaluates to 1. So now let's look at two evaluations The first evaluation would be of the expression const1 1 plus 2 loop. So loop is in the second call by name position. And the second expression would be the same, but with the arguments reversed. So loop would now be in the call by value position. So let's look at call by name first. So if we start with const1 1 plus 2 loop, then we have to evaluate call by value arguments left to right. So we would evaluate 1 plus 2 to 3. And then, as a next step, we would simplify the call to the body of const1, which is essentially just its first argument. So 3 is the result, but the important thing to note here is it terminates. So let's look at the reversed arguments now. Loop appears in the call by value position. If we have this expression here, then we have to evaluate loop as first call by value argument, and that would just essentially evaluate to itself, which means that we get an infinite sequence of steps where the function just evaluates to itself and evaluation never will terminate. So in this unit, we will learn about two new constructs in our toolbox: conditionals and value definitions. So the first construct is if-then-else. It allows you to choose between two alternatives. And the if-then-else in Scala resembles an if-else in Java, but it's an expression, not a statement. So let me explain what that means. If you have a function like abs for absolute value that takes an x int, and then the right-hand side would be if x greater or equals 0, then x else minus x. So here, that right-hand side, it's an expression. It returns a result. In Java, you would use the if-then-else for a statement that has a side effect. For instance, it would maybe assign to a variable. But that's not available to us in purely functional programming. So of course, a Java buff would know that Java also has a conditional expression. It would look differently. You would write it like this. But that's actually rather cryptic, so most people prefer the if-then-else, and in fact that's the only form that's available in Scala. The x greater than or equals 0 here is a predicate. That's an expression that has Boolean, the type of truth values, true and false, as its type. So you can form Boolean expressions from the two constants true and false, negation, which is expressed with a bang, conjunction, which is expressed ampersand ampersand, disjunction, or, which is represent bar bar, and then you have the usual comparison operators, less than equal, greater than equal, and so on. You will note that that's exactly the same operators as in Java. So that's the syntax of Boolean expressions. What about their semantics or meaning? In fact, we can express the meaning of a Boolean expression by giving a reduction rule, similar to the simplification rules that we've seen so far. So here we would say that not true gives false, not false gives true, then true and some arbitrary expression gives that expression, and false and some arbitrary expression always gives false. True or some arbitrary expressions gives true, and false or some arbitrary expression gives that expression. So why did I write it this way? Well, one particularity here is that for these evaluations, you don't need to have a value here. I said it's an arbitrary expression. So if I have something like, let's say, true or loop, where I assume now that loop is a function defined on booleans, but that's still loops. So is that an expression that will terminate or not? In fact, it will terminate. I just used the rewrite rule that I have seen here, and I say, well, that reduces to true. So this idea that sometimes we actually do not need to evaluate expressions to know the result is called short-circuit evaluation. And most programming languages have Boolean expressions that use short-circuit evaluation, and Scala is no exception. The difference and the nice part is that instead of having something very operational, we can explain what a short-circuit evaluation is simply by giving the rewrite rules. So, as an exercise, what would rewrite rules for if-then-else be? We have a Boolean conditional expressions, we should fill it with meaning. So let's set that up and say, well, if we have an if-then-else and the condition is true, then that rewrites to the first part, E1. On the other hand, if the condition is false, would rewrite to E2. So much for conditionals. Now, the second construct we're going to look at in this unit is value definitions. So we've already seen that function parameters can be passed by value or by name, as expressions or as values. And in fact, the same distinction applies to definition. What we've seen so far is the def form of definitions, and that one is by name. We said that each time we mention the name, we replace the name by its right-hand side, by the full expression. There's also a val form, which is by value, as the name implies. So, for instance, if you write val x equals 2 and then val y equals square of x, then the right-hand side of that definition will be evaluated immediately at the point of definition. Afterwards, when you write y, you will essentially replace y not with square of 2, but immediately with 4, with the value that you have already pre-computed. The difference between val and def becomes apparent when the right-hand side does not terminate. So if you have a function like loop boolean equals loop again, then if we have a definition x equals loop, then that's okay, but a definition val x equals loop would lead to an infinite loop. So here's my loop function. Instead, our REPL is smart enough to detect that this is an infinite loop, and it warns us with infinite recursive call. But that yellow expression here and the yellow twiddles, that's just a warning. We can still use loop, for instance, like here. And that's fine. So we have defined x to be equals to loop, but we haven't called x, so we are still in the REPL. On the other hand, if we would write val x equals loop, what would happen? Well, nothing. That's the infinite loop for you. We have to take it out with Control-C. And that will lead us back to the command line. So here's another interesting exercise. Write functions and or such that for all argument expressions and xy is the same as x and y, and or xy is the same as x double bar y. Of course, you should use not the double ampersand and double bar in your implementation, otherwise it would be too simple. What are good operands to test that the equalities hold? Okay, so I'll show you how to do it with the AND function, and I leave the formulation of the OR function to you. So here's the signature of AND. It takes two booleans and gives back a boolean. How could we implement it? Well, we're not allowed to use ampersand ampersand, but we can use an if. So let's see. If x, so if x is true, then the AND of true and something else, what did our rewrite tool say? Then it's the something else. And if x is false, then our rewrite tool said that the whole result will be false. Okay, so we have defined the AND function. Now let's test it. Let's see, AND true false. That gives false, and true true. That gives true, and you trust me that the other combinations will also hold. But is that everything that we need to test it with? No, in fact, we should also test it with non-terminating expressions, because short-circuit evaluation can handle those as well, and we said AND should behave just like double ampersand, so it has to handle those. So let's see, what could we do with AND false loop? So that should give false, right? Oops, I haven't defined loop yet, so let's quickly do that. And false loop. Oops, we got non-termination. So where did we go wrong? Well, in fact, it turns out that the second parameter, the y parameter, that one is called by value. And that means that the expression, in this case loop, will be evaluated. And that's not what we want. So let's change that and make it call by name. So we add an arrow in here. And now we test it again. We have to define loop first. And now we can define the test case, and now it works. So with that change in the definition of AND, it turns out that all the test cases that we need actually pass. Okay, I think you're ready for your first example, which is a little bit larger than a single line. What we're going to do in this unit is define a function to compute square roots with Newton's method. So specifically, we define a function def square root, which takes a double parameter and returns a double result, and it calculates the square root of the parameter x. The classical way to achieve this is by a successive approximation technique that dates back to Isaac Newton. So the idea is as follows. To compute square root of x, we start with an initial estimate, let's call it y, and pick y equals 1. And then we repeatedly improve the estimate by taking the mean of y and x divided by y. So let's look at the first elements of the sequence of computing square root of 2. So we start with 1. The quotient then would be 2 divided by 1 equals 2. The mean is 1.5. Our next estimate is 1.5. The quotient is 1.33, and our mean is 1.4167. And you see that it converges actually quite rapidly to the true value of square root of 2. So let's define a program that does this approximation. Our first step towards this program is to define a function which computes one iteration step. So the iteration step, call it square root iter for square root iteration. It takes a guess, an estimate, and the value for which we want to compute the square root, which is called x here. And the implementation says, well, if the guess is good enough already, it means close enough to the real value, then stop and return the guess. And otherwise, we call square root iteration again with an improved guess and the original value for which we want to take the square root. So this example already shows two quite fundamental techniques of functional programming. One is we split our program up into lots and lots of small functions. And the second one is we make use of recursion. Here we have square root iter that calls itself with an improved guess, and unless the guess is already good enough in which it terminates. Recursive functions need an explicit return type in Scala, otherwise the type inferencer will get confused, so we have written :double here. For non-recursive functions, the return type is optional. However, if a function is public, that means used by others than yourself, then it's always good practice to add a return type for documentation. So our high-level design has left two things open. First, how to define is good enough, and second, how to define improve. So let's get to these now. Improve is straight out of the textbook. We say to improve a guess, we take the mean between the original guess and x divided by the guess. So the mean is the sum divided by 2. Guess plus x divided by guess divided by 2. For it's good enough, we have a number of possible choices. Here we pick a particularly simple one, which we will improve on later. So our choice for it's good enough just says, well, take the square of the guess and the difference between the square and the original value, and that must be a small number. So a guess is good enough if the guess multiplied by itself is close to the original value, x. So now we're almost done. We just have to define the square root function, which is square root iteration with the original guess. We pick 1.0 and the value x, and we're done. So here's an exercise for you. I suggest you take out the Scala REPL, type in the function or copy them, and then play with it. So one shortcoming of it's good enough is that it turns out it's not very precise for small numbers x, and it even can lead to non-termination for very large numbers. Can you explain why? So to explain why, you have to know a little bit about floating point numbers. If you don't know anything about floating point numbers, then after you can skip this exercise. Knowledge of floating point numbers will be by and large not necessary to complete this course successfully. Second, if you know what the problem with this good enough test is, can you define a different version that doesn't have the problems? And 3, test your versions with some very small and some very large numbers. For instance, try to take the square root of 001 or something even smaller or something very large or something even larger than that. In this unit, we are going to stay with the square root example and learn several techniques how to organize it better. So, I've written all the essential things we did last week into this editor in a program called square root.scala. So you see here the square method, the square root iter, improve is good enough, and finally square root. We can also add a test method. So here's the test method, and we can also run it. Let's open the debug console here. And that gives us the number, the square root of 2, as expected. Now, things are fine so far, but there's one problem, and that problem is that we have many functions that essentially all sit here, one is equal to the other, and they're all together pollute a little bit the global namespace. So in fact, it's good programming style to split up a task into many small functions. We've seen that in the last week. But it turns out that the names of the functions square root iter, improve, and is good enough, they really matter only for the implementation of square root, not for its usage. So normally we wouldn't like users to access these functions directly. So if a user shouldn't access the functions, then why should they be there, visible and callable to the user? So we can achieve the hiding of the function and avoid namespace pollution by putting the auxiliary functions inside square root. So let me do that in this example. I take square root, put it on top, and then put everything inside. So now it's going to look like this. So here you see that the square root iter, improve, and is good enough. They're now all inside square root, and square root itself, the body of square root, it consists of this last statement, which in turn calls square root iter and starts the iteration. So what we've seen here is a block. A block is delimited by braces. Here's a simple example of another block. It can contain definitions, like a val definition here, or in the square root example we've seen several def definitions. And then it ends in a final expression, and that expression is the result of the block. A block is itself an expression, so a block can appear everywhere an expression can. And furthermore, in Scala 3, the braces are optional around a correctly indented expression that appears after equals, then else, and so on. So we can also write square root like this. We can leave out the braces and have it look a little bit cleaner. So blocks influence visibility. In fact, the definitions inside a block are only visible from within the block. They cannot be accessed from the outside. And furthermore, the definitions inside a block shadow definitions of the same names outside the block. So for instance, in this case here, the value x, it would go to this x, which is the definition inside the block, which is implied by the indentation here. It wouldn't go to this outer x. The outer x is essentially shadowed. So that's a shadow from the inner x that essentially hides the outer x here. So let's put this to an exercise. We have another program here, lots of uses of x and y. What's the value of result in that program? Take a look and digest it a little bit and then answer. The possible answers are 0, 16, 32, or reduction doesn't terminate. So let's see. The result expression consists of the y plus x. So where does the y go to? The y gets access, the y here. It certainly doesn't see the y here because that's a parameter, so it's local to the def here. Where does the x go? Well, the latest definition of the x was here, but again, the x is inside the block, which is implied here, so it's not visible at this point, so it means the x goes here. Okay, so the x is definitely 0 here. What's the value of y? Well, the value of y says it defines its own local x, which is f of 3. F of 3 would be the parameter 3 passed to y, so that would be 3 plus 1 equals 4, and then it returns x times x, so that's 16. So 16 plus 0 is 16, so 16 is the correct answer. So one consequence of lexical scoping is that definitions of outer blocks are visible inside a block unless they are shadowed. And that's actually very useful because that lets us simplify square root by eliminating redundant occurrences of the same parameter, the x parameter, which means everywhere the same thing. So we see here that the parameter x is repeated all over again, and it's always the same value. It's always passed as x again to the result. So what we can also do is we can simply delete it in all the nested occurrences, here, here, and here. And the program would still work. Now we get errors. Why do we get errors? Well, because we have passed it on, and we no longer need to pass it on because it's no longer a parameter. So we can simplify the calling positions as well. And now we have a program which is shorter, clearer, and does exactly the same as the previous one. So far we have seen definitions and expressions, and definitions and expressions together are called statements. And again, so far we used one line per statement. Every statement was on its own line. But in fact we can write more than one statement on a line, but then they need to be separated by a semicolon. So here you have an example. You can have a definition of y, and then you immediately follow that with the expression y times y, but here you need a semicolon, otherwise it wouldn't work. Semicolons can be written at the end of lines, but are usually left out. So if you write this, then that probably means that the person came recently from a language that required semicolons, such as Java, and isn't yet used to the new style. That leaves the semicolons out. In fact, one way to use Scala is very much as an imperative and object-oriented language in the style of, let's say, Java or C#. And if you use it that way, then often people say Scala is like Java without the semicolons because you don't need the semicolons. But in fact, there's much, much more to Scala and to functional programming. So this is essentially just typically the first steps in a long journey towards a completely different programming style. So in summary, you've seen simple elements of functional programming in the Scala language. We've seen arithmetic and Boolean expressions. We've seen if-then-else, conditional expressions. We've seen functions and recursion. And we've seen nesting and lexical scope. You've learned the difference between call by name and call by value, which is two really important concepts. And even more importantly, you have learned a way to reason about program execution, reduce expressions using the substitution model. This model will be an important tool for the coming sessions. So you've seen in the last sessions that recursion is a fundamental tool for functional programming. Whereas in an imperative language, you would probably rather use a loop, like a while loop or a for loop. Now it turns out that recursion and loops have a lot to do with each other, and there is a form of recursion that is essentially exactly the same as a loop. So that form of recursion is called tail recursion, and we're going to find out more about it in this session. Before we do that, let's review again how we treat function applications in our evaluation model. So there's one simple rule. One evaluates a function application f applied to arguments e1 to en by evaluating the expressions resulting in the values v1 to vn, and then replacing the application with the body of the function f, in which the actual parameters, values v1 to vn, replace the formal parameters of f. Now that notion is so important that it warrants to have a notation for it, a specialized notation. So we can visualize that by a rewriting of the program itself. So here we would have a program that has a definition of the function f with these parameters. I've left out the types and the body. And here we have a call of the same function. So that program can be rewritten to a program with the same definition and the same ... in between, the filler in between here. But the call here would be replaced by the body with the substitution where every formal parameter x gets replaced by the corresponding value v. So this notion with this in brackets v1/x1 vn/xn, that means precisely the expression b, where all occurrences of an xi have been replaced by the corresponding vi. And that whole block is called a substitution, and that's where the name substitution model comes from, because essentially that's the core step of evaluation in that model. So let's do an example of this rewriting. We consider a new function, GCD, or greatest common divisor. So the greatest common divisor of two numbers is the greatest number that divides both A and B. And there's a very old algorithm, goes back to Euclid in the antiquities. So that algorithm is like this. It says, well, if the second number is 0, then it's the first. And otherwise, you call GCD again with the first argument is now the second argument, B, and the second argument is the first argument, A, modulo B. So that operator here, the percentage is a modulo operator in Java and also in Scala. So now if we have a call GCD 1421, we can visualize its evaluation as follows. So we start with the call, then we expand it to the right-hand side of GCD. That would be this one here with the correct parameters. We simplify the condition to false. We simplify the if then else. Since it's false, it's the else part. So it's this one here. And we go on into the next call. Now we simplify the argument 14 modulo 21 is 14. And we go on, we expand to the call, we simplify the call, so that's still false, so it's the second GCD, we simplify that as well. We arrive at this GCD 14.7, and so on. So finally we will arrive at GCD 7.0, and that means 7. So this double arrow here means reduction by several steps. So I've left out some steps between here and here, but it should be clear what they are. Okay, so now that we've seen that, let's try another function. Consider factorial. So the factorial function is defined like this. It takes an n, int, and it gives you an integer result. It says if the argument is 0, then the factorial of 0 is 1. Otherwise, the factorial is the number n times factorial n minus 1. So let's consider factorial 4. So that would be the body of factorial that we see here. So there are really two reduction steps. One is the body here, and finally that one reduces to 4 times factorial 3, the right-hand side here. So if we go on, then factorial 3 reduces to 3 times factorial 2. That reduces to 2 times factorial 1. Finally, we have 1 times factorial 0. And finally, we have the argument equals 0, so that would give us 1. And then finally, the whole reduction will go back to 24. So do you see a difference between the two reduction sequences, the one for GCD and the one for factorial? So if we look at the reduction sequence for GCD, we see it's essentially flat. So it will oscillate between if then else's and recursive calls, but essentially the expression we reduce to always follows the arrow immediately. Whereas if we see the reduction sequence for factorial, then we notice that we have deeper and deeper nesting. So we have essentially something that we know already, some operands 4, 3, 2, and then the recursive call of factorial. And here we reach a 4 times level of nesting, and then it unravels again until we have 24. So why is that? Why do we have the difference between those two reduction sequences? Well, if we look at GCD, then we see that GCD calls itself recursively as its last action. There's nothing after the recursive call. The recursive call is at the same time the result of GCD. Whereas if we look at factorial, then we notice that after the call, there's still work to do. We still have to multiply with n. So here the call is not the last action of the body of the function. And that leads to the different reduction traces. If the call is the last action, then essentially the intermediate expression in the reduction has always about the same size. Whereas if the call is not the last thing, then we essentially goes deeper and deeper. And that observation, which we have done on a very high level and on a very abstract level on the reduction traces, translates directly to an observation on the actual implementation hardware. Because for function calls, we have things called stack frames in a call stack, and if a function calls itself as the last action, that stack frame can be reused. We can immediately use the same stack frame for the recursive call, and that is called tail recursion. So tail recursive functions are in essence iterative processes. There's nothing different between a while loop and a tail recursive function. In general, if the last action of a function consists of calling another function, or maybe the same one, then we only need one stack frame for both functions. Such calls are called tail calls. In Scala, because it runs on the JVM, we can only optimize directly recursive calls to the current function. Such an optimization can help runtime speed of the function, and it also can avoid stack overflows. It turns out that in a normal stack on the JVM, you have maybe 2,000, 3,000 recursive calls until you get a stack overflow. So if your programs are large enough and your data structures are large enough that that isn't sufficient, it's very important that your calls are in fact tail calls. So you can, in fact, know that at compile time without running the program, because you can tell the compiler that you require that the function must be tail call optimizable. And you do that with an annotation which is called tailrec. You import it from Scala annotation tailrec, and then you can use tailrec. And that means that if the implementation of GCD for some reason is not tail recursive, then the compiler will tell you. It will give you a warning that says this function is declared tailrec, but it's actually not tail recursive. On the other hand, even if you leave tailrec out, the compiler will still optimize your GCD function to be tail recursive when it can. So basically, tailrec is not a command that tells the compiler it must optimize. It will optimize in any case. It's just essentially a check for you to know that the compiler could actually do that in the end. So an exercise for you, open-ended. You've seen factorial. And we've seen that it's not tail recursive. Can you design a tail recursive version of factorial? In this session, we're going to cover an important concept in functional programming: higher order functions. They let you pass functions as arguments and return them as results. You'll also learn about Scala syntax and how it's formally defined. Finally, you'll learn about classes, methods, and data abstraction through the design of a data structure for rational numbers. In this unit, we are learning several new ways how to compose functions into more interesting functions. The key concept here is called higher order functions. In fact, functional languages treat functions as first-class values. That means, like any other value, a function can be passed as a parameter and returned as a result. And we'll see that this provides a flexible way to compose programs. Functions that take other functions as parameters or that return them as results are called higher order functions. So let's start with an example. Take the sum of the integers between a and b. So we have a function sumInts, lower bound a, upper bound b, and we have a recursive definition. If a greater than b, then the interval is empty and the sum is 0. Otherwise, we take a plus sumInts of a plus 1 and b. Good so far. Now, let's take the sum of the cubes of all the integers between a and b. So the cube function would be just like the square function, only 3 times x multiplied. So some cubes, you could write this: if a greater than b, then 0, else cube of a plus some cubes a plus 1b. Okay. Now let's take the sum of the factorials of all the integers between a and b. So we could write a function sum factorials from a and b, and then it's the same thing here, except where we wrote cube, we write fact for factorial of a plus some factorials a plus 1b. So I assume here that fact is the factorial functions. Now, A mathematician would get bored very quickly, and they would say, well, these are all special cases of what we know as the sum functions, and here's the way mathematicians would write it. So it's a big sigma, and we say the start value is a, the end value is b, and we take essentially the sum of all the values of f of n, where n goes from a to b. Can we do the same in programming? Can we factor out the common pattern? So what varies in these things? Well, the thing that varies is the functions that I pass into the summation function. So what we can do in functional programming is we can make a parameter that is a function. So here we have a new definition of sum that takes now a function f and a lower bound a and an upper bound b, and it has exactly the same pattern as before, only it uses the function parameter f at this position here. So if the interval is non-empty, then we take f of the lower bound, and then we go on with sum of f and a plus 1 and b. So once we have that, we can write our sum functions in this way. We can say, well, sum ints is the sum of the identity and a and b. Sum cubes is the sum of the cube function and a and b, and sum factorials is the sum of the factorial function and a and b, where the ID function is just x, the cube function is x times x times x, and the factorial function is the usual definition of factorial. So what we've seen here is a new type, int to int, and that type is a type of a function. So generally, the type A arrow B is a type of a function that takes an argument of type A and returns a result of type B. So int to int is the type of functions that map integers to integers. So generally, passing functions as parameters leads to the creation of many small functions, and sometimes it's tedious to have to define and invent a name for all these functions using a def. Compare that to strings. We do not need to define a string using def. Instead of def string equals abc println string, we can directly write println abc, because strings exist as literals. Analogously, we would like a literal for a function that let us write a function without giving it a name. And these literals exist. They are called anonymous functions. So for instance, here's a function that raises its argument to a cube. It takes a parameter x of type int and returns x times x times x. So that function doesn't have a name. We haven't given it a name. That's why it's an anonymous function. X colon int is the parameter, and x times x is the body. The type of the parameter can be omitted if it can be inferred by the compiler from the context. And if there are several parameters, they are separated by commas. So for instance, x int, y int, arrow x plus y would be the function that sums its two arguments x and y. Anonymous functions are very convenient sometimes, but they're not essential. In fact, we can always express an anonymous function like this one here using a def. So instead of writing the anonymous function, we give it a name, call it f here, but it could really be any name, write the same parameters, the same body, and then follow that by f, and put it in braces to make it a block. So that's exactly the same as the anonymous function. The name here doesn't matter because it's inside the block, so nobody can refer to it from the outside. Because anonymous functions expand like this to something that we know already, we can therefore say that anonymous functions are syntactic sugar. Syntactic sugar means it makes life nicer, but it's not essential. So with anonymous functions, we can now write sums in a shorter way. So for instance, sum ints would be simply sum functions where the function that we pass is the identity. It takes an x, gives us back the x, and the bounds are a and b. And sum cubes would be the function that calls sum with an anonymous function, and the anonymous function takes an x and returns x times x times x. What you've seen in both of these examples is that we don't need a type for these parameters. That's because essentially the compiler knows that the sum function expects a function from int to int, so it can infer that the parameter must necessarily be of type int. So here's an exercise for you. The sum function uses linear recursion. That means the stack grows as the sum function sums up its operands. Can you write a tail recursive version? So I'll give you a hint. Here's the general scheme, and what you should do is replace the triple question marks with expressions of your own. Okay, so let's see how we would write the body of loop. It essentially follows the scheme that we've seen before. So we say if A is greater than B, then we have the case where essentially we can return what we already computed. And the idea is what we computed, we put in this accumulator, which we call ACK. So ACK is essentially the intermediate result. So we return ACK. And if not, then we go on with the loop. So the loop takes a new lower bound, that would be A plus 1. And it takes an accumulator of the things that we have already summed up. So that would be the old accumulator plus f of a. The initial call, so how do we set off the iteration? Well, we call loop with the original lower bound a. And what is our accumulator? Well, it's the 0 value for the sum, so it's 0. So in this section you'll learn about a particular way to compose and abstract functions that's called currying. Look again at the summation functions, some ints, some cubes, some factorials. Note that a and b get passed unchanged in each case to the sum functions. Now whenever there's a common pattern like this one, you should ask yourself whether it's possible to eliminate the repetition. So can we be even shorter by getting rid of the a and b parameters? At first this looks difficult, but here's an idea. Let's use the fact that in our language functions can return other functions. Let's redefine sum as follows. So here we have the sum function, and it takes now a single parameter, the function f, and it returns a function that takes two ints, which are the bounds a and b, and gives you back the final value. How can we formulate f? Well, f has to return a function. Let's call that sumf. And this sumf function, it takes the bounds, and then it has the usual pattern. So if the lower bound is bigger than the upper bound, it returns 0, and otherwise it returns f of a plus, and now we have the sumf function applied to a plus 1b. So that function captures the common pattern where the two bounds a and b are still left open. They're parameters to the function sumf. So all sum then returns is the sumf function. Sum is now a function that returns another function. So how do we apply sum? Sum now returns a single argument, so we can define a function sumInts that applies sum to the identity function, sumCubes to the cubing function, and so on. So what's the type of sum x to x? Its type is int and int to int. So that's the return type of the sum function. So since these things are functions, they can be applied in terms. So one could write then sumCubes 110 plus sum factorials 1020. All this is possible because we have returned a function that takes the bounds separately. Okay, so you've seen we have now proceeded in two steps. We first define the intermediate functions sumInt, sumCubes, sumfactorials, and then we apply them to the actual bound arguments. You might ask, can we cut out the middleman and avoid the sumInts and sumCubes and so on intermediate functions? And the answer is of course. You can write sum applied to cube applied to 110. Well, let's analyze that a bit further. So we have first the function sum of cube. That applies sum to the cube function, and it returns another function, one that takes two integers which are the bounds. So this sum of cubes function gets in turn applied to the two bounds 1 and 10. So sum of cube is equivalent to sumCubes that you have seen previously, and that function gets applied to the arguments. Generally, function application associates to the left. So if you write sumCube 110, that means you first apply sum to cube, the parents go like this, and then you apply the result to 1 and 10. Now, this might look quite weird to many of you, but in fact there's something that you probably know that is quite close to that and behaves in exactly the same way. What is that? Well, what I have in mind is arrays. In a language like Java or C#, you write array selection with a single argument, and if you have several dimensions, then you write them one after the other with brackets. So Aij would be a selection into a two-dimensional matrix with indices I and j. In fact, you can think of an array as a function from the index to the element type of the array. So here you have the first function application, and here you have the second. Now you might ask yourself, well, if arrays are like functions, then why do we write array application or array indexing with brackets instead of parents? And the answer is no good reason. It's really historical reasons only. So in fact, in Scala, when we will introduce arrays at some later point, you will find that in Scala we will write array selection with parentheses like this, because after all, arrays are morally just functions, and so you should write array indexing as function applications. But we will not see arrays for quite a while because they are a mutable concept, and we want to concentrate on the purely functional aspects of the language first. Now, one downside of this new way of writing functions with arguments given one after each other in separate parameter section is that defining a function like that is a bit clumsy. So this thing is a bit scary, the way we set up these functions. But in fact, the definition of functions that return functions is so useful in functional programming that there's a special syntax for it in Scala and many other functional languages. So for instance, the following definition of sum is equivalent to the one with the nested SUMF function, but clearer and shorter. Here you just write two parameter sections. You write sum takes first the function as a parameter, and then you follow immediately with the second parameter section, a and b, and the result is int, and the body is just what you've written before. So what that implicitly defines is a function that takes a single parameter, f, and that returns a function that takes the two following parameters, a and b. But you don't have to invent a name and an inner function to do it. You can write it all in one line. So let's play with this a little. Let's say you have a function that takes a number of parameter lists. That function would be equivalent, from what we've seen, to a function where the last parameter list becomes essentially this nested function. That's how we have defined this idea of writing many parameter lists on one line. They expand to essentially defining nested functions with arbitrary names. Here the name is g. Or, for short, this thing here is just an anonymous function, as we've also seen. So the function definition that you saw up here would be equivalent to a function definition with one fewer parameter lists that has an anonymous function on the right-hand side. Now we can repeat the process and do that for every parameter list of the function, and that will end up in a function with no parameters at all, that is an anonymous function of the first parameter list, that returns an anonymous function of the second parameter list, and so on. Finally, that returns a function of the last parameter list, and that returns a body e. So that means that theoretically you wouldn't need function parameters in defs at all. All you would need is anonymous functions like that. And that style of definition, function application, has a name. It's called currying, named for its instigator, Haskell Brooks Curry, who was a logician in the 20th century. So it's no coincidence that Haskell is a very well-known functional programming language. It was named after the same logician. In fact, this idea that you can write every function as essentially a sequence of anonymous functions that each take a single parameter goes back even further to Schönfinkel and Frege, but the term currying has stuck. So let's look at the sum function again. Given this function here, what is the type of sum? Well, we can read it off the parameter list. It takes a parameter of type int to int. Then it takes two parameters, which are both ints, and then it returns a result of type int. So if you're picky, you might want to write parentheses around here, because the thing in the red parentheses is the result type of the sum function. But in fact, functional types associate to the right That means that int arrow int is in fact equivalent to putting the parentheses here the way you see it here. So these red parentheses can also be left out. So here's an exercise. Write a product function that calculates the product of the values of a function for the points of a given interval, similar to what we did with the sum function. As a second step, write the factorial function in terms of product. And as a third step, can you maybe write a more general function that generalizes both sum and product? Okay, so to solve this exercise, I'm going to make use of a new tool which is called worksheets. So a worksheet is like a REPL, a thing where you can type in definitions and expressions, but it's more like a complete editing surface, and you will see that the answers together with the expressions that you type. So to start a worksheet, we select a new Scala file of type worksheet, and we give it a name. Let's call it products. Okay. So how would I define product? Well, a similar way to how I define sum. If A is greater than B, then the product is empty, so I give you back the unit for products. And otherwise, I apply F to A, and I multiply that with product of F, A plus 1, and B. Okay, so let's test this. Let's say write product of the square function and the bounds 1 and 5. So the worksheet responds and says, well, you've defined an integer and it is 14,400. Once more. Okay, so let's use that to define factorial. So what would factorial be? It's the product of the identity function, so that's x to x, and 1 up to n. So it's 1 multiplied by 2 multiplied by and so on until n. Okay, so factorial of 5, just to test it, would be 120. Okay, so what about the third question? Can we write a more general function that generalizes both product and sum? So what would this function do? Well, essentially it would say, well, we want to abstract over the way we combine things. So we had a plus for sum and a times for product. And also we have to abstract over the case which should be returned when this interval is empty. It was 1 for products and 0 for sums. So let's define a function that keeps both of these values as parameters. So I call this function MapReduce because it takes a map function, a thing that gets applied to every element. That's those things we usually call a map. I call this f here. And it takes a reduce function, which is called combine here, that then takes 2 of the results of maps and combines them into a single int. And it also takes a 0. That's the thing to return in case the interval is empty. And that function returns a second function that essentially takes our interval of bounds from A to B. So I define MapReduce with a helper function that's called recur here, that takes essentially the next value in the reduction to apply. So the pattern of recur is very much like what we've seen before. It says if A is greater than B, then we return the 0, whatever the 0 is. And otherwise we combine the application of f to a, so that's my next value, and the result of recurring with the next step value. Then the result of MapReduce would simply be recur with the current lower bound a, this one here. So now that I have MapReduce, how can I redefine sum? So the sum function would take a function f and its MapReduce of f. The combine function is the function that takes 2 integers and sums them, and the 0 is 0. So let's try it. Let's say we want sum of factorial between 1 and 5. Here you go. So one thing which is interesting for sum is that I haven't bothered writing the two arguments for the bounds, and I don't need to pass them on to MapReduce either, because both sum and MapReduce are curried functions. That means what we do here is we just compute the final function that then works on an interval, and we don't need to mention that interval yet. The interval will be mentioned only later when we apply the result of sum and fact. So how would we define a product function using MapReduce? So let's delete the body here and just take the signature and drop the A and the B. We don't need them anymore. So product would be MapReduce of the function f. Now our combination function is multiplication, and our 0 is 1. Let's put that to the test. Let's say product of identity 1 and 6. 720. Good, so you've seen how we can become very abstract and very concise, defining functions that take functions as arguments and that return functions as values. In this section, we are looking at a somewhat larger example using higher-order functions in interesting ways. The example is about finding fixed points of functions. A number x is called a fixed point of a function if f of x equals x. So f maps x to itself. For some functions f, we can find the fixed points by starting with an initial estimate and then applying f repetitively. So it's x, f of x, f of x, and so on, until the value does not vary anymore or the change is sufficiently small. It doesn't work for all functions, but for quite a few it does. So that leads to the following set of functions for defining a fixed point. The idea is we take a function, from double to double in that case, and a first guess. And then we iterate until we're close enough. So iteration means we define the next function as the application of f to the guess. If we're close enough with the next value, then return the next value, and otherwise iterate recursively. So to find a fixed point, we then iterate from the first guess. The only thing to do is define the function is close enough. So the idea of is close enough was that the difference between x and y divided by x should be smaller than some tolerance. So the absolute value of x minus y divided by x should be smaller than some tolerance, which is some small double value. That definition of is close enough is quite similar to what we did for square roots, but it answers the question that I asked when we did the square root example, that we want a definition for is close enough that's robust for very small as well as very large numbers. So this one is better than what we had before. So let's return to square roots. We can actually use the fixed point function to come up with a new and more principled definition of what the square root function is. So the idea is that if we look at the specification of the square root function, then square root x is just the number y such that y times y equals x. We can also divide both sides of the equation with y. So that means square root x is a number y such that y equals x divided by y. So that means that square root x is a fixed point of the function that takes a y and gives you x divided by y. Indeed, that function would map square root x to x divided by square root x. Well, and that's just square root x. So a square root x is a fixed point of that function. So now that we know how square roots can be expressed as fixed points, we can try to calculate square root of x by iteration towards a fixed point. So we could try this to say square root of x is simply the fixed point of this function that we've developed previously, and 1.0 as a first guess. Unfortunately, if we try that in a worksheet or REPL, it doesn't converge. It will loop forever. I've copied the fixed point program to a program with a main method test that runs square root of 2. Let's try to run that. nothing happens. So we stop it. Let's see what goes on. We can try to find out what goes on by putting a strategic println statement here. So we want to, for each iteration, we want to print the value that it just computed at that iteration. So to see what comes out of the println statement, I have to add a debug console here. Okay, let's run the program. So we've seen that, okay, it's an infinite sequence of ones followed by twos. So it doesn't converge, it always oscillates between 1 and 2. So here I've written the same thing. If we do add the println to the iterate, then square root of 2 produces as output 2 followed by 1, followed by 2, followed by 1, and so on. One way to control such oscillations is to prevent the estimation from varying too much. A good idea to do that is by averaging successive values of the original sequence. So what we could try to do is take the fixed point not of the function x divided by y, but y plus x divided by y divided by 2. So it's the average of the previous value y and the new value x divided by y. So let's do that and run the program again. Okay, so now we see something much nicer. So after 4 iterations already, we are close enough. So it converges very rapidly. In fact, if we expand the fixed point, replace this call to fixed point by the body by its definition, then we'll find a square root function that's quite similar to what we developed last week. So in a sense, fixed point really captures the essence of what we did with square root and generalizes it to other functions as well. So you've seen in the previous examples that the expressive power of a language is greatly increased if you can pass function arguments. Sometimes it's also useful to return functions as results. For instance, if we look at the iteration towards a fixed point, we began by observing that square root of x is a fixed point of this function. Then we noted that we need to average successive values. And this technique of stabilizing by averaging is quite general. It's general enough to merit being abstracted into its own function. So what would this function look like? Well, average damp would take a function from double to double and an argument of type double. It would return the average of the previous value x and the new value f applied to x. So now that we have average damp, let's rewrite the square root function using it and the fixed point function that we've seen before. What would that look like? Well, here's the answer. Square root of x would be the fixed point of the function y maps to x divided by y subject to average damping. So its fixed point of average damp of the function y goes to x divided by y. I believe you'll agree with me that this expresses the elements of the algorithm, why square root computes what it computes and why it has to be written this way as clearly as possible. So to summarize, we saw last week that functions are essential abstractions because they allow us to introduce general methods to perform computation as explicit and named elements in our programming language. This week we've seen that these abstractions can be combined with higher order functions, function parameters and function results to create new abstractions. As a programmer, one should always look out for opportunities to abstract and reuse. The highest level of abstraction is not always the best, but it's important to know the techniques of abstractions so as to use them when appropriate. By now you have a useful set of tools to work with functions, including higher order functions. It's time to take a step back and summarize what kind of language constructs we have encountered. So when I describe this language construct, I use a formal notation called extendis bacchus now form that describes what's called context-free syntax. Essentially, we describe the language by alternatives, by optional elements, and by repetition, as well as simple elements. We'll see that in the next slide in an example. So let's start with types. What kind of types have we seen? Well, here it says a type is either a simple type or a function type. And a simple type is just an identifier. And a function type is a simple type followed by an arrow followed by a type. Or, that's the bar, it can also be a list of types in parentheses followed by an arrow and a type. So types is a type followed potentially by one or more commas and a type. So if we look at the identifiers that can be types, then what we've seen are numeric types like int and double, and they're also byte, short, character, long, and float. We've seen the Boolean types with the values true and false. We've seen the string type, and then in the compound types, in the structured types, we have function types such as int to int or int and int to int. Later we'll see more forms of types, but for the moment that's all we need. Now let's look at expressions. What kind of expressions are available? Well, the simplest expressions are listed here. They're just identifiers or literals like 5 or ABC. Or you can also have an expression followed by another expression like x dot y. Then expressions can also be formed from operators like minus x or plus x. There's also bang for a not, and there's a tilde for one's complement. Then you have infix expressions like x plus 1. So that would be an expression that consists of an infix expression and an operator, in this case plus, and an infix expression. And finally, you have the conditional expressions like if x greater 0, then minus x else x. So that would be composed of an expression here, and then expression here. And you have function expressions like x times x. So a function expression is given here. It's a list of bindings followed by an arrow and an expression, and the binding is either a simple identifier, what we've seen here, or it's a list of identifiers in parentheses, like in this binding here, where we describe the anonymous summation function. Finally, we have blocks. So a block is listed in braces, like val x equals 2, x times x. So that would be a definition, and that would be an expression. And as we've seen, instead of the braces, we can also use indentation here and here. So these indent, outdent markers, they indicate essentially that here we have the next columns to the right, and here we go left again. So here you see again a list of all the expressions with examples. Finally, a definition. So a definition can be a function definition, such as def square x equals x times x, or a value definition, such as val y equals square of 2. And the parameter of a function definition can be a call by value parameter or a call by name parameter. So that's indicated here by this production for parameter, which says a parameter starts with an identifier, it's followed by a colon, then there's an optional arrow, which indicates a call by name parameter, and finally there's the type of the parameter. You can think of this as the basic syntax that describes the core functional features of the language. So far, all our programming was about functions that were operating on values of primitive data types, such as int or string. This will change from now. We'll introduce ways to introduce new customized data structures. We'll do that with an example, namely rational numbers. So we want to design a package for doing rational arithmetic. A rational number x over y is represented by two integers, its numerator x and its denominator y. Suppose we want to implement addition over rational numbers. Without having a special type for rational numbers, we could still write something like this. Add rational numerator, and it gets the rational numbers in pairs of two integers here and here, numerators here, denominators here, and would give you, according to the formulas, the numerator of the new rational number. And then you'd need another complementary function, add rational denominator, that would give you the denominator. But of course, it would be really difficult to manage all these numerators and denominators separately. A better choice is to combine the numerator and denominator of a rational number in one data structure. In Scala, we do this by defining a class. Here you see a possible start of a class rational. You see two parameters here, which are the parameters that become the numerator and the denominator. Numerator and denominator are methods, so-called methods inside class rational. So a class definition like rational introduces two entities. It introduces a new type named rational. In the future, one can use rational like one can use int or string. And it also introduces a constructor, also named rational, to create the elements of this type. There's no confusion because Scala keeps the names of types and values in different namespaces. Otherwise put, it's always clear from the context whether we talk about a type or about a value, and constructors form part of the values universe. We call the elements of a class type objects. We create an object by calling the constructor of the class. So rational 1, 2 would create the rational 1 over 2. Once we have a rational number, we can select its members using the infix operator dot. So if x is the rational 1 over 2, then x.numer would give you 1 and x.denom would give you 2. We can now define the arithmetic functions that implement the standard rules. So here you see the formulas for the addition of two rational numbers, subtraction, multiplication, division, and equality. So one way to do that would be to add new functions outside class rational. For instance, the add rational function would take two rationals, r and s, and implement the standard formula for addition. It takes the numerator of the left, multiplies with the denominator of the right, then the numerator of the right gets multiplied with the denominator of the left, and the denominator of the whole thing is the product of the denominators of the two rationals. Another thing we might want to add is a method makeString, which takes a rational number and turns it into a string. So our rational number 1/2 should be printed as 1/2. The way we do that is we use here what's called an interpolated string. That syntax s quote mark to quote has a special meaning in Scala. It means that inside these interpolated strings, anything that follows a dollar is treated as an expression. So it's evaluated, and then the string value of its result is inserted into that string. So what this expression here would do is it would take the numerator, that's 1, convert it to the digit 1. Here it would take the denominator, convert it to the digit 2, and then splice these results into the resulting string with the slash in between. So that's what you will get. Once we have makeString, we can write expressions like this one here. We can add two rational numbers, 1, 2 and 2, 3, and convert the result to a string, and we would expect to see 7/6. One can go further and also package functions that operate on a data abstraction in the data type itself. Such functions that are inside a class are called methods. Rational numbers now could have, in addition to the functions numer and denom, the functions add, subtract, multiply, divide, equal, and toString. So here's a possible implementation. We have the class rational that starts as before, and then we could add a method add that takes a rational number as arguments. So if you have a rational number x and one which is y, then you would invoke it like this, x.add of y. So it's like .numer, but you add an argument here. That means that what the argument here is the right operand of the addition operation, and the left operand is the rational number itself in which the add occurs. So consequently, the formula to create a new rational number, it's almost the same as our previous standalone method add rational, but instead of writing the left-hand side .numerator, we just refer to numerator directly. It's that numerator of the current rational, and we multiply it with the denominator of the other rational number, and analogously for the other parts of the formula. So that was addition. In the same vein, I can define multiplication. And what about makeString? In fact, there is already a standard method toString that all Scala classes support and that you can customize as you want. So the idea is that for rational, we would customize this toString method to just return the interpolated string. So it's numer denom. We could put it in braces as before, but if the expression is a simple identifier like numer denom, we don't have to. So we can write it shorter, just $numer divided by $denom. So one thing to note is that we had used the modifier override in front of the def. That's because, like I said, every class already defines a toString method. And the override modifier essentially states that we do not want this default definition of toString, but we want to use our own in-class rational. So here's how one might use the new rational abstraction. We can define three rational numbers here, x, y, z, and then add x and y, and then multiply the result with z. So in each case, the method gets called with the infix dot, and the argument of the method is just passed as you would pass a function argument. So let's put this to the test. I have defined my class rational. I've added a multiplication method. And now let's just define three numbers and add them and multiply them. So what we see is not very comprehensible. So what we got here is actually the toString that the class rational got by default. It's so-called inherited from class Java-lang object. And that one is not very nice because basically it just tells you what the type is and then it tells you a hash code afterwards. Not something for human consumption. So what we need to do is we need to add the toString method as indicated. So we say def toString equals interpolated string of numer and then denom. And then we get an error that says we can't override this method toString of class in class any because we need an override modifier. So the compiler helpfully tells us that we are changing the default behavior and we have to be explicit about it. And once we do that, then we get still not quite the right thing because we forgot to put a dollar here. So let's do that. And now everything looks nice and tidy. So let's finish this session with an exercise. In your worksheet, add a method neg to class rational that's used like this. x.neg should evaluate to -x. Once you've done that, add a method subtract to sub to subtract two rational numbers. And as a test, you might want, with the numbers x, y, z as given in the previous slide, try out the expression x minus y minus z. So let's get to that. How would we define the neg operation? Well, a simple way to do it is to just create a rational with the negated numerator and the denominator. Okay, now for subtraction. So we subtract a rational from the current object. Well, we could alternatively write a expression just like this one here, except with a minus, or maybe more elegantly, we just make use of neg, so it would be add r.neg. So we add the negated rational, and that gives us subtraction. Now let's do the x subtracted by y subtracted by z. And that gives us the result that you see here. So in this unit we are going to learn about data abstraction. So the previous example has shown that rational numbers aren't always represented in their simplest form. For instance, we saw a rational number 66 to over 42. So you might have expected to see 33 over 21 instead, which is the same rational number but reduced. The numerator and denominator are both the smallest possible. So what we would like to is simplify rational numbers which means reduce them to the smallest numerator and denominator by dividing both with a divisor. We could, of course, implement this in each rational operation, but it would be easy to forget this division in an operation, and besides, we don't want to repeat ourselves over and over again for each of the implemented operations. So a better alternative is to simplify the representation of the class when the objects are constructed. So the way we could do that is we can define a method GCD, that's the greatest common divisor function that you've already seen in class rational. Now GCD is used only internally, so it's labeled here private. Clients of class rational can't call GCD directly. It's used only for the internal functioning of class rational. Then we have another value, G, which is the GCD of the numerator and the denominator, which is always also private. You shouldn't access it from the outside. And then finally we have the numerator, and the denominator is x divided by g and y divided by g. So that gives us the smallest possible numerator and denominator. So in that example, we have calculated the GCD immediately so that its value can be reused in the calculations of numer and denom. It's also possible to call GCD in the code of numer and denom directly. So here, instead of having a separate variable g, we would just divide by GCD here and here. And that can be advantageous if we wouldn't expect the functions numer and denom to be called very often. It's equally possible to turn numer and denom into vals, so they are computed only once. And that can be advantageous if the functions numer and denoms are called often, which we would expect is the normal case. So the normal case would be a private method GCD, which is called in the initializer for the numer and denom values. So the point is that if you're using rationals, clients of class rationals observe exactly the same behavior in each case. It doesn't matter where exactly you define the GCD, whether you create a separate value to hold it, or whether numer and denom are values or methods. This ability to choose different implementations of the data without affecting clients is called data abstraction. And it's a cornerstone of software engineering, really, because it allows you to adapt and refine the implementation without affecting the clients. You can see locally in a class, you can reason locally about a class without having to keep the whole program in your head and track the side effects that your class might have on all the rest of the program. So another important concept when we talk about objects and classes is the self-reference. Inside a class, the name this represents the object on which the current method is executed. So for instance, if we would like to add functions less and max to the class rational, then here's what we would do. We define the less method as usual. So if we want to say x1 over y1 is less x2 over y2, and that's equivalent to, essentially we just multiply everything by y1 and y2, so that's equivalent to x1 y2 less than x2 y1, and that's what we implemented in this formula here. Now let's look at the max method. To implement max, we would ask whether the current rational number is less than the right-hand side argument. In that case, we return the right-hand side arguments, and otherwise we return the rational number itself. So you can see here that the ability to name the current object with this is essential, because otherwise we couldn't return the current object as a result of an operation. The other occurrence of this was here, where we used the less method on the current object. That one is equivalent to just writing less of that. So in general, a simple name that refers to another member of the class is just an abbreviation for this.m. Thus, an equivalent way to formulate less is as follows: this.numer times that.denominator less than that.numer times this.denominator. So now we have made it explicit everywhere that we mean the current object. But we can also leave out these two references to this and just write numer and denom as before. The meaning is exactly the same. So let's look at more tools that are useful for dealing with data abstractions and classes. Let's say in our class rational we want to require that the denominator is positive. We can enforce that by calling the require function. So we could start class rational with a function which is require y greater 0, denominator must be positive. Require is a predefined function. It takes a condition and optionally a message string. If the condition is false, then it throws an exception called an illegal argument exception, and that takes the message string as an argument. Throwing an exception will usually terminate the program with the message string, but there are ways to handle it later, and we'll learn about those later on. For now, we can think of throwing an exception as just a way to terminate the program. Similar to require, we also have the predefined assert function. Assert, like require, takes a condition and an optional message string as parameters. So for instance, we could write val x equals square root y, assert x greater or equals 0. An assertion like this states something that should be true. If the condition is false, then it will also throw an exception, but it's a different one. It's called an assertion error for assert, whereas it was an illegal argument exception for require. That reflects a difference in intent. Require is used to enforce a precondition on the caller of a function. So if require goes wrong, then the fault is with the code that called the function, whereas assert is used to check the code of the function itself. So if assert is wrong, then essentially we have a bug in the implementation of the function. It was called probably with the correct arguments, but the implementation is wrong. So we've seen that a class implicitly introduces not just a type, but also a constructor, a way to construct elements of that class. This implicit constructor is also called the primary constructor of a class. So the primary constructor takes the parameters of the class and executes all statements in the class body, such as the require a couple of slides back, or the value definitions of numerator and denominator, or any other statement that's in the body of a class. So when I said primary constructor, that implies that there could also be other constructors, and in fact that's the case. Scala allows the declaration of auxiliary constructors, which are just methods named this. So here's an example. Let's say we want to have a constructor for a class rational that takes a single argument. So we want to be able to write something like rational of 2, and that should just give the number 2 over 1, so the integer number 2 expressed as a rational. So we can do this by defining an auxiliary method this, that takes the single integer, the numerator, and that creates a rational with the numerator and 1 as the denominator. Now I've put everything we've covered so far in the worksheet with the definition of the class rational. So we have the require, the secondary constructor, the this, then the normalization with GCD, then all the methods, and so on. So in the examples we see that something doesn't work. So what do we see? Well, it said denominator must be positive, but we got 8 divided by minus 21. So the denominator was negative. Where did it go wrong? So that we can debug it a little bit and comment out the thing. So it was the first subtraction that is already the case, that went already wrong. So if we think about it, where could the problem be? In fact, it turns out the problem is in the definition of GCD and the calls to GCD here. Because the definition of GCD assumes that the two operands are both positive. Whereas here the denominator, the y, must be positive, but the x can be negative. So the GCD with a negative number, the way we've defined it, would come out as negative again. And to fix that, we would have to define the absolute value of the x value. So that's in fact the greatest common divisor through which we have to divide. There's no need to take the absolute number value from the y, because the require here already indicates that y must be positive. So with that change, we have that the final expression evaluates correctly without throwing an exception. Another thing you saw is that the class is getting quite long, so it's sometimes hard to see where it ends. And to help here, there's a way to specify that. So in Scala you can write a so-called end marker, which tells you what's the end of the class. If you get the column wrong, like this, then you would get an error which says that the end marker is misaligned. So the end marker has to start at exactly the same column as the class that it closes. So generally, an end marker is followed by the name that's defined in the definition that ends at this point, and it must align with the opening keyword. In this case, the end must be in the same column as the class. End markers can also be used for other constructs. For instance, they can be used to terminate a def or a val, like what you see here, or to terminate a control construct like an if-then-else that spans several lines. If it's a control construct that's terminated, you follow the end by the name of the control construct instead of the name that's being defined, because of course for control constructs there is no name that is defined. So here's an exercise for you. Modify the rational class so that rational numbers are kept unsimplified, so no GCD, but the simplification is applied when numbers are converted to strings. Do clients observe the same behavior when interacting with the rational class? Yes, no, or the third choice is yes for small sizes of denominators and numerators and small number of operations. So let's see. We would delete the simplifications of the numerator and denominator. They're now unsimplified, and we would add the simplifications when they are printed. That's all we have to do. Now in this example we see the same output, so the question is that always the case? Let's think a bit about it, and I believe the fair answer is really 3. For small sizes of denominators and numerators you wouldn't see a change, and as long as the number of operations is small. Why would you see a change if denominators and numerators can get very large? Because of the problem of overflow. If the rational numbers are not simplified, the denominators and numerators can get increasingly larger until they don't fit into the range of an integer anymore. In this unit, we're going to look at how operations on objects evaluate, and also we're going to learn some handy new syntax for defining operators. Previously, we defined the meaning of a function application using a computation model based on substitutions. Now we extend this model to classes and objects. The first question is, if we have an instantiation of C to E1 to En, how is that evaluated? And the answer is, well, the class arguments E1 to Em are evaluated just like the arguments of a normal function. And that's it. The resulting expression is already a value. So if V1 to Vm are values, then passing them to a class constructor C gives you another value. Now let's suppose we have a class definition of a class C, which takes formal parameters x1 to xm, and it has a method f, which takes another set of parameters y1 to yn and has a body b. For simplicity, we've omitted the types of the formal parameters because they're irrelevant for the discussion here. The question is, how's the following expression evaluated? C applied to some values that are the class arguments, select f and then applied to some further values that are the method arguments. The answer is that we can rewrite that expression using substitutions, and in this case we actually need 3 substitutions. Let's analyze them one by one. So the first substitution here passes the actual function arguments for the formal parameters of the function, as we do that for normal functions. The second substitution passes the class arguments v1 to vm for the class parameters x1 to xm. And the final substitution passes the class value c1 to vm itself for any references of this in the body. So let's see that with some examples. Let's say we have rational 1, 2 dot numer. So that would be, according to the definition, substitute 1 for the class argument x, 2 for the class argument y. There are no function arguments, so the second substitution is empty. And finally, substitute rational 1, 2 for this in x. So that gives simply 1 because x gets substituted by 1, as expected. So let's do a more complex example. Let's say rational 1, 2 dot less rational 2, 3. What would that evaluate to? According to the definition, we again pass 1 for x, 2 for y. Then the argument of less is the rational number 2, 3, so that gets passed for the formal parameter that. And the rational 1, 2 gets passed for this. And the body of less is that expression that you see here, this dot numer, that denom, less than that dot numer, times this dot denom. So that then would substitute to rational 1, 2 dot numer times rational 2, 3 dot denom, less than rational 2, 3 dot numer times rational 1, 2 dot denom. And if we apply the definitions of numer and denom, that would substitute to 1 times 3 less than 2 times 2, and then to true. So you see that calls of methods can be described very much like calls of normal functions, only that now we have not just the substitution of actual arguments for formal parameters, we have a similar substitution for the class arguments and the class parameters, and finally we have the substitution of the left-hand side from the dot, that value here, for the reference to this in the class. So here's a variant of what we've seen before. So far we defined all the methods of a class inside the class. That can lead to very large classes, and it's not very modular. A lot of the methods we defined don't really need access to the internals of a class. They could have alternatively be defined as so-called extension methods. For instance, we could ask further methods, call them min and abs, to class rational like this. So now we are outside class rational, but we define an extension of a rational number r, and we add the two methods min, that takes another rational number with the usual definition, and abs, that takes a rational number and gives you the absolute value of that rational number. The advantage of using extensions instead of class methods is that you can define an extension anywhere. You can define it together with the class, but you can also define it in different modules, and there can be different people who can define different extensions of the same class without having to step over each other's feet, changing the same source code. Extensions of a class are visible if they're defined together with the class, or if they're visible in the current scope where they're defined or imported. And members of an extension of a class C can be called as if they were normal methods of that class. So for instance, you could write rational 1, 2 dot min, rational 2, 3, no matter whether min was defined as a method of class rational or as an extension of it. So the idea of an extension is that it adds new functionality to a class without changing existing functionality. That has two consequences. The first is that extensions can only add new members, new methods, not override existing ones. And the second is that extensions cannot refer to the internals of a class or to other members of a class via this, because this is not available in the extension. You see the instance from the outside, not from the privileged access that can see this. So if we look at the operations of extension methods using substitutions again, then we find that extension method substitution works basically like normal substitution, but instead of this, it's now the extension parameter that gets substituted. And furthermore, since class parameters are not visible, they don't need to get substituted at all. So we see here this example for the extension. So what happens here is that the value to the left of the dot replaces the extension parameter, that was r, and the argument rational 2, 3 replaces the method parameter of min, that was s. And under these replacements, we replace the call with the body of min, which is this expression here. So if we perform these substitutions, we get what we would expect, this expression here. Here's a final tweak to make dealing with rational numbers more convenient. In principle, the rational numbers we've defined by our class rational are as natural as integers. But for the users of these abstractions, there's still a noticeable difference. For integers, we would write x plus y, but for rational numbers, so far we wrote r.add s, so we used method syntax. And that's in a sense a shame. If rational numbers are as natural as integers, then we should be able to use the same natural and convenient notation for dealing with them. And in fact, in Scala we can do that. We can eliminate the difference. And to do that, we proceed in two steps. The first step is to relax the notion of what an identifier is. In fact, in Scala, an operator such as plus or less counts as an identifier. So in general, an identifier can be alphanumeric. It starts with a letter followed by a sequence of letters or digits, or it can be symbolic. It starts with an operator symbol followed by other operator symbols. It's also possible to combine the two. You can have an alphanumeric identifier that is followed by an underscore and then followed by some operator symbols. So all these would be valid identifiers in Scala. x1, asterisk, then this funny thing here, probably not recommended to use that, vector underscore plus plus or counter underscore equals. Since operators are identifiers, it's possible to use them as method names. Here we use plus and times as method names for an extension of class rational. So plus is just an alias of add and times is an alias of multiply. You could also use plus and times as methods in class rational itself, so that's your choice. Here we have made the choice to use the operator names preferably as extensions. The second step is that an operator method with a single parameter can be used as an infix operator. So for instance, you can write r plus s, and what it means is you call the method plus on the left-hand value r with the argument s. The two are completely interchangeable. Likewise, r less than s is just a shorthand syntax for r dot method call less than with the argument s. So that explains what operators are. They're just essentially a more convenient notation for method calls. We can use the same trick for alphanumeric methods. So we might want to write, for instance, r min s with infix operator syntax instead of r dot min s. If we want to do that, then we have to declare the infix operator with an at infix modifier. So here, to be able to use min like that, you should define min with this at infix modifier as an extension of class rational, and that means it's usable like that. The reason for demanding an explicit modifier is that that enforces a certain uniformity between usages. So we do not want users to essentially freely mix infix and method syntax. So it is the designer of an abstraction and a method that decides whether the method should be called infix, in which case it gets an infix modifier, or whether it should be called as a normal method call, which is the more common case. So once you have operators, you need to worry about precedence. For instance, if you have 1 plus 2 times 3, so how is that parsed? Where do the parentheses go? What Scala does here, it has a fixed order of precedence that depends on the first character of the operator. So the highest precedence is times, divide, and modulo, followed by plus or minus, followed by a colon, equals, bang, less than, greater, and up arrow, bar. And then the lowest precedence are all letters, so min would have a lower precedence than any operator, and the highest precedence are all special characters that are not in this list. You will notice that from here to here, this is actually the same precedence that operators in Java would have. Of course, in Java you have only a fixed set of operators, but their precedence is exactly in that order. So Scala reuses that notion and generalizes it by allowing you to define your own operators that are not only in this set, but can also be use other special characters or be followed with other operator symbols. So here's an exercise for you. Provide a fully parenthesized version of this expression here. Every binary operation needs to be put into parentheses. without changing the structure of the expression. So the conceptual structure of the expression should be the same with or without parentheses. So let's see, how would we go about this? Let's go from highest to lowest precedence. Which of these operators has the highest precedence? It's this one here, because it starts with a question mark, which was not in our list of operators, so all our other special characters have the highest precedence. Question mark is one of those. So that's the highest precedence. We put the parentheses like this. The next highest then would be the plus operation here. So plus, the parenthesis would go like this. The next highest operator is the equals here. That follows up after the plus in our list of expressions. So that would be this expression here. We would do the parentheses like this. That one is followed by the up arrow. And that one is followed by the bar. And finally, less is the operator that remains with the lowest precedence. Over the last sessions, you've learned about objects and methods. So far, these are all instances of a single class. This is going to change in this session. We're going to introduce hierarchies of classes that extend each other. Once we have class hierarchies, an important aspect is the model of evaluation. Now, the actual method might depend on the runtime type of the receiver of that method. This concept is called dynamic binding. It's one of the key aspects of object-oriented programming. You're going to find out how our model of term rewriting already supports this concept. So dynamic binding and term rewriting go very naturally together. In the last units, you have seen a data type rational described by a single class. But there are also situations where it's natural to describe what's conceptually a data type by a hierarchy of several classes. For instance, consider the task of writing a class for sets of integers with the following operations: include and contains. So include takes an integer and returns a set that contains the previous set plus that integer that got added, and contains asks whether a given integer is in the set and returns a boolean. Int set is an abstract class, which is made clear here with this modifier. Abstract classes can contain members which are missing an implementation. In our case, both incl and contains are not implemented. These members that are not implemented are called abstract members. Because abstract classes can contain abstract members that are not implemented, it follows that we cannot create instances of abstract classes because they would miss the implementations. So a call like int set would be illegal. Let's consider implementing sets as binary trees. There are two types of possible trees: a tree for the empty set and a tree consisting of an integer and two subtrees. For instance, the set 1, 2, 4, 5 could lead to the following tree. It could have, let's say, a 4 at the top, and then a 2 and a 1 at the left, and that would be empty, 5, and that would be empty. And the 2 has again two empty subtrees. So that's one possible representation. We start with one of the numbers 4, and then we notice that on the left subtree there are all the numbers which are smaller than the root number, and on the right subtree there are all the numbers that are larger. So that's an invariant that we want to keep for the sets because it makes it efficient to both query with the contains method and add new members with the include method. So let's look at the implementations of the empty set and the non-empty set. The empty set you see here. For it, the contains method is always false. Empty set doesn't contain an element. And the include method would create a non-empty set with the included element and two empty subtrees. So if we start with the empty set and we include 2, then we would get the tree that you see here, 2, empty, empty. Empty sets are a special case of an inset. They're one of the possible implementations, and that we made clear with this extends clause. So we say the class empty extends inset, which means that it conforms to the interface of inset. It implements all the methods that are defined in inset. So now let's look at the non-empty set. It's another extension of inset. It takes an element as the first parameter and two insets as the left and the right subtree. Now let's look at the method implementations. Let's take contains first. So to ask whether the set contains an element x, we ask whether the element x is smaller, larger, or equal to the root element. If it's smaller, then we know that we have to look in the left subtree. If it's larger, we look in the right subtree. And if it's equal, then yes, the set contains the element and we return true. What about include? So include is similar to contains in that we also ask whether the included element is smaller, larger, or equal to the root element lm. If it's smaller, then we insert it in the left subtree. But this insertion, remember we are in a functional language, so this insertion would return a new tree. It wouldn't change anything, and that means that that new tree would have in turn to be wrapped with a tree that adds the element and the right subtree. If the x is greater than the element, then we go analogously on the right element, so we include in the right subtree and we wrap with element left. And if it's the same as the element x, then there's nothing to do. The element is already in the set and we can return the set itself. So let's look at the operation on include with this set that we have formed here. Let's say we want to include the element 3 in the set. How would we go about it? So we would ask, is 3 greater or smaller or equal to 4? Well, it's smaller, we go to the left subtree. It's greater than 1, so we go to the right subtree. It's greater than 2, so we go on the right subtree. Now we have an empty tree, and empty tree include would then give us 3 empty empty as the new subtree. So now we wrap with 2 and the empty set. Now we wrap with 1 and its left empty set. And finally we wrap with 4 and its right tree. So we formed a new tree. We left the blue tree alone. We formed a new overlaid tree, which is the red tree, that now contains 3 as well as the elements that are in the blue tree that are reachable through the blue tree. At the same time, the red tree doesn't completely copy the blue tree. It contains some elements that are left untouched. For instance, this subtree here. That's now a part of the blue tree, and it's a part of the red tree. So this idea that we can create new data structures from old ones without changing the old ones incrementally is called persistent data structures. Because the old one persists. We just create new ones out of the old ones, and it's one of the standard techniques in functional programming. Some more terminology. Inset is called a superclass of empty and non-empty, and empty and non-empty are subclasses of inset. In Scala, any user-defined class extends another class. If no superclass is given, the standard class object that's defined in the Java package Java lang is assumed. The direct or indirect superclasses of C are called the base classes of C. So the base classes of non-empty would be first inset and then object. We've seen that there are overall 3 defs for contains and incl. One pair was abstract, that was in the class inset, where we have left out the implementations. And then there were 2 implementations, one for in class empty and the other in class non-empty. In that case, we say that the definitions of contains and incl in empty and non-empty implement the abstract functions in the base trait inset. It's also possible to redefine an existing non-abstract definition in a subclass by using override. So if you have, say, a class base, which a concrete method foo and an abstract method bar, then you can define a subclass that extends base, and you can just implement bar like this. But if you want to change, if you want to re-implement foo to be 2 here, then you need the override. So you can't just write def foo, that would give an error. The reason why you're forced to do that is that the compiler wants to make sure you don't have an accidental collision where you just define a method, think it's a new method, but that method accidentally replaces a method in the subclass. So override is essentially an opt-in marker that says that's what I intend. So in the inset example, one could argue that there's really only a single empty inset. It makes sense to have many instances of non-empty insets, but all empty insets really are alike. So it seems overkill that the user needs to create many instances for the empty inset. And in fact, we can express this case better with an object definition. So an object definition would look like this. Object empty extends inset, and then come the 2 implementations of the method, and then comes the optional end marker. This defines a singleton object named empty. The structure is exactly like a class, but instead of a class that needs to be instantiated, an object exists already, and there's exactly one object that exists, which is called empty here. No other empty instance can be or needs to be created. Singleton objects are values, so empty evaluates to itself. An object in a class can have the same name. This is possible since Scala has 2 global namespaces, one for types and one for values. Classes live in the type namespace, whereas objects live in the term namespace. If a class and an object with the same name are given in the same source file, we call them companions. So for instance, you could have a class inset with the usual methods, and then you could have in the same source file an object inset that adds a method, let's say singleton, that creates a set consisting of exactly one given element. A companion object of a class plays a role similar to what static class definitions are in Java. That means in the companion object you would typically put methods that exist only once per class and not once per class instance. Static methods are absent in Scala because Scala is a purer object-oriented language than Java. So in order to emulate what you would do with a static method, you define a singleton object with the name of the class, and you put the methods in that singleton object. So far we've mostly executed Scala code from the REPL or the worksheet, but it's also possible to create standalone applications in Scala. Typically such an application takes the form of an object that has a main method, and the main methods have to follow a particular convention which is inherited from Java. They have to take a single argument of type array of string, and they return unit. A main method then has a body that is executed when the program is called. So you call the program by typing Scala in the command line and then the name of the object. So once this program here is compiled, you can start it with Scala hello, and you would see hello world. So writing main methods is similar to what Java does for programs, but Scala also has a more convenient way to do it, and you've seen it already, that you can have a Scala program, a Scala text, and you can just put in the Scala program a single method that's annotated with main. So that method then also gives you a main method for the program. You can have a method here, let's say birthday, that takes a name and an age, and it prints happy birthday name, age years old already. Once this function is compiled, you can call it from the command line with Scala birthday, and then you pass just arguments for the 2 parameters here, Peter for the name and 11 for the age. And that's what you would get. So typically using main as an annotation is a more convenient way to start a whole or to define a whole program. Under the covers then it will translate into an object with a main method as the JVM prescribes, but you won't see that. That's essentially the compiler wrapping this birthday method for you in a synthetic object that has the correct main method. So here's an exercise. Let's write a method union for forming the union of 2 sets. So you should implement the following abstract class inset as before, but now it has a third method union that takes another inset and returns an inset. So I've prepared a worksheet here where we see the union method up here, and already templates for the union method in empty and non-empty, and so far the implementation is missing, which is indicated by this triple question mark. So the task is to replace the two triple question marks with something that implements union. What's the union of the empty set and another set S? Well, that's obviously S, so that was simple. What's the union of a non-empty set consisting of an element and a left and right subset and some other set S? That's actually harder. So here's one way to do it. The idea is that what we need to do is we need to reduce it somehow to include. So we need to do include with the union of something that is smaller. So one way to do it would be to say we take the left set and form the union with the right set and the union with S, and then we finally include LM in that. So this is very recursive. One union call gets replaced by two more and a call to include. How are we sure that this terminates? Well, the argument here would be to say, well, each of these following unions here, union sets that are smaller than the sets we have started with. So we started with the current set. That set is clearly bigger than left or right, so that union here will essentially work on something which is smaller. And then finally we take the union with S, and that union here has to work on the same right-hand side, but the left-hand side is one element smaller. And then we compensate finally by including the element at the end. So if we do that, then the left-hand side set will get smaller and smaller and smaller until finally it will be the empty set. And when it's the empty set, then okay, then we know what it is. It's just S. So then the recursion terminates. So that's the termination argument, and it's correct. But nevertheless, a call to union like that is pretty inefficient, because essentially we decompose and reconstitute that set multiple times, and it would be much, much nicer if we could simply go through the second set, inset, and say, well, pick all the elements of that set and just include them one by one into the current set. But for being able to do that, we'd have to look inside the second set and say, well, what are the elements of the second set? And so far, that interface doesn't give it to us. So we'll learn techniques to decompose data structures to find out what's inside data structures in the units that follow this one. So one interesting consequence of class hierarchies is that they lead to dynamic method dispatch. That means that the code that's invoked by a method call depends on the runtime type of the object that contains the method. And in fact, that falls out directly from our substitution model. So we can put that to the test and just ask, let's say, for the empty set contains 1. So that would be the contains method in the empty set, which is simply false with these substitutions, and that would give us false. Now, if we use the same method call contains 7 with a non-empty set, then what that would give us is the implementation of contains in the non-empty set. So that's this one here. Subject to the substitutions that substitute formal for actual parameters and that substitute the non-empty set here for this. And we can trace this substitution, and that will eventually give true. So what we've seen here is that the sequence of reductions that gets performed depends on the value to the left-hand side of the method, and that's what we call dynamic binding or dynamic dispatch. So here's something to ponder for you. Dynamic dispatch of methods looks quite analogous to calls to higher-order functions. In each case, the target where the call goes is not obvious from just looking at a single expression. For higher-order functions, it depends what got passed as the actual argument to the parameter. And for dynamic dispatch, it's what is the value to the left of the dot. So the question is, can we implement one concept in terms of the other? Can we implement objects in terms of higher-order functions? Or can we implement higher-order functions in terms of objects? Or maybe can we do both, implement one concept in terms of the other in either direction? In this unit, we are going to learn a little bit more how classes are organized into larger programs. Classes and objects are conceptually members of packages. You can think of a package as similar to a directory in a file system. In fact, packages often correspond one-to-one to directories. To place a class or object inside a package, you use a package clause at the top of your source file. So you write package procfun examples and then object hello, and that would give you an object in the package procfun.examples. Usually you organize your sources so that you would have a directory procfun, and that directory would contain the file hello.scala. So that's the normal way you organize source files, but it's not enforced by the system, it's just a convention. Once you have an object in this package, you can refer to it by its fully qualified name. So to refer to hello, you would write procfun.examples.hello. For instance, to run that hello program, you would write Scala procfun examples hello. Now, to avoid having to write long package names over and over again, you have imports. Let's say we have a class rational in package week 3. We can use the class using its fully qualified name, like this, week 3 rational. Alternatively, you can also use an import. You can say import week 3 rational, and that makes rational known under its simple name here, so you don't need the week 3 dot prefix. Imports in Scala are quite flexible. They come in several forms, so you can either have an import that imports one specific thing, or several things. So import week 3 rational hello in braces would import both rational and hello, or you can have a wildcard import which we write with an underscore. So that third import would import everything in package week 3. The first two are called named imports, and the last is a wildcard import. And you can import from either a package or an object. In fact, conceptually, packages in Scala are just essentially very large objects that have members that are each in individual source files. Some entities are automatically imported in any Scala program. These are all members of the package Scala, all members of the package java.lang, and all members of the singleton object scala.predef. So some of the names you've seen before actually live in these packages and objects and are imported automatically. The int type is really scala.int, so it's defined in the Scala package and it's made available because of this first automatic import. The same happens for the Boolean type and object, which you get from java.lang object. The require and assert methods that we've used in the rational example are actually defined in the Scala predef object as methods, and you get them by the automatic import from the Scala predef object. So they're really Scala predef require and Scala predef assert. You can explore the standard Scala library using the Scaladoc web pages. You can start at this web address. So here we see the root page of the web pages, and we can look for the definition of a type, let's say int. And that would then give us the Scala int type and all the methods that are defined on that int type. So you see the usual suspects, all the operators that you can have on int, and several others more. Another important concept in Scala are traits. So traits are similar to classes. The difference is that in Scala as well as Java, a class can only have one superclass. It can extend only one class. But it often happens that a class has several natural supertypes to which it should conform and from which it sometimes wants to inherit code. In that situation, you could use traits. A trait is declared like an abstract class, just with trait in front instead of abstract class. So here we have a trait planner that has methods height and width, which are kept abstract, and surface, which is defined as height times width. Classes, objects, and traits can inherit from at most one class, but arbitrarily many traits. So for instance, you could have a class square that extends shape, which might be a class, and then it also extends traits planner and movable. Traits resemble interfaces in Java, but they're more powerful because they can have parameters and they can contain fields and concrete methods. Here's an outline of the class hierarchy as seen from every Scala program. The AnyClass has two subtypes, AnyVal and AnyRef. AnyVal is the common superclass of all primitive types. So we have 9 primitive types in Java as well as Scala. They are double, float, long, int, short, byte. Those are the numeric types. And then character, Boolean, and unit. On the other side, are most user-defined types. They are all subclasses of Scala AnyRef, which is just another name, an alias for Java-lang object, the Java's root class. So typical subclasses of object would be string, or Scala classes like Scala list, Scala sequence, Scala iterable, other Scala classes defined by the system or defined by you, or other Java classes. They all inherit from AnyRef aka object. And then dually to the top type any, Scala also has a bottom type nothing. So the nothing type is a subtype of all the other types, and it doesn't have a value. So nothing essentially represents a computation that never returns a value. That could be a computation that loops forever, never terminates, or a computation that finishes with an exception, but not with a normal value return. So the arrows here mean subtyping. That means everything at the bottom of an arrow conforms to the thing at the top of an arrow. There's also the dashed arrows here. They are conversions. So you have implicit conversions along these edges. For instance, you can convert a byte to a short, can convert that to an int, can convert that to a long. You can convert a long to a float or a float to a double, and you can also convert a character to an int. They're similar to subtypes, but there's also a difference. When you have a subtype relationship, the two classes on either end have typically the same representation, whereas for a conversion, the representation changes. Internally, an integer is not represented the same way as a long. A long has twice the bits of an integer, and again, a long is not represented the same way as a float and a double. So let's take a closer look at the top types of this hierarchy. At the very top we have any, which is the base type of all other types. It has methods for comparisons, equals, not equals, or an alphanumeric equals method that's inherited from Java. You can take the hash code of every object, and you can turn every object into a string using the toString method. The two child classes are AnyRef and AnyVal. So AnyRef is an alias for Java-lang object, and AnyVal is the base type of all primitive types. So we've seen also nothing at the bottom of Scala's type hierarchy, which is a subtype of every other type. There's no value of type nothing, but nothing is nevertheless very useful as a type to signal abnormal termination, and also as an element type of empty collections. We'll see that in the next week. Another issue we should briefly touch on are exceptions. So Scala's exception handling is quite similar to Java's. The expression throw exception with a type of an exception aborts the evaluation with the exception XC. And the type of this throw expression is nothing because there's no value that's returned from the expression. So let's finish with an exercise. What's the type of this expression? If true, then 1, else false. Is it int or boolean or anyval or object or any? To answer this question, let's look at the class hierarchy. So we had as the two branches of the if an int and a boolean, 1 and false. So their common supertype is anyval, and indeed that's also the type of the if then else. So anyval is the correct answer here. You might have said, well, why isn't the compiler smart enough to say, well, the condition is always true, so the if statement will evaluate to the first side, which is an int, in which case the type maybe should be int, which is a subtype of anyval, when subtypes are considered as better types of the supertypes. The compiler is intentionally not doing that because it would lead to instability of programs. If you change this condition to something that was less obviously true, some condition P, let's say, then suddenly the type of the if would become less good. It would go from int to anyval, and that might break your program. So that's one of the things where a programmer would know more than what the type system of a compiler actually gives you. In this section, we are going to introduce polymorphism, which is a way to define classes so that they can be used more flexibly. Before we get there, let's introduce a data structure that's truly fundamental for most functional languages, the immutable linked list. An immutable linked list is constructed from two building blocks. Nil is the empty list, and cons is a cell containing an element and the remainder of the list. Let's look at some examples for cons list. The first list is list of 1, 2, 3. That would be represented as 3 cons cells. Each cons cell contains one of the elements of the list, and the remainder is the list that contains the other elements. So the list 1, 2, 3 would start with a cons cell containing the element 1 and would contain as the second half the list 2, 3, and that would contain as the third half the list 3, nil, and that finally has the rest nil. So you construct lists recursively by adding progressively more and more elements at the front. Lists can also contain lists, and they also contain lists of different types. So here we have a more complicated list, a list whose first element is a list that contains true and false, and whose second element is a list of 3. So that would look as follows. So here you see the structure of the second list. Its structure is a cons cell that contains a list as its first element, and the rest of that list would be a list containing 3 as its element and nil as its rest. To represent lists like this, we can define a class hierarchy. For the moment, let's keep it to list of integers only. So we would have a trait int list at the top, could also be an abstract class, and 2 subclasses, cons and nil, that both extend int list. So the nil class doesn't have any arguments. The cons class takes 2 arguments, which is the head of the list and the tail of the list. So that means a list is either the empty list, or it is a cons object that contains a head x and a tail list xs. So we used a new abbreviation here where we defined a val head and a val tail directly as parameters of the list. That just means that the parameters are taken also as fields in the same list. So a val head int, val tail int list means exactly the same thing as if we had defined parameters with some different names, let's say underscore head and underscore tail, and then had defined 2 value definitions, head, which is underscore head, and tail, which is underscore tail. So using vals in parameter position, we can define at the same time parameters and fields of a class, which is sometimes handy. However, it seems too narrow to define only lists with int elements. We then need another class hierarchy for double lists and one for booleans and so on, one for each possible element types. That's clearly not sustainable. So we can generalize the definition using a type parameter. The way we do that is that we add a type parameter, t in brackets, to the definition of class list and the definitions of the 2 subclasses, cons and nil. So type parameters are written in square brackets. That's how you see that you pass a type and not a value. So let's analyze this in more detail. We have a list of t, where t is the element type. Then that has 2 subclasses. Cons of t is a cons cell of type t. That would have a head of that very same type and a tail of type list of t. Whereas a nil of t is another subclass of list of t. Using type parameters, we can give a complete definition of the list class hierarchy as follows. We have a base trait, list of t. It has methods isEmpty, head of type t, tail of type list of t. We have a cons subclass that defines the head and the tail as the parameters that are given. So that would contain already implementations for the head method here and the tail method here, because the value parameter here also defines a field. So all that needs to do is really to define the isEmpty method, which for a cons class would be false. And finally we have the nil subclass of list. For nil isEmpty is true, and for head and tail we don't really know what to do, because nil doesn't have a head nor a tail. So what we do instead, we throw an exception. So if somebody would try to call head or tail on a nil instance, they would get a no such element exception, nil.head and nil.tail. Just like classes, functions can also have type parameters. For instance, we can define a function singleton that creates a list consisting of a single element where we leave open what the type of that element is. That means singleton takes a type parameter t and an element of type t, and it returns a cons instance with that type t and the element and nil as the tail. That means we can now write singleton of int and 1. That would give the list 1 cons nil. Or a singleton boolean and true, and that would give the list cons true nil of type list of boolean. In fact, the Scala compiler can usually find out what the correct type parameters are by looking at the value arguments of a function call. So in most cases, type parameters can be left out. And that means concretely for singleton, you could also write singleton of 1 and singleton of true, and the compiler would figure out that the correct type parameter is int in the first case and boolean in the second. So now that we have type parameters, do we have to change our model of evaluation by substitution? Turns out the answer is no. Type parameters do not affect evaluation in Scala in any way. In fact, one can assume that all type parameters and type arguments are removed before evaluating the program. So type parameters are a compiler-only property. This property is also called type erasure. Types get erased during the compilation process. Many languages that have type parameters use type erasure, including Java, Scala, and most other functional languages like Haskell, ML, or OCaml. Some other languages keep the type parameters around at compile time. These include C++ and .NET languages like C# and F#. When we talk about type parameters, often the word polymorphism comes up. Polymorphism means that a function type comes in many forms. Poly means many and morphism means forms. In programming, that means that a function can be applied to arguments of many different types, or also that a type can have instances of many types. And we've seen those two forms of polymorphisms by now. In fact, the subtyping that arises in class hierarchies means that instances of a subclass can be passed to a base class. That's sometimes called subtype polymorphism. And then we have the second form with type parameters, that's sometimes called generics. That means that instances of a function or class are created by type parameterization. So we can have many different instances that work on different types by passing type parameters. So here's an exercise that uses type parameters. Write a function nth that takes a list and an integer and selects the nth element of the list. So the signature of this function should look as follows. We have def nth, it should take a type parameter t, xs, which is a list of t, and an index n, and it returns t, and you should fill in the body of the function indicated by the 3 question marks here. Elements in a list are conceptually numbered from 0, so nth of a list and 0 should return its first elements. And if the index is outside the range from 0 up to the length of the list minus 1, then an index out of bounds exception should be thrown with a throws statement. So I've copied the list class hierarchy into the worksheet. I've renamed all the class names to all uppercase to avoid conflicts with Scala's predefined list and nil classes. And I've also already given the outline of the nth method with the types as given. And the first clause of the nth method says, well, if the list here is empty, then we throw an index out of bounds exception because we can't take the nth element of an empty list. And then we have two other clauses. One is if the index is 0, then we need to do something, and we need to do something else if the index is non-zero. So what do we need to do if the index is 0? In that case, we return the head of the list, the first element of the list. Okay, and if the index is not 0, then we do a recursive call to nth. With the list would be xs.tail, and the index would be n-1. So we can test this by defining a list of 3 elements, 1, 2, 3, so that would be cons of 1, cons of 2, cons of 3, nil, and take the second, the element at index 2, so that would really be the third element because elements start at 0. So indeed that would be 3. You can test it and say, well, what would we get for the 0th element? Yes, that's 1. What would we get if we put in 3 here? Then we get a red underscore twiggle, and it says that there was an index out of bounds exception as expected, as we have implemented in the nth method that you saw. This section is titled Objects Everywhere. The topic of the section is that this model that values are objects and operations are methods can really be applied quite universally in Scala. So we say a pure object-oriented language is one in which every value is an object. If the language has classes, this means the type of each value is a class. Is Scala a pure object-oriented language? At first glance, there seem to be some exceptions. For instance, we saw primitive types or function types. But let's take a closer look. A class such as int or boolean is represented by the computer quite differently from an object. An object is typically a multi-word record on the heap, and an integer or boolean is just a primitive value that can sit in a register. Conceptually, types such as int or boolean don't receive any special treatment in Scala. They're just like the other classes defined in package Scala. It's true that for reasons of efficiency, the Scala compiler represents values of type Scala int by 32-bit integers and values of type Scala booleans by Java's booleans and so on, whereas a normal object would be represented as some form of record with multiple fields in the heap of the program execution. So for efficiency, the Boolean type maps to the JVM's primitive type Boolean, but conceptually one could define it as a class from first principles. Here's a way to do it. Let's say we are in a package idealized Scala. We define an abstract class Boolean that has a single abstract method called if-then-else. If-then-else resembles an if expression. It takes 2 parts, a then part and an else part, which are both by name parameters, and their type is arbitrary. So if-then-else takes a type parameter t, which is the type of the then part, and the else part. So we'll get to the other operations shortly. Let's skip ahead and see how if-then-else would be implemented. So the type Boolean would have 2 concrete objects, true and false, that both extend Boolean. And for true, if-then-else is implemented to always pick the then part, and for false, the if-then-else would be implemented to always pick the else part. So what we would have as expressions is if we write true dot if then else a b, that always gives a, and false if then else a b always would give b. So what you see is this if then else method is really the same thing as writing if true then a else b. That's what it encodes. Okay, so now that we've seen how if then else is implemented, let's see how we can put it to use. I go back to the previous slide. So the definition of the AND method on booleans would then be AND takes a by name parameter x and it returns if then else x false. So let's see how this would work. So if we have true and let's say false, so that's the same thing as the AND method applied on the true object. That's just what the infix operator and means. And then if you look it up, then the that would be true dot if then else. I abbreviate it like this: false, false, and that would be false because either operand is false. On the other hand, if we do true and true, that would be true dot if then else true, false, and that would be true because if then else on true picks the first argument, so that's okay. You can write by hand yourself the cases false and false and false and true, and you will find out that the answer is always the right one. Similarly, the OR operation would then if then else true and x. The negation would be if then else false and true. So that means if the boolean in question is true, then it returns false. If it's false, it returns true. So equals and not equals can also be defined in if then else, and here you find their definitions. I invite you to try that out for yourself, that you get the right values each time. So here's an exercise. Provide an implementation of an implementation operator for class idealized Scala boolean. So the implementation should be true if A implies B. So A is either false or B is true. So let's see what that would look like. So we can define it as an extension method, def equals arrow between two booleans, and that would say if then else y true. So if A is false, then we return the second part, that's true. If A or x here is true, then y must be true also, so we return the first part. Okay, so you can see that you can define any operation on booleans by instantiating if then else in the right way, where if then else is really just a proxy for the if then else expression that you have with Boolean conditions. So Boolean was a simple class because it had only two possible values, but we can do similar techniques for other classes. So here's a partial specification of the class Scala.int. So int would have methods plus that take an int and give you back an int, but you can have several overloaded variants of such methods. So you can also add an int to a long, giving a long, or add an int to a double, giving a double. Then you have shift operators, you have bit mask operators, and so on. So you have a whole set of these operators that can all be defined as methods on class int. Question: can this class int be represented as a class from first principles? That means not using primitive ints. To answer this question, it's better to look at a slightly simplified version. We look at a class nat for just natural numbers. That means numbers that are non-zero. And we reduce the set of operations that we look at. We want essentially just those 5 operations. An is0 operation that returns whether the natural number is 0. The predecessor of the natural number, in case it is not 0, it can throw an exception for 0. The successor of the number, which gives the next higher number, and then we want to implement addition and subtraction on those natural numbers. And we should do that from first principles without referring to class int or any of the other primitive number types. So what we want to do instead is we want to have a object 0, which is a sub-object of class nat, and we want to have a class successor of n that is another subclass. So successor of n would be the instance that represents n plus 1 for any number n. So this is an open-ended puzzle for you. It's quite a bit more involved than the previous quizzes, but it's quite illuminating if you manage to solve it. So I've given the class hierarchy as specified in a worksheet. We have the abstract class nat with the 5 methods to implement, and then we have the sub-object 0 and the subclass successor, and I've already added the method definitions, but the method bodies are all the triple question mark, which means they still need to be implemented. So let's start with is0. Is 0 for a natural number? Well, if the natural number is 0, then obviously is0 is true, and for the successor it would be false. What about predecessor? Predecessor is defined only for successors. We don't know what it is for zeros. So for the successor object, it would be n. That means the number from which we took the successor, that's the predecessor of that number. What about successor? So successor of a number would be simply we wrap it in successor. So the successor of this number is successor of this, and the successor of 0 is also literally successor of 0, or we can write this because this in this case is 0. What about plus? To add a 0 and any other natural number that, so the result would obviously be that. What about adding a successor to a number that? So here the idea is we can say, well, that's the successor of n plus that. So we take the addition on the number which is 1 smaller, and we form the successor. That's the same thing. So that leaves subtraction. Subtraction on a 0 number, that would be defined only if the that number is in fact 0 as well, because otherwise we would go in the negatives which cannot be represented as natural numbers. So let's write that. So again, I've left the case where the number is not 0 open with triple question marks, meaning that I don't really know what to do there. For successor, what do I do for successor? So I start off in the same way. So if the other number is 0, then this number minus 0 is this number, that's fine. And otherwise, what do I do? So otherwise, I take the predecessor n and I subtract from it the predecessor of nat. And that's it. So we can already test the worksheet. So let's define natural numbers. So I defined 1 and 2. Let's add them. We don't really see much, so what's missing here is we need to add a toString method so that we can actually make sense of these things. So let's add this method as a sixth method. We don't need to add it here because toString is already implemented in object anyway, so we just have to override it in the two implementations here. So for 0, the toString would say 0. And for successor, I can define toString like this. So I literally write successor and then recursively the toString of the predecessor number. So if I do that, I get an error because I forgot the override. Yes, toString needs an override because we've seen that they are already implemented in objects. So now I get something that is more reasonable. I get here the same things that I have defined, and 2 plus 1 is 3. No big surprise. So what do we do with, let's say, 2 minus 1? Just look at that. So that would be 1, also fine. What would we get for 1 minus 2? And that's an error. So what we would get is a not implemented error. An implementation is missing. In fact, the things that we have left open, this triple question mark, is a predefined operation in Scala, which gives you an exception called a not implemented error. So that's a good approximation if you don't want to be bothered defining your own exceptions, which in this case is not really relevant for the project, for the problem at hand. So we've seen how to construct natural numbers from just 3 classes, a base class nat, and then an object 0, and a subclass successor. In fact, that's a well-known concept in mathematics. These numbers are called Peano numbers, after the Italian logician Giuseppe Peano. And it doesn't stop there. You could now also add multiplication, division, or other operations to natural numbers, and you can then extend the concept to more complicated number types, such as integers, or rational numbers, or any other kind of numbers, or really any other kind of data structures. In fact, it's possible to build up the whole of computable mathematics on just this simple basis. Efficiency is another matter, of course. These Peano numbers in their implementation that we've given are notoriously inefficient because even a simple addition would be linear in the size of the numbers. So the bigger your numbers are, the longer you have to hunt down a chain of successors. So while these things are quite beautiful in their simplicity, they're far from an efficient implementation. But that's not a problem. We can very well keep apart the abstract concepts and the actual implementation. One should be simple and elegant, and the other should be efficient and fast. In this session, we're going to take a closer look at the relationship between functions and objects. We've seen that Scala's numeric types and the Boolean type can be implemented like normal classes. But what about functions? In fact, function values are treated as objects in Scala. The function type, a arrow b, is just an abbreviation for the class type Scala function 1 ab, where the class Scala function 1 is defined as you see here. It's a trait. It has two type parameters, a, b, and it has as only member an apply method that takes an a and returns a b. So functions are objects with apply methods. There are also traits function 2, function 3, and so on for functions which take more than one parameter. So much for function types. What about function values? Well, the classical function value is an anonymous function like the one you see here. It takes an x and let's say it squares the x. That function value is expanded to what you see here. It's an anonymous class, function 1, with the type of the parameter and the type of the result type, and an implementation of the apply method. In this case, the implementation of the apply method is simply the body of the anonymous function. An anonymous class like this can itself be thought of as a block that defines and instantiates a local class. So this syntax here is available for any class. You can have new and then a class name and then some method definitions or some other member definitions in a block that follows the class name. Such an anonymous class is a shorthand for what you see here. It's a class with a compiler synthesized name, in this case it's $anonfun. It extends what you wrote here, function 1 int. It has the definition that you give in the anonymous class, and at the end of the block you just return an instance of that class. So an anonymous class like this one creates a class with a name that is compiler generated, doesn't matter, and creates an instance of that class, which is the value of that expression. Now let's look at function calls. So let's say we have a function called fab, where f is a value of some class type. Then that call is expanded to f.applyAb. So we're looking for an apply method that we can select from that value, and that will be the method that gets applied to the arguments ab. So the object-oriented translation of this anonymous function value, followed by this call, would be an anonymous class that you see here, followed by an invocation of the apply method that we have defined here with the given argument. So that means that we can use the same syntax for method calls also in the application of function values. Note that a method that's defined with a def, like this f here, is not itself a function value. But if f is used in a place where a function type is expected, it's converted automatically to a function value by converting the f into an anonymous function that takes a parameter, as indicated here, and applies f to that parameter. So an example where this happens would be the following. So here I've defined a function g that takes a parameter of type int to boolean. And I can pass my method f to g because f can be converted to a value of that type by the conversion that you see here on the left. So let's finish with an exercise in package week 3, where we have defined the inset class hierarchy, define a companion object inset with 3 functions so that users can create insets of lengths 0 to 2 using the syntax that you see here. So that would create the empty set. Inset of 1 would create a set with single element 1, and inset 2, 3 would create a set with elements 2 and 3. So let's see how this would work. So here we have our original inset class and 2 subclasses. Let's create an object inset. And then we need 3 apply methods. So for the empty set, that's simple. That's an apply method here. For a set with 1 element, we take the empty set and include x, and analogously for a set with two elements, we take the empty set and include first x and then y. So far, we were mostly concerned with building up data from objects and functions. You have learned that functions can be data values themselves and have seen the relationships between functions and objects. In this week, we'll shift the focus from data construction to data decomposition. If you have some data, what are good ways to find out what's in it and to act on that knowledge? We'll also look at pure data structures that don't encapsulate any behavior, but exist only for being decomposed. In this unit, we're going to look at decomposition, how to inspect a value and break it up in smaller parts. For instance, suppose you want to write a small interpreter for arithmetic expressions. To keep it simple, let's restrict ourselves to just numbers and additions. Expressions can be represented as a class hierarchy with a base trait expr and two subclasses number and sum. So it would look like this. So to treat an expression, it's necessary to know which shape it is. Is it a number? Is it a sum? And also to access its components. This brings us to the following object-oriented implementation. Here we see a trait expr with 5 methods. Two of the methods allow us to find out what kind of expression it is number or is sum, and the other 3 allow us to access the components of the expressions. In case the expression is a number, num value would pull out its numeric value as an integer. In case it's a sum, left op and right op would pull out the left and right operands. So these 5 methods now have to be implemented in the 2 subclasses of expr. Let's look at class number first. So a number is defined by an integer value. It extends expression. It is a number. It's not a sum. Its numeric value is the given integer, and its left and right operand are both undefined, which we model here by throwing an exception. So that would be an illegal call if the expression is a number. For sum, it goes the other way around. So a sum is not a number, but it is a sum. Its num value would throw an error. Its left operand would give you the first parameter, its right operand the second parameter. With that setup, we can now write methods that operate on expressions. So for instance, here's an evaluation function that evaluates an expression to the integer number it represents. So we would have def eval, it takes an expression, returns an int. If the expression is a number, then return its numeric value. Otherwise, if it's a sum, then evaluate the left operand, evaluate the right operand, and add the 2 values. And finally, in case we find another subclass of expression, we throw an error with unknown expression. Now that works, but there are also problems. One problem is that writing all these classification and accessor functions quickly becomes tedious. It was already tedious for something as simple as an expression with 2 subclasses. We will see how much more tedious it gets once we add further cases to expressions. And the other problem is it's not really very statically safe. There's no static guarantee that you use the right accessor functions. Many of the functions throw exceptions when they're called, which means you don't have a compile time guarantee that your program will execute without exceptions being thrown. So to illustrate the first problem, let's study what happens if we add 2 new expression forms. Say we want to add a product expression that takes 2 operands and a variable expression that takes a string and represents a variable. We need to add methods for classification and access to all the classes defined above, and we have to define the methods for these 2 new classes. So think about it. If we integrate product and variable into the hierarchy, how many new method definitions do we need? I include here method definitions in product and variable themselves, as well as any new methods that we have to add to sum and number, but not the methods that we have already shown on the slides. Possible answers would be 9, 10, 19, or is it 25, 35, or 40? So to come up with an answer, let's look at the existing classes first. we need two new methods, is var and is product, in trait expression that have to be implemented everywhere. And furthermore, if it's a variable, we need a method called var name or something like that to get out its name. And if it's a product, we might need product left op and product right op, but we could maybe also reuse the left op and right op operations here. So maybe there are two more op operations depending on how far we want to separate things. So it makes, depending on how we count, 3 or 5 methods in expr that have to be added also to number and also to sum. So if we do the sums, then depending on how we do things, we need either 3 or 5 methods in addition per existing class, and either 8 or 10 methods in a new class, because a new class has to contain the previous 5 methods that we've seen already as well. So there are 3 existing classes, so that makes 9 or 15, and there are 2 new classes, so that makes 16 or 20. So that means if you do the sums, it's either 25 or 35. And that means both of these answers would be plausible. It's either 25 or 35, which means it's quite a lot. Even at 25, it's quite a lot. Okay, so we conclude that this is not very scalable. What else can we do? So one thing one could try is using type tests and type casts, but I find that quite hacky. So in Scala you can test whether a value is of a certain type with the is instance of operation. So x is instance of t tests whether x is at runtime a value of type t. And x as instance of is a cast. It simply treats an object as an instance of type t and throws a class cast exception if it isn't. These correspond in Java to instance of and to the special cast syntax that you see here. But the use of type tests and type casts in Scala is actually discouraged because they're better alternatives. That's also the reason why we've chosen very long names for them that are intentionally hard to type. So staying with type tests and type casts, here's a formulation of the eval method. But as you can see, it's actually quite ugly. It's also potentially unsafe, because we don't have usually a guarantee that a type cast, which can throw an exception, is always protected by a type test of the same for the same type. That's the case here, but you might easily make a mistake in a larger program. So something which is a more reasonable solution is called object-oriented decomposition. For instance, suppose all we want to do is evaluate expressions. Then we could define an abstract method def eval inside the expression trait itself that gets implemented in both of the subclasses. So for number eval would be n, and for sum eval would be e1.eval plus e2.eval. So this looks quite concise. But what happens if we'd like to display expressions now? Well, we'd have to add a new method in each subclass. Let's say def show here, and we need one here, and we need one here as well. So we need potentially to touch a large number of classes to add some piece of new functionality. So we've seen that object-oriented decomposition mixes data with operations on the data. The data are the fields and the classes, and the operations are the methods. This can be the right thing if there's a need for encapsulation. We want to hide the data, and data abstraction. On the other hand, it increases complexity and adds new dependencies to classes. It increases complexity in the literal sense of the word, where in Latin complex means plaited or woven together. Thus, complexity arises from mixing several things together, which is the case for object-oriented decomposition. Of course, complexity is not by itself bad, and often there's no way to avoid it one way or another. But we should use it only if there's a tangible advantage. And the tangible advantage could be that we need encapsulation or data abstraction, or another advantage of object-oriented decomposition is that it makes it very easy to add new kinds of data. Because in that case we just have to invent a new class and give it all the operations that we have predefined, and we're done. Whereas it makes it much harder to invent new kinds of operations. If we want to add a new operation like show, we would have to touch all the classes that we currently have. One other limitation of object-oriented decomposition is that it works only well if operations are on a single object. To illustrate that, think about what you have to do to simplify expressions, say using the rule a times b plus a times c becomes a times b plus c. So we pull the b and the c together into an addition. The problem here is that this is a non-local simplification. It can't be encapsulated in the method of a single object. So you're back to square one. You need test and access methods for all the different subclasses. In this unit, we are going to learn about a functional way to do decomposition, which is called pattern matching. So the task we are trying to solve is to find a general and convenient way to access heterogeneous data in a class hierarchy. The example we had was a class of expressions, and then that had subclasses number and sum, and then possibly others, product, variables, and so on. Our first attempt was to use accessor and classification functions. That suffered from quadratic explosion. Our second attempt to use type tests and typecasts wasn't very safe nor pretty. And the third attempt to use object-oriented decomposition worked in some cases but had limitations. So another solution is to use functional decomposition with pattern matching. This relies on the observation that the only purpose of test and accessor function is to reverse the construction process. Namely, we want to know which subclass was used for the construction of this value and what were the arguments to the constructor. That situation is so common that many functional languages, Scala included, automate it. Scala supports functional decomposition through case classes. A case class definition is similar to a normal class definition, except that it's preceded by the modifier case. So here we have our expression class hierarchy, and number and sum are now case classes. Those two classes are now empty. There are no methods given in either one. So how can we access their members? That's where pattern matching comes in. Pattern matching is a generalization of switch from C Java to class hierarchies. It's expressed in Scala using the keyword match. So for instance, to define an eval function on expressions, what we could do is do a pattern match on the expression in question. There are two cases. If the expression is a number, then we return its numeric value n. If it's a sum over expression e1 and e2, then we evaluate e1 and evaluate e2 and add the two results. So what you see here is that a pattern at the same time identifies a case, number or sum, and names the elements in that case. Here the n for the numeric value, or the expressions e1, e2 for the left and right operands of the sum. So in general, match is preceded by a selector expression and is followed by a sequence of cases that all take the form pattern, arrow, expression. Each case associates an expression with a pattern. If no pattern matches the value of the selector, an exception is thrown, and the exception is of the class match error. Here's a more complicated pattern. So that pattern is formed from a constructor sum that gets applied to arguments. The first argument is a constructor number that gets applied to a variable pattern, so that's a second form here. And the second argument to sum is a wildcard, which says it's essentially a don't care operation. It says it can match anything, and we don't bother to give it a name. Besides these forms of patterns, you can also have constants in patterns, such as 1 or true, and you can also have type tests in pattern such that n:number. So we could, for instance, say here an x:number as the second argument, and that would match any number, so not another sum, and name it x. Variables such as x or n always begin with a lowercase letter in patterns. If they would start with an uppercase letter, they would be interpreted as constants. And the same variable name can only appear once in a pattern, so sum xx is not a legal pattern. Names of constants all should begin with a capital letter, with the exceptions of the reserved words null, true, and false. So let's look at evaluation. If we have a match expression of this form, that expression matches the value of the selector E with the patterns P1 to Pn in that order, in the order in which they are written. And the whole match expression is then rewritten to the right-hand side of the first case where the pattern matches the selector. And references to pattern variables in the pattern are replaced by corresponding parts in the selector. We'll see how that works in an example shortly. So what do patterns match? If you have a constructor pattern like this, then that matches all values of type C or a subtype that have been constructed with arguments that in turn match the patterns P1 to Pn. A variable pattern matches any value and binds the name of the variable to this value. The same thing is a wildcard pattern matches any value and does not bind any name to that value. A constant pattern C matches values that are equal to C in the sense of equals equals. So if we have, let's say, 22, so then that would match the value 22 and no other value. And finally, a type pattern like n number would match any value that is a number and name it with the name n. So here's an example. Let's evaluate sum of number 1, number 2. So as usual, we replace the call to eval by its right-hand side, where the parameter e of eval would be replaced by the argument here. So that gives the argument here in selector position of a match that you see here. Now we match this selector with the patterns one by one. The first pattern does not match because this one is a sum and that one is a number, but the second pattern matches. So we replace that match expression by the right-hand side, this one here, where furthermore E1 gets replaced by the corresponding part in the selector, so that's number 1, and E2 gets replaced by number 2 because that matches this part of the selector. Now to evaluate that expression further, we replace the first call of toEval here by its right-hand side. That would give number 1 match, again the same two cases, and then once we've done that we still have to add with eval number 2. Now we see that it's the first pattern that matches, so number line up here, and the variable n gets replaced by the selector expression 1. So that leads to 1 plus eval number 2, and proceeding in the same way we get eval number 2 gets 2 and the whole result becomes 3. Paramatching functions can be defined anywhere. So far we've defined eval outside the expression type hierarchy, but we could also put it as a method inside trait expression, and in that case the match would be on the current value, so on this, instead of a given parameter. Otherwise it would be exactly the same match. So here's an exercise for you. Write a function show that uses pattern matching to return the representation of a given expression as a string. So we want to write this method, and you should fill in the triple question marks here. Okay, so I've added what we had so far into a worksheet. We have the expression class hierarchy, the eval function. I have a sample expression, which is just 1 plus 1, and we evaluate it. Now we have to define a show function, and the template is quite obvious. We will match on the expression. If it's a number, we have to do one thing, and if it's a sum, we have to do another thing. So if it's a number, what do we need to do? Well, we just return the number here as a string, because that's the result type of show. So it's n.toString. Remember, all values in Scala have a toString object that converts them to a string representation. Or we have a sum expression, sum E1, E2. What do we do in this case? So in this case we return a string that contains the recursive calls of show on the two operands and a plus in the middle. Let's put that to the test. Let's say show of expression. What do we get? We get 1 plus 1 as expected. So here's a second exercise which is a bit harder. Add case classes var for variables x and prod for products x times y as discussed previously. Change your show function so that it also deals with products. But pay attention that you get the operator precedence right and at the same time use as few parentheses as possible. So for instance, if you have a sum of products, then you can leave out the parentheses. That's a valid output. But if you have a product of sums, then you need the parentheses around here, because otherwise you would change the meaning of the expression. Okay, so let's see what we have to add to the worksheet. First, the two case classes. Here's the var class, and here's the product class. How do we change show? So for the var class, we just return the name of the variable. And for the product class, we might try this. So essentially treat it like the sum class. Okay, let's put it to the test. Define another test value, expr1 equals, let's say, product expr var x and show expr1. I forgot to make var extend expression. Good, now we see something. So we have the expr1, but if we show it, then it's actually wrong, because it looks like we multiply x by 1 and add 1, where in fact we wanted to multiply x by 2. So how do we fix that? Well, the problem is that we can't really use show here, because it doesn't put in the right parentheses. So what I propose is we call another function, call it show p, that puts the proper parentheses around the operands of a product. So how do we define show p? So show p starts like show, but says, well, if the result is a sum, then print the expression in parentheses. And otherwise, just show the expression as usual. And now we see that indeed here at the bottom the two parentheses are put in around the right expression 1 plus 1. In this section, we are going to introduce one of the most fundamental data structures in functional programming, which are lists. A list with elements x1 to xn is written list of x1 to xn, like you see here. For instance, here's a list of fruit, list of apples, oranges, pears. Here's a list of numbers. Here's the diagonal of a 3 by 3 matrix. That's a list that consists of 3 lists as sub-elements. And here's the empty list. Lists resemble a lot arrays, which is another fundamental data structure used in imperative programs, but there are two important differences. The first difference is that lists are immutable. The elements of a list cannot be changed after the list is constructed. And the second difference is that lists are recursive, while arrays are flat. So to see that, let's draw the structure of some of the lists that you've seen here. Let's start with the first list of fruits. So you see the fruit list consists of a cell which we call a cons cell, and which we often write with a double colon. That cons cell has a head element which is called apples and a tail which is another list, which has a head element oranges and a tail element which is another list. And that third list has a head element called pears, and its tail is nil. So lists are recursive. Every list contains in its tail position another list that can be nil. So they're a little bit like Russian dolls. Each doll contains a slightly smaller doll inside. The elements of this list are simple values, but it's also possible to design lists of lists. An example is the second list that we see here, diagonal 3. So here you see the structure of diagonal 3. It has at the top level 3 cons nodes, 1, 2, 3, and each cons node has a head element that is another list, one of each of these 3 lists of 3 numbers each. Like arrays, lists are homogeneous. The elements of a list must all have the same type. The type of a list with element of type t is written scala.list of t, or shorter just list of t. So if we add the types to the lists we've defined before, then fruit would have type list of string because its elements are strings. Nums has type list of int. Diagonal 3 is a list of ints. Its elements are list of ints. And finally, empty is a list of nothing. We will see the significance of this nothing value later on. We've seen that all lists are constructed from the empty list nil and the construction operation double colon, which is pronounced cons. So x cons xs gives a new list with the first head element x, followed by the elements of xs, where we say those elements form the tail of the list. So for instance, the fruit list that we've seen can be written like this: apples, cons oranges, cons pears, cons nil. Or the numbers list can be written like this, or empty is simply nil. In fact, we have a convention that operators that end in a colon associate to the right. So that means you can write A colon B colon C, and it means the same thing as A double colon B double colon C in parentheses. And that means we can omit the parentheses in the definitions above. So val nums, which was list of 1, 2, 3, 4, can be written 1, cons 2, cons 3, cons 4, cons nil. There are three fundamental operations on lists, and all other operations can be expressed in terms of those three. The first fundamental operation is head, which returns the first element of the list. The second fundamental operation is tail, which returns the list composed of all the elements except the first. And the last fundamental operation is empty, which is true if the list is empty and false otherwise. So these operations are all defined as methods on objects of type list. For instance, fruit.head would be apples, fruit.tail.head would be the second element of fruit, that is oranges, diagonal3.head would be the list 100, and empty.head is not defined, and in fact it throws an exception and no such element exception which says head of empty list. Instead of using head and tail, it's also possible to decompose lists with pattern matching, and that one is often preferred. Patterns for lists follow exactly the way we construct lists, so the nil constant can be used as a pattern. The pattern P cons PS is a pattern that matches a list with a head that matches P and a tail that matches PS. And the pattern list of P1 to Pn is actually the same as P1 cons and so on, Pn cons nil. So it matches a list consisting exactly of n elements that each match patterns P1 to Pn. So here are some examples of list patterns. 1 cons 2 cons xs. That matches all lists that start with 1, are followed by 2, and then can be followed by arbitrary elements that are captured in the variable xs. X colon nil matches all lists of length 1. List of x is the same as x colon nil, also matches all lists of length 1. List simply like that is the empty list, that's the same as nil. And list of 2 colon xs, what is that? Well, that matches a list that contains one element, and that element is another list that starts with 2 and is followed by arbitrary elements. So to check whether you've understood that, let's consider the pattern x cons y, cons list xs, ys, cons zs. What is the condition that describes most accurately the length L of the list it matches? Here you have 6 choices. So the answer is it describes lists of length at least 3. Let's see why. So we have a pattern that matches a head x, a second element y, a third element that must be of this form. So that's a single element, but it must be a list. So that makes 1, 2, 3 elements. And then it can be followed by any tail zs, including the tail could be nil. So if the tail is nil, then that list would have 3, the length of that list would be 3. Some people might get confused and says, well, I see 1, 2, 3, 4 elements here. Why does it not say list length greater or equal 4? Well, it helps if we draw that list. So that's the structure of the list that you see here above. And you see, indeed, if you count the cons node here, it's 1, 2, 3, and then it's followed by some arbitrary tail zs. So the xs, ys, they don't count towards the length of the outer list because they make up together an element of that list, namely the third element of the outer list. Okay, so let's start with writing simple functions over lists. One common function is sorting a list of numbers in ascending order. There are several ways to do it. Here's a particularly simple one, which is not very efficient. So one way to sort the list 7392 is to say, well, let's sort the tail of the list first. That would give the list 239. And then let's insert the element 7 at the right position in that list. Functionally, of course. So we can't change the list, but we would return then a new list, which would be 2379. So that idea describes this insertion sort, a particular sort algorithm. And here's the outline of insertion sort. It takes, if we work with integers, a list of integers and gives us back a list of integers. We do a pattern match. If the list is empty, then we return the empty list. Otherwise, if the list is non-empty, then we recursively sort the tail of the list and we insert the head of the list into that sorted tail. So it remains to define the insertion function that inserts an element x into a list xs at the right place, returning a list of the new elements. So again, we do a pattern match over what kind of list it is. If we want to insert an element into the empty list, what would we get? Well, that's simply the list x, right? And what about if it's a non-empty list? So what do we need to do in the case where the list is not empty? Let's say it has a head y and a tail ys. Well, then it depends whether the element we want to insert, the x here, is less than y or greater or equal to y. If the element we want to insert is less than y, then it will be the first element of the result list, because we start with smallest elements first. So we simply return x and then xs, the list itself. If the element is greater or equal to the head element y, then the list keeps its old head element and we insert x recursively into the tail of the list. So that leads us to this else branch. Now if we look at complexity, what's the worst case complexity of insertion sort relative to the length of the input list n? So here we see that insertion sort would go linearly through each element, so it has one pattern match and one operation per element of the list, and each of those operations calls the insert call on the remaining list. So what's the complexity of insert? Well, insert is again, its worst case complexity is it has to go through the whole list. And that would give a complete complexity proportional to n times n, where n is the length of the list. So the first n comes from essentially having to insert each element of the outer list, and the second n comes from having to traverse the inner list potentially up to n for the longest and then successively smaller ones, but it's still n times n. So here, that's actually wrong, because the question was what's the worst case complexity of insertion sort. So the worst case complexity of insert is proportional to n, and that means the worst case complexity of insertion sort is proportional to n times n. In this section you'll learn about enums, which are a convenient way to construct data composed from cases. In the previous session, you've learned how to model data with class hierarchies. Classes are essentially bundles of functions that operate on some common values that are represented as fields. They are very useful abstraction since they allow encapsulation of data. But sometimes we just need to compose and decompose pure data without any associated functions. Case classes and pattern matching work very well for this task. Here's our case class hierarchy for expressions again. We have the base trait expression, and then we have 4 case classes for variables, numbers, sums, and products that all extend expressions. This time we've put all case classes in the expression companion object in order not to pollute the global namespace. So here it's expression.number1 instead of just number1, for example. So that means the type number or var couldn't accidentally clash with something of the same name that we have defined on the outside. Of course, one can still pull out all the cases using an import. So you can write import expression dot underscore that would pull out everything that's defined in object expression and make it available in the global namespace. So note that there are no methods in these definitions. All we've done is define some base trait and case classes that extend the base trait and thus define in particular cases how data of the case trait can be constructed and pattern matched upon. Pure data definitions like these are called algebraic data types, or ADTs for short. ADTs are quite pervasive in functional programming. To make them even more convenient, Scala offers some special syntax. What you can do alternatively is use an enum to define an ADT. An enum enumerates all the cases of an ADT and nothing else. So the way to do it here would be to write enum expression instead of the base trait, and then simply the cases var, number, sum, prod inside. That enum is equivalent to the case class hierarchy of the previous slide, but it's shorter since it avoids the repetitive class blah extends expression notation. So that was the case class hierarchy, and that's the equivalent enum. Since enums are just shorthands for case class hierarchies, we can use match expressions on them as usual. For instance, to print expression with proper parameterizations, we could use this show method here. That implementation is like the one we did in the exercise 2 sessions ago. The only difference is that now, since the case classes are inside the expression object, I have to prefix them with expression dot, as you see here. Of course, I could also import the expression object like this, and then I could use the normal patterns, which you can see here in the show p method, where we used sum without an expression prefix. Even simpler enums. The cases of an enum can also be simple values, so no case classes, just constants, in which case they wouldn't have any parameters. So for instance, we can define a color type with values red, green, and blue like this. Enum color, case red, case green, case blue. Or even shorter, we can put the 3 cases on a single line. So enum color, case red, comma green, comma blue would give us a simple color type. For pattern matching, these simple cases count as constants. So for instance, I could define an enum day of week with the 7 days. I can import it, and then I could have a function isWeekend that says takes a day and matches the day. If it's a Saturday or a Sunday, it returns true, and otherwise it returns false. Here's some more refinements of enums. Enumerations can also take parameters, and they can define methods. So here we have an enum direction that has 2 parameters, which have happened to be val parameters, dx and dy. So that's the displacement in the x coordinate and the y coordinate. So right would be the direction 1, 0. That's x. That's y. Up would be 0, 1. Left would be -1, 0. And down would be 0, -1. The other thing we define here is the method left turn, which is a method defined on enums of this direction type. The way we do it is that we make use of 2 auxiliary functions, ordinal and values. So ordinal is the ordinal number of an enum value. That's essentially just a number that starts with 0 and goes up 1 per case that we have defined. So what we do here is we take the ordinal number plus 1, so the next one modulo 4, so we have wraparound and go from down to right. And that gives us an integer number, and then we can make use of the second method, which is called values. So values takes an int and gives us the enum that has the ordinal number that's given as the int. So in this case, left turn would be direction.values of ordinal plus 1 modulo 4. So let's do an example. Let's say we start with direction right and we want to do a left turn on that. So right has the ordinal number 0. So if the next ordinal number that we compute here is 1, and the direction values of 1 would be up, so we get up as the result of left turn on right. And then if we want to get the fields of the up value, so dx would be 0 and dy would be 1. So here are some further explanations for this example. Cases that pass parameters to their enclosing enum always use an extends clause. So it extends direction, and then that's followed by the actual arguments for those parameters. The expression e.ordinal gives the ordinal value of the enum case e. Cases start with 0 and are numbered consecutively. Values is an immutable array in the companion object of an enum that contains all enum values. And furthermore, only simple cases have ordinal numbers and show up in values. Parameterized cases do not, because there's not a single value that represents a parameterized case. So you've seen that ADT enums are shorthands for class hierarchies with case classes. Similarly, enums with simple cases are shorthands for classes and simple values. So the direction enum that we've seen is expanded by the Scala compiler to roughly the following structure that you see here. We have a base class direction that takes the parameters as given. So we would see a left turn here as the method. And then in the companion object of direction, we would have the 4 cases, which in this case are all individual values, right, up, left, and down. Each value is an instance of an anonymous subclass of class direction with the proper values for the parameters. And then, of course, there are also the compiler-defined helper methods ordinal in each case, and values, and there's another method, value of, in the companion object. Value of lets you get the enum case that corresponds to a string, which is the name of that case. ADTs and enums are quite common in more applied functional programs where the task is often to model some domain. So in that case, one often needs to define a large number of data types without having to attach any operations. So as a small example of this, let's say we want to model payment methods. There could be an enum payment method where we could say, well, one payment method would be by credit card, in which case we want to know the kind, so what card it is, who's the holder, what's the number of the card, and what's the expiry date. Or a payment method could be PayPal, in which case we would want the email, or a payment method could be cash. The most concise ways to write these things down is as an enum in the way you've seen here. Or here's a simple enum where for credit cards, where we just say a credit card is Visa, MasterCard, or Amex. So to summarize, in this unit we've covered 2 uses of enum definitions. First, as a shorthand for hierarchies of case classes, in which case we talk about an ADT typically. And second, as a way to define data types that accept alternative values, similar to enums in many other languages. The 2 cases can be combined in Scala. An enum can comprise parameterized and simple cases at the same time. We've seen an example in payment method where a payment method has 2 parameterized cases here, credit card and PayPal, and a simple case, cash. Enums are typically used for pure data, where all operations on such data are defined elsewhere. In this session, we're going to take a closer look at the interactions between subtyping and generics. We've already seen the 2 principal forms of polymorphism. One was subtyping and the other was generics. In this session, we'll look at their interactions. In fact, there are 2 main areas of interactions. One is bounds of type variables and the other is variants. So let's look at type bounds first. Consider a method assertAllPos, which takes an insert, returns that same insert if all its elements are positive, and throws an exception otherwise. What would be the best type you can give to assertAllPos? Maybe this one, assertAllPos, it takes an insert and returns an insert. In most situations this would be fine, but can one be more precise? Well, one observation is that assertAllPos would take empty sets to empty sets and non-empty sets to non-empty sets. If we want to express that in the type, then a way to do so is like this. We can say assert all pos takes a type parameter s, which must be a subtype of int set, and a value r of type s, and it returns that type s. Here, the less than colon int set is an upper bound of the type parameter s. It means that s can be instantiated only to types that conform to int set. So let's see what one can do with assert all pos. Can one pass an empty set to it? Yes, because we can instantiate s to empty, and then the actual set is an empty set, and we get back an empty set. Can we pass a non-empty set to it? Yes, for the same reason. S can be instantiated to non-empty set, which is a subtype of int set, then we can pass a non-empty set and get back a non-empty set. So how is this new version assert all pos better than the old one? Well, in the return type, because now the return type is coupled with the parameter types, it expresses that whatever we put in, we get out. If we put in a specific subtype of int set, we get out that same int set. That was lost in the previous version where the return type was always int set, so the information what kind of int set it was lost. Generally, the notation s less than colon t means s is a subtype of t, and s greater colon t would then mean s is a supertype of t, or t is a subtype of s. In fact, the supertype notation can also be used as a bound, and then it forms a lower bound. So you can write a lower bound for a type variable like this. So that would introduce a type parameter s that can range only over supertypes of non-empty. So specifically s could be non-empty, or int set, which is a supertype, or any ref, or any. We will see in the next session examples where lower bounds can be very useful. Finally, and for completeness, it's also possible to mix a lower bound with an upper bound. In that case, the lower bound comes first. So to write an s which is lower bounded by non-empty and upper bounded by int set, you would write s greater colon non-empty less colon int set. And that means s can now be either int set or non-empty, but no other type. So much for bounds. Let's look at variants next. In fact, there's another interaction between subtyping and type parameters we need to consider. Given that non-empty is a subtype of int set, do we also have that list of non-empty is a subtype of list of int set? Intuitively, this makes sense. A list of non-empty sets is a special case of a list of arbitrary sets. We call types for which this relationship holds covariant, because their subtyping relationship varies with the type parameters. So if the type parameter goes up, then the type as a whole also goes up. They vary in the same direction, and that's why they're called covariant. So one question that's fair to ask is whether covariance makes sense for all types, and not just for list. For perspective, let's look at arrays in Java and C# where they're similar. As a reminder, an array of elements of type t is written t brackets in Java, and in Scala we use instead the parameterized type syntax array of t to refer to the same type. In fact, arrays in Java are covariant, so one would have in Java that non-empty brackets is a subtype of int set brackets. But in fact, that covariance rule for arrays causes a lot of problems. To see why, consider the Java code below. We create a non-empty array, which has a single element, which is some non-empty set. We then assign that array to an array of int sets. Then we create an empty array and put that into the first element of the int set array B. And finally, we pull out the first element of the A array and put that in a non-empty set S. Now what you need to know is when we have an assignment of arrays in Java like this one here, then those two arrays really point to the same objects. So after the assignment, it would look like this. We would have the A array, which is an array which contains a single non-empty element, and the B array, which is an int set array, points to the same array. So by the third line, we don't have a non-empty element in the array anymore. The element here is now empty. And that means by the fourth line, it seems that we assign an empty element into a variable of type non-empty. which is of course a violation of type soundness. That means our type system lets us do something at runtime which is clearly wrong. In fact, the Java runtime system patches this security hole by storing a runtime tag in arrays that remembers with what type it was created. So the non-empty array here would remember that the only non-empty elements can be stored, and that means by the third line, this one here, you would actually get a runtime error similar to a class cast exception that says, well, you can't store an empty element in an array that was created by non-empty. But that's still troubling because we write something which looks completely reasonable, and the end result is a runtime error, which is an array store exception similar to a class cast exception. So those things normally shouldn't happen. So now we're confused. Arrays can be covariant in Java, but when we use that, then we get into trouble, runtime exceptions. So when is it sound to state that a type should be a subtype of another type? In fact, we can base reasoning on a principle that was first stated by Barbara Liskov, which tells us when a type can be a subtype of another. The principle says if A is a subtype of B, then everything one can do with a value of type B, the supertype, one should also be able to do with a value of type A. So it means everything I can do with B, I can also do with the subtype A, and potentially I can do more things with A. In a sense, A is better than B. It can fulfill every role that B plays, plus potentially more. The actual definition Liskov used is a bit more formal. It says, let Q of X be a property provable about objects X of type B. Then Q of Y should be provable for objects Y of type A, where A is a subtype of B. So these characterizations together have the name Liskov substitution principle. Now consider arrays again. Can an array of non-empty be a subtype of an array of int set? That would mean that everything I can do with an array of int set I can also do with an array of non-empty. But if you think about it, there's one thing I can do with an array of int set that I cannot do with an array non-empty, and that's store an empty set in it. I can store an empty set in an array of int set, but it's definitely not in an array of non-empty. So by that logic, arrays cannot be covariant because covariance of arrays would violate the Liskov substitution principle. So let's look at the example again in Scala. What do you think? If you see the same four statements that we've seen before in Java, but now written in Scala, would you observe a type error? And if yes, in what line? Or would the program compile and maybe throw an exception at runtime, like it does in Java? Or would the program compile and run without exception? In fact, I've already given it away. Since I said arrays cannot be covariant in Scala, that means that that assignment here that assigns an array of non-empty to an array of int set, that's illegal, because an array of non-empty is not a subtype of an array of int set. So we would get a type error in line 2. In this session, we are going to take a closer look at variance, how variance is computed, and how you can structure your program to make them variance correct. The material in this session is a bit more advanced than the other sessions, so you can also skip it in a first pass through that course. So we've seen in the previous session that some types should be covariant, whereas other types should not. Roughly speaking, a type that accepts mutations of its elements, like array did, should not be covariant. But immutable types can be covariant if some conditions on methods are met. Before we go on, let's define what we mean by variance. Say C of t is a parameterized type, and A, B's are types such that A is a subtype of B. In general, there are three possible relationships between C of A and C of B. C of A could be a subtype of C of B. We say then C is covariant. Or C of A could be a supertype of C of B. Then we say C is contravariant. Or neither C of A nor C of B is a subtype of the other. Then we say C is nonvariant. So covariant means the application with C varies in the same direction as the elements. Contravariant means it varies in the other direction, and non-variant means the two types are unrelated. In Scala, you can declare the variance of a type by annotating the type parameter. So you can declare a class to be covariant by writing a plus in front of the type parameter, a in this case, or for contravariant classes you would write a minus in front of the type parameter. If you don't write anything, then the class is assumed to be non-variant. So here's an exercise that requires some thought. Let's say we have a type hierarchy fruit with subclasses for apples and oranges. And then we have two functions. One converts a fruit to an orange, and the other takes an apple and returns a fruit. According to the Liskov substitution principle, which of the following should be true? Should fruit to orange be a subtype of apple to fruit? Or should apple to fruit be a subtype of fruit to orange? Or should the two types be unrelated? So let's look at the first subtyping relationship. What can I do with the second function, apple to fruit? Well, I can pass it an apple and obtain a fruit. Can I do the same thing with the first function? Yes, you can pass an apple to the first function. Apples are fruit, and you will obtain a fruit because oranges are fruit as well. So this one seems to be true. What about the second relationship? Is apple to fruit a subtype of fruit to orange? Well, what can I do with a fruit to orange function? I can pass it a fruit and obtain an orange. Can I do the same thing with the second function? No, because the second function requires an apple. To the first function I could also pass an orange. Oranges are fruit, but oranges are not apples. So I can't pass the same things to the second function. Furthermore, the second function actually returns a type that is less precise than the first one. The first guarantees to give back an orange, whereas the second only guarantees to give back some fruit. It could be an orange, but it could also be an apple. So that relationship is not true, and so the correct answer is 1 in this case. So we can generalize from that reasoning to arrive at a rule for subtyping between arbitrary function types. Here's the rule. We say the function type A1 arrow B1 is a subtype of the function type A2 arrow B2 if B1 is a subtype of B2, so that's covariant, and the arguments, there it goes in the other way. A2 must be a subtype of A1. So functions are contravariant in their argument types and covariant in their result type. So that means that if we want to come up with a revised definition of the function one trait that takes account of variance, we have to write it like this. Function 1 is contravariant in its argument type t and covariant in its result type u. So how does the compiler verify whether your variance annotations are correct? We've seen in the array example that the combination of covariance with certain operations is unsound. In this case, the problematic operation was the update operation on an array. If we turn array into a class and update into a method, it would look like this. Class array, let's assume it should be covariant, and then we have the update method that takes a parameter x of type t. The problematic combination here is the covariant type parameter t, which appears in parameter position of the method update. So that led to problems, and that's probably something that the compiler should disallow. So the Scala compiler will check that there are no problematic combinations when compiling a class with variance annotations. Roughly, covariant type parameters can only appear in method results, contravariant type parameters can only appear in method parameters, and invariant type parameters can appear anywhere. The precise rules are a bit more involved, but fortunately the Scala compiler checks them for us. So let's see whether the rules work out for our function type that we've just defined with variances. Here's the function type. Here, t is contravariant and it appears only as a method parameter type, so that's okay. And u is covariant and appears only as the result type of the apply method, so that's also okay. And the method checks out correctly. Let's get back to the previous implementation of lists. One shortcoming was that nil had to be a class because it needed a type parameter that indicates the type of the list, whereas we would prefer it to be an object. After all, there's only one empty list. Can we change that? The answer is yes, because we can make list covariant. So here are the essential modifications. We would give the list trait a covariant type parameter t. We have already seen that a list of apples is a subtype of list of fruit. And then the object empty can be a list of nothing. So we can write object empty extends list of nothing. Now that's beautiful because it works on two different levels. On the one hand, we have nothing is a subtype of t for any t, and lists are covariant, so list of nothing can be used for any list type t. On the other side, the type list of nothing really conveys the information that there's nothing in the list. So list of nothing on the one hand says, well, there's nothing in the list, and on the other hand ensures that that object is a subtype of any list type that the user might care to give. So far we have followed in this course the no magic rule. Everything you see should be constructible from first principles, and those principles are stated explicitly. So now we have enough machinery to apply the no magic rules to lists as well. So we can show you how one could write lists as they are used in Scala in a library, at least roughly and approximately. So lists would be a trait with a covariant type parameter. The isEmpty method would do a pattern match and say, well, if the list is nil, then it's true, and otherwise it's false. The toString method is a little bit more involved, so it would use a local function recur that takes a prefix and the list of elements that should be still converted to a string, and it returns a string. So it would say, okay, if the list is empty, then I close my string with a closing parens. If it's non-empty, then I print the prefix, I print the head element, and I follow with a recursive call to recur, where I say the new prefix that should follow x, if there are more elements, is a comma. And I start the recurrence with the prefix list open parens. So the first time we print an element, we print it after list open parens, and every other time we print it after a comma. So to continue, there would be a subclass and a subobject of lists. The subclass is called cons. It's also called covariant. It's a case class, and it has a head parameter of type t and a tail parameter of type list of t. And the other case is a case object, nil, that extends list of nothing, as we have seen. The final thing we need is cons as a method. We want to write one cons nil as an infix method. And we do that by defining an extension method. We say, okay, cons is written like this. It takes a first parameter x, which is of type t, a second parameter xs, which is of type list of t, and its right-hand side would be the class creation, which now is written prefix, so that now we create a new object with the parameters x and xs. And finally, we still need to implement calls like list of 1, 2, 3, things like that. For that, it turns out that we don't have quite the machinery yet to do it in general. So we do a fallback, and we just give you an overloaded apply method with several cases for essentially lists of parameters of smaller size. So apply without parameters would be nil, of course. Apply with a single parameter would be x colon nil. The two parameter case is here, and we would go on with apply methods as many are needed. Later on we'll see that we can do with just a single apply method that uses a vararg parameter, but to introduce vararg parameters we need a little bit more machinery for them, so for the moment we should leave it at that. Sometimes we have to put in a bit of work to make a class covariant. For instance, consider adding a prepend method to list, which prepends a given element yielding a new list. A first implementation of prepend could look like this. We are in trait list with covariant type parameter t. Prepend takes an element of type t, returns a list of t, and is implemented by essentially calling a new cons node with the given element and the current list as the tail. But that doesn't work. So what do you think? Why does the following code not type check? because prepend turns list into a mutable class, and that violates variance, because prepend fails variance checking in other ways, or because prepend's right-hand side contains a type error. Well, let's look at these possibilities. Prepend gives you back a new cons node, so no, there's no mutation involved. It doesn't turn list into a mutable class. But it still fails variance checking. Why? Well, because the type parameter t is used as the parameter of the prepend method. And we have seen that's illegal only for contravariant type parameters or invariant type parameters, but t is declared covariant. So that's a variance error. So is the compiler overzealous in rejecting prepend? In fact, no, indeed, the compiler is right to throw out list with prepend because it violates the LSP, the Liskov substitution principle. How? Well, here's something one can do with a list XS of type list of fruit. Prepend an orange. You would still get a list of fruit. But the same operation on a list YS of type list of apple would lead to a type error. So if I do the same operation, then the compiler would complain and said, well, I required an apple, but I found an orange. So I can't prepend an orange to a list of apples, which means that list of apple cannot be a subtype of a list of fruit. But you might argue, prepend is such a natural method to have on immutable lists. Is there a way to make it variance correct? In fact, yes, we can use a lower bound. So we can write prepend like this. Prepend takes a new type parameter u, which is now a supertype of t, and an elem of type u, and returns a list of u, and it has the same body with the cons as before. This passes variance checks because covariant type parameters may appear in lower bounds of method type parameters, whereas contravariant type parameters may appear only in upper bounds. So in a sense we have a double flip. We go to a parameter, but then we go to the lower bound of that parameter, and that turns variance around again and makes covariant parameters legal to appear. Okay, but is this more than just a trick to make the variance checker happy? In fact, yes, we have added some useful functionality to prepend. If we look at prepend again, the question is, what is the result type of this function? We take a list of apples and an orange, and we call x as prepend x. Previously, that wouldn't have worked because we said I can only prepend an apple to a list of apples. But now I can prepend an orange. And what do I get? Well, it does type check. And I get a list of apple? No. The list would contain an orange. A list of orange? Surely not. A list of fruit? Yes, that's the answer. I would obtain a list of fruit. So how does that work? Well, I'm in a list of apples. I get the element which is an orange. The compiler will have to find a type u which is a supertype of apple and can take an orange. And the smallest such type is indeed fruit. So the compiler will instantiate my type u with fruit, and that's the result type list of fruit then that I get back. But there's a simpler way to obtain the same functionality, and we've seen it already. It's called extension methods. In fact, the need for a lower bound was essentially to decouple the parameter of the class and the parameter of the object that is newly created. The newly created object could be a fruit where the class was a list of apple. Using an extension method such that the cons method that we've already constructed sidesteps the problem and leads to the same result. So if we define an extension method here, then the compiler will also instantiate the type t to be a supertype of the type of the element that we prepend and the type of the tail that we pass here. So we would, if we prepend an orange to a list of apples, we would again obtain a list of fruit. This week we're going to put the spotlight on lists. The list type is one of the most common data types in functional programming. You'll find out about many useful list processing methods, and you'll also learn how some of these methods are implemented in terms of the fundamental operations on lists as well as pattern matching. Finally, you'll learn about structural induction, which is a powerful method that can prove the correctness of algorithms over lists and other recursive data structures. In this session, we're going to take a closer look at lists. Lists provide quite a rich catalog of operations, and we'll learn how to use some of these operations in our work. So to recap, there's the type list, which takes the type parameter of the list elements. We can create lists by writing list in front of the elements of a list we want to create, or alternatively, we can create lists using a sequence of cons operations like you see here for nums. To decompose lists, we can do that either with the three standard methods head, tail, and isEmpty, or preferably with a pattern match like what you see here for the example where we pull out the first and second element from the list nums. So here are some of the most commonly used list methods. First, there's length that gives you the length of the list, that means the number of elements in the list XS. Last gives the list last element, exception if XS is empty. So last is the analog of head. Init gives you the list consisting of all elements of XS except the last one, exception if XS is empty. So init is the analog of tail. XS.takeN gives you a sublist that consists of the first n elements of the list XS, or of the list XS if the list is shorter than n. So let's say you have the list 1, 2, 3 and you take 10 elements, you still get the list 1, 2, 3. XS drop n gives the rest of the list after taking n elements, or nothing if the list is exhausted before getting to the nth element. XS applied to n, or written out simply XS.apply n, is the element of XS at index n. And if the index is out of range of the list, you'll get an exception. So to create new lists, there's first concat written double plus. That gives you the list consisting of all elements of XS followed by all elements of YS. There's also reverse, that reverses the elements of XS. That means it gives you a new list where the elements of XS appear in reversed order. And finally, there's updated NX. That gives you a new list that has the same elements as XS, except at position n, which must be in range, it gives you X. So updated is still purely functional. It doesn't touch the list XS, but it gives you a new list with the properties I've described. The following two methods are useful for finding elements. First, there's index of XS. Index of X gives you the index of the first element in XS that's equal to X, or minus 1 if X doesn't appear in XS. XS contains X gives you a boolean that tells you whether X is an element of XS. XS contains X is thus the same as XS.index of X greater or equal 0. So let's take a look how some of these methods are implemented. We know that the complexity of head is small constant time because head just pulls out one of the fields of a cons node. What is the complexity of last? To find out, let's write a possible implementation of last as a standalone function. So here's what we could write. Last of a list XS of type list of t is we match on XS. If it's the empty list, then that would be an error. If it's a list consisting of just one element X, then the last element of that list would be X itself. And the third case would be it's a list consisting of a head Y followed by a list YS. In this case, we have to search for the last element in the list YS. So the result is last of YS. So if you look at this implementation, we see that last takes steps proportional to the length of the list XS. It has to go through the length of the list to find the last element. And that makes last a lot less efficient than head. So if possible, always define your operations in terms of head and tail, and not last and init. In fact, looking at init, we can see here a possible implementation scheme. We have the same triple pattern match. If the list is empty, then init is not defined, so we get an error. If the list consists of just a single element, then init is the list without that element, so that would be the empty list. And if the list consists of an element y followed by a list ys, then init would definitely contain y and the initial elements of ys. That's the complete implementation of init, and like last, its complexity is proportional to the length of the argument list xs. As a third method, let's look at concatenation. How could concatenation be implemented? Let's try for a change to write an extension method for ++. So we have an extension method ++ that follows a list xs and has as additional argument a list ys. As usual, we'll start with a pattern match, but a pattern match on what list? Should we match on xs or should we match on ys? Turns out that it's advantageous to match on xs, so let's do that. So we write xs match. If xs is nil, what do we return? Well, in that case, the concatenation of nil and ys is ys. If xs is not nil, let's say it's an element x followed by a list xs1, then the concatenation would start with x and be followed by the concatenation of x1 and ys. What's the complexity of aka concat? Well, we have to do a pattern match only on the left list, but we go to the end of that left list, so the complexity would be proportional to the length of the left list xs. As another example, let's look at reverse. How can we implement reverse? Let's try again by writing an extension method. In this case, there's only one list xs, so let's try to pattern match on that list. If the list is nil, so reverse of the empty list is the empty list, of course. Reverse of a non-empty list starting with y and being followed by ys is, well, one way we could do it is to say, well, let's reverse the list ys and append the y as the last element to that list. So it's ys reverse concat list of y. What's the complexity of reverse? Well, we go through the list xs, that gives us a factor linear in the length of the list, and then for each of the sublists we call concat, and that concat is, as we've learned, proportional in the length of the left list. So that gives us a factor of x.length times x.length, so the complexity of reverse is quadratic in the length of the list xs. That's a bit disappointing, because if we had an array, we would know, of course, how to reverse it in linear time, just swap pairs of corresponding elements. So one question is, does functional programming in this case have an inherent performance overhead, or can we do better? And we'll solve that question later. But before that, let's do an exercise. Let's write a function to remove the nth element of a list xs. If n is out of bounds, it should return xs itself. So we're after a function with this signature. It takes an index n and a list xs, and the implementation should satisfy a usage example like this one here. Let's say if we remove the element at index 1 of the list abcd, we should get the list acd, because the element at index 1 is b, so that element should be dropped. Okay, so I have set up the worksheet with the signature of the remove at method and the example list xs. For the moment it doesn't work, so if we look at the remove at call, then it says not implemented error. Yes, of course, we have still a triple question mark as the body. So the task now is to fill in the body of remove at. So one proven strategy is we pattern match on what xs is. So we write xs match. If it's nil, then we said, well, remove anything from the list where the index doesn't exist should return the list itself. So we return nil. If the list is not nil, say consists of y followed by ys, what do we do? Well, now we look at the index n. if n equals 0, then we should return the list consisting of all elements except the first, so that's ys. If n is not 0, then we'll have to do a recursive call, so y would be part of the list, and that would be followed by remove at n minus 1 and ys. Okay, so if we test that, then remove at 2 xs indeed gives us the list a, b, d. We can do some other elements, let's say 4. That doesn't do anything because there is no fourth element. 3 would remove the last element, and so on. The second exercise is a bit harder. We want to flatten a list structure. So we're after a method with a signature like this one. It should take a list of any, and it gives us a list of any. And what it should do is, if we have a list that has nested lists as elements, then those nested lists should all be flattened so that we get a single list that contains just the elements themselves without any embedded sublists. So if we take flatten of that input, then we should just get the leaf elements 1, 1, 2, 3, 5, 8 in that order in a single list. Again, I've given the setup here. We have this the signature of flatten, the example list that was given in the exercise, and if we look at the call, then it says again not implemented. In fact, it turns out that its advantages if we give flatten a somewhat more general type, so it takes an any and gives us back a list of any, and the understanding is if the argument that it takes is not a list, it would just return a list consisting of that single argument. So flatten takes any combinations of arguments and it will always return a single list. So let's do that. So what we do is we match on XS. So we see we can match on more things than lists. It can also be any. So if the list XS is nil, then flatten the list of nil gives us nil. If it's another list consisting of a head y followed by ys, then what do we do? Well, y could have embedded sublists, so let's flatten those. And so could ys, so let's flatten ys. And then we concatenate the results because we are interested in a single list. The other case is it is something that we don't know what it is. In this case, we return the XS followed by nil. So if it's not a list, then just turn it into a list by making it the only element of the list we return. Okay, so let's try that. So if we do that, then indeed flatten of ys gives us 1, 1, 2, 3, 5, 8. So what we've seen here in the example of flatten is that pattern matching can be done on very general types, including any. So the patterns will always essentially pick out the right subparts and match it with the right-hand side. This can be quite useful for code that is weakly typed, so that works on many different types in a homogeneous fashion. In this session, we'll learn about more methods on the list type, and we'll also introduce a new data type, the tuple. We look at these things in the context of a somewhat larger example, namely, we want to design a function to sort lists that's more efficient than insertion sort. A good algorithm for this is merge sort. The idea is as follows. If the list consists of 0 or 1 element, it's already sorted. Otherwise, we separate the list into 2 sublists. Each sublist should contain about half the elements of the original list. Then we sort the 2 sublists, each in turn, and finally we merge the 2 sorted sublists into a single sorted list. Here's an outline of the implementation of that algorithm in Scala. We define a function msort, short for merge sort, that takes a list of ints and returns a list of ints. We compute the length of the list divided by 2. If that is 0, the original list was of length 0 or 1, then we return the original list. Otherwise, we postulate a merge function for 2 sorted lists, so it remains to, the triple question marks here remain to be filled in. We split the list at the point in the middle. That gives us two sublists, first and second. We recursively sort first and second using merge sort, and we merge the results of those two recursive sorts. That sorting function used the split add function on lists that returns two sublists, the elements up to the given index and the elements from that index. And those lists are returned in a pair. A pair consisting of the two halves x and y is written x, y in parentheses in Scala. For instance, here you can say val pair equals answer 42, and that would give you a pair of type string int and value answer 42. So the type of the pair is string int. It's again the individual types in parentheses separated by commas. Pairs can also be used in patterns, so you can decompose that pair by writing val label value equals pair, and that would give you two values, a label which is the answer, a string, and a value which is an integer 42. The whole thing works analogously for tuples with more than two elements, so you can have as many parts in a pair as you want. So using pairs, we can write the extension method splitadd like you see here. So it's defined on lists of t for arbitrary t. It takes an int and it gives you back a pair where the first element of the pair is xs take n, so the elements of the list up to index n, and the second half is xs drop n, so all elements of the list except the n first ones. Now we can test that by writing, let's say, splitadd 2 with our list of xs from the last section, and that would give us a list where the original list ABCD was split into two halves, AB and CD. So far every type in Scala was an instance of some class. The same holds for tuples. So for smallish n, the tuple type T1 to Tn is just an abbreviation for the parameterized type Scala tuple, then the number n, and then the arguments T1 to Tn. So the pair int string would be an abbreviation of tuple2, I leave out the Scala prefix, of int string. For larger tuples with length more than 22, we have a special class tuple XXL that essentially collects all elements in an array and then stores them in the tuple XXL class. So yes, tuples are instances of classes, but there is a difference whether the tuple is of moderate size, so up to 22, or beyond that, where we have essentially a class that collects all tuples of all different sizes. So if we look at each of the tuple classes, then they're all modeled after the following pattern. Here we have the example with tuple2, the pair class. So it takes two type parameters, T1 and T2, and it takes two selectors which are written _1 and _2. And the first one is of type T1, the second is of type T2. They're both covariant, so tuples are covariant in both of their argument types, and they override the toString method so that they look like a pair. Because tuples are case classes, it means that these selector values are also available as fields. So instead of the pattern binding val label value equals pair, you could also have written val label equals pair dot _1, which selects the first half of the pair, and val value equals pair _2. Normally, at least if you want to match on all elements of a tuple, the pattern matching form is more concise and it's clearer, so it's generally preferred. The individual selectors can sometimes be useful if you have a long tuple and you just want to select a single element, for instance. So to complete merge sort, we still have to define the merge function. Here it is. So merge takes two lists of integers, which are both assumed to be already sorted. It then does a pattern match on the pair of xs and ys. So we form a pair of the two lists and we match with pairs in turn. So if the two lists are nil ys, that means the first list is nil, the second list is arbitrary, then we return the second list. There's nothing to merge. If the second list is nil and the first list is either nil or has some elements, we return the first list. If both lists are non-empty, so the first list, let's say, starts with x and the second list with the variable y, then we have a distinction whether x or y is the smaller elements. So if x is less than y, then the merged list would start with x and be followed by the merge of the rest of the xs list and all of the ys list. Otherwise, it would start with y and be followed by the merge of all of the xs list and the rest of the ys list. Okay, so that was merge sort on int lists. But of course we'd like to generalize it so that it can also be used for lists with elements other than int. If we just add a type parameter to msort like this, so we replace the int by t, where t is a type parameter, that wouldn't work. Why? Well, because the comparison in merge is not defined for arbitrary types t. So let's look at merge again. Here's the comparison. It is defined for int, of course, but it wouldn't be defined for arbitrary types t. If we just given a type t of which we know nothing, then we cannot assume that it has a comparison function less than defined on it. But what we can do is we can parameterize merge with the necessary comparison function. So let's do that next. So here we have a new version of merge sort, which is now polymorphic. It takes lists of t for arbitrary t, and it also takes a comparison function less than that takes two elements of type t and returns a boolean. So if we have set up things like this, then in the recursive call we have to go on and pass less than to the two recursive invocations of merge sort, because otherwise they would miss a parameter. And then merge also needs to be adapted. The merge function is defined inside merge sort, so it would see the less than function, that's okay. But here at the comparison we would have to call that comparison function less than x and y instead of calling x less than y, what we did previously. We can now call msort as follows. To sort a list of integers, we pass that list xs and the comparison function less than on integers. To sort a list of fruits, which is a list of string, we pass the comparison function on string, which in this case would be the function that takes two strings, applies the compare to function, which is a function known in Java from strings, and says the value of compare to should be less than 0. So that's equivalent to a less than on strings. Note that the type arguments of msort have been inferred in each case, so we could have written int here and string here, but that's not necessary because the compiler will infer it from the types of the arguments. And as another simplification, the compiler can also infer the types of the parameters here, because it knows when it sees the list xs that we intend to do a merge sort on int, so we need a comparison function on two ints. So that means we can write it even shorter, merge sort xs and x, y, arrow x less than y. So we don't really need the parameter types here, nor do we need them in the string example. Now you could say, well, even that is too much noise for me. Couldn't the compiler have inferred the correct comparison function for the parameter type? So that means we now ask the compiler not just to infer a type, but to infer a value. That we say, well, for int, what's the correct comparison function, or for strings, what's the correct comparison function? And in fact, we will see that this is possible, but it will take us several weeks to get there. We will have a week on implicit parameters that does precisely that it can infer missing parameters from their types. In this session, we'll introduce higher order list functions. You've seen already that higher order functions can be very useful. That holds particularly for lists where there are many very common operations that can be abbreviated with higher order functions. The list examples we've seen have already shown that functions on lists often have quite similar structures. We can identify several recurring patterns, like transforming each element in a list in a certain way, or retrieving a list of all elements that satisfy some criterion, or combining the elements of a list using some operator. Function languages allow programmers to write generic functions that implement patterns such as these using higher order functions. So here's an example of the first category. A common operation is to transform each element of a list and then return the list of results. For instance, we might want to multiply each element of a list by a given factor. We could do this with this function here, scale list. It takes a list and a factor and says, well, if the list is nil, then return it. If it's non-nil, starting with y, then multiply y with factor and do a recursive call of scale list of the rest with the same factor. This scheme can be generalized to the method map of the list class. A simple way to define map is shown here. We've defined it as an extension method on lists of arbitrary type t. Map takes a function from t to some new type u as additional parameter, and it returns a list of u's. And it's implemented as follows. We do a pattern match on xs. If the list is nil, then we return the empty list. If the list is non-nil with head element x, then we apply the function f to x and cons it with the recursive call on map over the rest of the list with the same function f. In fact, the actual definition of map is a bit more complicated because it is tail recursive and also because it works for arbitrary collections, not just lists. But to understand the functioning on map for lists, this will do. Using map, we can now write scale list more concisely. We can just say scale list is xs.map of x taken to x times factor. So let's do a similar exercise. Let's consider a function to square each element of a list and return the result. There are two equivalent ways to do it, one as a recursive definition and the other as a call to map. Let's fill in the question marks for both of the alternatives. So the recursive definition, we map nil to nil, we map y followed by ys to y times y, cons square list ys as usual. And for map, it's a lot simpler. Square list is simply xs.map with the squaring function. So we see that map is a very handy tool for all cases where we transform each element of a list given some transforming function. Another common operation on lists is to select all elements that satisfy a given condition. For example, here we have a function that takes the positive elements of a list of integers. Pos elements, it's defined with the usual recursive pattern match. If the list is nil, we return xs. If the list is not nil with head element y and y is greater than 0, then we return a new list with y followed by pos elements ys, and otherwise we just return pos elements ys without the head element y. This pattern is generalized by the method filter of the list class. Here's a possible definition of filter as an extension method. It's defined on lists of arbitrary type t. It takes a predicate function that maps values of t to type boolean and returns a list of t. And its implementation is a pattern match on the list xs. So if xs is nil, we return xs unchanged. If xs is not nil, then if the predicate holds for the first element of the list, then that gets included in the result, and we follow with the recursive call filter p on the other elements xs, and otherwise we just return filter p over the other elements xs without the head element x. Using filter, we can now write pos elements more concisely like this. It's just xs filter with the function x that tests whether x is greater than 0. Besides filter, there are also the following variations that extract sublists based on a predicate. We have filter not, so that's the same as filter with the predicate that negates p. So it's the list consisting of those elements of xs that do not satisfy the predicate p. Then we have partition. That's the same as the pair of lists. The first list is xs filter p, the second list is xs filter not p. So the first list gives you all the elements of xs that satisfy p, the second list gives you all the elements in xs that do not satisfy p. But the two lists are computed in a single traversal of the list xs. So it's more efficient than two separate calls to filter and filter not. The take while method is a bit like filter, but not quite. It gives you the longest prefix of the list xs consisting of elements that satisfy the predicate p. So the first element that does not satisfy p terminates the output, whereas filter would go on and look for other elements that satisfy p in the rest of the list. Drop while is the dual of take while, so that means we drop elements of the list until there's an element that does not satisfy P. We drop the longest prefix of the list of elements that do satisfy P. And finally we have XS span P. That's the same as take while, drop while, but computed in a single traversal of the list XS. So to illustrate the difference between partition and span, let's write a list of numbers 1 to 6 and partition the list with the predicate testing whether an element is odd. So what we get is two lists. The first list are the list of odd elements, 1, 3, 5, and the second list is the list of even elements. Let's do the same thing now, but with span instead of partition. So now we get a list 1 as the first element, so that's the longest prefix of the list that consists of odd elements. That's just a single element, and the remaining list is all the elements after this first element, so 2, 3, 4, 5. So here's an exercise for you. Write a function pack that packs consecutive duplicates of list elements into sublists. So for instance, if you have a list consisting of 3 A's, a B, 2 C's, and then again an A, then we should return a list consisting of 4 sublists. First the 3 A's, then the single B, then the 2 C's, and finally the remaining A. You can use the following template. Pack takes a list of arbitrary type T, returns a list of T, and it uses the usual pattern match between nil and non-empty lists. So I've set up the example in the worksheet. We have the template for the pack function. We have the example list elements, and the call pack elements right now gives us a not implemented error because of the triple question marks here, which we have to replace. So what do we do in the case of nil? Well, if the list is empty, then we should return the empty list because there's nothing to pack. What if x is not nil? Let's say it starts with x and is followed by xs. Then one thing we should do is we should collect all elements that are equal to x, and they will be collected into the more list. And then that should be followed by all elements that remain in the list. So we can do that with the call to span and the predicate that tests whether a given value is equal to x. So once we have that, what do we do? Well, we could return more followed by pack of rest. Let's see whether this would work. We get a result, but there's always the first value missing. We get only 2 A's instead of 3, no B instead of 1, 1 C instead of 2. So where did we go wrong? Well, we haven't included the x in the result list. It's just the following elements that equal x that we excluded, but we forgot x. So let's add x to the first element as the first element of the first element of the result list. And that would now give us a result which is correct, and the logic looks good as well. Now let's follow this up with another exercise. Using the pack function that you've written before, write a function encode that produces the run length encoding of a list. The idea of a run length encoding is that we want to encode n consecutive duplicates of an element x as a pair xn. So for instance, the encoding of this list here should give us a list of 4 pairs. The first pair says we have 3 A's, the second pair says we have 1 B, 2 C's, and finally 1 A. So a run length encoding of a list can compress a list if it is quite common that an element appears several times consecutively in the list. So here's the outline of encode. It takes a list of T and returns a list of pairs of T's and ints, that's the length counts. And all that remains is implemented. So I've given the template for encode in the worksheet. To implement it, let's start with packing elements. So that would give us a list of T's. Now what we have to do is get from this list of T in the element list to a pair which is the element in the list plus the length. And we do that with a map. So we say map with the function x that returns x.head as the element and x.length as the list. And if we do that, then we get a list of pairs of strings of integers, which consists indeed of 3 A's, 1 B, 2 C's, and 1 A. In this session, we are going to look at another set of operators that serve for reducing lists. In fact, it's quite common to combine the elements of a list with a given operator. For instance, to sum all the elements of a list, you could use an operation like this one, so x1 plus xn, and for the empty list you would return 0. Or to take the products of all elements, you would arrive at this formula, multiply all the elements of the list and multiply by 1, which gives you 1 for the empty list. We can implement this with the usual recursive schema. So, for instance, for sum it would look like this. Sum xs takes a list of int, returns an int. Xs match. If it's nil, then it's a 0. Otherwise, if it's a list starting with y, it's y plus sum of the remaining elements ys. This pattern can be abstracted out using the generic method reduce left. Reduce left inserts a given binary operator between adjacent elements of a list. So if you have a list of x1 to xn and you do a reduce left with op, then that would give you x1.op x2.op x3 and so on until .op xn. If you have reduce left, then we can simplify sum and product as you see here. Sum would be just 0 cons xs, reduce left with the summation function, and product would be 1 and xs reduce left with the multiplication function. As an aside, we can write these functions that we pass to other functions also in a shorter way. Instead of x, y, arrow, x times y, for instance, one can also write shorter underscore times underscore. Every underscore in a formula represents a new parameter going from left to right. And the parameters are then defined, so this thing here would be inserted at the next outer pair of parentheses or the whole expression if there are no enclosing parentheses. So essentially you go left to right, you note the occurrences of an underscore. Once you hit a pair of parentheses, you insert a parameter section, one parameter for each underscore that you have encountered. So with that, sum and product can also be expressed like this, which is aesthetically a bit more pleasing. So sum would be 0 followed by xs reduce left with plus, and product would be 1 followed by xs reduce left and multiply. The function reduce left is defined in terms of a more general function, fold left. Fold left is like reduce left, but it takes an additional argument, an accumulator named z here. That accumulator is returned when fold left is called on an empty list. So if we take a list of elements x1 to xn and we do a fold left with the 0z and the operation op, then that would be 0.op x1.op x2 and so on until .op xn. Or visually it would look like this. So you have the 0 on the left and you have the x1 here. Then you have the operation and you build up operations until you finally combine with xn. So it's a left-leaning tree with operations at the node and 0 at the lower left corner and the elements x1 to xn as the leaves on the right. So with fold left we can now define sum and products as follows. Sum of xs would be xs fold left with 0 as the identity and plus as the operation, and product of xs would be xs fold left with 1 as the identity and times as the operation. So now that we have fold left, we can define reduce left in terms of it. So reduce left takes an operator from t and t, the list element type to t, and returns a t. And its body is defined only for non-empty lists. So if the list is empty, we throw an unsupported operation exception. If the list is non-empty, x followed by xs, then we do a fold left on xs with the 0 element x, so the first element and the given operation. So we've seen that applications of fold left and reduce left can be visualized as trees that lean to the left. There are also two dual functions, fold right and reduce right, which produce trees which lean to the right. So here are the definitions of reduce right and fold right. Let's look at fold right first. So if we do a fold right on a list x1 to xn with a 0z and an operation, then we get this right-hand side. And if we want to draw that, then it looks like this. So it's x1 up, x2 up, and then the list goes down until finally we have xn up and z. So we get a right-leaning tree. The spine of the tree is again the operations. The elements appear from top to bottom, x1 to xn, and the 0 is on the low right corner. And reduce right is like fold right, but instead of having a separate 0, it just combines the elements in the list itself. So it would look like this. So fold right and reduce right can also be seen as functions inside class list. Let's look at fold right first. It takes a 0 and an operation, and it returns the result type of the 0 or of the operation, which is a type parameter which we didn't write here. So the u here goes in the brackets. That was a typo in the slide. So the implementation of fold right would be we match on the current list, so that's this, the list itself. If it's nil, then we return the 0. If it's not nil, then we perform the operation with the first element of the list and a fold right of the rest of the list with the same 0 and the same operation. And reduce right is essentially like fold right, but only defined on non-empty lists. So it gives an unsupported operation exception for the empty list. If the list consists of a single element, then that element is the result. If the list consists of more than one element, then it does the operation with the first element and a reduce right of the remaining elements. So does it make a difference whether you use fold left or fold right or reduce left or reduce right? Well, if the operator op is associative and commutative, then fold left and fold right are equivalent, even though there might be a difference in efficiency. Often fold left, for instance, can be implemented in a tail recursive way, whereas fold right is not tail recursive, so it needs more stack space. But sometimes only one of the two operators is appropriate. So you can find it out yourself. Here's another formulation of concat. So we can say concat of two lists, xs and ys, is the first list xs fold right with 0 ys and the cons operation as an operation. We can visualize the operation of concat by just drawing this operation with a diagram. So we have the fold right. That would be here, the cons operation as the operation. So it takes the elements x1 to xn, one after another. And the 0 then is the list ys. So let me just write out the list ys. What would ys look like? Well, that's what it would look like. It is ys1 to y1 to yn and nil. So we see indeed this version of concat neatly aligns all the elements of x, followed by all the elements of y, followed by nil, which is exactly what we want. Okay, so could we have also used fold left instead of fold right for this? The answer is no. And the question to you is why? Is it because the types wouldn't work out, or the resulting function wouldn't terminate, or the result would appear in reversed order? I invite you to copy the function concat in the worksheet, verify that it works correctly, and then replace fold right with fold left. What you'll find is that the types would not work out. Indeed, we can again visualize that. If we do a fold left, then we would have as a 0 the list x1 to xn, and then we would essentially apply the same cons operation on y1 to yn. But that's not type correct, because here we're mixing a list with single elements for the y1 and yn, so the two don't have the same type, and that's why it doesn't work out. So remember that some sessions back we wrote a definition of reverse which was not very performant. It had quadratic complexity where linear is what we want to achieve. We'll now fix that problem, so we develop a function for reversing lists which has a linear cost. The idea is to use the operation fold left for this. So our template will look like this. The reverse function, it takes a list, returns a list, and its body is xs.foldLeft with some 0, which we have to determine, and some operation, which also leaves to be determined. So all we need to do is replace the 0 question mark and the operation question mark. Now we could guess what they are, but the interesting bit here is that we also can compute what they are. We can try to compute 0 and operation from examples. To compute z, let's consider reverse of nil. We know reverse of nil is nil, so we can compute as follows. Nil is reverse of nil. Now we plug in the template of reverse, so that would be nil, fold left, some operation z and op. And now we plug in the definition of fold left, where we say nil fold left is z. So fold left of the empty list is always a 0. So that gives us z. And consequently, because all these are equalities, z equals nil. So we still need to compute op question mark. To do that, let's plug in the next simplest list after nil into our equation for reverse. So we start with list x. And we know that's the same as reverse of list x. Reversing a singleton list gives the list itself. Now we plug in our template, so that would be list of x, fold left, nil, op. And now we apply the definition of fold left. So on a single element list, fold left is the 0 and the element combined with the operation. So that means operation of nil and x is the same as list of x. And list of x is, of course, x colon nil. So that suggests we should take for the operation the cons operator, but with its operands swapped. So here we have the nil on the left-hand side and x on the right-hand side, and here they are in the other order. So putting everything together, we get this definition of reverse. So reverse is a fold left with the empty list and the operation that performs a cons on its operands, but with the operand swapped. So it takes a list and an element, and it returns the element prepended in front of the list. So there's a remark that this type parameter list of t here, that's necessary because otherwise the type inference of Scala will get confused. We're working on that, and maybe we can improve it in a future version, but it's not easy given the type inference algorithm that Scala applies. So it's one of the cases where you actually do have to write an actual type arguments. Now, what's the complexity of this implementation of reverse? Well, let's see. We've seen the operation tree of fold left. That's obviously linear in the length of the list xs. It goes once through the list xs and combines all elements with one operation. And here it's just a fold left with an operation which is constant time. So the answer is it's still linear in the list xs. Linear instead of quadratic, so we have achieved our objective. So here's an exercise for you. We have two functions that you know by now. That's the map function and the length function. I've just wrote them outside of list as functions like this. Can you implement them in terms of fold right? So I've already given you the outline. So for the map function, we would do a fold right on the empty list, because map on the empty list gives the empty list, and an operation that we have to fill in. And the length function would give you a fold right with 0 for the empty list, and again an operation that you have to fill in. So let's see, for the map function, what we need to do if we have a fold right, so we get an element and the remainder of the list, and we do apply the function to the element, and we do a cons with the remainder of the list. If we show that together with fold right in a diagram, it would look like this. So it would be f of x1, f of xn, nil, which is exactly what you would expect for the map function. So what about the length function? The length function can also be expressed with fold right. Here the operation we need to use is the operation that takes a list element and a length that was computed so far on the right and just returns the length plus 1. So the element and the contents of the elements are ignored here. In the last session, we've seen that our function definitions give us certain equations that can be used to compute parts of an expression. In this session, we go on in the same direction by showing that the same equations also allow us to reason about the correctness of our operations. Recall the concatenation operation plus plus on lists. What would it mean to say plus plus is correct? Correct in what sense? So one thing we could do is verify that concatenation satisfies certain laws. For instance, that it's associative and that it admits the empty list nil as neutral element to the left and to the right. So we would postulate these three laws, that we say xs plus ys in parentheses on the left followed by plus zs is the same thing as xs plus ys plus zs. Xs plus plus nil is xs, nil plus plus xs is xs. Okay, so now that we've established the properties, how can we prove them? And the answer is by using structural induction on lists. So what is structural induction? Well, let's take a step back and first have a look at natural induction. Probably most of you know that already. To show a property p of n for all integers n greater or equal 1 base case b, we show that p of b holds, and for all integers n greater than b, we show the induction step. If one has p of n, then one also has p of n plus 1. Natural induction can be used also in programming. For instance, in this example here, we have the factorial function that you know, and we want to show that for all n greater or equal 4, factorial of n is greater or equal power of 2 to the nth. So that's the implementation of 2 to the nth. So to prove that, we start with the base case, which is 4, and that case is established by simple calculation. Factorial of 4 is 24, 2 to the 4th is 16, so 24 is greater or equal 16, and we're done. For the induction step, we proceed as follows. We have for n greater or equal 4 that factorial n plus 1 is greater or equal n plus 1 times factorial of n. And that's simply by the second clause of factorial. That's an equality. Factorial n plus 1 is that. So if we have equality here, we can also assume greater or equal. And that's in turn greater than 2 times factorial of n simply by calculation. N plus 1 is at least 5. Now by the induction hypothesis, we know that for n, factorial of n is greater or equal power 2 to the nth. And that, by the definition of power, is power of 2 to the n plus first. So we have again a chain of greater or equals that starts with factorial n plus 1 and ends in 2 to the n plus first. And in the sequence we used here the induction hypothesis, which says we are allowed to assume, if we want to prove the case for n plus 1, that the case for n already holds. In these proofs, we have freely applied reduction steps as equalities to some part of a term. That means we have replaced the left-hand side of a function with its right-hand side or vice versa. That works because pure function programs don't have side effects. So a term is equivalent to the term to which it reduces, and a function left-hand side is equivalent to its right-hand side. That principle is called referential transparency, and it's really the basis that makes everything in this kind of proof system work. So the principle of structural induction is analogous to natural induction. It goes like this. To prove a property P of xs for all lists xs, show that P of nil holds, that's the base case, and for a list xs and some element x, show the induction step. The induction step to show is if P of xs holds, then P of x cons xs also holds. So let's apply this principle in the proof of associativity for concat. So we want to show that for all lists xs, ys, zs, this equation holds. To do this, we want to use structural induction on XS, the leftmost list. So we saw the previous implementation of ++ that you saw here, and we can distill from this two defining clauses of ++ that state how ++ works on its left operand. So we know that nil ++ ys is ys, and that x followed by xs1 ++ ys is x followed by xs1 ++ ys. So we read that off the second clause here. And we're going to use these two clauses in turn for our proof. So let's look at the base case. For the left-hand side, we have nil ++ ys ++ zs. By the first clause of ++, nil ++ ys is ys, so that's ys ++ zs. And for the right-hand side, we have nil ++ ys ++ zs. Again, by the first clause of ++, that's ys ++ zs. So the two are the same, and that in turn proves that this term here is the same as that term here. The case is therefore established. So now let's do the induction step, where our left-hand list is assumed to be of the form x cons xs. So the left-hand side now looks like this: x cons xs ++ ys ++ zs. Let's simplify that. To do that, we have to look at the second clause of ++. So the second clause is here. It says essentially that if I have a cons and a ++, I can move the parents from the left to the right. So that's the case here. We have the parents here. Let's move them to the right. That gives this term here. So we now have x colon xs now associates with ys ++ zs. Now we can simplify that further using the same trick. So we now move these parents to the right. So that gives us x and then xs ++ ys together with zs. Now we can apply the induction hypothesis. We have x ++ ys ++ zs. So we can assume that one is associative. So by the induction hypothesis, we get xs ++ and ys and zs then in parentheses together. And that's as far as the left-hand side goes, so let's stick with that and concentrate on the right-hand side. So for the right-hand side, we have this. By the second clause of ++, we can move the parents here from the left to the right, so that gives x colon xs ++ ys ++ zs. And that's actually exactly the same as what we have seen here before. So the equality is established. We have the left-hand side, which is equal to this. And then that's where we picked up, and that's again equal to the right-hand side going up. So we have a series of equalities which established the inductive case. So here's an exercise for you. Show by induction on xs that xs ++ nil is xs, so that nil is a neutral element on the right. How many equations do you need for the inductive step? 2, 3, or 4? Well, let's see. The inductive step would look like this. So it would be x followed by xs ++ nil. So by the second clause of ++, that's the same as x xs ++ nil. And by the induction hypothesis, that's the same as x colon xs. So 2 is correct. We need 2 equations to get there. After our deep dive into lists, this week we'll explore other data structures: vectors, maps, ranges, arrays, and more. They differ from lists, both in their functionality and in their performance. One thing will stay the same, however. All the collections we're going to study in depth are going to be immutable, no mutations allowed. We're going to start this session by looking at different kinds of sequences. The second important topic of this week are Scala's powerful and flexible for-comprehensions for querying data. You'll learn how to use this construct to solve some non-trivial combinatorial search problems. In this session we are going to look at some other sequence collections beyond lists. We've seen that lists are linear. That means access to the first element is much faster than access to the middle or end of a list. The Scala library also defines an alternative sequence implementation, which is called vector. This one has a more evenly balanced access pattern than list. The idea with a vector is that it's essentially a tree with a very high branch out factor. So you have essentially here, if the vector is small, up to 32 elements, then it's just an array. If the vector grows beyond 32 elements, then it becomes an array of arrays, each of which has 32 elements. So we have 32 times 32 equals 1024 elements. And if the vector grows beyond that, then each of the subarrays will again spawn 32 children of 32 elements each, and so on. So that one gives now 32 times 1024 elements, and so on. The vector could have a maximum of 5 levels, which would give you 2 to the 5 times 5, so that's 2 to the 25th elements. That's the maximum size of a vector. Now, if you have a structure like that, then let's see what would happen if you have to change a single element functionally without actually modifying the vector, creating a new vector. So let's say you change an element in this subarray here. What you would need to do is essentially create a new array of 32 elements which contains the changed element. Let's say this one is this one here. So that's the one you changed. And then its parents need to change as well. So that one would go here and here, and to all the other ones. And then finally the root has to change as well. So it's not free to change a single element functionally. You have to create, in this case with a depth 3, three arrays. In general you have to modify as many arrays as is the depth of your tree. But the depth of your tree is very shallow, maximum is 5. But it's still much better than having to copy an array of 1,000 or 32,000 or 2 to the 25th elements, clearly. So it's essentially what you have here is a compromise to have reasonably fast access times and reasonably fast update times in all situations. Now, how can you use vectors? They are created analogously to lists, only you write vector instead of list. So here you define two vectors, a vector of numbers and a vector of people. Vectors support by and large the same operations as lists, with the exception of cons. So there's no cons, but there are two operations that add an element to the left of the vector or add an element to the right. Since vectors are symmetric, there's no bonus anymore to only add elements to the left. Adding them on the right is just as efficient as adding them on the left. So note here, as a reminder, the colon always points to the sequence. So x plus colon xs means add a single element to the left to the sequence xs, and xs colon plus x means the opposite. The sequence goes left and the element goes right. So we've seen list and we've seen vector, and those two are in fact instances of a larger class hierarchy of collections in Scala. The common super trait of list and vector is called seq for sequence. And that is again not the most general one, so that is again an instance of an even more general trait called iterable. Iterable has other sub-traits, namely set and map, that we are going to see in the sessions that will come. You might ask, what about array? Is that not a collection? Yes, you can see it as a collection, but since it's defined in Java, it can't be a direct subtrait of sequence, because sequence is defined in Scala. What happens instead is that array is a separate class, but there are automatic conversions that upcast array to sequence and that also give array, again, all the operations that you find in sequence. So arrays and also strings support the same operation as seq and can implicitly be converted to sequences where needed. So for instance, you can write xs equals array 1, 2, 3, and then you can use a map on an array, or you can write val ys equals a string, and you can use a filter on the string. This filter here would pick all the characters which are in uppercase. Arrays and vectors are not the only kind of sequences in the Scala collection library. Another important one is the range. That's a very simple kind of sequence of integers only. It represents a sequence of evenly spaced integers. It has 3 operations to build ranges: to, until, and by. So 1 until 5 would give you the range consisting of the numbers 1, 2, 3, 4. So the 5 is not included. Whereas 1 to 5 would give you the same numbers with the 5. So 2 is inclusive and until is exclusive. And then you can also vary the step of the range using the by clause. So 1 to 10 by 3 would give you the sequence 1, 4, 7, 10. And 6 to 1 by minus 1 would give you 6, 4, 2, and the 0 would no longer be included because it's already smaller than the end 1. Ranges have a particularly compact representation. A range is represented as a single object with just the 3 fields: the lower bound, the upper bound, and the step value. Here are some more operations that work on all sequences, on vectors, on lists, on ranges. So you can ask whether there is an element in the sequence that satisfies a predicate P. That's the call xs exists P. And dually, you can ask whether all elements in the sequence satisfy predicate P. That's done with a for all. You can have a zip. A zip takes 2 sequences, and it forms a sequence of pairs drawn from corresponding elements of sequences xs and ys. If one of them is longer than the other, then it's truncated to make them fit. So for instance, if you had, let's say, the list 1, 2, 3, zip, vector AB, you can zip sequences of different type, and the result will always be the same type as the first sequence. So that would give a list of pairs, namely 1 and A, and 2 and B. Unzip is the opposite of zip, so it takes a list of pairs and gives you 2 lists, one list consisting of the first halves of the pair and the second list consisting of the second halves of the pair. Flatmap is an important function. It's a little bit like map, but it takes a function that returns itself a collection. And what it will do is it will apply f to each element and then concatenate all the results. It will concatenate all the collection results to give a single sequence. Sum and product form the sum and product of a sequence of numbers. Maximum gives you the maximum of all elements of this sequence, and minimum the minimum. Let's do an example that uses some of the operations that we discussed. To list all combinations of numbers x and y, where x is drawn from 1 to n and y is drawn from 1 to n. What would we do? Well, we start with the range 1 to n, and then we do a flat map of the following operation. We have the range 1 to n, and for each element in that range, call that y, we give you the pair xy. So the x comes from the first range, the y comes from the second range, and with the pair we do all combination. That by itself, the 1 to n map operation, gives you a sequence, and all these sequences are concatenated by this flat map call that you see here. So if you're curious, you might ask, well, this is a range and I do a map on a range. What kind of collections do I get back? It can't be a range because the elements of that collections are pairs and not integers. The answer is what I get back is the default sequence type, which in this case would be a vector. So the runtime type of this thing is vector. Here's another example. To compute the scalar product of 2 vectors, we can write a function like this. Def scalar product of xs vector double, ys vector double. It's xs zip ys map, the function that takes corresponding elements x and y, forms the product of x and y, and afterwards we sum it all up with dot sum. Note that there's some automatic decomposition going on here. XS zip ys gives a list of pairs, so map takes a pair, but here the lambda we pass to the map is a function of two parameters. So behind the scenes the compiler will automatically decompose the pair and put the first half in x and the second half in y. If we wanted to be more explicit, we could also write scalar product like that. So instead of decomposing the pair and letting the compiler do it, we take the xy, which is now the parameter that ranges over the pair, and we take the first half of xy and the second half of xy and multiply. On the other hand, if we wanted to be even more concise, we could also write it like this: xs zip ys map of underscore times underscore dot sum. As we've seen before, the function underscore star underscore is the function that takes a parameter x and a parameter y and multiplies them. Most people would write scalar product like this. It's clearly the most elegant way to express it, and in terms of runtime performance, all three versions are basically equivalent. Here's an exercise for you. A number n is prime if the only divisors of n are 1 and n itself. What's a high-level way to write a test for primality of numbers? For once, value conciseness over efficiency. So fill in the triple question marks here for the test whether a given integer n is prime. So let's see, how would we write that test? So if we go literally, we say for all numbers between 1 excluded and n excluded, that number is not a divisor of prime. So let's just write that literally. So we say 2 until n for all these numbers, we have that n modulo the parameter not equal 0. So you see, one of the nice aspects of functional programming and powerful collection operations is that you can write very, very high-level code that directly translates a mathematical specification into code. In this session, we're going to take a look how we can use Scala collections for combinatorial search. In imperative programming, when you search for something, you often do that by means of a loop or a series of nested loops. The loops would terminate when an element that matches the condition is found. In functional programming, you don't have loops at your disposal, but you do have higher-order functions, and it turns out that higher-order functions on sequences are a very good toolbox to achieve the same objective, combinatorial search, and they often lead to code that is clearer and shorter than using loops. For example, let's look at this problem. We are given a positive integer n. We want to find all pairs of positive integers I and j, such that j is between 1 and n exclusive, and I is between j and n both exclusive. And a pair of those two integers should meet the condition that I plus j is prime. For example, if n equals 7, then the pairs of the solution are here in this list. No, the smallest set of integers with a prime sum is 2 and 1, and the largest is 6 and 5. So how do we find a solution to this problem? A natural way to do so is to generate the sequence of all pairs of integers ij that are within bounds as I specify, and then filter that sequence for the pairs for which I plus j is prime. So how do we generate the sequence of pairs? Well, we first generate all the integers I between 1 and n, excluded, and then for each integer I given like that, we generate a list of pairs I1 and so on up to I minus 1. And that can be achieved by combining until and map. So we start with the list 1 until n, we map it so that for each of those we get the list 1 until I, and we map that list with a j so that we can get back the pair I and j. So that's close to the solution, but not quite yet, because like that we get a sequence of sequences. Let's call that sequence of sequences XSS. So that's a good step towards a solution, but it's not quite what we need yet, because the previous step gave us a sequence of sequences. Let's call it XSS. What we still have to do is combine all the subsequences into one single sequence, and we can do that with fold right and plus plus. So for instance, XSS fold right with the empty sequence and plus plus with the operation. Or equivalently and simpler, we can use the built-in method flatten. So we can just write xss.flatten. So that gives together the expression that you see here. We map over 1 until n, we map over 1 until I, we form the pairs of I and j, and we flatten the results. Here's a useful law. For any collection XS, XS flat map f is the same as XS map f and then flatten. So the above expression can be simplified to 1 until n flat map I, 1 until I map j, form the pair of I and j. So now we need to reassemble the two pieces, and we obtain the following expression: 1 until n flat map I, map j, ij, and then we filter the pairs xy to keep only those pairs where x plus y is prime. This works, but it makes most people's head hurt. Is there a simpler way? Generally, higher order functions such as map, flat map, or filter provide powerful constructs for manipulating lists. But sometimes the level of abstraction required by these functions make the program difficult to understand. In this case, Scala's for expression notation can help, and that's what we are going to discover next. We introduce for expressions with an example. Let persons be a list of elements of class person with fields name and age. So here's the definition of that class. To obtain the names of persons over 20 years old, you can write for p left arrow, so this is pronounced taken from, persons, if p.age greater 20, yield p.name. This for expression is equivalent to writing persons.filter such that p.age is greater than 20, and then .map, take the name of the person. So that for expressions looks a bit like a for loop in an imperative language, except that it builds a list of the results instead of working by side effects. So you've seen a particular example of a for expression. In general, for expressions are of this form: for s yield e, where s is a sequence of generators and filters, and e is an expression whose value is returned at each iteration step. So each e designates one element of the collection that is returned by the for as a whole. So what are generators and filters? Well, a generator is of the form p left arrow e, where p is a pattern and e is an expression whose value is a collection. And a filter is of the form if f, where f is a Boolean expression. The sequence must start with a generator, and if there are several generators in the sequence, the last generators vary faster than the first. Here are two examples which were previously solved with higher order functions. The first example was: given a positive integer n, find all pairs of positive integers with these range conditions such that I plus j is prime. So that can now be written like this. We can write for, let's take I from 1 until n, let's take j from 1 until I. If is prime I plus j, then yield I, j as a pair. So this is clearly clearer than the previous example using higher order functions. As a second example, let's write scalar product with the use of a for. So here you have the outline of scalar product. What would it look like if you write it with a for? So here's the answer. We would have a for expression that still needs to zip xs and ys. It matches that with the pair xy, and for each xy that comes from this range, it yields x times y, and finally we have a sum of the whole sequence. You might ask the question, well, why couldn't we write it like this? For x taken from xs, y taken from ys yield x times y. Would that work as well, or would it do something different, or maybe not compile? The answer is it would compile, but it would do something different. It would multiply every element of xs with every element of ys. So not just corresponding elements, but every element of xs times every element of y, so it would be a quadratic number of terms that we multiply and then sum up. In this session, we'll use the techniques we have explored in the previous sessions in a larger combinatorial search example. Before we do so, we need to introduce one more collection type, sets. Sets are another basic abstraction in the Scala collection. A set is written analogously to a sequence, so we write while fruit equals set of apple, banana, pear, or here we have the range 1 to 6 dot to set that would give us a set of the numbers 1 and up to 6. Most operations on sequences are also available on sets, so we can map sets. s.map _ +2 would to add 2 to each element of s, giving you the set 3 to 8. Fruit filter starts with app, that would give you the set of fruits that consists just of apple, and s.nonempty would return true. Here are the principal differences between sets and sequences. There are 3 overall. The first difference is that sets are unordered. The elements of a set do not have a predefined order in which they appear in the set. So if you print out the elements of a set, you do not know a priori which element will come first. The second difference is that sets don't have duplicate elements. So for instance, if we take the set of numbers 1 to 6 and we map it with the division by 2 operation, then we get a set of numbers 1 to 3, and each number appears only once in that set, even though 6 and 5 both would map by division of 2 to 3. But you don't have a duplicated 3, you have a single one here. And the third difference is that the fundamental operation on sets is contains. So s contains 5 would give you true. So now let's get to the combinatorial search problem that we want to tackle. The problem is the n queens problem. The 8 queens problem is to place 8 queens on a chessboard so that no queen is threatened by another. In other words, there can't be 2 queens in the same row, column, or diagonal. We now develop a solution for a chessboard of any size, not just 8. I'll show you the example for a chessboard of size 4. That's the chessboard, so to find a solution, we can place a queen here, and a queen here, and a queen here, and a queen here. So here you see each queen is in its own column, in its own row, and none of them checks the other by a diagonal. This is not the only solution. You can find other solutions by rotating that image or taking the mirror image according to one of the axes. It turns out that for larger boards there are many more solutions, so the number of solutions grows as the board grows. So let's now develop a solution for a chessboard of any size. So one way to solve the problem is to place a queen on each row. We start with the first row, and the queen is arbitrary. Then we go to the next row and we pick a column there where the queen is not yet in check with the previous queen, and so on. So generally, once we have placed k-1 queens, we must place the kth queen in a column where it's not in check with any other queen on the board. Of course, it's possible that one gets into a dead end, that one ends up in a row where no position of a queen would be legal. In this case, you have to backtrack and change some of the previous queens so that a place becomes free in that row. For instance, if we had placed the first queen here instead of one to the left, then it would have turned out that there is no way to complete the puzzle, so one would have to backtrack all the way to the first queen and say no, that we can't place it here. We have to place it one field to the right. So we can solve this problem with a recursive algorithm. The idea is, let's suppose that we have already generated all the solutions consisting of placing k-1 queens on a board of size n. Each solution is represented by a list of length k-1 that contains the numbers of the columns between 0 and n-1 of the queens that have been placed. The column number of the queen in the k-1st row, so the last queen that was placed, comes first in the list, followed by the column number of the queen in row k-2 and so on, and the last queen in the list is the queen on row number 1. The solution set is thus represented as a set of lists with one element for each solution. So all solutions are a set, and each solution is a list of column numbers. Okay, so now to place the kth queen, we generate all possible extensions of each solution preceded by a new queen. So here's the implementation. We have this method def queens. It takes the size of the board, n, and it simply consists of a call to place queens n. Place queens takes a parameter k, which says how many queens are still to be put on the board. And it returns a set of list of integers. As discussed, a set of solutions, each solution is a list of int. So if k equals 0, that means we don't need to place any queen, so we can respond with the empty list. That's the solution, and we return with a set that consists of just this solution. So if k is not 0, then we recursively call place queens of k minus 1. So we have a problem that is one simpler than before, and we let queens range over the result. So place queens k minus 1 is a set of solutions. Now each queens here is a solution, so it's a vector of column numbers. Now the task is to place the kth queen. So we do that by letting col range from 0 until n. That's the possible columns of the board where we could place the queen. And we ask whether the queen would be safe in this column relative to the queens that already have been placed. If that's the case, we yield the column, the new column, preceding the queens that have been placed. And that's it. It's actually surprisingly simple and concise as a solution for this problem. Well, it's not quite the solution yet. We still have to write the function isSafe. So isSafe takes a column where we want to put the new queen and a list of ints, which is the column numbers of the queens that have been placed so far. And it should test whether a queen placed in that column is secure amongst the other placed queens. So it's assumed that the new queen is placed in the next available row after the other placed queens. In other words, in row queens.length. So try to come up with an implementation of isSafe as an exercise. So here's a possible solution. isSafe of column versus queens is that the column is not in check with a distance of 1 to the list of queens, which uses an auxiliary method checks that takes an additional parameter delta. So it takes a column number where the new queen is put, the queens that remain to be checked, and delta, which is the distance of the row where the new queen should be placed, and the last row, the first queen of the list here was placed. Initially delta is 1 because we follow the queens directly by the column we place. So the checks method now is implemented like this. It says, well, if the queens is empty, then the result is false. The queen is not in check. If the queen is non-empty, so let's say we have a queen column and some others, then if the queen column is the same as the column, that's a check. That's a vertical check. Or the queen column minus the column absolute value is the same as the distance delta here, that's a diagonal check. Or it might be in check with some of the remaining queens, so that's a recursive call, checks with the column delta plus 1 and the others. So you know by now how to deal with sequences and sets. In this session we'll get to know the third fundamental collection type, namely maps. Map takes two type parameters, a key type and a value type. It is a data structure that associates key of type key with values of type value. Here are two examples of maps. Roman numerals, it's the map that goes from the letter I to 1, the letter V to 5, the letter X to 10. You can extend that to further letters, of course. So that's a map from strings as the key type to numbers as the value type. The second map we have here is capital of country. That's written map, US, Washington, Switzerland, Bern. So that's a map from strings to strings. The key type and the value type are both strings. Maps are a special subtype of iterables. The the type map key of value extends the collection type iterable of pairs of keys and values. So since maps are iterables, they support the same collection operations as other iterables do. For instance, we can map a map itself. So we can write country of capital is capital of country map, and then it takes the key and the value, so that's the country and the capital, and it reverses the two. So now we have the capital first and the country second, and that would give the new map country of capital, and if we print it out, it's Washington, US and Bern, Switzerland. Note that maps extend iterables of key value pairs. In fact, the syntax key arrow value is just an alternative way to write the pair key value. The right arrow here is implemented as an extension method in predef, which is an object that's implicitly imported into every Scala program. So the right arrow here is not syntax, it's just essentially another method definition. You can think of the extension method to be defined like this. So it would be extension with arbitrary parameters k, v, a key of type k, a value of type v returns the pair of k and v. So we've seen that maps are iterables, and we've put that to good use. But maps are also functions. So the class map key value also extends the function type key arrow value. So that means that maps can be used everywhere functions can. In particular, maps can be applied to key arguments. So you can write capital of country US, and that would give you Washington. What happens if you apply a map to a key that's not defined in the map? Well, applying a map to a non-existing key would give you an error. If you tried capital of country Andorra, then you would get an exception, a Java util no such element exception that would tell you furthermore that the key Andorra was not found. So you should use the application syntax for maps only if you're sure that the key is in fact in the map. But in most cases you're not. So in that case there's a second operation which is called get that doesn't throw an exception if the key is not in the map. So to query a map without knowing beforehand whether it contains a given key, use the get operation. Here's what it's used like. A capital of country.get US, that would give you a value called some Washington. So it says there's something there and it's Washington. And if you say capital of country get Andorra, then you would get a different value which reads none. The result of a get operation, which has these values some and none, is of type option. So the option type is defined as you see here. It's a trait with a single type parameter a, which is covariant. It has two cases, some and none. Some is a case class that takes a value of type a and extends option of a. None is an object and it extends option of nothing. So an expression map.getKey would return none if the map does not contain the given key, and sum of x if the map associates the given key with the value x. So how do you work with options? Well, since options are defined as case classes, they can be decomposed using pattern matching. So here's a typical method. Let's say we want to show the capital of the given country and not fail with an exception if the country is actually not in the map. So here we would say capital of country.get country match. If we found a capital, then report that. If we found nothing, then return missing data instead. So here we would now have show capital US would give us Washington, show capital Andorra would give us missing data. Options also support quite a few operations of the other collections, even though they are not a collection type, because common to all collections is that I can add arbitrary data to a collection. Since an option has only 0 or 1 elements, it's not a collection in that sense. But it supports quite a few operations such as map or fold or filter. I invite you to look at the Scala doc pages for option and try them out. So you might ask, why does capital of country, or any map really, return an option in the get method? In some other languages it would return either the country or a null in case of a missing string. So why not use null? Well, it turns out that null is actually really dangerous, because if any value can be null, then you never know beforehand whether certain operations on that value are defined or not. If the value is null, you would get a null pointer exception. So that's why the inventor of null, that was Tony Hoare, He was also the inventor of quicksort and many other things. So the inventor of null called it his billion-dollar mistake. In Scala, null is actually available. We need it already for interoperation with Java, but it's generally considered bad style to use it. So this course will generally not use null and replace it with safer alternatives such as option. So why is option safer than null? After all, in an option also, I mean, I have either something or nothing. Well, it's safer because the types force you to handle both cases. So if you do a capital of country get country, then that doesn't pretend to be a string. It's an option of string, and you have to process it further by typically pattern matching on the sum case. And if you forget the none case, then the compiler will complain and say the pattern match is not exhaustive. So it will essentially nudge you to really handle both of the cases. That makes option so much safer than null. Back to maps, we've seen how we can query a map and how we can define a map from a sequence of key-value pairs. But can we also update a map? In fact, yes, that's available, so we can have functional updates of a map, and they are done with the plus and plus plus operations. So this operation here, m plus key value pair, that would give you the map that takes key k to value v and is otherwise equal to m. So k might already be defined in m, in which case it will be overridden, the new binding maps k to v, or it might not yet exist in m, in which case we add a new binding for k. Then there's also a bulk operation m plus plus key values, so that would update map via plus with all key value pairs that are given in the collection KVS. Let's go back to this one. Then there's also a bulk operation plus plus m plus plus key value pairs. So here KVS is itself a collection of pairs of keys and values, and the map that gets then updated via plus with all the pairs in the KVS collection. So of course these operations are purely functional. They don't change the map M, they create a new map. So for instance, if I define a map M1, red becomes 1, blue becomes 2, and then I add blue becomes 3 to that map with a plus, then I get the new map red becomes 1, blue now maps to 3. But the old map M1 is still the same. Red becomes 1, blue becomes 2. You might wonder, how can we implement maps like that so that the old map stays in place while we update the new one? Well, for small sizes, maps are just essentially single objects, and we do copy the whole object. That holds for sizes up to 4. And for larger sizes, what we do is we essentially use a scheme similar to the vector scheme. So we have essentially arrays of a shallow depth up to 5, and in each array we have essentially key value pairs, and we use a hash function to essentially select either the right subarray or the right element in that array. Similar to vectors, if we update, we get essentially a log n update of these subarrays, where n is the depth of the tree. So basically we copy between 1 and 5 of these subarrays, which is still a reasonably bounded cost for updating a map. So if you know SQL from databases, then maybe by now you have realized that a lot of the collection operations we have really correspond to what you can do in these database queries as well. And that's no accident, because essentially both of them are rooted in the same theory, relational calculus. So two other common operations from SQL queries are group by and order by. Order by we don't have directly on collections, but they can be expressed using the function sort with and sorted. So here I present them with an example. Let's say we have this fruit list, and then fruit sort with underscore length less than underscore length. So that would sort the list with the function that shorter strings appear first. Consequently, that would give you the list pear, apple, orange, pineapple. There's also another function that is written sorted. So fruit.sorted sorts with the standard comparison function for the underlying type. Here, the standard comparison function for strings is lexicographic ordering. So essentially we compare first the first letter, if it's the same, the second letter, and so on. So that would give you this ordering instead. So here apple comes first because it starts with an A, then orange, pear, and pineapple. So much for ordered by, or rather sort with and sorted. What about group by? So group by is directly available on Scala collections. What it does is it partitions a collection into a map of collections according to a discriminator function f. So again, it's best explained with an example. Let's say we have the fruit list and we want to group it by its head. So that means we take the head of each element. Here we have an A, a P, an O, and another P, and we create a map from these heads to the lists of original elements. So what we would get here is that P now maps to the list of pear and pineapple, A maps to a single element list apple, and O maps to a single element list orange. So let's use these operations in an extended example, which is to construct a class for polynomials. One way to look at a polynomial is as a map from exponents to coefficients. So for instance, the polynomial x to the third minus 2x plus 5 could be expressed with the map that says exponent 0 maps to 5, exponent 1 maps to minus 2, and exponent 3 maps to 1. Based on this observation, let's design a class polynom that represents polynomials as maps. In fact, there's one other operation that comes in handy to treat this use case, and that has to do with default values. So we've seen that previously maps were partial functions. Applying a map to a key could lead to an exception if the key was not stored in the map. But for polynomials, that's actually not very useful, because we could say, well, it does make sense to ask, well, what is the exponent 2 coefficient for a polynomial? Even if it's not given, you could just say it's 0. So basically, you could say x3 plus 0 x2 is the same thing as x to the third. So we can treat missing coefficients as just coefficients of 0. So the fact that these maps are partial and might fail is actually inconvenient. We would like the map to just give us back a 0 for the cases where it's not defined. And we can do that with the operation with default value. So the operation with default value turns a map into a total function. So here we have capital of country. That was a normal map that could fail. And we can give it the default value, or we can create a new map rather, that is the old capital of country map, but now with the default value unknown. And that means we can now apply cap1 to Andorra directly, and we would just get back the string unknown instead of an exception that an element was not found. So with these tools, I think we have enough now to embark on the design of the polynomial class. Okay, so I've given you the outline of the class polynom. It takes a map from int to double as parameter, which is a normal map, which I call here non-zero terms. So that's essentially the terms consisting of coefficient and exponent that are not 0. So the map maps the exponent, so 0, 1, 2, 3, and so on, to the coefficient, which is a double number. Then we have the terms, which is non-zero terms with a default value of 0.0. And that should actually be a val, because we probably use it several times. Okay, then we want to define two operations. One is the addition, so that adds two polynomials, giving a polynomial, and the other is toString, so that should print or show a polynomial in a nice way, in a nicely formatted way. So let's do toString first. So let's start with something really simple. Let's say the toString of a polynomial is this toString of its terms map. We can test it by creating a polynomial, let's say this one here, and then it would indeed print us the map in the way we would expect it. But that's of course not very nice, because the toString method exposes the internal implementation of a polynomial in terms of a map. So we would rather want to see something that has recognizable coefficients and exponents. So how do we do that? So one thing we could do is first define the right coefficient exponent pair for each of the terms that we have in the map, and then essentially create a string that just concatenates them all with pluses in between. So let's do that. So we can improve that by taking each of the terms of the polynomial, printing that out as a exponent coefficient pair, and then concatenating all those strings with pluses in between. So let's do that. So I'll delete the old version and I write the new one here. So what happens here is we take the terms, we map it to a list, we sort it, so that gives us the lowest exponents first, and then we reverse the sorted list, so that gives us highest exponents first. So now we let exponent in coefficient range over those terms, and we print the exponent as x up arrow exponent, and we print the coefficient as it is, and then we concatenate the whole thing with pluses in between. So now my polynomial would read like this: 1.0 x to the second plus 3.0 x to the first plus 2.0 x to the zeroth. Now there's room for improvement, in particular x to the zeroth, that's 1, so we typically don't print that. So let's try to change that. So that would simply say if exponent equals 0, then we don't print an exponent, and otherwise we print that. So that one looks better now. Another thing to improve would be what happens if we take the 0 polynomial. So that would be the empty map, no coefficients at all. And that would give us the empty string, which is not ideal. So what do we do about that? Well, we have to create another special case and say, well, if the term map is empty, so no coefficients at all, then let's print a 0 as the only element, and otherwise print term strings make string plus as before. So now we have handled that as well. A third improvement I leave up to you, it's a little bit more involved, would be to handle negative coefficients gracefully. So let's say I have actually -3 here. What would I get? Well, I would get plus minus 3.0 x to the first, which is legible, but which could be improved by essentially removing the minus here and changing the plus with a minus. So that's a little bit more involved, and I leave that up to you as a polishing exercise. So let's turn now towards the plus operation. To add two polynomials, we have to combine their terms. If a term has an exponent which is only in one of the polynomials, we can just keep it like it is in the result. But if a term has an exponent that figures in both this polynomial and the other polynomial, then we have to add the coefficients. So here's a way to do this. So let's analyze this expression in detail. So if we return a polynomial, it takes a map. The map contains the current map terms updated by this other map. And this other map is the terms of the other map that are then mapped, so that if we have an exponent with coefficient in this other map, then we take the exponent and the coefficient plus the value of the current map terms at this exponent. So we add up the coefficients of both maps. And we do that for all terms that are in both this map and in the other map. If a term is only in the other map, then terms of exponent would be 0, so that would effectively return exactly the same term that we had in the other map. And if a term is only in terms, then that wouldn't be updated, so again, it would stay as it is. So we can test the operation by just, for instance, taking x plus x or x plus x plus 0, and that would give you the polynomial that has all coefficients doubled as expected. So there's one further refinement I'd like to do. It's a bit awkward to have to write polynomials like this, because again it exposes the implementation strategy, implement polynomial in terms of a map, and second, there's this nested call polynomial of map, where it should be clear that if we want to create a polynomial, we want to create it with just essentially the elements that are here. So the question is, could we get rid of the map call like this and write polynomial like that? For the moment, of course not. There's not an operation, so It said, well, it found three int pairs and it needs a map. So what we can do is we can give a map a secondary constructor that would work with these parameters. So what we would do here is we can define a secondary constructor, this, and that would take, well, what would it take? The problem is that we have to deal with a varying number of parameters. A polynomial could have any number of terms that should be given in this parameter list. So for that, we're going to introduce another language feature of Scala that you haven't seen yet, and that's var parameters. So we've seen that it's quite inconvenient to have to write polynom of map everywhere. Can one do without the map? The problem is that the number of key value pairs passed to map can vary. But we can accommodate this pattern using a repeated parameter. So the idea here is that we can give a definition bindings that takes a list of int doubles. So this list is represented by the star here. So var parameter is given by a parameter type followed by an asterisk. And what that gives internally is a sequence. And what we can do then is essentially convert the sequence to a map. There's a handy toMap function for that. Give it a default value 0, and that would essentially create a polynomial with the correct map. And if we do that, then we could write polynomial of, and then just the bindings like that. That's just 3 pairs. And so that would match this type int double star, and that would invoke this method definition of polynomials. So inside the polynomial function, the bindings here are seen as a seq of int and double. So generally, a var parameter, a repeated parameter like this, generates a sequence of the element types that precede the asterisk. So back to the worksheet. In my worksheet, I'm going to do it slightly differently. So instead of creating a separate def that creates a polynomial, I create a secondary constructor directly. So it would be bindings, and that would say. So with that secondary constructor, now we see that our polynomial syntax works and we don't need the intermediate map anymore. So here's an exercise for you. The plus operation on polynom used map concatenation with plus plus. Design another version of plus in terms of fold left. So that version would look like this. So plus takes another polynomial, creates a polynomial, and it essentially folds the other terms with something that you have to fill in, and an add term method. So the type of the add term method is known from the outline here. So it would have to take a map of int and double and a term which is an int and double, and would have to create the map that consists of the terms map plus the additional term. So overwritten with the additional term. So once you've solved the exercise, then try to answer the following question. Which of the two versions do you think is more efficient? The previous version using plus plus or the version using fold left? So I've added the outline as from the slide to the worksheet. We have the plus operation, which is defined in terms of fold left, and we have the add term operation, which also remains to be defined. So let's try to fill in the triple question marks here first. If we do a fold left, so what's the map we start with? Well, that's of course the map, our own map, so that would be terms. Okay, and how do we add a term to a map? So one way to do it would be to first decompose this term. So we say, okay, we know that's the exponent and the coefficient. That's my term. This just gives me a handy way to talk about the two parts. And then it would be what? It would be terms plus the exponent maps to. What does it map to? Well, the terms of exponent, what I have in the current map, plus the coefficient that I have given here. And that should be it. So let's see whether my examples still work. Yes, everything still works. So judging by these tests, the new implementation of plus is equivalent to the old one. But is it faster or slower? So what's the answer here? Well, I would think it's probably faster. So the reason is that with the new implementation of plus, essentially we go directly on the terms and we do a single scan with the fold left. We add essentially each term in a single scan. Whereas the previous implementation that built up a map of all the common terms, and building up a map is costly, then we are left with two maps, and then the maps were essentially folded with plus plus. So that this intermediate step to going through a second map probably costs some time. So I would imagine that the fold left version is faster than the other. So to conclude this week, let's put the pieces together. You're going to use what you've learned about collection operations together with some of the other functional techniques to solve a non-trivial programming problem. The task you want to solve is the following. Once upon a time, before smartphones, phone keys had mnemonics assigned to them. The mnemonics were always the same, so each digit from 2 to 9 had a string of 3 or 4 letters assigned to them. The purpose of these assignments were as a way to remember phone numbers better. So for instance, if I wanted you to remember the phone number 722-524-7386, I would have to come up with a phrase that you could type, or rather you would type the digit corresponding to every letter here, and that would then in the end give you the phone number that we wanted you to dial. The point of this map was as a help to remember phone numbers. So for instance, if I wanted you to remember this very long phone number here, then I could have given you a phrase instead. In this case, maybe I could give you the phrase Scala is fun. And the idea then is you would just essentially type out the letters instead of the digits. So you would type the letter S, well that corresponds to the digit 7, so that gives you the first digit of the number. Then S, C and A would both map to 2, so that gives you 22. And then L would map to 5, and so on. So you get the principle. It's easier sometimes to remember a phrase like that than to remember a phone number. And of course, at about the same time that phones had these mnemonics, there were no URLs or internet addresses, so the way to contact a business was to dial a phone number, and that's why there were a lot of radio ads or other things that gave you essentially these mnemonic strings instead of the real numbers, which nobody can remember. Okay, so the aim now is that you're given a dictionary of words that you can use and a phone number, and you should encode the phone number that gives me all phrases of words that can serve as mnemonics for that given number. Typically there would be more than one phrase. I want them all so that I can pick the one which is nicest or cutest or most easy to remember. So I've given you the outline of a class to do that here, and we are going to proceed to the solution in 4 easy steps. So the class is a class coder. It contains the dictionary, which is a list of string, as a parameter. It has a field mnemonics, which is exactly as it was given here, so I haven't bothered to repeat the definition. And then we have 4 methods that we should implement one by one. So the first method, carcode, maps a letter to the digit it represents. So mnemonics was a map from digits to letters in these strings. Now we want to go the other way. So that amounts to essentially inverting the map. We want to swap essentially keys and values, but it's a little bit more complex because 1/2 is essentially buried in the string. So what we do is we let digit and string range over all the pairs in mnemonics, and we let letter range over all the letters in string, and then we return the pair letter to digit. So each letter that we find here corresponds to this digit, of course, so we just return these bindings as individual pairs. Good, so now that we know carcode, let's scale that up to word code. So we want to map a word to the digit string it can represent. So here's the implementation. Essentially, we map each letter in the word with carcode. So for each letter in the word, we want to know the digit it can represent. We want to concatenate all these digits. That gives us a digit string that the word as a whole represents. Before doing that, however, we should convert all the letters in the word to uppercases because card code is only defined for uppercase characters. So that leads to this right-hand side here. The third definition is words for num. What we want is a map from strings to list of string that maps a digit string to all words in the dictionary that represent it. So it's again, in a sense, the inverse of what we've done here. Here we, given a word, we know the digit string it can represent, and now, given a digit string, we want all words that represent that digit string. So is there an operation in the collection library that corresponds to that? And the answer is yes, that's a group by. So it's words grouped by word code. Indeed, if we look at it, we say, okay, for each word, take the word code, that's a digit string represented by it, and then that becomes the key of the map, and we add to the key as a list of strings all the words that have this word code. That's exactly group by. Furthermore, what we want for words for num is a total map. So we want to say even if a string doesn't appear in the map, we still want to map it to something. In this case, we map it to nil. That means that digit string doesn't correspond to any word in my dictionary. So now we're just left with the encode method. Encode is the method that essentially does the main work. So it takes a number, a digit string, and it should give us back a list of strings where each of these is a phrase that essentially maps to the number. And we want to have a set of solutions. So because we said we're interested in all the possible word combinations that map to the given number. So our result type is a set of list of strings. So it's a set of phrases. Each phrase is represented as a list of strings. So to implement encode, we use a principle which is very common in functional programming, and in fact which we have used time and time again without calling it as such. The principle is called divide and conquer. So the idea with divide and conquer is that we split the problem into essentially two or more easier subproblems. We solve the subproblems and then we put back the solutions together for the final solution. So what are two subcases for splitting a number? So I guess the first distinction would be, is the number empty or not? We have to handle either case. So if the number is empty, what do we return? So we want to have a phrase that corresponds to the empty number. That's easy, that's just the empty phrase. So we get a set consisting of a single solution, which is the empty list. Well, so what do we do if the number is not empty? We have to find another divide criterion to split the problem into two simpler subproblems. So one divide criterion could be to say, well, we have this digit string, let's say 7225563, and then we want to say, well, how many digits do we use for the first word? We have a choice. It could be one, or it could be the whole digit string, or anything in between. So that would be a possible split point, and we work from there. So that leads to the following outline. So we say we take the split point, which starts at 1 and ranges up to the length of the number, and that gives us a point where we want to split it. Then we compute the word that contains the digits up to split point. We compute the rest of the phrase that contains the digits following split point, and we compose the rest and the word together to our solution. So that's the outline. Why did I write .toSet here? Well, it's because in the end I need a set of list of strings, whereas here I have a sequence. I start with a range and that will get transformed to other sequences, vectors normally. But that's not what I want in the end. So I could either have written here the whole thing .toSet, that would have worked. Or like I did it here, I put the toSet immediately around the range. Now I'm working with sets here, and in these four expressions, essentially the collection you start with is also the collection of the result. So the result then in this case will again be a set. But I have still two things to fill in, namely how to compute the leading word and how to compute the rest. Okay, so to fill in the first triple question mark, here's the solution. We take the digits of number up to split point and pass them to words for num. So words for num will give us back a list of words that correspond to these digits. And we let word range over the elements of that list. So each word is a possible solution for the first part of the phrase. So how do we define rest? Well, rest is just a recursive call where we now encode the number without the first split point digits. So what we've done is we've reduced the encode problem by two case distinction. One was number is empty or not, and the other was essentially where do we have the split point, to a simpler problem, namely a recursive call of encode where the number is smaller. We have dropped at least one element from our number here in the argument to encode. And the conquer then is essentially putting the things together, and that was just word cons rest. So here's a little test program. So we can have a function code which takes a number, and we build up a coder with some sample words in the dictionary. We encode the number, and we essentially that would give us a set of lists. And what we do is for each element of the set, we just form a phrase from the list by putting spaces between the words in the list. So if you have a sample run Scala code and then that number, then that would be the resulting set that you get. So this example actually has a history. It was taken from a paper by Lutz Brechelt, which is called An Empirical Comparison of 7 Programming Languages. So the languages also show the time when it was taken. It was essentially the task was for students to solve this problem in different languages. Each group of students had a different language, so there were several groups per language. The languages were Tcl, Python, Perl, Rex, Java, C++, and C. And essentially the question was, how long are the programs, how correct are the programs, how many bugs, how fast do they run? The interesting bit was the code size of the solutions. So the code size medians were about 100 lines of code for the scripting languages, so essentially the first 4 here, and 200 to 300 lines of code for the others. What's also interesting was the runtime. So you would expect naturally that C, C++, and maybe Java would run a lot faster than the scripting languages. If you take the average running speed of the solution, then the big surprise was that actually the scripting languages were quite competitive. Why was that? Well, it was because scripting languages have built-in collection data structures like maps and lists and all the things we were using, whereas C++ and C had not, and Java only had in a limited form. So that meant that people were essentially using the standard building blocks and not going terribly wrong, whereas in C, C++, people would tend to essentially build their own data structures. And sometimes they would get it horribly wrong in terms of performance, and that would give you very, very slow solutions that then would ruin the average. The fastest solutions, of course, were again in C and C++ as well, it has to be said. But what's interesting in our case now is we have something which is very well performing and even much, much shorter than the scripting languages. So we ended up with maybe 15 lines of code instead of 100 lines of code. And we have essentially strong type safety and pure functional programming as additional bonuses. So what we've seen is that Scala's immutable collections are very easy to use because there are only few steps to do the job. We have powerful operations such as group by that do what in other languages sometimes takes a long sequence of steps. They're very concise. A single word like map replaces a whole loop. They're safe because the type checker is really good at catching errors. They're very fast because collection ops are tuned and they can also be parallelized, and they're universal. So there's one vocabulary to work on all kinds of collections. We've seen that essentially the same words, filter and map, can work on sequences, all kinds of sequences, even sort of degenerate sequences such as strings or arrays, but they can also work on sets and they can work on maps. And that's not the end of it. We'll see in the next units that this idea of collection-like structures actually extends to a lot more things than just a narrow notion of collections. So we have essentially a universal vocabulary to attack many, many problems in a safe and fast way. And that makes them indeed a very attractive tool for software development. Over the past 6 weeks, you have explored the traits of functional programming as they present themselves in the Scala language. In particular, you've seen higher-order functions and how they're composed. You've seen how to represent data with case classes and how to decompose it with pattern matching. You've seen how to work in the absence of mutable state, in particular with immutable collections. And you have seen several evaluation strategies, namely strict evaluation, call by value, versus call by name, and you have seen how they can be mixed in flexible ways. I hope you will find that a useful toolkit for your everyday programming, and I also hope that it has shown you a different way of thinking about programs. If you find out more about functional programming in Scala, there's actually a wealth of material out there. There's the Scala cheat sheet, which is actually from a post of a student of a previous course. The cheat sheet shows you the essential elements of the course in a condensed form. Another approach to learning Scala is the Scala School by Twitter. It gives you a lot of courses on the basics of functional programming up to the concurrency libraries that are used in Twitter's massive systems that are all written in Scala. Another fun way to continue your Scala experience and your Scala learning is doing some of the Scala exercises by 47 degrees. So that's a way to learn the individual features of programming by means of solving simple exercises. So for instance, I can come up and have a look at the maps exercises. So here you see essentially first some description and this explanation, and then it asks you to essentially fill in the blanks here to say, well, how many pairings does map have here? And it says 4. No, that's actually wrong. So 3 is the right answer here. So it's a fun way to test your knowledge about Scala and also to extend it. If you're more into reading a book, well, the reference book is Programming in Scala, which I co-wrote. It's currently out in 2nd edition. The 1st edition is actually free download on the web. The 2nd edition is available from the Artima publishers. And finally, there's the Scala website, which contains a lot of documentation from, again, getting started and tutorials to a link to the Scala doc and a general API overview, to links to the community, and a lot more. So, it was quite a tour what you did over the last 6 weeks, and I believe you learned a lot about functional programming, but there are also quite a few topics that we couldn't cover yet and that would be worthwhile to study in a future course. The first topic would be, well, how can we use the principles and the elements that we learned in this course in the design of larger programs? How can we apply functional programming in a larger context? Related to that is the question, what are some useful design principles of functional programming? We know all about design patterns in object-oriented programming languages, so do they carry over to functional programs? Probably not. But then the question is, well, what would be typical functional design principles? Another important and interesting question is about the relationship of functional programming and mutable state. So far, all our functions have been pure. There were no side effects, and that meant we also had very powerful reasoning principles about functional programming that are all rooted in the idea of that substitution model that you have learned. Once we add mutable state, do things change? That's a very important question. And also, if we don't want to add state in a straightforward way, can we maybe simulate state in a purely functional setting? Another important development is from sequential programming, what we have seen in this course, to parallel and distributed systems. I've mentioned at the beginning of this course that functional programming is very suitable for parallel evaluation, but so far all our programs were sequential, no parallelism involved. So once we go parallel, it would be interesting to see what are the data structures, what are the algorithm and programming techniques to do that. And one step beyond parallel programming are distributed systems, in particular distributed collections that it turns out are very, very useful for big data and data science, data analytics. So there's a fascinating set of topics still to be explored, and I hope I can see you back in future classes to do that. Welcome. In this course, you'll learn how to apply the functional programming style in the design of larger applications. You'll get to know important new functional programming concepts from lazy evaluation to type classes. We'll work on larger and more involved examples, including state space exploration, random testing, and discrete circuit simulation. In doing that, you'll also learn some best practices on how to write good Scala code in the real world. Several parts of this course deal with the question how functional programming interacts with mutable state. We'll explore the consequences of combining functions and state, and we'll also look at purely functional alternatives to mutable state using infinite data structures or functional reactive programming. Once you've finished this course, you should be able to recognize and apply design principles of functional programs. You should be able to design functional libraries and their APIs. You should be able to competently combine functions and state in one program and understand reasoning techniques for programs that do that. And finally, you should be able to write simple functional reactive applications. What about prerequisites? Well, this course is intended as a continuation of the course Functional Programming Principles in Scala. You typically will have taken that first. To take both courses, a familiarity of maybe 1 year of programming is sufficient. Java and C# would be ideal, but Python, JavaScript, Ruby, or many other languages would also be sufficient. Welcome. We'll start this week by revisiting some concepts that we've learned in Principles of Functional Programming in Scala: collections, pattern matching, functions. We'll then touch on 4 comprehensions, which are a powerful way in Scala to traverse a collection, process it, and return a new collection. You'll see that 4 comprehensions are actually a lot more general than that. For instance, they can also be used as a query language for any kind of database. This generality is possible because of the way 4 comprehensions are translated into higher order functions by the Scala compiler. In fact, 4 comprehensions are related to the concept of monads in category theory. You'll find out what monads are, and we'll learn by means of examples some techniques to verify that the monad laws are satisfied. In this session, we are going to do a quick recap from weeks 1 to 6 of the Programming Principles in Scala course. So the first topic to review is case classes. Case classes are Scala's preferred way to define complex data. As an example, let's come up with a case class hierarchy to represent JSON, the JavaScript object notation. So here you see typical JSON data structure. So you have fields and definitions of those fields, and it can be recursive. So a field can map to another JSON object in braces, or it can map to a JSON sequence in brackets. The difference between an object and a sequence is that objects have names for the bindings here, and sequences just have data. One advantage of JSON is that it's a very simple format, so it's also straightforward to come up with a hierarchy of case classes for it. So here's a possible representation. I have an abstract class JSON, a companion object JSON, and in that companion object, the 6 cases that make up the alternatives of a JSON data structure. A JSON data structure can be a sequence of elements, which would be represented as a list of JSON objects. It can be an object, which would have bindings that are a map from string to JSON objects. So the strings are the field labels, the values are the embedded JSON objects. It could be a number, which is a double, could be a string, which contains a string. It could be a boolean, which contains a boolean, or it could be null. So unlike Scala, where null is discouraged, JSON data do have nulls in their definition. All these 5 case classes and this case object extend JSON, the abstract root class. We've also seen that we can represent case class hierarchies more concisely as enums. So here it would be the same thing written as an enum. I would write just enum JSON and then the 6 cases without any extends clauses. The extends clauses would be redundant here. So let's do an example. Let's represent this data object in the enum that we have defined. So that's what it would look like. So our JS data, JS could mean Jason or also John Smith, because that's the person we define, would be a JSON object which contains a map. The map contains bindings for first name, that's the string John, last name, that's the string Smith, address, that's the JSON object that's recursively defined by street address, what you see here, state, New York, postal code, what you see here, and it would have 2 phone numbers, so that would be a sequence. Each phone number has a type and an actual number. The type and the number are both strings. So that's just one example data structure and the way how we can define it. So the canonical way to work with enums and case classes is by pattern matching. Here's a method as an example that returns the string representation of JSON data. So the method is called show. It takes a JSON object, returns a string, and it does a match on the JSON object with those 6 cases. So we would have, if it's a JSON sequence, then we would recursively map the elements of the sequence and we would convert them with a string where the string starts with open brackets. We place a comma between adjacent string elements and the string ends with closed brackets. That's what that make string function does. If the JSON is an object with bindings, which are a map, then we go through the map. You take every key and value binding in the map and we convert that to a string by showing the key in quotes, because that's what JSON does, and showing the value. So in quotes is an auxiliary method that takes a string and prints the string in quote marks. So that first operation gives us a list of strings, 1 string for each binding in the original bindings, and we now assemble them by placing them in braces and comma new line between them. So we put each binding on its own line. The other cases are simpler. If it's a number, then we convert the number to a string. If it's a string, we print the string in quotes again. If it's a boolean, we convert it to string. And if it's a JSON null, then we return the string null. So I've pasted what we've discussed so far in a worksheet. Here's my enum. Here's the JS data example value. And here's the show method. So what we can do to test it, we can do show of JS data, and that would give us, the hover says it, essentially the string that we see here, first name John, last name Smith, so it resembles very much the JSON value that we started with. So another topic to quickly recap are Scala's collections. We've seen that Scala has a rich hierarchy of collection classes. They form a hierarchy in that sense that there's a base collection called iterable, and then 3 fundamental collection kinds, which are called sequence, set, and map. And we have seen each in the previous 6 weeks. Sequence has multiple subtypes. One important one was the list, but there were also others like vector or array, which is not really a sequence but behaves like a sequence and has all sequence operations. And sets and maps all have multiple implementations with different efficiency trade-offs. So all these different types could be quite confusing, except that they all really support the same operations with the same names. So that gives you an element of regularity that makes it easy to deal with these collections. So all collection types share a large set of general methods. Some of the methods that are quite important, and that's why I wanted to point them out, are the map method that transforms elements of a collection, creating a new collection, flat map that transforms elements and concatenates the collection results, filter that picks all elements that satisfy a predicate. There's also fold left and fold right that do a reduction of a collection. That means they map the elements of a collection with some binary operation to a single value. Let's have a quick look at the idealized implementation of map on lists. So map would be defined as an extension method that you see here. It takes a function from t to u, returns a list of u, and it says, well, if the given list xs is non-empty, then it maps the first element applying it to f, or rather applying f to x, and follows it with xs.mapf. If the list is nil, then the result is nil. Here's the implementation of flatmap. It's almost like map. The only difference is flatmap takes a function that returns lists of u's instead of single u's, and it concatenates the results not with cons, because that would give a list of lists, but with plus plus. So the list valued result of f is concatenated with the result of xs.flatmapf. And finally, we have filter, which can be defined like this. It's defined on xs of t's, takes a predicate from t to boolean, and if the list is non-empty and the predicate is true for the first element, then it returns that element and the recursive filter of the rest of the list, and otherwise the first element is dropped and it just does the recursive filter of the rest of the list. And as always, empty lists are mapped to empty lists. In practice, the implementation of these methods is a bit different, so that they can be applied to arbitrary collections, not just lists, and also to optimize them so that they can be tail recursive on lists. So these are some tweaks that are applied to the implementations of these methods, but you needn't be concerned with them to understand how they work in principle. Besides collection operations, we also introduced for expressions, and for expressions they can simplify combinations of core methods map, flatmap, and filter. So the example we've seen was, instead of this rather incomprehensible expression that essentially takes two ranges and then it does a map of a filter and whatever, we can write this, which is much clearer. So we can say for I taken from 1 until n, so that's the range including 1 but excluding n. For j from range 1 until I, if I plus j is prime, then yield the pair of I and j. Here's something that we didn't cover yet in the previous 6 weeks, namely that the left-hand side of a generator of a for expression can also be a pattern. So previously we've seen only a single variable that is followed by the left arrow in a for expression, but in fact we can combine pattern matching with generation by placing a pattern on the left. So here's an example. Let's say I want to get out of my JS data all phone numbers that start with 212. To do that, I define an auxiliary method bindings that takes a JSON object and gives me, if it's an object, the list of strings and embedded JSON objects that make it up. So if X is a JSON object with bindings, then we convert the bindings to a list. That gives us this list here. And otherwise we return nil to say that object doesn't have bindings. So now to get up the right phone numbers from JS data, we can write this. We can say for, and here we have a pattern, the binding that starts with phone numbers, and that then on the right-hand side has a sequence of number infos. Take that from the bindings of JS data. So what that does is it goes through all the bindings, and the bindings that match this pattern, they are selected. Turns out there's only one in JS data. And then the fields that are embedded in the binding are recursively matched. So we would get the pattern match to say the right-hand side of phone numbers then would be matched against this pattern here. It is a sequence, so what's in the sequence would be matched with number info. Okay, so number infos is a list. We now let number info range over the elements of that list. That gives us the info for each phone number in JS data. And that info for a phone number is another object. We take its bindings, and we essentially match against the number field of that binding. So we want to find the number of that number info, and that would have a JSON string on the right-hand side against which we match recursively. And then finally we have a condition that that number should start with 212, and in that case we would return number. So we have combined in one for expressions the traversal aspect. We generate essentially everything that is in here, and here. And the filtering aspect, that means we only pick certain elements that match these patterns. To get the filtering behavior, you should prefix the pattern with case. If you leave out the case, then essentially you're telling the compiler that your expectation is that every binding on the right will match that pattern. So case tells the compiler, please filter this. So if we add this code to the worksheet, then we will find that indeed, yes, it pulls out the single phone number that starts with 212. In this session, we're going to look at how one can write common queries with for. In fact, the for notation is essentially equivalent to the common operations of query languages for databases. To see that, let's do an example. Let's say we have a little in-memory database of books, and in this case we just represent it as a list of books where each book is a case class. And the case class would have a title and a list of authors, which are all strings. Of course, often your database is much bigger than a simple list. It could be a Spark cluster or a Postgres database on your computer, but the same principle applies for accessing all of these. So let's write our database. It's not exactly big data because it just contains 5 titles here. So here you have structure and interpretation of computer programs, and here you have some other books in that library. Each book is an instance of the book case class. So here are some queries you might write. To find the titles of books whose author's name is Bird, you could say, well, let B range over books, let A range over the authors of B. If A starts with Bird and then a comma, then yield B.title. Okay, so let's see whether this works. I've written the query here. And indeed, I get the Introduction to Functional Programming, which is the only book with Bird as the author. Or I could ask for all the books which have the word program in the title. So here's that query. And if I hover over that, I see that there are 3 books, and those are the 3 books that have the word program somewhere in the title. So you see that these 4 expressions, they are a very natural way to formulate what otherwise would be a database query. It's really quite natural, so it's a pretty obvious way to query databases or things that look like databases. So let's pursue this a bit further. Let's find the names of all authors who have written at least 2 books that are present in the database. How would we do that? Well, we could say let B1 range over the books and B2 range over the books. There must be 2 different books, so that's a condition. Then let A1 range over the authors of B1 and A2 over the authors of B2. If the authors are the same, then we have a hit and we return A1. So let's look at what we get here. We get Bloch Joshua, Bloch Joshua. Why is that? Well, we return the list of all possible pairs of books here. And if you look through the book list, then there are 2 pairs of books that match that. One is Effective Java and Java Puzzlers, and the other is Java Puzzlers and Effective Java. So that's why the name appears twice. Can you think of a way to modify the query to prevent the duplication? Well, one thing we could do is we could discriminate and say that first, in the pair of books, the first book must always have a title that is lexicographically smaller than the second book. So instead of saying B1 different from B2, we say B1.title is smaller than B2.title. And that would work, because now we have essentially only one pair, the pair that starts with the lexicographically smaller title that is the left element of the pair and the other the right one. But does it scale? So what if an author has published 3 books? What would we get now with the new solution with a comparison of titles? Would the author be printed once or twice or 3 times, or maybe not at all? In fact, the answer is the author would be printed 3 times. Because if you have 3 book titles, let's say A, B, C, then there are 6 possible pairs and 3 possible pairs where the first one is smaller than the second, namely AB, BC, and AC. So for each of these pairs, the author would show up. So we need a more robust way to deduplicate the authors. So one way we could do is we could use the distinct method on sequences. So here we define the query as before, name it repeated, and then finally return repeated.distinct. So distinct would keep each element in the repeated list only once. Subsequent copies of the same element would be omitted. Or we could attack the problem at the root and compute with sets instead of lists, because after all, if we want to remove duplicates from the results, then we shouldn't introduce those duplicates in the first place. So by going to sets, we avoid any duplicates. Every set can contain an element only once. So what we could do here is we can write book set equals books to set, and then have the query range over sets, and that would also deduplicate all the results of the query. I can show that here in the worksheet. So that was the previous query that contains the duplication, and it actually suffices that we convert the first books to set, because then afterwards essentially all the computations will be done on the first collection type, which is set. So that would now give us not a list with Broch Joshua twice, but a hash set where he appears only once. In this session, we're going to look at the translation of 4 expressions. 4 expressions have been a little bit of a mystery so far, in that we haven't really explained what they mean. I mean, they're very natural, but you haven't seen a rewrite rule using the substitution model for them, for instance. In fact, what happens is that 4 expressions are translated to simpler elements that you know already. And in this session, we will explain that in detail. So you've probably noticed already that the syntax of 4 is closely related to 3 higher order functions, namely map, flatmap, and filter. The first observation is that these functions can all be defined in terms of 4. So we could define a function which is like map, let's call it mapFun over xs and f, and mapFun is just let x range over xs yield f of x. That's the same as mapping f over xs. Or to do flat map over a list xs with a function f, we could let range x over xs, let range y over the result of f of x, and yield y. That's in fact flat map. Or to do filter over a list xs with a predicate p, we let x range over xs. If p is true, then we yield x, otherwise we yield nothing. So these 3 methods can be naturally defined in terms of 4. But in fact, in reality, it goes the other way around. The Scala compiler expresses 4 expressions in terms of map, flat map, and a lazy variant of filter. Here's the translation scheme used by the compiler. We limit ourselves here to simple variables and generators, so this scheme also extends to patterns, but here we won't explain in detail how that works. So if we have a simple 4 expression, say 4x taken from a generator E1 yield E2, then that's a map, so it's translated to E1.map with the function that takes an x and returns E2. So you see that we respect variable bindings here. The x is visible in E2, and it's also visible in the translation because it is the parameter of a lambda that has E2 as its body. So that was the simplest case where our 4 expression consisted of exactly 1 generator. We now handle the cases for when the generator is followed by something. Let's assume first the generator is followed by an if, and then possibly some other sequence of generators and filters. So we have a 4 expression of this form. That 4 expression is translated to what you see here. It's the 4 expression that uses the same generator, E1, but followed with a filter of the predicate that maps x to f. Then that's followed by whatever followed the filter before, and the translation continues. You can think of with filter as a variant of filter that does not produce an intermediate list, but instead applies the following map or flat map function application only to those elements that pass the test. So essentially, with filter is like filter, but it avoids the creation of an intermediate data structure. So the last remaining case is if our leading generator is followed by another generator, and then possibly a sequence of filters and generators. That template is translated to what you see here. So the tail here, the remaining for expression you find here again. So that will give you a collection valued result, and then the results of that inner for expressions are concatenated via a flat map. So again, we can verify that the variable bindings all work out. So the x here is visible in the remaining code from y to e3, and that's also the case here because we have a lambda where we bind the same variable x. And once we have that, of course, that inner for expressions might itself be complicated, so translation continues recursively with that. So as an example, take the for expression that computed pairs whose sum is prime that we've seen already. So for I taken from 1 to n, j taken from 1 until I, if is prime I plus j yield I, comma j. If we apply the translation scheme that we have seen, that's what we get. So it's exactly this expression here, which is almost exactly the expression which we came up with first, before we mapped into the much clearer for notation. So essentially the compiler, it works in the other way. It translates a high level for expressions into low level code that for our eyes looks more obfuscated and less clear than the original for expression. On the other hand, that code that it maps to doesn't contain any for expressions anymore. It's just function applications, and we know how to deal with that in our substitution model. So here's an exercise for you. Translate the query here about books that you have seen already into higher order functions using the translation rules that we have just covered. What did you come up with? The expression above translates into one of the following two expressions. Which one is it? The first one here or the second one here? Well, if you've applied the rules correctly, you'll find out that the answer is the first one. So one interesting aspect of the translation rules for for that we've covered is that it's not limited to lists or sequences or even collections. All we need for the translation is the presence of the methods map, flat map, and with filter on the data in question. And that means you could use the for syntax for your own types as well. You must only define map, flat map, and with filter for these types, and you're done. It turns out there's surprisingly many types for which this is useful. Obvious examples are arrays or iterators, but also databases, optional values, parsers, random numbers, and so on. For example, books might not be a list, but a database stored on some server or on some cluster of servers. As long as the client interface to the database defines the methods map, flat map, and with filter, you can use the for syntax for querying the database. And that's in fact the basis of many database connection frameworks in the Scala ecosystems, such as Slick or Quill, and it's also the basis of big data platforms such as Spark. In this session, we'll learn about a new abstraction which is very useful in testing, namely functional random generators. A question: are for expressions tied to collection-like things such as lists, sets, or databases? The answer is not really. All that's required is some interpretation of map, flat map, and with filter, because that's the translation target of for expressions. There are many domains outside collections that afford such an interpretation. An example are random value generators. You probably know about random numbers from languages such as Java. So in Java, you would create a random number generator like this. You invoke Java util random. That gives you a generator called rand here. And then you would get the next random number by calling rand.nextInt. And you can do that arbitrarily often, and each time you will get a new random number. So that works for integers. But the question would be, what's a systematic ways to get random values for other domains, such as booleans, strings, pairs, tuples, lists, sets, or trees. So that's what we're going to do now. We're going to define a trait generator of T that generates random values of type T. So here's the trait. It takes a covariant type parameter T, and it has a generate method that, when called, returns a new random value of type T. Here's a possible instance of generator, the integers. So that would be a generator of type int. We create a new random value generator, so that's essentially our root generator, and then to generate a new integer we just call rand.nextInt. So it's just a wrapper around Java util random, really. What about generating random booleans? So here's a way to do it. We define a val booleans. It's a new generator of type boolean, and its generate method would call the integers generate and ask whether the result is greater than 0. So 1/2 of the values generated by the integers generator would be greater than 0, so that would give true, and the other halves would be less than or equal to 0, so that would give false. Another thing we might want to do is generate random booleans. For that we define a new generator boolean. Its generate method calls the integers generate method and returns true if the result is greater than 0 and false otherwise. About half the values returned from integers generator will be greater or 0, so the distribution is about 1/2 for true and false for the booleans generator. What about structured random data? As a simple case, we define a generator for pairs of random integers. Its generate method would call integers generate twice, once to produce the first half of the pair and the second time to produce the second half of the pair. So I've put what we have in a worksheet. Let's test, maybe by writing pairs.generate. So that would give us 2 numbers, and if we call it again by saving again, it would give us 2 different numbers and so on. So that's essentially the random number generation at work. So you might object, haven't we left the domain of purely functional programming? After all, the more often I save this expression, I get a different value each time. So that's not really functional, is it? And I'd have to agree with you. The one saving grace here is to say, well, it doesn't really matter what the actual random number is. The whole point of random numbers is that they are random. One number does just as well as the other. So in that sense, while we are definitely outside purely functional programming, we are so in a relatively benevolent way. So as a next step, can we avoid the generator boilerplate, that every generator we create has to be a class instance of an anonymous class and we have to override the generate method and so on? Ideally, what we would like to write is this. We would like to write val booleans is let x range over the integers and yield x greater than 0. Or def pairs of tu, it takes a generator of t and it takes a generator of u and it gives you back any x ranging over t, y ranging over u, the pair of x and y. So in a sense, that's more a streams view. We are no longer looking at individual random numbers, but at the stream of all random numbers that are generated. That's the integers, and we convert that stream by saying, well, to convert it to a stream of booleans, we just ask for each element whether it's greater than 0. Or here we produce a stream of pair random numbers by essentially composing the stream of t random numbers with the stream of u random numbers. So how do we achieve that? Well, what do these expressions expand to? The first expression expands to integers.map x greater than 0. And the second expression expands to a flat map of the pair construction, as we have seen when we looked at the translation of 4 expressions. Okay, so to be able to do that, we need map and flat map. So here's how we can dress up generator to provide this new syntax. We just have to add map and flat map to it. So let's do that with extension methods. The map method you see here, it takes a generator of t and a function from t to s, where s is some other type, and it creates a new generator of s, whose generate method calls the ggenerate, the original generate, and transforms it with f. So that was map. What would flat map look like? Here it is. So flat map takes a function now that from t to some generator of s, and it itself produces a generator of s. So what its generate method does is it calls again the original generate from g, transforms it with f, that gives you a generator of s. So to produce an s random number, we call again generate on this second generator. So that gives you this right-hand implementation of generate. So here we have defined map and flat map as extension methods of trait generator, but we could also have defined it as methods directly inside the trait. If we had done that, that's what it would look like. So we would put map and flat map inside trait generator, and the implementation is very much the same as before, only now we refer to the enclosing generator object. That's the original generator. So there's actually a tricky bit going on. We can't just write this here without the prefix, because if we write this in a new generator s, then remember that this expression creates an anonymous class, and that this would reference to the anonymous class itself. So if we wrote just this.generate, we would get simply a recursive loop to the generate method that was defined here. To break out of the current class and refer to the this of the outer class, we prefix the this with the name of the class, in this case generator.this. So generator.this is used to refer to the this of the outer object of class generator. So this all looks very abstract. We define map and flat map for generators, and then some for expressions translate to them, and the original for expression then is supposed to be the right random generator. How do we know that? Well, we can apply some equational reasoning. We can use what we know of the translation of for expressions and how the resulting expressions reduce to verify that indeed this expression that we write is the generator for booleans. Let's do that. So we've seen that the expression on the right translates to what we see here. That's what the compiler does when it translates for expressions. Now we plug in the implementation of map, so that's what we see here. The implementation of map says take integers.generate, so the left-hand side here, and transform it with f, where f is the function that gets passed to map. So here we have that function again, it's a lambda. So now we have an anonymous function that's immediately applied to an argument. What we can do is essentially just rewrite. We rewrite it to the right-hand side of the function and replace the x by the actual argument. So that's what we get then. We get def generator equals integers.generate greater than 0, which you notice is exactly the generator for Boolean that we have defined initially. Let's do the same exercise for the pairs generator. I've left out the initial for expression, so we start directly with its translation into flat map and map. So that's what we start with. So if we look at the map function, here's what it expands to. So we create a new generator whose generate method is the application of this pairing function to the original generator from u. So it's u.generate then wrapped with x as first element in a pair. I haven't written the anonymous function anymore, so I've directly written its expansion, and that you see here. So let's expand flatmap next. Here's what we get. So flatmap gives us a new generator with a generate method that is the original generator, we call that, and that would essentially give us a generator back, and we call generate again on that generator. So that's the expression that we're left at. Now we do rewriting again. We have here an object with a method, and we call the method directly. So what we do, of course, is replace it with the right-hand side of that method. So that would be t.generate and u.generate, which is exactly the original generator for pairs that we started with. So here are some more example generators that are useful to build up more complicated generators. The single generator always returns the same value x. So it's a generator that when called always returns x. The range generator returns a random value between the low and the high values that are given here. So its implementation is we let x range over the random integers and we yield the low value plus the absolute value of x modulo high minus low. So that would give us values in the interval between low inclusive and high excluded. Finally, the one-off generator gives you random values that are taken from a list of values xs here. So the way it's implemented is we let index range over the range of random values between 0 and xs.length, and for each such random integers we return the value of xs at the index of that integer. So I've added these definitions to the worksheet. Now we can define, let's say, a generator choice, which is one of three colors red, green, or blue. So that gives us a generator of strings. And now we can write choice.generate. And that would give us a random string. And if we go several times with saves, then it would be essentially a sequence of random strings. Lots of greens, red, blue, blue, and so on. Can we also have generators for random values of recursive data types? Yeah, of course. So let's start with lists as a simple recursive data type. A list, as we know, is either an empty list or a non-empty list. So to generate a random list, we make first a coin toss whether we want empty or non-empty. So we let isEmpty be taken from the Boolean random numbers. And then the list that we produce is, if the coin toss says it should be empty, then we return an empty random list, which is always the empty list, and otherwise we return a non-empty random list. So what is an empty random list? Well, it's this generator, the single generator nil, that will return nil every time it is asked to generate a new value. And what is a non-empty lists generator? Well, it's a generator that generates a head, which is a random integer, and it generates a tail by calling recursively the lists generator here, and that yields the list consisting of the head and the tail. So I've added the new definitions to the worksheet. If we now type lists.generate, we get a random list, and if we do that several times, we get in each case a new random list, as you see here. One thing we notice here is that these lists tend to be rather short. Indeed, in about half of the cases, the expected length of the list would be 0, because essentially then isEmpty would be true. Can we find another generator that would generate lists that also can reach longer lengths with higher probability? Question to you, what would we have to change to get such a generator? Well, the thing we need to work on is this condition here, the Booleans, which essentially split between empty and non-empty lists evenly. So we can reduce the probability that we generate an empty list by using a different generator. So let's say we use range and say we have essentially 5 slots of lists, and so call that kind. We let kind range over that, and we generate an empty list only if kind equals 0. So in 1 out of 5 choices we generate an empty list, and otherwise we go on with a non-empty list. If we do that change, then you see the list has gotten much longer. So of course it's still random what we get. Sometimes we get the empty list, but we get it less often and we get longer lists with higher probability. Here's another exercise for you. Can you implement a generator that creates random tree objects, where the tree is an enum that is either an inner tree with a left and right subtree, or it is a leaf, in which case it has a field of type int. Okay, so here's our tree type. Let's write a generator for it. We would expect that this generator resembles quite a lot the list generator that we've written. After all, lists and trees are both recursive data types that are quite close together. So let's use the same schema. We use a for. Now we have first a test whether we should generate an inner node or a leaf. So let's say isLeaf taken from booleans. So that gives isLeaf is a random boolean. And then our tree would be, well, if isLeaf is true, then we generate an inner node, and otherwise we generate if leaf is true, then we generate a leaf node, and otherwise we generate an inner node. And that's a tree that we return in the end. So that would be the trees method, which it has type generator of tree. Good. Well, we still have to define the leaves and inners generators, so let's do that next. So what would leaves be? So leaves would be 4x taken from integers, yield tree dot leaf of x. And inners would be 4x taken from trees, y taken from trees, yield, tree dot inner xy. Let's test this. So we write trees dot generate, and here's our tree. Or other trees, we have a lot of leaves, but also some inner nodes and some trees that are deeper. We can, of course, have a less unevenly balanced trees in the same way we did it for lists by replacing the Booleans criterion here with something that essentially is less oriented towards leaves, so that generates leaves less often as before. An interesting application of this random value generation scheme that we've seen is random testing. You probably know about unit tests. To test a function, you need to come up with some test inputs and a post condition. The post condition is a property of the expected result of the function. Then we run the function on the inputs and we verify that the result satisfies the post condition. So a question, can we do without the test inputs? That would certainly be nice to be able to test program functions without having to come up with the arguments to them that we need to test. And the answer is yes, we could generate random test inputs. So basing ourselves on the generator framework that we've developed, we can now write a random test function. So here's a possible implementation. The function takes a function to test that you see here. That function has an argument type t and the result type boolean. We then take a generator of t that generates random inputs of type t and an additional parameter num times that tells us how many tests should be run. And then the implementation is simply that we have a loop that goes through the input num times. Each time through the loop we generate a new random value. We test the test function with that value. And if the result of the test function is not true, then we fail the assertion with the string test failed for value. If we passed num times runs, then we print we passed num times test. So that's a successful outcome of the testing function. So here's an example usage of our test function. So we can say test pairs of lists and lists under the condition that if we have two lists, then the concatenation of these lists has a length that's always greater than the length of the first list XS. Does that property always hold? Yes or no? Well, let's test it. So I've pasted our test function into the worksheet. Let's test it on the condition that we saw here. So we get an assertion error that says the test failed for some random list and the second list was empty. We can run it again and we get it now for the pair of empty lists. So what's of course the case under all these failing tests is that the second list ys was always empty. And now it's of course also clear that if ys is empty, then the concatenation doesn't have a length that's greater than XS. It's just greater or equal XS. And if we fix our condition in that way, then indeed we will get past 100 tests. Okay, so the answer to the original question is no, and we also have learned that we have to change the condition by adding an equals here. So this looks quite cool. We can just write the property we're interested in, and we give a generator for the data types in question, and then we can run tests for that property, as many as we like, without having to come up with different inputs. Of course, you might object that, well, this naive random number generation, it's not really very good at detecting corner cases, which is true, and also that some of the counterexamples that we've seen, they were needlessly long. The first XS list, that was a counterexample. It doesn't really matter whether it's 10 or 11 or 1,000 elements, any list would do. But these are things that can be overcome, and indeed there are testing frameworks that are much better at finding good random distributions that also execute the corner cases, and that then can minimize the counterexamples. So if it finds a counterexample, let's say with a list of length 10 for XS, then it would go and say, well, can I find a smaller one? And it would continue until it found the smallest possible one, which in this case would be, well, nil plus nil has the same length as nil. So what this leads to in the end is a shift in viewpoint. Instead of writing tests, or traditional unit tests, I should say, let's write properties that are assumed to hold, and then let's pass this to a random testing framework. This idea is implemented for Scala in the Scala check tool to check a condition for lists that you see here. Here's some syntax you would use. You would say for all, and then essentially come the arguments of type list of int, and then comes the property. So if you look at this, you might be puzzled. You might ask, where are the generators? We have just a function over two list arguments, but we see nowhere the lists generator that actually generates these random numbers. To solve the mystery, essentially the generators are provided by the for all method itself, and it can do that automatically based on the types it is passed. We learn useful techniques to do that in 2 weeks' time when we discuss type-directed program generation. For the moment, let's just assume that we can write these generators ourselves, or let's just trust in the magic of Scala check. I should say that Scala check is not the first tool that did that. There are now a number of tools for different languages. The original tool that pioneered the domain was called Quick Check, and it was written for Haskell. Nowadays, the Scala check tool is embedded in quite a few testing suites. It can, for instance, be used as part of Scala test, but of course it can also be used standalone. In this session, we're going to talk about monads. If you're at all interested in functional programming, then you probably heard the term already or read an article of what monads are. In fact, there's a zillion of such articles that compare monads to such exotic things as burritos or elephants. The truth is quite a bit more prosaic, and in fact, once you have done this session, you probably will find out that you knew monads all along. So an observation is that data structures with map and flat map seem to be quite common. We have seen quite a few of them. And in fact, there's a name that describes this class of data structures together with some algebraic laws that they should have. And that's called a monad. So a monad M is a parametric type, so a type that takes a type parameter with two operations, flat map and unit, that have to satisfy some laws. The shape of these operations looks like this. So flat map is typically used as an infix method, so we define it here as an abstract extension method. So it takes an instance of the monad type m of t and a function that takes a t, so what's in the monad, to an m of u, and it returns an m of u. Unit, on the other hand, it takes an x of type t and returns an m of t. In the literature, flat map is also called bind. It can be an extension method, or it could also be defined as a regular method in the monad class M. So if you take this definition, then we see that quite a few of the data structures that we encountered are monads. So list is a monad with unit of x is the single element list x, and flat map being flat map on lists. Set is a monad with the unit element set of x, option is a monad with the unit element sum of x, and generator is a monad with the unit element single of x. In each case, the flat map on the monad is just the flat map as defined on the type. So what about map? Do we need another definition of map? In fact, for monads, we can define map as a combination of flat map and unit. So here's the general definition of map. For any monadic value m.mapf is defined to be m.flatmap with a function that takes an x and returns unit of f of x. And that in turn is the same as the m.flatmap f and then unit. And then means function composition. It's defined in the standard library, so you can think of and then as being defined like this. So it takes as left operand a function from a to b, and as right operand a function from b to c, and it yields the composition of those two functions. So that's a function from a to c, and its implementation is simply take an x of type a, apply first f and then g to x, so that yields a value of type c. So let's see whether this makes sense with an example. Let's say m.map f, where m is a list value. We know that lists are monadic values. So that would be the same as m.flatmap, where we apply f, yielding a single value, and then pass it to unit, and that gives essentially a singleton list of that value. And with flatmap, we concatenate all these singleton lists. So yes, mapping a function f over a list is the same as flat mapping the function that arises from first taking f to the argument and then wrapping the result in a singleton list. In other words, boxing in a singleton lists and concatenating the results cancels each other out. So that was an argument why it makes sense to define map that way. But if we argue in a monadic framework, then indeed we turn things around. We say we only define flat map, and that here is the definition of map. So it can, of course, then be implemented more efficiently, like avoiding the boxing and the flat mapping. But any such implementation has to satisfy this equation. So having unit and flat map of the right shapes is necessary but not sufficient to be a monad. To qualify as a monad, a type also has to satisfy three laws that relate flat map and unit. So the first law is associativity. It says that m flatmap f and then flatmap g is the same as m flatmap, a combined function that first applies f and then flatmaps with g. So here you can see the parentheses go like this, of course. That's how dot is defined. And here the parentheses are on the right. So that's an associative law. The second law is the left unit law. That says that if I take unit x of a monad and then I flat map with a function f, then that's the same as just applying f to x. And the last law is the right unit law, which says that if I flat map a monadic value with unit, then I get back the same monadic value m. So these three laws of associativity, left unit and right unit, one typically knows from monoids. So a monoid is a structure with these three laws. So that observation gave rise to the often cited remark that monads are just monoids in the category of endofunctors, which will probably leave you either utterly confused or utterly impressed. But to go on, we don't need to know about endofunctors, so you can treat this as just a funny remark alongside the remarks that monads are burritos or monads are elephants. So those monad laws, of course, they have to be checked for each type that is a monad or that pretends to be a monad. So let's do that for option. So here's flatmap for option. So flatmap on option says we have a function from t to option u, and it says, well, if the original optional value is sum of x, then we apply f to the original value. That gives an option. And if it's none, then we return none. And we've already seen that unit for option was sum of x. So let's test whether these two functions satisfy the monad laws. Let's check the left unit law first. We need to show that sum of x, flatmap f, is the same as f of x. So sum of x flatmap f, by expanding flatmap, that gives sum of x match, case sum of x f of x, case none, none. And that gives, by straightforward computation, we pattern match this with that pattern f of x. So the left unit law holds. Now let's check the right unit law. So what we need to show is that optional value flat map sum is optional value. So optional value flat map sum, we plug in the definition of flat map, that's what we get. Optional value match, if it's sum of x, then sum of x. If it's none, then it's none. And now to continue, we just make a case distinction. Optional value is either sum of x, in which case we get back a sum of x, or it is a none, in which case we get back none. So in either case we get back the optional value itself, and that means that the right unit law holds. The most complicated to check is the associative law. So we need to check that optional value flatmap f flatmap g is the same as optional value flatmap f underscore flatmap g. So let's start with the left-hand side. That left-hand side is by expanding flatmap twice this expression here. So the left expression here is optional value match case sum of x f of x, case none none. So that's the condition up to here. And then the second line is the second flat map, so that scrutiny would be matched against, again, case sum of y, g of y, case none, none. So what we do next is distribute this second match into the first. So we have this optional value match, case sum of x, f of x, and then we continue with the second match. Let's take the two together. So that gives f of x, continue with match, case sum of y, g of y, case none, none. And the same way for the second case here. So we would say, well, if it's a none, then it's none match, and then the same cases as before. So let's work on the second case first. So here we have none match, this one here. So that would reduce directly to none, because that none matches up with that pattern. So that leaves us this expression here. Now let's work on the first one. So here what we see is that this definition here is the right-hand side of the definition of flatmap, or more precisely f of x flatmap g. If we expand flatmap, we get exactly that. And we have seen that the equations in our program, in our Scala program, are true equations. We can essentially expand them and reduce them in both ways. So here we go from the expansion to flatmap to the original call of flatmap. And we apply the same trick again. So now this thing here is the right-hand side of this expression here, opt flatmap x, f of x flatmap g. So if we expand that, we get that. So that's also an equality. And that last one is just another way to write the original right-hand side of the equation. So that means that the associative law holds as well. So we've seen that monad-typed expressions are typically written with four expressions. What's the significance of the laws we have developed with respect to four expressions? Well, associativity says essentially that one can inline nested four expressions. So if you have an expression like this, 4, and then y is taken from the result of another 4 expression, and then z is taken from something else, then that's the same as inlining this inner 4 and putting it in front of the z. So it's the same as saying, well, let x range over m, then y range over f of x, and then z range over g of y yield z. So we can take nested four expressions and splice them in front of the things we define on the left-hand side and what follows. So the significance of the associative law is that it lets us flatten four expressions in that way. The right unit also has significance with four expressions. It just says that this is the identity. So 4x taken from m yield x is the same as m. Left unit, interestingly, doesn't have an analog for four expressions that I could discover. So it's right unit and associative that are relevant for four expressions here. In this session, we are going to talk about exception handling in Scala and what it has to do with monads. You've already seen exceptions as part of throws expressions. In fact, exceptions in Scala are defined similarly as in Java. An exception class is any subclass of Java-lang throwable, which has itself subclasses Java-lang exception or Java-lang error. So typically you inherit either from exception or error or from another class that in turn inherits from these. Values of exception classes can be thrown, so they can be parts of throw expressions. So here's an example. You can have a class bad input that extends exceptions. You typically have a message parameter, which is a string, as a parameter for these exceptions. And once you have defined that, you can have a throw expression with bad input and missing data as the exception that is thrown. A thrown exception usually terminates computation unless it is handled with a try-catch expression. So we'll see those next. A try-catch expression consists of a body and one or more handlers. So here's an example. Let's say we want to write a function validated input of type string that validates a user written input string. So it gets the input using getInput, and let's assume that this function here can throw a bad input exception if the input is not of the right format, say. So here we handle that exception with a catch clause. So we say catch case bad input message. In that case, if the exception is thrown, then we print the message and we call validated input recursively, which means we invite the user to type in another input string. Here we also have a catch-all or catch-most exception, second clause, that says, well, if it's some other exception, not bad input, then we print fatal error aborting and rethrow the exception. If there's no further try-catch clause around validated input, this thing will abort the program. So generally, an exception is caught by the closest enclosing catch handler that matches its type. We can formalize this with a variant of the substitution model. So roughly, we would formalize it like that. We would say, well, if we have a try, and then we have somewhere embedded in a so-called execution context E, a throw exception expression, and then the try catches the exceptions with a catch clause case XXC arrow handler, such that the type of the expression X matches this type XC in the catch clause. Then we continue the whole program with the right-hand side handler, where the formal parameter X of the handler is replaced by the actual exception EX. So the evaluation context E here can also be defined formally, but we won't do that here. It's basically a context that has the throw X at some place in some surrounding program code, such that the throw X is the next instruction to execute, and that context does not contain a more deeply nested handler that also matches X. Exceptions and try-catch are a convenient and low overhead way for handling abnormal conditions, but there are also some shortcomings. The first shortcoming is that exceptions don't show up in the types of functions that throw them. For instance, in the validated input example, that method here could throw an exception, but its type doesn't tell us that. Its type just says it will return a string. So exceptional values are not part of the return type of a function, which means that we are ignoring something which could be very important for software safety. That's the situation in Scala. Actually, in Java, certain exception types do show up in so-called throws clauses, but it turns out that this has its own set of downsides. These throws clauses are typically quite inconvenient to write and not very flexible. It would be very hard, for instance, to write a function like map that handles throws clauses correctly in all circumstances. So that's why the example of Java, by and large, has not been followed by other languages. Most other languages do not have exceptions in the result types of functions. But as I said, this is a problem from the standpoint of program safety. One of the research topics of my group at EPFL is precisely to find a new way to express effects, which what exceptions are, that doesn't have the shortcoming of the throws clauses in Java. So that can be written flexibly, that is polymorphic, and can be used to augment the contract of a function to also represent its exception types. But that's research, so we're not there yet. The other shortcoming of exceptions is that they don't really work in parallel computations where we want to communicate an exception from one thread to another. Exceptions are by their very nature tied to one thread. So it's in one thread that an exception gets thrown and caught, but to signal an exceptional condition from one thread to another, we need something else. So definitely in some situations it makes sense to see an exception not as something special that gets thrown and caught, but as a normal function result value. This idea is implemented in the type Scala util try. So here you see the definition of the try type. It resembles option, but instead of some and none, we have two cases, success and failure. So the success case is the analog of some. It takes a single value that it returns. The failure case, however, has some additional information, and that is an exception. So the failure case would be returned if the original computation threw an exception. As is the case for some and none, success extends try of t with the type parameter t, and failure extends try of nothing because no normal value is returned in that case. A primary use of try is as a mean of passing between threads and processes the results of computations that can fail with an exception. So how do you go from exceptions to tries? Well, you can wrap up an arbitrary computation in a capitalized try here. So try of expression gives success with the value of the expression if there's no exception, and it gives failure with some exception if that expression threw that exception. As usual, this is not magic, but simply an application of an apply method in an object named try, and here's its implementation. So apply takes a by name parameter expression, so expression is not yet evaluated when it's passed to apply, and it returns a try of t. And says, okay, wrap the value of the expression in a success, unless there is an exception, a non-fatal exception, in which case we wrap the exception that got thrown in a failure. Here, non-fatal matches all exceptions that allow to continue the program. Among all the exceptions that can be thrown from a Java program, some of them are really terminate the virtual machine and there's no good way to recover from them. So those are bypassed, but the others are caught in non-fatal. Okay, just like with options, try-valued computations can be composed in four expressions, which means that try has flat map and map defined. So you see an application here. For x taken from some computation, y taken from some other computation, yield of the function f of x and y. So what this does is that if compute x and compute y succeed with results success x and success y, this will return success f of x and y. If either computation fails with an exception ex, this will return failure of ex. So it will first do compute x, and if that's successful, do compute y. If either of them fails, you get a failure. If both of them succeed, you get this success value. So to be able to write four expressions on tries, we need a map and flat map. Here they are. Let's do flat map first. So it takes an xt of type try of t and a function f that maps a t to a try of u and returns a try of u. And here's the implementation. If xt is success of x, then it goes on with f of x. But there's a catch clause that says, well, if the second operation throws an exception, a non-fatal exception, then we convert that to a failure x. So in essence, what this does is we won't let exceptions escape the flat map of the try. If the first try was already a failure, then we just propagate that. Here's the definition of map. So it says, well, if the original try is a success, then apply f to x and wrap it again in a try. And if it's a failure, then fail. So we can establish a relationship between map and flat map as follows. So t.mapf is the same as t.flatmap x try of f of x. So by working with these definitions, we can establish the following relationship between map and flat map. T.map of f is t.flatmap of the function that maps x to try of f of x. And that again is just t.flatmap f and then try. So that looks familiar. It's just the relationship between map and flat map in a monad where the unit is try. So it looks like try might be a monad with unit equals try. Is it? possible answers are yes, or no because the associative law fails, or no since the left unit law fails, or no since the right unit law fails, or no because two or more monads laws fails. The solution is, it turns out the left unit law fails. So try expression.flatmapf is not the same as f of expression. Why not? Well, the left-hand side, what we've seen, we know that it will never throw a non-fatal exception. That was the definition of flatmap. Essentially everything we do here in the definition, if the computation of flatmap gives a non-fatal exception, we catch it and return failure instead. So the left-hand side doesn't return an exception, but the right-hand side could, of course. Any exception thrown by either expression or f would be propagated in the result. So that means that the left unit law here doesn't hold. You can see it this way. Try trades one monad law for another law, which is probably more useful in this context. Let's call it the bulletproof law. The law says an expression composed from try, map, and flatmap will never throw a non-fatal exception. And that, of course, is another good property to have, which just goes to show that laws, whether monad laws or others, are not sacrosanct. It always depends on essentially what the situation is and what we need these laws for. Even if try is not completely a monad, it's still very useful, and it's also possible to use for expressions with try, because it turns out that the left unit law is the law that actually is not relevant for the correct expansion of for expressions. So to conclude, we've seen that for expressions are useful not only for collections. Many other types also define map, flatmap, and with filter operations, and with them for expressions. We've seen generators, we've seen option, and we've seen try as examples. Many of the types that define flatmap are indeed monads. If they're also defined with filter, they are called monads with zero. The three monad laws give useful guidance in the design of library APIs. So essentially, break them at your peril. You should know what you're doing when one of the laws is broken. And generally, it's better to strive to actually have these laws and verify that they do hold. This week, we'll revisit performance issues caused by combinatorial search, and we'll discover an important concept in functional programming that can address these issues. The concept is laziness. Being lazy means computing a result only when it is needed. It turns out that this is a general and quite effective technique to speed up some functional code. You'll also learn a little bit about proofs on trees. In particular, we'll see how to extend structural induction to trees. In this session, we're again looking at proving things about functional programs. More specifically, we are going to prove laws about data structures using structural induction on trees. You know structural induction on lists from the first half of the course. But structural induction is in fact not limited to lists, it applies to any tree structure. The general structural induction principle is like this. To prove a property P of t for all trees T of a certain type, show that P of L holds for all leaves L of a tree, and for each type of internal node T with subtrees S1 to Sn, show that P of S1 and P of Sn and so on implies P of T. So if you have a tree with leaves here and some internal nodes, something like that, then the structural induction principle says, well, prove it for all leaves, and assuming that you have already shown it for the subtrees, let's say for this one and this one, show it for the interior nodes as well. So if you can do that, then you have established the principle for all trees. So to demonstrate that proof principle, let's go back to int sets. Recall our definition of int set. There was an abstract trait with two operations, include and contains. And that was implemented either by an object empty, where you see the definition of contains and include like that, or by an object non-empty, where you saw the definitions of contains and include like that. For a non-empty object, we always had a case distinction where the element to look up or to include is less than or equal or greater than the element on the right. And depending on that, we would then proceed with the left or the right subtree. So the invariant of these sets was that elements are ordered in the sense that if we have a tree here, so that's, let's say, lm equals 8, and then we have some subtrees here and some subtrees here, then all elements in the left subtree would be less than the element at the root, so less than 8 in this case, and all elements on the right subtrees would be greater than that root element. So that's a class hierarchy that claims to implement inset, but how do we know it's correct? Or what does it even mean to say an implementation is correct for insets? Where's the specification of inset? Well, for that it's good to go back to the introduction of the very first week of this course, where we talked about paradigms and why functional programming is based on theories. And there we said a theory is characterized by some values, operations on these values, and laws that relate the operations. So we can do that for inset, and then if you have laws for inset, then one way to define and show the correctness of an implementation means prove that the law of insets holds for this implementation. So what are the laws of insets? I propose those three here. So the first law is that empty contains x is always false. The empty set contains nothing. The second law says S include x contains x is true for any set S. So if we include an element in the set and then ask whether the set contains the same element, then that's true. And the third law says that S include x contains y is S contains y if x not equal y. So that means if I include an element x in a set and then ask whether the set contains another element different from the included element, then that's the same as asking whether the original set contains that other element. So these laws obviously make all sense of insets, and furthermore one can convince ourselves that these laws completely characterize what makes up an inset if we restrict ourselves to just the operations contains and includes. So we now proceed to prove these three laws using structural induction on trees. The material that follows is a bit more on the theoretical side. If you're more practically minded, then you might want to just essentially quickly browse it or skip it altogether and continue with the next session after. So let's go on and prove these laws. First law is empty contains x equals false. Well, that's obviously true because that's how contains was defined on empty. So according to the definition of contains, that's false. The second law is S include x contains x equals true. We prove that by structural induction on the tree S. So the base case is S is empty, then we have to prove empty include x contains x. So that's by expanding include, that gives us non-empty x empty empty contains x. And then by the definition of contains for non-empty trees, that is true. So let's now prove the induction step. The induction step means that our set S here is of the form non-empty, then some root element, some left tree, some right tree. And there are several cases to consider. The first case we consider is that the root element x and the element we include is the same one. So we have this expression here, and that one simplifies directly, because including an element in a set that already has that element at the top is the set itself, and asking whether this set contains x is, according to the definition of contains, true. So the law holds for that case. But that was just one of the possible cases for the induction step. Let's look at the other. So the next case would be non-empty YLR for the set S where y is less than x. What do we have in that case? So we have non-empty YLR include x. What does that give? Well, according to the definition of include, it means that if we include x in a set where x is greater than the root element, we recursively include it on the right subtree and reform the set with the remaining elements. So that's what you see in this expression here. And we ask whether that expression contains x. Now we look at the definition of contains, definition of contains says, well, if x is greater than the root element y, then look in the right subtree. So that would give us r.incl x contains x. And now we can use the induction hypothesis, because we are allowed to assume that on each of the two subtrees of this non-empty set, the condition holds. So we know for the tree R that R include x contains x, that's the second law, is true, and that means that the same holds for the non-empty tree here. There's a third case to consider, namely that we have a set of the form non-empty YLR, where now y is greater than x, and that one is of course completely analogous, so I won't repeat the reasoning here. You can try it for yourself if you want. So the last proposition is this one here. So if we have a set, let's call it XS, and an element x that's different from y, then XS include y contains x is the same as XS contains x. So asking whether a set contains an element after another element is included is the same as asking whether the original set contains that element. So we prove that law by structural induction on the set XS. There are two cases to consider. If x is different from y, then either x is smaller than y or larger than I, and we just assume the second case, that x is larger than y. The case where x is smaller than y is again completely analogous. So let's look at the base case. We have empty include y contains x, and we need to show that empty contains x. That's the right-hand side here. So let's expand incl. That would give us non-empty y empty empty contains x. And that means we have to look in the right subtree, so it's empty contains x. And that is our right-hand side. So that's what we needed to prove here. So we've established the law for the case empty. For the inductive step, it gets a bit more complicated. Here we need to consider a tree non-empty ZLR, where the element Z and the left and right subtrees L and R are arbitrary. And now it depends on where z is relative to y and x. So we have y and we have x, and essentially the z could be anywhere here. It could be less than y, it could be between y and x, it could be greater than x, or it could be one of y and x. So that gives us 5 cases. Z is x, z is y, z is less than y, z is between y and x, and z is greater than x. So let's tackle each of these 5 cases in turn. The first case is z equals x. So we have non-empty XLR include y contains x, and we have to show that this is the same as non-empty XLR contains x. So we know that y is less than x, so we construct a left subtree with y included and wrap the non-empty node around. That's what that looks like, and we ask again whether it contains x. And now the answer is true, of course, and that's also the answer if we ask non-empty XLR contains x. So we have established the equality. What if z equals y? Then our induction step would look like this, and we have to show that non-empty YLR contains x. And that follows directly by the definition of non-empty.include, because that's how include is defined. If we include an element that's already in the root, then we return the original set. So we're done for the 2 simple cases z equals x and z equals y. So what about the case where z is the smallest of the 3 elements, so z smaller than y? So we now have non-empty ZLR, where z is smaller than y, and as always y is smaller than x. That's what our initial expression looks like, and we have to show that that's equal to non-empty ZLR contains x. So by definition of include, we now include y in the right subtree because y is greater than z. That gives this tree here, and we ask whether it contains x. By the definition of contains, z is smaller than x as well, so we look in the right subtree. That gives this expression here. And by the induction hypothesis, that is r.contains x. And if we compare that to the right-hand side, non-empty ZLR contains x, then we see that we again have equality, because that's how this contains is defined on that node. X is greater than z, so we look in the right subtree. So we have established a 4-step equality between the left-hand side of the law and the right-hand side of the law. So the second case for the induction step to consider is where z is between y and x. So we have the same left-hand side as before, and again we have to show that non-empty ZLR contains x. So since y is now smaller than z, we include y in the left subtree and wrap the non-empty, as you see here, and we ask whether it contains x. So that's the same as right contains x, because x is greater than z. And that's the same as non-empty ZLR contains x by the definition of contains. Since x is greater than z, we search in the right subtree, so this expands to that term over here. And the third step is the case where z is now greater than both y and x. So we have again the same left-hand side, and we need to prove again that non-empty ZLR contains x in this case. So if we do that, then we proceed as before in the first step. We know that include will expand to an inclusion of y in the left subtree, and we ask contains x. And x is also less than z, so to ask whether this set contains x, we look again in the left set, so we have L include y contains x. Now by the induction hypothesis, that's the same as L contains x. And again, by the definition of non-empty contains in reverse, that's the same as non-empty ZLR contains x. These are all the cases, so the proposition is established. So if you want to explore this further, here's a harder optional exercise that you might consider. Let's suppose we add a function union to int set. We have seen it already. Here's a possible implementation of union. So for the non-empty set, we say to take the union of a non-empty set with some other set. We take the left set union, right set union, the other set, and then we re-include x at the end. So what does it mean to say that this or any other implementation of union is correct? Well, we need to have a law for union, a way to relate it to the other operators that we have. There's one quite obvious law for union, it's this one here. To say, well, if we take the union of two sets and then ask whether that contains an element x, then that should be the same as asking whether the left operand contains x or the right operand contains x. So your task is to show this proposition by using structure induction on the set XS. In this session and the next, we are dealing with laziness. Laziness means computing something as late as possible, only computing it once it's first needed. We're starting with lazy lists. So for motivation, we've seen a number of immutable collections that provide powerful operations, in particular for combinatorial search. For instance, to find the second prime number between 1000 and 10,000 is really easy. You can write, well, between 1000 and 10,000, filter with the isPrime predicate, and take the second number, so at index 1. It's a lot more tedious to write this with a recursive function from scratch. So here you see a possible implementation. Second prime is implemented in terms of nth prime, and then essentially nth prime has this tedious thing with counters that essentially counts the number of primes that were found, and then if it found the last prime that's necessary, it will return it, and otherwise it will go into the recursion one way or another. On the other hand, this more convoluted implementation is a lot faster than the one we wrote up here. Indeed, from a standpoint of performance, that expression is really bad. It constructs all prime numbers between 1000 and 10,000 in a list, but only ever looks at the first two elements of that list. The rest is thrown away. Of course, we could reduce the upper bound. We know that the second prime number will be a lot closer to 1000 than to 10,000. But of course, if we do that too much, then we risk missing the second prime number altogether. So we have to put some knowledge in from the outside, which we might not have. However, we can make the short code efficient by using a trick. The trick is that we want to avoid computing the elements of a sequence until they are needed for the evaluation result, which might be never. This idea is implemented in a new class in the Scala standard library, which is a lazy list. Lazy lists are similar to lists, but their elements are evaluated only on demand. So here's how you can work with lazy lists. They're defined from a constant lazylist.empty, which is the analog of nil for strict lists, and a constructor lazylist of cons, which is the analog of : for strict lists. So for instance, lazylist.cons1, lazylist.cons2, lazylist.empty is the lazy list 1 followed by 2 followed by empty. In what sense is it lazy? Well, it's lazy in the sense that a sub-expression like this one here will be evaluated only when we need the second element of the lazy list. Lazy list can be defined just as the other collections by using the object lazylist as a factory. So you can write lazylist 1, 2, 3, that translates to lazylist.apply 1, 2, 3, and indeed the lazylist object has a suitable apply method that will convert these arguments to lazy lists. Another way to get lazy lists is by converting some other collections to lazy lists. You can do that with the to method, which is available on most collections in the Scala library. So you write 1 2000.to and then lazy list, and that will turn this range 1 2000 into a lazy list. So to is another utility method defined on Scala collections. It essentially takes a object, which is a factory, and calls the apply method on that object on the elements that are to the left of the to. We can use some of these elements to define further methods that construct lazy lists. For instance, lazy range here. So lazy range would be construct a lazy list of the numbers between low up to high. It's a lazy list of int. And it's simply defined as you see here. If low is greater or equal high, then it's the empty lazy list. Otherwise, it's the cons lazy list with the first element being low and the rest being the result of lazy range of low plus 1 and high. If you compare to the same function that produces a list, which you see here, then you see that the two functions are very, very similar. The only differences are that we use lazylist.empty instead of nil and lazylist of cons instead of : otherwise it's exactly the same. So the two functions have almost identical structure, yet they evaluate quite differently. List range start end will produce a list with end minus start elements and return it immediately. Lazy range start end will return a single object of type lazylist. The elements are only computed when they are needed, where needed means that somebody calls head or tail on the lazy list, or is empty, I should say. Until that time, the lazy list object is not evaluated. We don't know yet what's in it. So lazy list supports almost all methods of lists, including filter. So for instance, to find the second prime number between 1000 and 10,000, we can now write lazylist.range 1000, 10,000 filter is prime element at index 1. The one major exception where the operations are different is cons. So x cons xs always produces a list, never a lazy list. There is, however, an alternative operator hash cons, which produces a lazy list. So x hash cons xs is the same thing as lazylist.cons xxs, and what it does is it produces a lazy list consisting of x as the first element, xs at the rest, and it does so lazily. That means the whole thing will be evaluated only when somebody needs to access an element of that list. Like cons, hash cons can be used in expressions as well as in patterns. This idea of laziness looks a bit magic at the beginning, and indeed the actual implementation of lazy lists is quite subtle. As a simplification to approach the subject, we consider for now that lazy lists are only lazy in their tail. That means the tail of a lazy list is computed when the first time somebody needs it, but the head and the is empty predicate of a lazy list are already set when the lazy list is created. That's not the actual behavior of lazy lists, but it makes the implementation simpler to understand. So let's call this simplified lazy list tail lazy list, because it's only lazy in the tail. So here's the basic trait. Trait tail lazy list should be a subtype of sequence. It has an isEmpty method and a head and tail method, so the same fundamental operations as a normal list. As for normal lists, all other methods can be defined in terms of these three fundamental operations. So now to finish the implementation, we just have to give concrete implementations of empty and non-empty lazy lists that define these three methods. Here's the empty lazy list. So it's a tail lazy list of nothing. Is empty is true, head and tail, throw an exception. And there's also a toString method so that we can print these things nicely, which just says it's lazy list empty. What about cons? So the main difference between cons and the list cons we have seen is this. The tail function now is a by name parameter. So it takes a head, which is a normal by value parameter, and a tail, which is a by name parameter of type lazy list of t. And it returns a new lazy list of t where is empty is false, the head is the head, the tail is the tail argument here, and toString is lazy list head, and then comma, and then we just put a question mark in here in order not to force the lazy list. So we say, converting the lazy list to a string, we don't really want to find out what the elements are by forcing the elements. We just print what we know. And in this case, because the head is a by value parameter, we know what the head is, but we don't know by the what the tail is without calling tail. When we call tail, then it would call this by name parameter, and that would in effect evaluate the expression that computes the tail of that lazy list. So the only difference between lists and lazy lists is really this. It's just the arrow in front of tail. So to reiterate, for lazy lists, tail is a by name parameter. For normal lists, it's a by value parameter. And that's why the second argument of tail lazy list.cons is not evaluated at the point of call. Instead, it will be evaluated each time someone calls tail on a lazy list object. You could argue, well, that's actually pretty bad, because if tail could be called multiple times, which would lead to multiple evaluations of this by name parameter. And that's a correct objection, and we will address that in the next session. Once we have defined lazy lists or tail lazy lists like that, we can define other lazy list methods just like the methods for lists. So for instance, here's the implementation of filter on a tail lazy list. It's really exactly the same as we would define filter on a normal list if we wanted to base it on the three fundamental operations is empty, head, and tail. So as an exercise for you, here's a slight instrumentation of lazy range. So it's what we had before, but each time we go into the body of lazy range, we print the current value of low. When you write lazy range 110 take 3 to list, what gets printed? Nothing, 1, 1, 2, 3, 1, 2, 3, 4, or 1 to up to 9. Okay, so let's see for a solution. If I just write lazy range 110, what would be printed? Well, I would expand it to the right-hand side, which would print 1. And then, depending on the two branches, would in each case return a lazy list, which means that nothing further needs to be printed because that expression is not executed. So lazy range 110 just prints 1. What is lazy range 110 take 3? Well, we don't have an implementation of take 3 here, but essentially you can imagine that it takes the head of the list, it takes the head of the tail of the list, and it takes the head of the tail of the tail of the list. That's the 3 elements it takes. So if it takes the head of the list, nothing further is printed because the head is already evaluated. So we already have the 1. If it takes the head of the tail of the list, now we go into tail once, so we go into this recursive instance again. So we print the second element, 2. And if we take the head of the tail of the list, we print the third element, 3. And that's it. So that's all we need for take 3. So if we convert it to a list, then of course we get the list 1, 2, 3. But before we get that, we print the elements 1, 2, 3, and not more than them. In this session, we'll introduce the concept of lazy evaluation, which is some language support and runtime constructs to make lazy computations more efficient. So we've seen that the previous implementation of tail lazy list suffers from a serious potential performance problem. If tail is called several times, the corresponding lazy list will be recomputed each time. This problem can be avoided if we store the result of the first evaluation of tail and reuse the stored result instead of recomputing tail another time. In a purely functional language, this optimization is sound, since the tail expression will produce the same result each time it is evaluated. So that means there's no need to actually do the evaluation several times, since we know that every value will be the same. We can just use the first value that we have computed. We call this scheme lazy evaluation, and that's opposed to the by name evaluation in the case where everything is recomputed, and strict evaluation, or for parameters by value evaluation, for normal parameters and val definitions. So by default, Scala is strict by value. It has by name parameters that evaluate each time they are called. And we now also want to have lazy evaluation, where we say we evaluate 0 times or once, but not multiple times. Some functional languages, including Haskell, use lazy evaluation by default. Scala, on the other hand, uses strict evaluation by default, but it still allows lazy evaluation of value definitions with the lazy val form. So you can write a lazy in front of a val, and then the value definition is as usual. And what that means is that the right-hand side of the val definition will be evaluated the first time x is used instead of immediately. So as an example, let's consider the following program that you see here. So I have def expr, and then a val, and then a lazy val, and then a def, and then I sum them all up like this. And for each definition, I actually print what gets evaluated on the right-hand side. If you run this program, what gets printed as a side effect of evaluating expr? So when I evaluate expr, I have a strict value definition x, so I evaluate its right-hand side immediately, which gives me an x. So x is the first thing that is printed. The lazy val will not yet be printed because it's lazy. The right-hand side of the def will not yet be printed because it's a def. So then we look at the expression here. So now we call z, and that prints z. So we have an x followed by a z. Now we evaluate y, so that would print y. Now we want the value of x, that's already evaluated, so nothing gets printed. Now we want the value of z again, so that will re-evaluate the right-hand side. That will print another z. Now we want the value of y again. In this case, because y is lazy, it is already evaluated. It was already evaluated once, so nothing gets printed. And finally, we want the value of x again, which of course is evaluated. So again, that's what we get on the right-hand side, x, z, y, z. So lazy vals allow us to overcome our performance problems for lazy lists. So tail-lazylist.cons can now be implemented like you see here. Instead of a def tail equals tail, we have a lazy val tail equals tail. That's all that's needed really. That means that the first time somebody calls tail, we will evaluate the call by name parameter TL, but the next time somebody wants tail, we have the value already stored here, so further evaluations of tail are avoided. So this laziness business might look a little bit like wizardry to you in the sense that it's pretty smart at avoiding computations. To see it in action, we can just essentially use our basic substitution model and verify step by step that indeed laziness does what it promises. So let's start with the original expression that we have. Lazy range 1000, 10,000, filter is prime, apply 1. And we want to reduce that from first principles using our standard rewrite rules, and then verify how much of the list 1000 to 10,000 actually gets constructed. So we first expand lazy range. That gives us this expression here with the parameters substituted, and then we plug that into the rest of the expression that you see here. Now we simplify the if then else, so that reduces to the else part, which you see here. So one thing that's important here is that this expression here hasn't been reduced yet. It's left as it is because it is a call by name parameter to cons. Let's abbreviate this expression to just C1. So we have C1.filter is prime, apply 1. So we now expand filter on the C1 value. which gives us here the right-hand side of filter with the isPrime method at the right place here. So if we simplify that, then we know that C1 is not empty, so it's going to be this one here. If isPrime C1.head, then this cons expression, otherwise C1.tail filter. Now we evaluate C1.head, so that gives isPrime 1000, and if we follow the computation of isPrime, we will see that this reduces to false, so we are left with this expression here. Now we can simplify the if then else, so we are left with C1.tail filter isPrime apply 1. And now we go back to the actual argument of the C1 expression that corresponds to the tail. That was lazy range of 1000 plus 1, 10,000. So at this point we compute that 1000 plus 1 is 1001, and we plug it into the expression here. So it's lazy range 1001, 1000, filter isPrime, apply 1, which is basically what we started with, except that we have a 1 here now. And that evaluation sequence continues like this until we hit this situation here, where we have lazy range 1009, 10,000, filter isPrime, apply 1. And now by the evaluation of lazy range, we get a cons 1009 and this expression here, filter isPrime. If we abbreviate that to C2, and we are left with C2 filter isPrime, apply 1. Now 1009 is a prime number, so we get the second case that we get, okay, our prime numbers consists of a cons followed by the tail. And now we have to finally evaluate the apply method we get there. So let's assume apply is defined like this. So if n equals 0, then head, else tail apply n minus 1. So what we would get here is, for the right hand side of the apply method, a 1 equals 0, because 1 is the index here. So that's false, so we continue with the cons in the else part that you see here. And that means now we have a call to tail, because that comes from the apply method. So we take essentially this tail of the cons, which gives us C2.tail filter isPrime, apply 0. And that by computing what is the tail of C2, we get lazy range 1010, 10,000, filter isPrime, apply 0. And that process continues until finally we have lazy range 1013,000, filter isPrime, apply 0. That then gives the cons expression as before. So it's cons 1013, lazy range of the rest, filter isPrime, apply 0. Let's call that C3. If we filter that expression, we get cons 1013 and then this tail, because 1013 is in fact a prime, so the filter will include it as a first element. And that then is the final result. So if we look at our rewrite trace, then we will see that indeed we have never constructed a lazy list beyond the element 1013. So we have computed exactly as many elements as we needed to verify that the second prime number following 1000 is 1013. Good. So the simplified implementation of lazy lists that we have worked with has a lazy tail, but not a lazy head, nor a lazy is empty. The real implementation of lazy list is lazy for all three operations. So lazy list is a lot lazier than tail lazy list. To do this, it maintains a lazy state variable, a bit like this. So there is a class lazy list in the standard library that has essentially an init parameter that computes the state of the lazy list. And the state of the lazy list is either that it's empty or that it's a cons of a head of type T and a tail, which is a lazy list. But that state, so that the lazy list knows whether it's empty or a cons and what the head is, that is altogether computed lazily by this by name parameter. So that's the essential difference between the two. In this session, we're looking at an interesting consequence of lazy computation, namely that we can compute with infinite sequences. You saw that the elements of a lazy list are computed only when they're needed to produce a result. That opens up the possibility to define infinite lists, For instance, here's the lazy list of all integers starting from a given number. From n, int, it's a lazy list of int, and it's defined to be n followed by from n plus 1. Or that's the list of all natural numbers. Val nats equals from 0. Or to compute the list of all multiples of 4, we can do nats map times 4. So why does this all work? Well, it works because when we create the lazy cons here, the expression here will actually not be evaluated. It will only be evaluated when we need the head of a tail of the resulting lazy list. So we can in complete confidence compute all natural numbers because they will in fact be computed only once somebody asks for a particular natural number. And of course you can never ask for all of them at the same time. It's always a particular one, and then you compute the natural numbers up to that number. The same holds for the multiples of 4. So I'll show you that in a worksheet. Here's the definition of from that you saw from the slides. Let's define nats. So that gives you a lazy list of int whose value is the lazy list that's not computed. So that's how it prints. Now if you would write nats, let's say take 10. So let's take the first 10 element of the natural numbers. And we still get lazy list not computed. So when do we see anything in a lazy list? Well, one good way is to convert it to lists. So we can do nats.take10.toList. And now we see something. What happens if we just write nats.toList? So I saved. And we get evaluate worksheet, so nothing happens, of course, because to convert all natural numbers to a list, that would never finish. The list would be infinite. So I stopped that computation. So you might say, that's cute, but is it useful? Yes, actually, you can do quite a few very useful things with infinite lists and other infinite data structures. One useful application is an ancient technique to compute prime numbers called the sieve of Eratosthenes. The idea can be visualized as follows. So we have an array of all numbers here, and we start with 2. So we say 2 is a prime number, so that's it. And now we cross out all multiples of 2. Now the next number that's 3 is 3, so 3 is a prime number, and we cross out all multiples of 3. So that one is already crossed out, that one is freshly crossed out, that one is already crossed out, that one is freshly crossed out, and so on. Now we see the next empty field, that's 5. So 5 is a prime number, and we cross out all multiples of 5. So at each step, we take the next free field. That field is a prime number, and then we cross out all its multiples. In the traditional formulation of the sieve of Eratosthenes, the array here was finite, so you computed prime numbers in a certain interval from 2 up to the last field of that array. What we want to do now is we want to generalize the technique to compute arbitrarily many prime numbers without having an a priori upper bound. So to review the algorithm is we want to start with all integers from 2, which is the first prime numbers. We eliminate all multiples of 2. The first element of the resulting list is 3. We eliminate all multiples of 3, and like that we iterate forever. So the list we work with needs to be a lazy list because it doesn't have an upper bound. So here's the sieve function that implements this principle. It's surprisingly short. So here we have def sieve. It takes a given list of integers and it filters them so that it takes the head of that list. Then all remaining elements we keep only those that do not have the head as a divisor, so that we keep only those elements x, where x modulo s dot head is different from 0. And that remainder of the list gets recursively sieved again. So the prime numbers now would be the sieve applied to all the natural numbers from 2. So let's test this in the worksheet. I have copied the definition of sieve and primes, and now let's just find out what are the first 100 primes. So here we see the list, or we see it also if we hover over it. So yes, that looks correct. Those are the first 100 primes. So the lesson to take home here is that many algorithms that previously required an upper bound can now be extended to arbitrary size by using lazy data structures such as lazy lists. Lazy lists are also useful to define components that can be put together in very flexible ways. For instance, if we come back to our previous algorithm for square roots, there we always used a is-good-enough test to tell when to terminate the iteration. So we had in one loop the iteration, so the next compute the next step, and the test when it was good enough and we could return the result. With lazy lists we can separate these two concerns. We can now express the concept of a converging sequence without having to worry about when to terminate it. So here we could have a square root sequence that essentially, instead of computing the final value of square root, gives us the sequence of the approximations. So each improved step is what we had before, so it's the average of the existing guess and x divided by guess. And then we have a lazy list of guesses that starts with 1 and is followed by guesses map improve. Now you might be puzzled and ask, well, that looks weird. Guesses uses itself its own value in its right-hand side, but yet it is a val and not a def. So how can that work? Well, it can work in some situations if the value of the valdef is a lazy list or other lazy data structure. So let's trace the construction of the first few values of the list that we do here. The first value is clearly 1. It's followed by the guesses map improve. So the first value of what follows is the first value of the original list map with improve, so it's I of 1, where I abbreviate improve to I to save some space. What's the next value of the list? Well, the next value of the list is the second value of guesses mapped with improve, so it would be I of 1. And the fourth value would be the third value with improve, so you see every value contains one further application of improve. So what you have here is essentially the iterate of improve, where every value applies improve one more time. And that's precisely the converging sequence that gives you a square root. So all you need to do in the end is return that guesses. You might still not be quite satisfied and ask, well, why is this a lazy val? Why can't it be a normal val if you have argued so convincingly that the resulting sequence is okay? So, as always, let's try it out. So we have here our original square root sequence. Let's remove the lazy val. What do we get? Well, we get a type error. It says guesses is a forward reference extending over the definition of guesses. So what Scala has is essentially it has built-in checks that verify that we cannot have a recursive or mutually recursive or forward definition of a val in a local list. And that check here refuses the program. But the check is conservative. So in principle, in this, if the compiler would let this program pass, then the execution would still give us the same result. So in principle, it would be okay, but the compiler is overly conservative. However, we can avoid the check if we declare the value a lazy val. So that is the solution of the mystery, why we need a lazy here. Okay, so the point of having a sequence of approximations is that we can add the criterion when to terminate the sequence later. So we could have now a separate method is good enough that takes the current guess and the original value from which we want to take the square root, and it just says, well, if the square of the guess minus x divided by x absolute is less than 0.001, then that's good enough. And then we can compose square root steps with good enough. So what this expression would do, it would keep only those approximations that are close enough to the value that we want. So let me show you that in the worksheet. We have the good enough test here, and here we have the expression that filters the original square root sequence with the is good enough test, assuming that the value we want to take the square root of is 2. So if we save that, we get a lazy list. It's not computed. So to actually get the final value of square root, we just take the head of that list. So we have a series of approximation. We take those that are good enough, and we take the first one that is good enough. That's the value of our square root algorithm. So this is a very nice decomposition of the original square root problem into smaller and smaller steps. It was used as the original argument of quite an influential paper, which is called Why Functional Programming Matters. The author of that paper was John Hughes. So let's finish with an exercise. Consider two ways to express the infinite list of multiples of a given number n. So we could say the multiples of n is take the list of all natural numbers and map each by times n. Or we could say take the list of all natural numbers and filter those numbers that modulo n are 0. Which of the two lazy lists, which both compute the same result, generates the results faster? The first, the second, or is there no difference? And the answer is the first, simply because the first doesn't compute any elements that then are later dropped. So for the first, every element we compute in the list will contribute to the result immediately with the map, whereas the second list generates more elements that then are discarded by the filter. So the first technique is faster. We conclude this week with a case study where we solve another well-known programming problem with the help of lazy data structures. The problem is the water pouring problem. So the water pouring problem is formulated like this. You're given some glasses of different sizes. For instance, you might have a glass of size 4 units, and a bigger glass of size 7. Your task is to produce a glass with a given amount of water in it. So for instance, you could say, well, we want 6 units of water in one of the glasses, so clearly has to be the second one. So we want 6 units of water in here. However, you don't have a measure or a balance. All you can do is fill a glass completely, empty a glass, or pour from one glass to another until the first glass is empty or the second glass is full. So what we're after is an algorithm that will produce a sequence of moves, where a move can be one of these three, that ends in a situation where one of the glasses holds the required amount of liquid. Before we jump into the code, let's develop a strategy. So we're given these glasses. I keep the same example as before, so 4 and 7, just as an example. And we need to produce a target in one of the glasses. So what we can do is, well, we would start in the empty state, and then from that state we can do moves. For instance, we can do the move which says fill the first glass. I'm going to start the indices at 0, so the first glass has index 0, the second glass index 1. So I would have a move fill 0, and that would give us a new state where the small glass is filled and the big glass is still empty. Or I could have another move which says fill 1, and that would give us a state where the small glass is full, where the small glass is empty and the big glass is full. Or I could have another move, let's say empty glass number 0, and that would of course do nothing because the glass 0 is already empty, so that would lead back to itself. So those are possible results of an initial move. I can then follow that with further moves. For instance, here I could have a move pour from 0 to 1, So that now would give me a state where the first glass is 0 and the second glass is filled with 4. And I could go on. I could then say, okay, for instance here, fill 0 would give me 4 in 0 and 4 in 1. So that's 4, 4. Then I could say, again, pour 0, 1. So that would give me a glass where now the second glass is full, 7, and the first glass has 3 units in there because I could pour sorry, the second class, the first class has 1 unit in there because I pour 3 units from the first to the second, and so on. And similarly, I can expand here the paths as well. And the idea is then I would essentially do this exploration until I find a path that ends in the required target state. But how do I do the exploration? Well, one idea is using a lazy data structure, I could simply compute all possible paths and then pick one that ends in the correct target state. But of course, there's an infinite number of such paths, so I have to answer the question, how do I avoid exploring a subspace of the search space without finding the correct solution where the solution is somewhere else? So the idea to avoid that would be that we produce shorter paths before longer paths. So we first produce essentially all paths of length 1, then we produce all paths of length 2, then length 3, length 4, and so on. So at each step we produce all possible paths that originate in the empty state and that have a length up to the length of that step. That avoids falling into an hole of infinite paths because we go essentially from smaller to larger. The second thing to watch out for is cycles. So another thing I could do here from this state is a move pour 1, 0, which would go back to the original state. And that's essentially useless because I have just done needless work. And that will never be on the shortest solution to the target state. So I want to avoid such cycles. And the way I do that is that I simply will keep track of what target states have already been reached. And if a path leads to one of the target states that have already been reached, then it's discarded. So that edge here would be discarded by this step of the algorithm. So before we put that in code, let's spend some thought on how we are going to represent things. I've already said classes are indices, they're numbered from 0 for the first class, 1 for the second, and so on. So the type class is just an alias for the int type. And then we have to represent states or configurations. That means how much water is in what class. So a state can be represented as a vector of int with one entry per class. So that means, for instance, the vector 2, 3 would be a state where we have two classes that have 2 and 3 units of water in it. So for instance, vector 2, 3 would be a state where we have two classes, and the first class has 2 units of water in it, whereas the second class has 3 units of water in it. So those were the states. What about the moves between states? A natural representation for them would be as an enum, where one case would be empty a glass, another move could be fill a glass, and the third move could be pour the content of glass from to glass 2 until either from is empty or 2 is full. Okay, so let's set up things in the worksheet. We have the type class and state as discussed, and then we have a class pouring, which contains as parameters the state with all glasses full. So that means for every glass we know what the capacity of the glass is, because that's in the full state. So that's the parameter for my pouring class. Then we have our enum of moves, which is empty, fill, or pour. And what I'll do is I'll already describe what each of these moves does to the current state. And I'll do that in an apply function. So I can apply a move to a state, and that gives me a new state. So what does the application do? So if the enum, so that's this here, is empty, so if the move is empty glass, then the state would be the state updated, so it's the old state except at the index glass where the state will be 0. If the move is fill glass, then the state is the state updated such that at the index glass now the glass will be full. So we have the original state where the glass is at capacity. And the third move is pour from one glass to the other, where is here we first compute the amount that is going to be poured from one state to the other. So the amount would be, well, we can only pour what we have in from, so that's state of from. and we can also only pour what remains in 2. So that would be full of 2 minus state of 2 is what's still empty in glass 2. So that those are two upper bounds for what we can do. So the amount that we will pour is the minimum of those two amounts. Once we have computed that, then the new state would be the state where the from glass has its contents diminished by amount, so its state of from minus amount, and the to glass has its state augmented by amount, so its state of to plus amount. So that's the move. The next thing we could do is, well, what moves do we have? Can we enumerate all the moves? Because that will be useful if we want to enumerate all the solutions. And yes, that's an easy exercise. So to enumerate all the moves, let's first enumerate all the glasses. So the glasses is just the range from 0 until full dot length. So that's the possible indices we have. And then what moves could we do? Well, we could empty one of these glasses. So that's the expression 4g taken from glasses, yield move.empty g. Or we could fill off one of these glasses. So that's the second one, 4g taken from glasses, yield move.fill g. Or we could pour from one glass to another. So that would be 4g1 taken from glasses, g2 taken from glasses. If g1 is different from g2, we can't pour from one glass into itself. Then yield move.pour g1 to t2. Okay, so the next step to model is a path. So how do we do that? So the way we want to do that is that we want to essentially record paths in reverse order. So a path is a list of moves, but what we want is essentially the history. So the last move in the path should come first, and the first move from the initial empty state would come last in that history. So a path would have a history, which is a list of moves, and then it's also useful to already record what the end state of that path would be. So that's the two elements of a path. So if you want to print a path, then what we do is we print the history in reverse, so that now we go forward from the empty state, and then we print an arrow and we print the end state. So that's the end state, the configuration that that path leads to. We also have a utility method extend. So that tells us what path results if we add and move to the existing path. And the path that results is given here on the right. So the history of the path would be the move that we extended with and the existing history. And the end state of the path is simply the move applied to the end state of the current path. That's the apply function that we have defined up here, which precisely tells us essentially what moves do to state. So the new end state is the move applied to the old end state. Okay, and then we start from the empty state. So that empty state is simply the full state where we map all content to 0. And our start path is then the path that has no history because we just started and has the empty state as current state. So one interesting observation is that so far we haven't actually written an algorithm to compute the solution. We just modeled the domain. We said, okay, how do we represent classes, states, moves, what moves do we have, what are paths, and that was it, basically. So good domain modeling helps to keep the actual search algorithm very clear and very short. So let's go to the algorithm next. There are two parts to it. One part builds the infinite list of possible paths, and the second part then picks out the right solution from that very, very large list. So the first part is done with the path from method. So path from is similar to the from method on natural numbers that we've seen. It takes an initial list of paths and an initial set of states that were already encountered, and it gives us essentially all lists that start in these paths. So that would be a lazy list of paths. The idea here is that the path from that it gives is ordered by length. So each element in that lazy list is a list of paths. And the first element, if we start from the empty state, would be all the paths that have length 1. The second element in that lazy list would be the list of all the paths of length 2, and so on. So the paths that are in the outer lazy list are ordered by length. Okay, so how would we produce that right-hand side within paths from? So if we go back to our strategy, so we're given a list of paths, all of the same length, and we want to extend it by essentially one move each of those paths. So what we are after is essentially the next circle around here. Call that the frontier. So the frontier is essentially the set of paths extended by one. And the frontier is computed here. So we say, okay, let path range over all the paths that we have now. Let move range over all the possible moves. Let's extend the path with the move. That gives us essentially the next path. And then let's keep the path if its end state is not already in explored. If it's already in explored, then that would be a cycle and we can drop that path. So the paths that survive that criterion form part of the frontier here, so they are returned. Okay, so that gives the frontier. So now we want to compute all the possible paths that start from an initial set, so that would then be the initial paths that we have, followed by the paths from, now the new frontier, and the set that we've explored is the previous set that we've explored, plus all the end states of the frontier paths, so frontier map end state. So we combine the two, that gives us a set of paths that's explored now. And of course that gives us an infinite list of paths, but that's not a problem because this thing here is a lazy cons and we produce a lazy list, so we will expand that list only to the degree where somebody wants to find an element in the list. Okay, so now that we have explored the search space using paths from, so that we can now span an infinite list of paths, let's find the paths that lead to a solution in that infinite list. So that's the solutions method. It gives us, again, a lazy list of paths, and it contains all the possible paths that we have constructed in paths from that end in the target state, so that have a class that contains the required amount, target, of units of liquid. So what we do then is we construct the search space here in paths from. We start with the empty state, and what we have explored, nothing so far, so no state has been explored. So now that we can construct all possible paths that start in the empty state using paths from, we use that to pick those paths that end in the required state. So we want to pick those paths that end in a state such that there is a class with target unit in it. So the way we do that is we span the possible search state with paths from. The initial path is just the start, the single list start, and the initial set of explored state is just empty because initially all classes are empty, so that's a state we know, that's the original state, and that's the only state in the set. So then we take an arbitrary path from the search space. We ask whether the end state of the path contains the target, and if that's the case, we yield the path. So now we have a lazy list of paths where every path is a solution to the original problem, and furthermore the lazy list will be ordered that shorter paths come before longer paths. So that's the whole algorithm. So to use it for an example problem, let's define a problem. Let's say it's pouring with the vector of two glasses of size 4 and 7 as discussed. And now to find a solution to have a certain target state, what we write is problem.solutions with the target. Let's say we want a glass with size 6 in it. So that would give us a lazy list of paths, and what we want is the shortest. Now to get one solution, we just take the head of that list. That will give us the shortest possible solution to the target state if one exists. And indeed it has found one. So here it is. It ends in the vector 4, 6. So one of the classes has 6 in it. And here's the sequence of moves. We fill first the first class, the one that, we fill the second class, the one that contains 7 units. We pour from the second class to the first. We empty the first, and so on. So I invite you to try it out and verify that we will indeed get the vector that it claims to get here at the end. So that was a solution to the water pouring problem that was quite elegant and short, and that made crucial use of lazy infinite data structures to achieve that. Of course, it's not the only possible solutions. There are many variants possible. We could, for instance, do a different choice of representations. Here we define specific classes or enums for moves and paths. One could have also encoded them. We defined object-oriented methods where it was natural. One could have also used naked data structures with functions. So the present elaboration is just one solution, not necessarily the shortest or most efficient ones, but it's reasonably short and reasonably efficient. Some guiding principles for good design that I sort of employed implicitly everywhere. One is naming is really important. Name everything you can. Avoid long expressions with lots of anonymous functions and things like that. So it's true that sometimes it's hard to come up with a good name, but it's definitely always worth the effort. So try to name everything you can and try to find good names for the definitions that you have. The second observation is that scoping is important. One should put operations in the scope where they fit naturally. And the third observation is essentially to come back to data abstraction. One should keep degrees of freedom for future refinements. So the interface of a module should not be concerned with the implementation details in that module. By now, you've gained quite a bit of experience with Scala's type inference, which lets you omit type parameters and type annotations in many situations. Type inference comes down to the compiler filling in certain types from values or expressions that you as a programmer provide. Typically, type parameters for a function are inferred from argument values to that function, and result types of definitions are inferred from their right-hand sides. In this week, we'll cover the dual of type inference, which is also very powerful and useful. Term inference means that the Scala compiler can, in certain situations, infer a value or expression from a type. Values and expressions are also called terms, hence the name term inference. There are several cases where this is useful, and we cover two important ones this week. First, this lets us do type classes, where implementations of certain types are generated by the compiler, knowing just the required types. Second, this gives us a rather general way to pass contextual data from the points where it is generated to the points where it is accessed. In this session, we are going to talk about contextual abstraction, what it is, and how it is supported in Scala. So if you look at the word context, it's formed from con, which means Latin with, and text. So it means what comes with the text, but is not in the text. So it's a very general concept, which in fact comes in many forms. So context could mean the current configuration, which is the same everywhere, except that maybe at some point you want to change it in some parts of your code. Or the current scope. Or the meaning of an operation like less than on this type. Or, going out further, the user on behalf of which an operation is performed. Or the security level in effect. It's really very general. It could mean many things. Code becomes more modular if it can abstract over contexts. Abstracting over context means that functions and classes can be written without knowing in detail the context in which they will be called or instantiated. So how can we represent context in programming? There have been so far several techniques to do that, and they all have downsides. So what we can see is we can represent context as just global values accessible to the program. But that means we have no abstraction, and that's often too rigid. That means the global value is just known for everybody, and we can't change it anywhere. So we might change that to global mutable variables that can be set according to the needs of various program parts. However, what if different modules need different settings? That could give you interference where you think you have one setting, but in fact somebody has changed the variable and you have a different one. And such interference can of course be very dangerous. Some dynamically typed object-oriented languages have introduced a concept called monkey patching. What that means is something similar to global variables, but instead of changing a global variable, you change a property of a root class. So for instance, you might have the base class object and you add a new method to object that's visible for everyone, or you change the behavior of a method. So that has a slightly more limited scope than globals, because it affects only classes inheriting that root class, but it's essentially just a more powerful way to shoot yourself in the foot, I think. Another solution is provided by so-called dependency injection frameworks. Examples are Spring or Juice in the Java world. These have sprung up because programming languages haven't offered out-of-the-box solutions to the problem of how to abstract over contexts. What they do is they are outside the language and essentially rely on bytecode rewriting to add dependencies to programs. So that's powerful, but it also makes programs harder to understand because now you have to understand the programming language and the bytecode rewriting framework. And it's in particular harder to debug because there's now a lot of code in your way that you haven't written yourself, but some framework has written. So all this was very imperative. What would be a functional way to represent context? Well, in functional programming, the natural way to abstract over context is with function parameters. So if you want to abstract over something that is known from the outside of a function, then make it a function parameter. That's, of course, very flexible. It's also type safe, since parameters have types and the types are checked. Your programs become safer. You can't have a type error when you read something from the context. And it's not relying on side effects, which is definitely a bonus. So why is not everybody doing that? Well, sometimes this is too much of a good thing. If you use that technique extensively, it can lead to many function arguments, and most of them are the same from one call to the next, so they hardly ever change, which of course means your code will be very repetitive, and in all these repetitions, errors will be hard to spot. So that's the downside of essentially overdoing this functional parameter approach to context representation. But as we will see, it has a solution in Scala. Let's demonstrate the problem with an example. You've already seen sort functions. For instance, here's the outline of a method sort that takes as a parameter a list of ints and returns a list of int. Somewhere in the body of sort you would find a comparison of two list elements, so if x less than y, something like that. Now that worked for a list of ints, but of course we want a more general sort that works for lists of arbitrary types. So here it is, that's a sort function which now takes a type parameter. But this does not work because there's not a single comparison method less than that works for all types t. So if you would write less than here, you would get a type error which said that the type parameter t doesn't have a less than method. In other words, we need to ask the question, what is the meaning of less than on type t, so the actual instance of type t, at the call site? And this means we need to query the call site context. So let's apply our strategy to represent context as parameters. That's the most flexible design. We just pass the comparison operation as an additional parameter. So sort would now take a list and a less than method, which compares two elements of type t. And instead of having the less method directly, we write less than xy. That works. We can now call sort as follows. So let's say we have a list of ints and a list of strings like that. Then we would write sort ints with the less than method, which is integer comparison here, and sort strings with the less than method, which is a string compared to less than 0 here. So in each case, we have passed the appropriate method to compare the elements of the list. In fact, there's already a class in the standard library that represents orderings with less than methods and also less than or equal, greater, and so on. It's called Scala math ordering, and it's parameterized by the type for which the ordering is defined. So that method provides ways to compare elements of type A. which means that instead of parameterizing with the less than function, we could parameterize with ordering instead. So that's what this would look like. We would have the sort method, and it takes an ordering of t, and then instead of less than, we would write ord.lt, which is essentially the less than method defined in that ordering. And calling the new sort method would look like this. We would import Scala math ordering, and then we sort the integers list with the integer ordering.int, and the strings list with ordering.string. That makes use of the values int and string in the ordering object, which define the orderings for the types int and string respectively. So for instance, here would be the int value in the ordering object. So it's an ordering for int, and what we have to do is we have to define a compare method that will give us back -1 if x is less than y, +1 if x is greater than y, and 0 if they're equal. So it would have the typical compare method for integers, and then the lt and the other less than, greater than comparison methods would all be defined in the class ordering in terms of compare. And of course the ordering.string would be defined analogously. So this works, but there's a problem, namely that passing around these ordering arguments is quite cumbersome. So sort int's ordering of int, sort strings ordering of strings looks heavy. And you could argue that sorting a list of int value should always use the same ordering int as an argument, whereas list of string value should always use ordering of string. So why make it mandatory to add these things? Can't the compiler figure that out? And in fact, we can let the compiler infer that and reduce the boilerplate by making ord an implicit parameter. We make it an implicit parameter just by prefixing it with the keyword using, as you see here. So now ord is an implicit parameter, which means that the compiler can synthesize the correct arguments that match the ord parameter. So you can omit the parameter and just write sort of ints, and the compiler will figure out it needs an ordering.int argument here. Or you can write sort of strings, and the compiler will supply an ordering.string. So in general, the compiler infers the argument value based on its expected type. And of course here the compiler knows at this point that since you sort a list of ints, you need an ordering of type int, and here it needs an ordering of type string. So the expected type is known, and with that expected type you tell the compiler to figure out what the right argument value here is. So what happens there is in a sense the dual of type inference. Type inference is when the compiler infers types from values. For instance, in the previous calls to sort that we see here, what the compiler really does, it supplies the type parameter int in the first case and string in the second case. And that it infers from the type of the actual values that get passed to sort. But the Scala compiler is also able to do the opposite, namely to infer expressions, which we sometimes call terms, from types. And so consequently this is called term inference. When there's exactly one obvious value for a type in a using clause, the compiler can provide that value to us. So it will further go and say, well, sort int ints will actually be augmented with the argument ordering.int, and sort string strings will be augmented with the argument ordering.string. So this looks very useful, and at the moment it also looks a little bit like magic. So in the following sessions we will explain the precise rules for this to happen. In this session, we'll explain the magic I alluded to in the last session, where the compiler could infer a value for a type. It comes down to using clauses and given instances. So an implicit parameter is introduced by a using parameter clause. That's the one you have seen, using ordering of t. If we have a parameter clause like that, we can pass a matching explicit argument in a using argument clause. So you repeat using again, you write sort strings using ordering of string, and that would match up with this parameter. But the point is that arguments for implicit parameters can also be left out, and they usually are. If the argument is missing, the compiler will infer one from the parameter type. So sort of strings will become sort of strings using ordering of string. Here are some variations of using clauses. So you can have multiple parameters in a using clause, but then you write the keyword using only once at the front of them all. Analogously, you can also have multiple arguments with a single using in the front. Or you can have several using clauses in a row. So for instance, you could have a using clause for A here, followed by a using clause for B. Or you can mix using clauses freely with regular parameters. So here you would have a case F where you have a regular parameter x, a using clause a regular parameter y, a using clause b. And if you pass arguments explicitly, then they follow exactly that pattern, x using a, y using b. But this one here or this one here can also be left out. You might ask, if I have two using clauses that follow each other and then I write a single using argument clause, like as in this using y, which one will be matched? And the answer is it's the first one. So essentially you fill in using clauses from the left, and if there are no using argument clauses left, then the rest will be inferred by the compiler. Parameters of a using clause can also be anonymous. You could write just using ordering of t and leave out the ord parameter. That's useful if the body of sort does not mention ord at all, but simply passes it on as an implicit argument to further methods. You see that situation here where the only use of the ord parameter is to pass it on to the merge method that does the actual comparisons. Code that you see here is analogous to the following code where the parameter names are put back and the arguments are made explicit. So here everything is named and I pass ord explicitly, and here the parameters are anonymous and the implicit argument is inferred. So this pattern where you have a type parameter t and then a using clause that uses t in some trait like ordering is actually quite common. So this syntax colon ordering is called a context bound in analogy to an upper bound or a lower bound, which you know already. So instead of having, let's say, an upper bound for t, we have essentially a constraint that says there must be an instance for ordering that is defined on t. And that's another form of bound, which is called context bound because it refers to the situation at the call site of the print sorted method in this case. So more generally, a method definition such as this one here, where t is followed by a number of types, each following a colon, would be expanded to just a simple type parameter t, and then for each of these types here, you have a using parameter, an implicit parameter, u1 of t up to un of t. So the t gets repeated each time in the argument of these type constructors u1 to un. So we've seen previously that a parameter in a using clause, such as using ordering of int, gets instantiated with an ordering of int value. For this to work, that ordering of int must be defined as a given instance. So you see here the given instance for that value int is written given int, its name, then the type it implements, that's ordering of int, and then the methods that need to be implemented for an instance of that type. In our case, ordering of was a trait that had a compare method that gets implemented here in the given instance. So that code defines a given instance of type ordering of int named int. Given instances can also be anonymous. You can just omit the instance name. An example you see here. To define an anonymous instance of type ordering of double, you just write given ordering of double and then the definition of compare for that type. You can leave out the name for the given instance. In that case, the compiler will synthesize a name. Here you see it. The name would read here given underscore ordering underscore double, and the rest would be as the same as what you have defined. Anonymous givens are nice because they're concise and concentrate on what's most important, namely what type do you implement. The name usually doesn't matter to the same degree. Sometimes you might find that two given instances give you a name clash because the generated name is the same. Essentially, the two types were too close to each other. They led to the same generated name. In that case, basically, you just fall back to named given instances to avoid the clash. We can summon an instance, which means we can refer to the instance, whether it's named or anonymous, by its type. That's done with the summon method. So summon followed by a type will create the value, the instance, that is the given instance for that type. Summon ordering of int would expand to ordering of int, that's the given instance. Or summon ordering of double would expand to ordering and then the name that the compiler has generated for this double ordering. So summon is a regular method. It's in the predef object, which is imported automatically into every Scala code. But it could also be defined like this. You could define summon takes a type parameter t and an instance of type t with a using clause, and it simply returns the instance. That's all there is to summon. So now for the fine print. Say you have a function that takes an implicit parameter of type t and the function call doesn't have a corresponding argument. In that case, the compiler will search a given instance that has a type which is compatible with t and that is visible at the point of the function call, or it is defined in a companion object associated with t. We'll get to that, what that means in detail in the next slides. If there is a single such instance or a most specific instance, we'll get to that as well, then that instance will be taken as the actual argument for the inferred parameter. And if there's not such an instance, it will be a type error. So what we still have to clarify is where exactly is the compiler looking for given instances and how does it decide whether an instance is more specific than another. So these 2 points need to be clarified now. Where does the compiler look for a given instance? The search for an instance includes all the instances that are visible at the point of call. Visible means they could be defined in an enclosing scope, or they could be inherited by an enclosing class, or they could be imported. If it doesn't find a given instance in the enclosing scope, it will also look at given instances in the companion objects that are associated for the queried type t. And this definition of when a companion object is associated is actually quite general. So it means that if t is a class, and the class has a companion object here, then a given instance in that companion object will be found, because the companion object is associated with the class type C. Beyond that companion object of the class itself, the compiler will also look in the companion objects that are associated in any of T's inherited types. So if class T extends, let's say, a base class B, then it will also look in the companion object of B. So that's another candidate here. No. Or the companion object might be associated with any type argument of T. So it's not just the type as a whole, but any part of a type that can give rise to companion objects that are searched for given instances. Or finally, if T is an inner class, the outer objects in which it is embedded also contribute to the companion objects associated with T. So if we look at, let's say, we have an object O and a class C, and we have a given instance here, and we look for, we need a given instance for the type O.C, then that T here would be eligible, because it's not a companion object of C, but it's defined in an outer object. So in summary, basically every object that sort of can be reasonably connected with the type T will be searched, and that means that you don't need to worry too much where you put your given instances. As long as they have some connection with the type, then it will be an associated companion and the given instance will be found. The search for given instances is done in 2 phases. It will first look in the lexically enclosing scope for something that's visible, and only if that fails it will look for companion objects associated with T. So here's an example. We have the class hierarchy that you see here, and we want to know what are the companion objects associated with the type bar of Y. So which companion objects would be searched for given instances. In fact, in this case, the companion objects would be the companion object of bar, because, well, that's the class that you have here. The companion object of y, because that's a parameter of bar. Companion object of x, because that's a base type of y. And the companion object of foo, because that's a base type of bar. But bar_t doesn't count because it's not a companion object of a base type of either bar or y. So I said one way to make a given instance visible is to import it. But that raises a question. Given instances can be anonymous, so how can we import given instances that don't have a name? In fact, there are three ways to import a given instance. The first way is by name. So that's just the same as importing any other definition by name. For instance, Scala math ordering.int would import the given instance with the name int from the Scala math ordering object. The second form is new and it applies only to given instances. We can also import them by type. So for instance, here you see we import Scala math ordering and then we write given ordering of int in braces. What that does is that it will import the given instance in that object that implements ordering at type int. So that is a given instance of that type. And we can also be more general. Instead of having a particular argument like int, we can also have a question mark, which is a wildcard. So here the second import would import any given instance that implements an ordering object of an arbitrary type. So it would import the ordering of int and the ordering of boolean and the ordering of double and any other orderings that were in this Scala math.ordering object. And the third way to import a given instance is as a wildcard, but the wildcard is different. Instead of using an underscore for a wildcard for normal values, we write given. And that makes it explicit that we in fact want the given instances and only the given instances from the Scala math objects, but not the normal values. So which form of import should you use normally? Well, I would say since the names of given don't really matter, use the second form. It's the most informative. It tells you exactly what you want to know, namely that we get the given instances for a specific type. So here's a little exercise. If you have this program here, so we define a list, we sort it with the sort method call that we've seen before. Where does the compiler in this case find the given instance of type ordering of int? Was it in the enclosing scope via an import or in a companion object associated with the type? Well, in this case, the ordering int was defined in a different module, so it wasn't in the enclosing scope, and we didn't have to import it explicitly, so it was found because it was a companion object of the type ordering. Given instance is found in that companion object. So if there's no available given instance that matches the query type, you get an error. So for instance here you write def f using an int and you just write f, you will get no implicit argument of type int was found for the parameter n of method f. The other kind of error you might get is an ambiguity. That happens if there's more than one given instance that's eligible. So here you see an example. You have a trait C and you have two given instances of C, C1 and C2, which both define the value x to be different values, 1 or 2. And we have a function definition f with an implicit parameter of type C. Now if we just call f, then we would get an error which says ambiguous implicit arguments, both value C1 and value C2 match type C of the parameter C of method f. So what do you do when you get an error like that? Well, one thing you could do is just pass the argument explicitly. So for instance, you could write f using C2 if it was C2 you wanted. So you don't always get an ambiguity if there's several given instances that match the same type, because it could be that one of them is more specific than the others. In essence, a definition given A of type A is more specific than a definition given B of type B if one of several conditions apply. So if A is in a closer lexical scope than B, so it's nested more deeply than B, then it takes priority. It will be selected instead of B. or if A is defined in a class or object which is a subclass of the class which defines B, then again A takes priority. Or if these conditions don't apply, but the type A is a generic instance of type B or is a subtype of type B, then again the A instance will be chosen over the B instance. So let's demonstrate this with some examples. What given instance is summoned here? Summon A int when you have these two things. So you have a universal one, which takes a type parameter and a using argument, and that is an instance of A of t for any t, and you have a specific one that is an instance of just A of int. So the answer is the specific one will be chosen because it's an instance of the generic type. So the more specific the type is, the more specific the given instance is as well, and more specific instances will be chosen over more general ones. What given instance is summoned here? So you have a trait A and a given instance AC and a trait B and a given instance BC, and then an object O that extends B, and we want a C. Well, it will be this one here because it's defined in a subclass. So instances in subclasses are more specific than instances in base classes, in parent classes. And finally, what given instance is summoned here? So you have an outer instance AC, and then a function f with an instance B inside f, and then a definition that needs a C. So it will be the inner instance that is chosen, this one here. So to conclude in this lecture, we've introduced a way to do type-directed programming. So the types direct our programming, and they even generate parts of our program with the help of a language mechanism that infers values from types. So the idea is that there has to be a unique, or at least most specific, given instance that matches a query type for it to be used by the compiler for synthesizing a value of that type. Given instances are searched in the enclosing lexical scope, so imports, parameters, inherited members, as well as normal definitions, and then if that doesn't give a match, in the companion objects that are associated with the queried type. In this session, you learn about a particular way to do context abstractions and to turn types into values, which is called type classes. In fact, you've seen the pattern of type classes already. Here it is again. So we have a trait like ordering and a compare method, and then we have an object, a companion object, with given instances for particular type instances of that trait. So we have a given instance for ordering of int, and we have a given instance for ordering of string, and both of these instances define the compare method as is appropriate for that argument type here. If you have a pattern like that, we say ordering is a type class. In Scala, a type class is made up of a generic trait, so a trait with a type parameter, and given instances for type instances of that trait. So in the ordering example, we have the given instances for ordering of int and ordering of string, and the type class is ordering. Type classes provide yet another form of polymorphism, being able to come in many forms, and that form is sometimes also called ad hoc polymorphism. To see what I mean, look at the sort method. It can be called with lists containing elements of any type A for which there is a given instance of type ordering of A. So sort can be called on arguments of many types, and its functioning is different depending on what type it is, because its functioning will depend on the given instance for the actual type A that you see here. At compilation time, the compiler resolves the specific ordering implementation that matches the type of the list elements. Resolving simply means providing an argument in a using clause that matches this ordering context bound. So as an exercise, let's implement an instance of the ordering type class for the rational type. I'm going to simplify a lot. For now, the class rational will simply be a case class with a numerator and denominator and no additional methods. We don't need any for this particular behavior. So for the ordering type class, we need to implement a compare operation. And here's a reminder what less than is on rational numbers Q and R. What we do is we simply multiply the numerator of one side with the denominator of the other. So that gives this here. And do the same thing on the right-hand side. So its numerator gets multiplied with the denominator on the left-hand side. And then we compare those two products. So let's do this in the worksheet. We have our class rational here, our trait ordering here, and we have a given instance, let's call it rational ordering of rational, which has a compare method, and we have to implement the right-hand side of that method. So according to the formula, we define two helper values, xn, the normalized is the numerator of x, times the denominator of y. Yn would be then the numerator of y times the denominator of x. And then we have the usual comparison. So if xn is less than yn, then we return -1. Else if xn greater yn, we return 1, else we return 0. So you might ask, why haven't I written simply xn minus yn, because that gives you arguments of the same sign as this expression here. The answer is this one here plays better with integer overflow. If I compare two numbers that differ by a very large amount, then that subtraction might overflow, whereas here the comparison will still give you the good result. So that's why it's written that way. So it's worth noting that we were able to implement the ordering rational instance without changing the rational class definition. That means that type classes support retroactive extension. We can extend a data type with new operations, such as compare in this case, without changing the original definition of the data type. In this example, we've added the capability of comparing rational numbers without changing the class rational. So that's one of the advantages of using type classes over using regular classes, that you can do that. Here's another advantage. You can do conditional instances. So the question arises, how do we define an ordering instance for lists? And well, it depends what lists of what elements, right? Because we can define an ordering on a list only if the elements have an ordering. So that leads us to a definition like this one here. We have a list ordering of with some type parameter a, and that is an implementation of an ordering of list of a. But we need an ordering of a as well, which we can express here by adding a using parameter clause to the given name here that you see over there. And then we need to define the compare method. Here it is. So the compare takes two lists of a's and it does a pattern match on the pair of xs and ys. If they're both nil, then they're equal. If the first one is nil and the second is not nil, then the first one is smaller. If the second one is nil and the first one is not, then the first one is smaller. If they are both non-nil, so they're both consts with heads x and y and tails x as 1, y as 1, then we compare the heads, and for that we need our type class here, our ord. So we use ord to compare x and y. That gives a result c. And then if that result is 0, then we compare furthermore the list x as 1 and y as 1. We compare the tails. If the result is different from 0, then we have our result, and that's what we return. So one new syntax that we've seen is that a given instance, list ordering, can take type parameters and implicit parameters. You could also leave out the name, in which case you would just have a given instance without a name and type parameters, given parameters. That would work as well. So we observe that given instances such as list ordering that take implicit parameters are conditional. That means an ordering for lists with elements of type T exists only if there is an ordering for T, because otherwise the compiler couldn't synthesize an actual argument for the using clause in list ordering. So this sort of conditional behavior is really best implemented with type classes. Normal subtyping and inheritance cannot express this. A class either inherits a trait or it doesn't, but you can't make a class inherit a trait depending on a condition of its parameter types. That's not possible. But with type classes it is. Things get interesting if we look at how instances of conditional implicit parameters are resolved. In fact, the resolution proceeds recursively. That means a given instance for the outer type, list in this case, is constructed first, and then its implicit parameters are filled in turn. So for instance, let's say we have the sort method, which takes an ordering A type class instance, and we want now to sort a list of int. So that's the original call. Type inference gives us list of int as the element type A that we want to sort. So now we need an ordering instance for list of int. So the ordering instance we find is list ordering. So that's what we pass. And list ordering itself needs a ordering instance for the element type, which is int in this case. So this expression in turn is expanded to this one here, using list ordering that takes an ordering of int parameter. So we started with this, and we got this. That is essentially the work of the compiler that added the missing pieces. It's also worth noting that each of the intermediate result is actually a valid Scala program. So you can write this, of course. You can also pass the type parameter explicitly, of course, but you could also add just list ordering, essentially to help the compiler along, and says, well, I need a list ordering, but now you can figure out yourself what parameter, what argument to pass to the list ordering instance here. So you could either write this last thing or leave it out in turn. So here's another exercise. Let's implement an instance of the ordering type class for pairs of type A and B, where A and B must have ordering instances defined on them. That's useful for examples like this one here. Let's consider a program for managing an address book. We would like to sort the addresses by zip codes first and then by street name. So two addresses with different zip codes are ordered according to their zip code. Otherwise, when the zip codes are the same, the addresses are ordered by street name. So that would lead to the setup that you see here. We have a type address, which is a pair of int and string. We have a list of addresses, and we want to sort that list. What is the given instance that we can pass to that sort function? So here's a solution. We have a given instance, let's call it pair ordering of A and B. Here, A and B are type parameters, so that works for any pairs of types A and B, but they must both have an ordering instance. So we must have an ordering instance for A and one for B. We give them names ord A for the one for A and ord B for the other one. So now we have to define a compare method for pairs. So the compare method takes two elements x and y, both of type pair of AB. And what we do is we compare first the first half of these pairs, so that's x dot underscore 1 and y dot underscore 1. That gives us a result. If that result is different from 0, then that's what we return. And otherwise, if the result is 0, we go on and compare the second halves of the two pairs. And for the comparisons, we use ord A in the first case, because that's the comparison we need to use for the A parameter, and we use ord B in the second case. Good. So we've seen that ordering has a compare method, but typically when we use an ordering, we don't really want to use compare. We want to use less than or greater than or methods like that. So that's possible because, like any trait, a type class trait can define extension methods. For instance, the ordering trait would usually contain comparison methods like this. So there's the compare method, which is abstract, and then we have extension methods less than or equal, greater than or equal, which all use compare to produce their results. So that's handy because now we can use the natural less than operators and the others for comparisons. So here's an example in the merge method of merge sort. So merge works for any type T that has an ordering, so that's an implicit parameter, the ordering of T that we assume here. And there's a usual pattern match which says, well, if one of them is nil, then take the other. And if they're both non-nil, then we compare X and Y. So that uses a comparison operation less than, which is the less in ordering. So that less is really the less that we have here defined as an extension method in the ordering class. Now, you might wonder, how does the compiler know that this less than means the ordering less than? It's not defined in the environment, it's not imported. In fact, we don't even have a name we could import it from. Ordering is just a context bound, it isn't a named parameter. Well, the trick is that there's an additional rule which says that if we have a type class instance such as ordering in scope, then its extension methods are eligible for the type that is the argument of the type class. So we have ordering t in scope, and that means its extension methods are defined on values of type t. That's what makes it work without any additional boilerplate. So to summarize, type classes provide a new systematic way to turn types into values. Unlike class extensions, type classes can be defined at any time without changing existing code, and they can be conditional. And that makes them a lot more flexible and powerful than plain class extensions that we have seen before. In Scala, type classes are constructed from parameterized traits, that's a type class, and given instances for that trait. Type classes give rise to a new kind of polymorphism, which is sometimes called ad hoc polymorphism. That means that the type TCA has different implementations for different types A. In this session, you'll get some taste how you can implement abstract algebra with type classes. Type classes let one define concepts that are quite abstract and that can be instantiated with many types. For instance, we could come up with the concept of a semigroup. A type is an instance of a semigroup if it has a combine method, a binary operator that takes two t's and returns a t. There are many possible instance types of semigroups. For instance, int with addition is a semigroup, so is int with multiplication. So we have a choice what operator we want to use here. So is string with concatenation, so that would be string plus. So is any sequence really, so seq of some A, type A, with concatenation again. And you can find many other examples. It's really very general. So semigroup is a concept that comes from abstract algebra, from mathematics. And there, to be a semigroup, it's required that the operator is associative. In fact, if you look at these examples, then each of these operators is indeed associative. Once we have defined semigroups, we can now define methods that work for all semigroups. So very general methods that work for all of these combinations up here. For instance, we could have a reduce method that reduces lists of t elements where t is a semigroup. So it would take the operator that is defined by the semigroup and use that operator called combine to reduce the elements of the list, yielding a single value of type t. So depending on what the type t and its semigroup instance are, reduce could do many different things. If you give it a list of ints and an instance of the sum semigroup here, then it would give you back the sum of the numbers in the list. Or if it's a product semigroup, the product. Or if you give it a list of strings, then it would give you back the concatenation of all these strings. It's a very general method that exists in many forms. In fact, if we look at abstract algebra, then the type classes that we find there form natural hierarchies. For instance, the next element down from a semigroup is usually called monoid. That's defined as a semigroup with a left and right unit element. So here's its natural definition. A monoid of T is a semigroup of T, and it has, in addition to the combine method, the binary operator, it has in addition a unit method that returns the unit element of type T. So unit means that if you combine it to the left or to the right with anything, you get back the other operand, the anything. So as an exercise, let's generalize reduce to work on list of T where list has a monoid instance, such that it also works for empty lists. If you look at the reduce operator before, it wouldn't work for empty list because reduce left doesn't work for empty list. It gives you an exception, illegal operation. So now we want to get a version of reduce that works on monoids. so that it returns the unit element for an empty list. So I have pasted what we have so far in a worksheet. So here's the old definition on reduce on semigroups. Let's make it work for monoids and empty lists. So we replace semigroup by monoid. And now we don't want to use a reduce left, because reduce left doesn't work for empty lists. We want to use a fold left. It could also be a fold right. It doesn't matter because combine is associative. But let's use a fold left. Okay, so we do a fold left. So for fold left, we need a unit element. So that would be m.unit. And we have the same combine method as before. So that's the definition of reduce that we came up with. Well, one thing you have noticed is that I changed the header of reduce a little bit. Instead of a context bound, I was using a plain type parameter and a using clause because I needed a name for the actual monoid in question to select the unit element from that. The question is, can we also do without? Can we do with a context bound? What would we have to do to work with that? So if we keep the context bound, then reduce would look like this. So then to actually get the monoid of t instance that we need, we can use a summon here. So we say reduce left and then summon monoid of t. So that would give us the monoid that's implied by this implicit parameter and take the unit from that. So this works, but it's unfortunately a bit clunky. So if monoid is used a lot, which is maybe to expected because it's a very general type class, then it might be worthwhile to streamline the notation a little bit. And we can do this by adding a helper method to the companion object of monoid. So we define a companion object, monoid, and we give it an apply method. And that apply method is essentially a summon. So it says, well, I need an implicit parameter of type monoid of t for a type parameter t, and I return that implicit argument. So I return the current monoid of t instance. So that defines now a global function monoid.apply of t that returns the monoid t instance that's currently visible. And with that helper, we can now write reduce like this. So reduce, it takes a context bound as before, and we do reduce left with monoid of t.unit. So monoid of t is, of course, monoid.apply of t. As always, we insert an apply. So it's this method here, and what it returns is the current monoid of t instance that is in scope, and we take the unit element of that. So that's precisely what we want. So that's a way to keep context bounds because they're nice and concise, and streamline the access to things that are not extension methods in the type class a little bit. Now, it's possible to have several given instances for a type class type pair. For instance, int could be a monoid in at least two ways. So it could be a monoid with plus as combine and 0 as unit, or it could be a monoid with times as combine and 1 as unit. So those are the two instance definitions. The given sum monoid is this. So combine is plus and unit is 0, and the product monoid is this. Combine is times and unit is 1. Assuming we have these given instances, define as an exercise the sum and product functions on list of int in terms of reduce. Well, here's what you would get. So sum of xs is just reduce xs with the sum monoid. And product xs is reduce xs with the product monoid. That's all there is to it. Now, question to you, if you have done that in the worksheet, could you just quickly try out what happens if you leave out those two using arguments? So I have the worksheet here with all definitions, and you see that indeed sum of xs and product xs work as expected. So what happens if I leave out the using clauses in the arguments here? I'll comment them out here. So I get two errors. They say both ambiguous implicit arguments, both the sum monoid object and the product monoid in class app match the type that's expected, which is semigroup. So that's quite normal because indeed I have two given instances, sum monoid and product monoid. They're both applicable. They can be both passed to the using clause of reduce, and neither is better than the other. So you get the classic ambiguity error. Now, one thing that's important is that algebraic type classes are not just defined by their type signatures, but also by the laws that hold for them. So for instance, if you have a given instance of monoid of T, then that instance should satisfy the laws of monoid, which are that combine is associative and that unit is a left and right unit. So it should satisfy these laws for arbitrary values x, y, z of type T. How do you verify the laws? Well, the type checker is not yet up to it to do that, so you'll need a proof. That could be a formal proof on paper or an informal proof, or it could be a proof with a mechanized proof assistant, such as Coq or Agda or Isabel or one of these, or you could just test them. And a good way to test these laws, or a good way to test that an instance is lawful, is by using randomized testing, because that will exercise these laws at many different random values, and that you can do with a tool like Scala check that we have seen a couple of sessions ago. In this session, I'm going to cover another broad category of contextual abstractions, which I call context passing. You've seen that type classes are about type instances of generic traits. That is, they answer the question, what is the definition of TCA for the type class trait TC and the type argument A? If we want to make A a type parameter, we need an implicit parameter to go with it that conveys this information, what the actual definition of TCA is. On the other hand, there are also uses for abstracting over the values of a simple type which is not parameterized. And then the question to ask would be, what's the currently valid definition of type T? So here's an example that comes up a lot in code that uses concurrency or parallelism. To do computation in parallel, runtimes need thread schedulers. A thread scheduler is essentially a piece of software that allocates runtime on processor cores to individual parallel processing threads. There's usually a default scheduler, but it should be possible to override that choice in parts of the code, because a different scheduler might have better performance characteristics or better availability guarantees and so on. So the question is, how are references to schedulers propagated? In Scala, they are embedded in values of type execution context. The default you see here, so there's a global execution context, which is a so-called fork join context. So that example illustrates a second form of given instances. You can also define a given instance as an alias like that. And as always, the name is optional. So you could also write given execution context equals fork join context. What happens here at execution is that the evaluation of join context is done lazily. The fork join context is created the first time global is used, either directly or as an argument to an implicit parameter. So execution contexts have this property that they rarely change. Most applications would be happy with the default execution context everywhere. But on the other hand, they should be changeable everywhere. So it should be possible at any point to override the execution context that's given by default and use a custom one. So this profile is a poster child for using implicit parameters. It means that we pass execution context as an implicit parameter to all code that needs it. And usually you'll just pick the execution context from the caller one. But at any point where you need to, you can use a different execution context just by having an explicit argument here instead of the implicitly synthesized one that the compiler gives you. So that was one example, but there are many other use cases. Passing a piece of context as an implicit parameter is actually quite common. For instance, we might want to propagate implicitly the current configuration or some capabilities and a set of available capabilities, or a security level, or let's say a layout scheme to render some data, or persons that have access to some data. And there are many more examples. In all of these cases, the idea is that a certain information has to be propagated widely to many places in your program, and it changes relatively rarely. That means, and of course it should change functionally. You don't want to update it. So that means that this piece of information, it gets propagated down the call graph, in the trees, and it's always the same. except at some point you might want to change it, and then in the subtree there will be a change, and at another point you might want to change it again, and so on. But these changes would happen rarely, because otherwise, if they happen often, then the right choice is an explicit parameter. It matters what the value of this parameter is. It's only if the usual case is that it's just the same, that we want to suppress the noise. We don't want to pass it everywhere explicitly if it's everywhere the same. So as this example implies, implicit parameters and context passing really are important for larger systems. Small systems rarely need them. So let's do a slightly larger application that points to essentially something even bigger. And what we want to track here is persons that have access to some data. So what we are going to do is a conference management system, or to stay modest, just one part of a conference management system. So we want to design a system to discuss papers submitted to a conference. And we assume that the papers have already been given a score by the reviewers. That's another part of the conference system that we leave out here. So to discuss, reviewers need to see various pieces of information about the papers. But some reviewers are also authors of papers. And an author of a paper should never see at this phase the score the paper received from the other reviewers. So the consequence of this is that every query of the conference needs to know who is seeing the results of the operations, and this needs to be propagated everywhere. Because if one of the persons who sees the result of a query is the author of a paper, then that person shouldn't see the real score of the paper or be able to infer the real score of the paper. So some action has to be taken, and for that action to be taken, we need to know first who is seeing the results of an operation. For a given top-level query, the set of persons seeing its results will largely stay the same. So I initiate a query, and then basically it's just me who will see the results. But that's not always the case. There are scenarios where we imagine this could change. For instance, I could delegate part of a task to another person, and if I do that, then it's myself and the other person who has access to the scores of that paper. So if either of us is the author, then the scores should be suppressed. So here's the outline of that conference management system. So we model persons with a case class and a name. A paper is a case class that consists of a title, the authors, which are a list of persons, and a body. The conference management system itself provides a class conference that essentially already gets the ratings. So ratings are a repeated argument from which consists of pairs, paper, and int, where int is the score. So I can immediately convert that to a map with just two maps of this sequence, and that would give me the real score of a paper. So the score that comes from the actual ratings. Then another thing I can compute immediately is the list of papers that have been submitted to the conference, because that's just the first part of the ratings and convert it to a list. The next function we look at is score, which gives us the score of a paper. And that's not always the real score, because if there is an author of the paper that is also a viewer of the result, then we should mask the real score. So what we do instead of giving you back the real score is just give back a very low made-up value, -100. And if that's not the case, so the authors of the paper are disjoint from the viewers, then we give you back the real score. So what this implies is that the scoring function must know who finally will see the result of this. But it's not just score that needs to see the viewers, it's also functions that use score, such as this one. So the rankings functions ranks the list of papers according to score, so papers with a higher score would come first and papers with the lowest score would come last. So here's the definition of ranking. So it's papers sort by score in reverse. And of course, score needs to see viewers, and therefore rankings also needs to know who the viewers are. The next function here is called ask, so that's essentially a top-level query. So we have the person who asks a query, and the query is a function from viewers to t. So the person submits a query, the query takes the viewer's argument and gives you back the result that the person is interested in, which is a type parameter, so can be arbitrary. And the implementation is simply we call the query with the person as the viewer, so it's a set of P. And finally, we have the delegate to method, which solves the task of delegating a part of the computation in a query to some other person. So query will be run with the current viewers, which has to be passed into delegate to, and in addition, this other person. Both the current viewers and person can now see the scores of the paper. So here we have an example data set. So we have 5 persons who happen to be both reviewers and authors. And we have 4 submitted papers that you see here. So here's the titles, here are the authors, and the body I leave out in each of the cases. And each paper has a score that you see here on the right. Now here's an example query. The query is, which authors have at least 2 papers with a score over 80? So we define that query in a method highly ranked prolific authors, and as we will see, the result of that query will depend on who's asking. So we also pass the person that's asking the query as a parameter. And we get back a set of persons which are the highly ranked prolific authors. So what we do is we ask the conference system with the current person, so that's asking, and this query here that you see here locally. So that query, as every query, has to take a viewer's parameter, so a set of persons parameter, and it gives you back a set of persons. So what it does is it first computes the highly ranked papers. Highly ranked papers means we get the rankings and we take the top papers, so we have a take while here. Top papers means that the score of a paper would be greater than 80. So we take them from the rankings list until the ranking is lower than 80 or equal to 80, and these top papers are converted to a set here. So once we have highly ranked papers, we can complete the query with this for expression that you see here. We let P1 range over all highly ranked papers, P2 the same. We let author range over the authors of paper P1. If P1 and P2 are 2 different papers, and the author list of paper P2 also contains our author, then the author is a highly ranked prolific author, and we return it. So now you see the rankings function is parameterized with the current viewers, so is the score function. So the answer of these functions will depend on who is the current viewer, and that in turn depends on who is asking. So I've put the conference management in the worksheet. You see it here. We have the query here. And now we have a test as method, which says, well, we call highly ranked prolific authors with the given person as the person who's asking. And we just essentially print it out slightly prettified, taking the name and separating with commas. And if we now do run this test as different persons who are asking, so Black, Smith, Abel, or Ed, then you get different answers. Because let's say in the first case where it's Mrs. Black that asks, you see here Mrs. Black is a co-author with Mr. Smith, and that means that she won't see this paper, or the score of this paper will be -100. So that means that the other paper of Mr. Smith, who is a highly prolific author, is seen, but this one is not. So from the viewpoint of Mrs. Black, Mr. Smith has only one highly ranked paper, the first one. If we ask as Mr. Smith, then we'll find that Mr. Smith has these 2 papers, so you can't see their scores, and in the other papers the author doesn't figure. So from the viewpoint of Mr. Smith, he doesn't see himself as a highly ranked prolific author. And if we finally look at Mr. Ed, so Mr. Ed, he's here. He hasn't published with the other, so he has the complete picture of these first 3 papers. So for him, both Smith and Mrs. Peters are highly ranked prolific authors. They both have 2 papers in the list of these 3. Okay, nice, but there is a problem. So far, passing the viewer set is a convention. That means nothing prevents just passing the empty set of viewers to a query. So our query highly ranked prolific authors could also have looked like that. It would be type correct. We would say, well, we want the rankings and nobody's seeing that really. And then we take the top ranked papers according to the score, which again nobody is seeing. That's a lie, of course, but the type system will not catch us out with that. So we can fix that by making the viewers type alias opaque. Previously, we've seen that viewers was just an alias for set of persons, and that's something that essentially is for everyone to see, so we can everywhere freely exchange viewers with set of persons. The left-hand side and the right-hand side are the same. But if we write the type alias with an opaque modifier that you see here, then it becomes an opaque type alias and the rules change. In fact, given an opaque alias such as this one here, the equality that viewers and set of persons is the same is known only within the scope where the alias is defined, in this case within the conference management object. Everywhere else, viewers is treated as a separate abstract type, so it's just a new type about which we know nothing. We certainly do not know it's an alias of set of person. So if we do that, how does it help against tampering? Well, when asking a query, we have to pass a viewer set to the conference management methods like rankings or score. But viewers is an unknown abstract type now, but because the queries are formulated outside the conference objects, viewers for them is an unknown abstract type. Hence, there's no way to create a viewer's value outside the conference management object. So the only way to get a viewer's value is in the parameter of a query, where the conference management system provides the actual value. So that means in this query here, we are forced to pass viewers here and here, because that's the only viewer's value we have access to. Indeed, if we look here, so if we can't create a viewer's value, then the only viewer's value we see is that one here in the parameter of the query. So we're forced to pass this on to rankings and score. There's a caveat that actually works only if queries are not nested. If queries would be nested, then we would have a choice. We could pick an outer parameter of an outer query or a parameter of an inner query. So that would still allow cheating. So for the moment, let's assume that queries are not nested, that every query we formulate is a top-level query. So let's look back to the conference management code. One downside is that we have to pass viewers arguments along everywhere they're needed. And that's tedious, and it also seems pointless, since by design there's only a single value we could pass. So the question is, can't we automate that? And the answer is, of course, just use implicit parameters. So let's apply this change to the worksheet. We make every viewer's parameter a using clause. And at the same time, we avoid explicit arguments with viewers because they can be passed implicitly now. So we still have a problem here. It says that there's no implicit argument of the viewers type available, and that's because here we actually haven't made viewers a using clause, because that was essentially the function type prevented us from doing that. So we need to correct that by essentially making it a given instance that's passable implicitly. So what we can write is given viewers equals viewers, and that's it. So now things are good. Okay, so what we've done is we have changed every explicit parameter viewers to a using clause, and we have omitted the actual arguments that refer to these viewers. So we've, in a nutshell, gone from this to this. So the parameters get the using keywords, and the applications get the viewers arguments dropped. So here we have viewers in score, and now it's gone, and here it's the same thing. So the We pass viewers twice, but afterwards we don't need to do that anymore. So you might say, adding all these using clauses just to save 3 explicit arguments is not really worth it, is it? And I'd have to agree with you. But remember, this is sort of an extremely minimized nutshell system. Real systems are much, much larger, and you would have many, many more implicit parameters where the savings would actually add up. So data about this have been collected in a paper called Scala Implicits Are Everywhere, and that appeared at the UPSLA conference in 2019. It analyzed a large body of code consisting of 7,280 Scala projects with together 18 million lines of code. And it found that 98% of projects use implicits, 78% of projects define implicits, and 27% of call sites use implicits. So it means these 27% of call sites, if they all had needed explicit parameters, then that would lead to a significant blow up in code size for these projects. Implicits really do save a lot of tedium and repetition in these real-world code bases. So in our case, the implicit parameters were of type viewers, which is an opaque type alias. And that has another benefit. Since outside conference management viewers is a type different from all others, there's no chance to connect a viewer's implicit parameter or given instance with given instances for other types. On the other hand, if viewers was a regular type alias of set of persons, we might accidentally have given instances for other set of persons in scope, and then we would get crosstalk. We would then get sets that are not intended as eligible candidates for viewers parameters that are eligible nevertheless. So that's a problem. So the moral of that is that given instances that you define should have specific types. That means types that don't appear very often in the rest of the program outside this use case of passing implicits, or they should be local in scope, or they should be both. So for instance, this would be a really terrible idea that you write a global given int equals 1. So that means we have a default integer that's 1 and then use that in some functions like this f function that uses a delta and returns x plus delta. That's really bad because you can do that once in your program, but if somebody else does the same thing, then you would get spurious, ambiguous instances and generally a huge mess. So never use a common type such as int or string as a type of a globally visible given instance. The best thing is you define your own class that essentially lives mostly for being passed as an implicit, or you define an opaque type. So here's an exercise. You've seen in week 4 of the first course an enum for arithmetic expressions. It consisted of numbers, sums, products, and variable cases. Let's augment it with a let form. So now an expression is a number, or a sum of 2 expressions, or a product of 2 expressions, or a variable with a name, or a let binding that says the variable with this name is defined to be this right-hand side in the scope which is given by this body here. The task is to write an evaluation function for expressions of this type. Def eval takes an expression, returns an int. And you should fill in the triple question marks here. So this let node, let x, e1, e2, should be evaluated as you would evaluate in Scala the block val x equals e1 and then e2. And you can furthermore assume that every variable x occurs in the body b of an enclosing let x eb. So that means you won't have variables that don't have an enclosing definition. I have a hint for a solution on the next slide. If you want the hint, then keep viewing. If not, you might stop the video here. So here's the solution hint. One issue we have is that given a var node like var abc, we need to know the value of abc. So we'd have to look in an enclosing let binding that defines abc. So how do we figure that out? Well, the idea is to use a map from variable names to their defined values and to use that map as an implicit parameter. Initially, the map is empty, no variables are defined, and at every let node, like here, we augment the map with the binding that is here the right-hand side, R. So this suggests the following code outline. In our evaluation function, we have a local function called that recur because it does the actual recursion going through the expression tree. It takes the actual expression to evaluate, and it also takes this environment, which is a map from strings to int, and it returns an int. And then we start the computation off by calling recur with the original expression and the empty map. So let's develop the solution step by step. We have our original outline, we have the recur function, and it's pretty obvious that we would proceed by a pattern match on what the expression is. So we have 5 cases and we have to fill in all 5 of them. If the expression is a number, then its value is just the number that's stored in the node. If the expression is a sum, then the value is recur x plus recur y. Both recurrences, of course, need an environment, but that environment is passed implicitly. You don't need to write it here. In the same vein, product xy, the value is recur x times recur y. Now, what's the value of a variable? Well, we need to look it up in the environment. We say the value of a variable is whatever is the entry in env under that name. And since we assume the global condition that every name is declared, we know that every name will be in the map, and we can use a map apply here safely. Otherwise, we would have to use an environment.get name and handle the error case appropriately. Finally, for a let node like this, the result is a recur of the body part using an augmented environment. So the new environment is the old one, env, and the additional binding that the name here has now the value that's given by recur of the right-hand side. So we compute the right-hand side with recur, combine it with the name, add it to the environment, and compute the body with that augmented environment. So again, you might ask, well, was it worth using an implicit argument for the environment? And I guess in this small example, not. But again, this example is just essentially an illustrator for something much larger. A real compiler and interpreter would have maybe not 5 cases, but 50, and it would not call itself or something else that needs the environment twice, but dozens of times. So then, of course, these things multiply, and you get numbers where it's really worthwhile not to have to pass the environment manually to every little nook of your computation graph. In this session, you'll find out ways to streamline our contextual abstractions even further using implicit function types. In the last version of the conference management system of the last session, we got rid of explicit viewers arguments, but we still need them for using parameter clauses. So if I look at the worksheet here, then score, rankings, delegate to all have these additional using clauses to track the set of viewers. One thing we could do to make this slightly more streamlined is to avoid the names of the viewers parameters. Instead of the names, we just define a new global viewers function that takes the viewers and returns it. So now essentially whenever we have an implicit viewers in scope, we can just refer to it with this viewers function, and consequently we don't need to name the parameters anymore. That's a trick that one can basically apply everywhere one does context passing. So now it looks slightly more streamlined, but of course there's still the overhead of writing these anonymous using clauses. So the question is, can we get rid of these as well? So to get to an answer, let's massage the definitions of rankings a bit. You know from the first half of the course that we can write any function with parameters alternatively as a function without any parameters, like this def rankings here. That takes on the right-hand side an anonymous function. The anonymous function has all the parameters of the original function and then continues with the function's body. So rankings alternatively could be written as the anonymous function that takes some viewers and does the sort by. But something important got lost now in this translation. Namely, previously the viewers parameter was with a using clause, so it was an implicit parameter, but now in the anonymous function it's just a regular parameter that has to be passed explicitly. So we can get back to parity by writing a new kind of function arrow, question mark arrow here. The question mark signifies that we want the parameter viewers to be implicit so that its argument can be inferred. In other words, that parameter now plays exactly the same role as the using clause on the left played before. One interesting question is, if you have a function like that, what is its type? For a normal anonymous function, the type would be viewers, arrow, list of paper, a normal function type. But for an anonymous function that represents a using clause on the left, the type is again written with a question mark. So the type is viewers, question mark, arrow, list of paper. And that type is called an implicit function type. So viewers, question mark, arrow, list of paper is an implicit function type. What can we do with such types? Well, there are two rules that are relevant. The first rule says that values of implicit function types behave essentially like methods with using clauses. They get their arguments inferred in the same way. So if you have a value like f here of an implicit function type a question mark arrow b and a given instance of type a, then the expression f expands to f using a. So the compiler will infer the value a as the correct parameter for the implicit parameter a of f here. So that's exactly the same as if f had been defined as a method like this, f def f, and then a using clause with a. The parameter inference is the same in each case. And then there's a second rule which makes implicit function types in a sense more powerful than just methods with using clauses. The rule is that implicit functions can get created on demand. What that means is that if the expected type of an expression, say b, is an implicit function type from a to b, then b will expand to an anonymous function where the parameter a, which is an implicit parameter, is synthesized, is inferred. And that expansion happens before the parameter b is type checked. So that means when the compiler type checks parameter b, there will be evidence of an implicit value of type a in scope, which can be used inside b. Now this might all seem quite abstract. Let's see how it applies in the concrete example of the conference management system. So let's use implicit function types in our conference management system. The first thing we do is introduce a type alias. We say type viewed of t is viewers question mark arrow t. That's in a sense just for conciseness. Viewed of t expresses the fact that, well, we return a result of type t, and we also have the info who's viewing that result. So it's the same thing as the implicit function types here on the right, but it expresses that thing with a custom-made name, namely the view thing here. Now we can apply two changes to our code. First, we can replace every method signature that ends in a using clause and some result type with just the result type wrapped in a viewed. It's the same thing. We just essentially trade a parameter to the left to a using clause in the implicit function type. And second, we replace every parameter query that has a function type like viewers arrow some type to be query, which is a viewed of some type. So let's apply these changes to our worksheet. So we have a new type viewed. Like this. And now we can replace all using clauses by viewed instances. And we further replace every query argument with an explicit function type with the same implicit function type, or rather its viewed alias. And that means that if we pass an explicit one now to query, because it's an implicit function type, we have to add a using clause here, and we have to do the same thing here. So let's see, we have some more problems here. Well, query now is the same thing. It's a viewed of set of person. And we can remove the viewers here, which is no longer needed because now query is already an implicit function type, so it will get an implicitly supplied viewers argument that will be used then in the body of query. So what we've achieved in the end is code that is quite streamlined. So essentially all we need to do is mention the viewed in the result type of the methods or in the type of the queried parameters, and that will automatically track through the correct viewer set as implicit parameters. So it all works without us having to do anything explicitly in this example. So let's see what we have done here. We know that implicit parameters in using clauses trade types for terms. That means the developer writes down the required type of the parameter, and the compiler infers a term, that means an expression or a value for it. Implicit function types go one step further. They trade types now for the parameters. The developer just needs to write down the return type of the method, and the compiler infers one or more method parameters that match the type. And from those parameters, of course, it will infer the correct anonymous function bodies and also the arguments to the parameters. So basically, at a very high level, you just essentially specify a single type and the whole machinery will be generated for you by the compiler. Another way to see this is that implicit function types are second-degree context abstractions. So what do I mean by that? Well, implicit parameters in using clauses abstract over the context at the call site. So they are first-degree context abstractions. And implicit function types allow to abstract over using clauses, as we have seen. Abstract in the original sense. They allow to introduce a name, such as viewed, that can be used instead of writing an explicit parameter clause. So together with type aliases, they enable abstractions of context abstractions, hence context abstractions of the second degree. This week, we'll extend our scope from pure functional programming to also cover mutable states and side effects, and we'll study what happens when we combine these with an otherwise functional program. It turns out that some of our techniques for reasoning about functional programs will no longer work in that case. On the other hand, the combination of mutable states and higher-order functions gives us added expressiveness that allows an efficient and sometimes also elegant formulation of certain programming patterns. In this session, we take a first look what happens when we add state to functional programming. Until now, our programs have been side effect free. Therefore, the concept of time wasn't important. For all programs that terminate, any sequence of actions would have given the same results. This was also reflected in the substitution model of computation. So as a reminder, let's look at that substitution model again. Here, programs are evaluated by rewriting. The most important rewrite rule covers function applications. So it says that if you have a function definition with parameters x1 to xn and body b somewhere, and you have a call to that function with actual arguments values v1 to vn, then the program would be rewritten so that the call gets replaced by the body of the function, where the formal parameters x1 to xn are replaced by the actual values v1 to vn. So that's the substitution model. Let's see it in action in an example. Say you have the following two functions, iterate and square. Iterate applies function f n times on an initial value x. So if n equals 0, then that's x, and otherwise it's iterate n minus 1 f of x. And then you have the square functions that we have seen a lot of times already. So now the call iterate 1 square 3 gets rewritten as follows. We expand the body, that gives you this. We simplify the if and pick the else branch and simplify the argument here, that gives you this. We convert the square 3 call to its body, 3 times 3, and then to a value, which gives this call here. which expands in turn to another body with an if then else, where now 0 is equals 0 evaluates to true, so that would in the end give you 9. So in that sequence we always picked one particular place where we would do the next rewriting step. But in fact, rewriting could have been done elsewhere. In fact, it can be done anywhere in a term, and all rewritings which terminate lead to the same solution. That's an important result of the lambda calculus, the theory behind functional programming. It's sometimes called the Church-Rosser theorem, or the confluence theorem, that's another name. So to demonstrate that, let's take the expression that we started with here again. And we have here our sequence that we performed, so that would lead us here. But another possibility would be to say, well, let's just keep the if then else as it is and concentrate on this call first. So that expression could also have been rewritten to this expression here by going deep inside the else part and rewriting the square here to 3 times 3. So the Church-Rosser theorem or confluence theorem says that what we can do is we can then find another reduction sequence from both sides to end in the same result, 9. In other words, it doesn't really matter where you reduce first, you'll always get the same result. And that in turn tells you that time cannot matter. The sequence of operations is immaterial to the final result that you get. On the other hand, of course, time is around us in the real world. One normally describes the world as a set of objects, some of which have state that changes over the course of time. And we say an object has a state if its behavior is influenced by its history. So for instance, a bank account has a state because the answer to the question, can I withdraw 100 Swiss francs, might vary over the course of the lifetime of the account. Initially it might be false because I have no money in, then I might do a deposit, then it will be true, and if I withdraw and the account is overdrawn, then the answer might become false again. So the answer to that question depends on the previous history of operations on that account. So that was a very abstract notion what it means to have a state, namely to be influenced by one's history. But in practice, and if we disregard input-output, then every form of mutable state comes down to be constructed from variables. A variable definition in Scala is written like a value definition, but with the keyword var instead of val. So here you have a variable, here you have another one. Just like a value definition, a variable definition associates a value with a name. So if it would be just that, then the variable definitions would behave like two vals. But in the case of variable definitions, this association can be changed later through an assignment. Assignments look like in Java with a single equals sign. So you could write later x equals high, and then after that statement is executed, the variable x would have the value high and no longer ABC. Or you could write count equals count plus 1, and then after that statement took effect, the count would be 112 and no longer 111. If you look at this with the eyes of a mathematician, you might cringe a bit because the equal sign is not an equality in the traditional sense. A count can never be equal to itself plus 1. It's really an update that takes place at a point in time. So some languages actually use a different operator for assignment, not equals, but for instance colon equals, which avoids that trap to see it as an equality. I quite like colon equals, but the majority of programming languages, including C and Java and almost all others, use equals, so Scala unfortunately followed along, and now it's too late to change that. So we have to live with equals. In practice, real-world objects with state are usually represented by programming language objects that have some variable members. For instance, here is a class that models a bank account. We have class bank account, and then we have a balance, which is the current balance on the account, initially 0. And that balance is private, so that not everybody outside the account can just fiddle with the balance and maybe add some Swiss francs to it. That would be very convenient, but I believe the banks wouldn't like such a class. So there are two methods that regulate the changes in balance. There's deposit and there's withdraw. So to deposit an amount of currency, you ask, well, the amount should better be positive. You can't deposit a negative amount, and if that's the case, then the balance is augmented by the given amount. And the other method is withdraw. So to withdraw an amount of money, again, the amount should be positive and the amount should be less or equal than balance, so no overdraws allowed. In that case, balance equals balance minus amount, so deducted by amount, and you return the balance. So the result of the withdraw method is the current balance. And if the condition is not fulfilled, then you throw an error with an error message, insufficient funds. So in essence, the class bank account defines a variable balance that contains the current balance of the account. The methods deposit and withdraw change that value through assignments. Note that balance is private in the bank account class. It therefore cannot be accessed from outside the class. To create bank accounts, we use the usual notation for object creation. So bank account, open parents, close parents would create a fresh account. So here's a worksheet with bank accounts. So I have defined my class as shown. I define a new bank account and I deposit 50 units initially. I then withdraw 20 units and it responds that the balance is now 30. And I withdraw a further 20 units and it responds that the balance is now 10. And I withdraw, let's say, 15 units. And I get an error, insufficient funds. So what we've seen here is that applying the same operation, account withdraw 20, from the account twice in a row produces different results, first 30 and then 10. So clearly accounts are stateful objects. If they were stateless, that would mean that the result of withdrawal is always the same, but clearly that's not the case, so accounts have state, and that we know even without looking inside account and discovering a variable there. Mutable variables can play a useful role even in purely functional programs. For instance, remember the implementation of tail lazy list, our simplified variant of lazy lists. It used a lazy val to compute the tail operation, but instead of using a lazy val, we could also implement non-empty lazy lists using a mutable variable. So here's how that would be done. So here's the non-empty lazy list constructor, cons, creates a lazy list whose head is as given, and then it has a variable, which is private, tailopt of type option of tail lazy list of t, initialized to none. So now to take the tail of a list, it would query tailopt. If it's none, that means nobody has asked the result yet. Then the result will be computed here. So tail will compute the by name parameter, stored in tailopt, and then tail would be called recursively, which would go into the first case. So if someone had already evaluated the tail, then there's no need to evaluate it again. In this case, tailopt would return sum of x and we would return the result x directly. It's an interesting question to ask, according to our definition of statefulness as being history dependent, is the result of cons a stateful object? It's a tricky question, and I would respond with, it depends. It's not a stateful object if the rest of the program is purely functional. So to see why, let's make the argument first that it is in fact not a stateful object, that it is purely functional. That argument goes as follows. It says, well, all this tailopt does, it avoids a recomputation of the tail definition here. But in a purely functional world, tail will always return the same value, even if it's called several times. So clearly there's no point in evaluating tail several times. We can just use the cached value, and that will not change any observation that we could make from this tail lazy list. And that's true, but it's only true if the environment is purely functional. Here's a counterexample where it would be false. So we do a cons of some number, 1, and the tail of the cons would print something. So that's a side effect, and return nil, or rather lazy list empty. This should be empty. And now we do xs.tail, and we do xs.tail again. So in the first execution, what you would see is an exclamation mark. It would print something. And in the second execution, we would see nothing. So, okay, so that's an output, println, but we could turn this easily into an observable effect inside the program by essentially changing a variable instead of doing a println. The println was just essentially to demonstrate what goes on. So the morale is that if the environment can have side effects, then the tail optimization with mutable state is not purely functional, but ironically, in a purely functional world, it would be, which means there's a role for having variables essentially as caches that work very well in a purely functional architecture and that are in fact not observable in that architecture, whereas they would be observable if the architecture was not purely functional. That's something to chew on. So staying with this line of questioning, consider the following class, bank account proxy. It's a proxy of a bank account and it simply forwards its deposit and withdraw methods to the bank account that's given here. The question is, are instances of bank account proxy stateful objects? The case for no would be to say, well, there's not a variable inside, how can there be stateful objects? But of course, they can be stateful objects because bank account is a stateful object. And that means the history of the deposit and withdraw methods here will mirror the histories of those methods on the original bank account. And that means the result will depend on what happened before. So by that more abstract definition, indeed, bank account proxy is a stateful object, even though it doesn't contain any variables itself. In this session, you'll learn how the introduction of assignments affects our notions of identity and change. In fact, assignment poses new problems for deciding whether two expressions are the same. If one excludes assignments and one simply writes val x equals e and val y equals e for some expression e, then it's reasonable to assume that x and y are the same. That is to say that we could also have written val x equals e, and then instead of repeating e again, we just write val y equals x. X is the same as e, so we might as well use the value of x instead of e, or so it goes. This property that we can do these changes in confidence is usually called referential transparency. Referential transparency means that a reference, such as x, is really the same as the thing it's bound to. So it doesn't matter whether you use x or the things it's defined as, namely the expression e. It comes down to the same thing. But once we allow assignments, things become more complicated. For instance, if now we would write val x equals bank account, val y equals bank account, are x and y still the same? Well, intuitively, no, because we have created two different bank accounts. But according to our previous definition, x and y would be the same. They have the same right-hand side, so we might as well write val y equals x. So what happens here? Well, to respond to this question whether x and y are the same, we should specify what is meant by the same. The precise meaning of being the same is defined by a property called operational equivalence. In a somewhat informal way, this property is stated as follows. Suppose we have two definitions x and y. X and y are operationally equivalent if no possible test can distinguish between them. So that begs the question, what is a possible test? So let's make that concrete. To test whether two definitions x and y are the same, we must execute the definitions and then follow it by an arbitrary sequence of operations, here called S, and that can involve both x and y, and we observe the possible outcomes. Then we execute the definitions with another sequence S prime that is the same as S, but every occurrence of y is replaced by x. So instead of using y, we use x in this new sequence here. If the results are different, then the expressions x and y are certainly different. It makes a difference whether I use x or y in the sequence of operations. On the other hand, if all possible pairs of sequences S and S prime produce the same result, then I can't observe a difference, and that means I have to conclude that x and y are the same. Note that this is not a test I can do mechanically. To be sure to observe a difference, I just need a single sequence S that, when I do the renaming here, yields a different result. So that's easy. But on the other hand, to prove that two definitions are operational equivalents, I have to reason about all possible sequences of actions that follow the definitions, and there are infinitely many of those. So I can't really do that in an experimental fashion. I have to find another way to prove that. So let's see, based on these definitions, let's prove that these two bank accounts x and y are different. So let's see, based on this definition, let's see whether the expressions val x equals bank account, while y equals bank account, define values x and y that are the same. Let's follow the definitions by a test sequence. Let's say deposit 30 units into bank account x and withdraw 20 units from y. So what you will get is a result of 30 in the first case and an error insufficient funds in the second case because y was empty before the withdrawal. On the other hand, if we rename all occurrences of y in the sequence with x, then what we would get is x withdraw 20. So we would get this sequence here, and we would observe 30 after line 3 and 10 after line 4. So the final results are different, the result of this withdraw operation, and therefore we conclude that x and y are not the same. That's the proof. On the other hand, if we define val x equals bank account while y equals x, then no sequence of operations can distinguish between x and y. So x and y are the same in this case. One can do a formal proof of this statement by essentially formalizing the semantics of programming languages, but that's beyond the scope of this course. The preceding examples show that our model of computation by rewriting or by substitution cannot be used anymore. Indeed, according to the substitution model, one can always replace the name of a value by the expression that defines it. For instance, if we have these statements here, x equals bank account, while y equals x, then the x in the definition of y would be replaced by bank account. That's what the substitution model predicts. It says simplify this to a value, where an object reference is already a value, and then replace the reference by the value that you find here. So the substitution model tells us that that rewrites to that, and if you rewrite things, then they're necessarily the same. But now we have seen that this change leads in fact to a different program. So that means the substitution model clearly is no longer valid if we add assignments. It's possible to rescue the situation, to adapt the substitution model by introducing a store that essentially tracks all variable bindings that you have in your program. But then things become considerably more complicated. So we see that adding variables and mutable state to functional programming gives us additional expressive power, but we pay for this with a loss of simple semantic foundations and also with a loss of reasoning capabilities, because we have seen that the substitution model actually was used extensively in proofs about programs based on structural induction. In this session, we're going to look at a core concept of imperative programming, namely loops. In fact, our proposition is that variables are enough to model all imperative programs. So what about control statements such as loops? In fact, we can model them just using functions. For instance, here's a Scala program that uses a while loop. So it's the imperative computation of the power function, takes a double and an exponent, and then you have a loop that while the exponent is greater than 0, you multiply the value r here with x, and you decrement I by 1, and finally you return r. So in Scala, while do is a built-in construct, but we could define it also using a function. Let's call it while do. How would that work? Well, here's how we could define that function. We have while do, it would take a condition and a command. So here's an example application of while do. We would write while do x greater or 0, y equals y times y, x equals x minus 1, let's say. Something like that, assuming we have two variables y and x defined. So what that translates to is a function call for while do, with a first argument x greater than 0, and a second argument, which is the body that you see here. So these are just plain function arguments. They can be written in parents or in braces. It doesn't make a difference. So to make this call syntax work, we need a definition of while do with two parameter sections. The first has type Boolean and the second has type unit, which is essentially the uninteresting type that only has the single value open parents, closed parents. The return type of the while do is also unit. It's important to note that both the condition and the command are by name parameters because the actual arguments will need to be evaluated multiple times as we go through the loop. The body of the while then is as follows. If the condition holds, then execute the command and recursively call while do with the same condition and the same command. Otherwise terminate, that means return the unit value as a result. So quick check, is while do tail recursive? The answer is yes. It calls itself only as its last action here. So that means while do can operate with constant stack size just like a native while loop. So here's an exercise for you. Write a function implementing a repeat loop that is used as follows. Repeat until, then a command, and then a condition. It should execute command one or more times until condition is true. So let's look at the worksheet. We need to implement this function here. So it will execute command at least once. So let's do that and get it out of the way. And then we say if the condition is not true, if the condition is true, we finish. But if the condition is not true, then we will do another iteration through the loop. Else we will return the unit value. We get an error here. It says overloaded or recursive method repeat until needs return type. Yes, that's a limitation of Scala's type inference, that as soon as a method is recursive, it needs a return type. In this case, it's just unit. As a simplification, if you have an if then else returning unit values, so of type unit, then you can leave out this else unit value, so this would work just as well. So let's put it to the test. I have here this little program involving variables x and y, and we go through the loop and until x is 5, doubling y at each iteration. So what we get are the initial values, and the final value for y is 64 as expected. So here's another exercise which is optional and more open-ended. Is it also possible to obtain the following syntax, which would look more like a repeat until in a traditional language? We want to write repeat and then a command, and then we want to write until like this, and the condition should follow the until. Can we write the Scala definitions that support that calling syntax? So to find a solution, let's analyze what this desugars to. It would be repeat of the command, in parents or not, or braces, it doesn't matter. And then it would come down to a method call until, which gets the condition as additional argument. So that means we are after a repeat function that returns something that has an until method. So you see a possible solution in the worksheet. I define a repeat method which takes a by name parameter body, and it creates an object of class until, capital Until, passing it the same body. So until takes body as a by name parameter again, and it has an until method, lowercase now, which takes another condition, also by name, and its body then would say, well, if the condition doesn't hold, then go once more around the body, so execute body, and recursively call until with the same condition. So that would be a solution. In future Scala versions, to be able to write this without a warning, I should declare until infix, because otherwise it would insist on a dot in front, and to keep the sort of more traditional command syntax, I don't want that. So that's why we have an infix annotation in front of the until at the worksheet. So we've seen that we can do while loops and repeat loops credibly using just functions in Scala. What about the classical for loop of C or Java? So the classical for loop cannot be modeled simply by a higher order function. The reason is that in a Java program like this one, the argument of for contain a declaration, this one here. So that's a new declaration of I. It defines a new I inside an argument, which then is visible in the other arguments and in the body. And that wouldn't work because whatever we write as actual arguments for a function in Scala would stay there. So anything we define here, its scope would just be the first argument here, and the remainder wouldn't see that the thing we define here. However, in Scala there is a kind of for loop similar to Java's extended for loop. So what we can write is for I taken from 1 to 3, do system.out.print and then the value of I. So a for loop like this is very similar to a for expression that you have seen already, except that where we have yield in a for expression, we have do in a for loop. Like for expressions, for loops also translate into combinations of higher order functions, but instead of a map and flat map, they translate into the function for each. For each is defined on collections with elements of type t, as you see here. So for each takes a function that maps t to unit and returns unit, and what it does is it applies the given function to each element of the collection. So for instance, this for expression for I taken from 1 until 3, j taken from the string abc, do println I and then g, that would translate to 1 until 3, the range, dot for each I, abc, the string, dot for each j, and then println the body that we have seen up here. This session will be all about an extended example program dealing with discrete event simulation of digital circuits. This example will show interesting ways how one can combine assignments and higher order functions. Our task will be to construct a digital circuit simulator. There are a number of things that we need to do. We need to define a way to specify digital circuits. We need to define a way to how to run simulations, and then we have to put everything together so that the circuits can actually drive the simulator. This is also a great example that shows how to build programs that do discrete event simulation. So we start with a small description language for digital circuits. A digital circuit is composed of wires and of functional components. Wires transport signals and components transform signals. We represent signals using booleans true and false. So it's a digital circuit simulator, not an analog one. A signal is either true or false, and but not something in between. The base components are also called gates. They are the inverter, whose output is the inverse of its input, the AND gate, whose output is the conjunction, logical AND of its inputs, and the OR gate, whose output is the disjunction, logical OR of its inputs. Once we have these three, we can construct the other components by combining the base components. One thing important for the simulation is that the components have a reaction time or a delay. That means their outputs don't change immediately after a change in their inputs. Logical gates are usually drawn with standard symbols. So this would be an AND gate, this would be an OR gate, and this would be an inverter. We can use the basic gates to build more complicated structures. For instance, here we have created a half adder. The half adder takes two inputs, A and B, and then it has two outputs, the sum and the carry. The carry is set if both A and B are set. So we have a logical AND gate that goes into the carry output. The sum is set if either A or B is set. We have an OR gate here, and the carry is not set. So we have an inverter here, so that one is set if the carry is false, and here we have an AND gate, so the sum is true only if either A or B is true and carry is false. Once we have defined a circuit like a half adder, we can use it in turn to define more complicated circuits. For instance, we can use two half adders to define a full adder. So what we do here is we first have a half adder that adds B and C in, producing a carry here and a sum here. We take the sum and add A, so with another half adder. So the final sum is the sum of the whole full adder, and the output carry is then the logical OR of the carries of the two half adders that you see here. So our next question is, how do we put that in code? What we have to do is essentially find code representations for these three basic circuit diagrams so that they can be composed to give you half adders, full adders, and any other components you might wish to construct. So our basic language then consists of the three gates here plus the wires. So a wire is needed to connect gates. And here it should be noted that a wire doesn't necessarily have two ends. Essentially any network that has the same current electrically counts as a wire. So for instance, the A wire would be not just this line here, but it would also, that would be part of the A wire. And the C wire would consequently be the whole network that you see here. So these colored things are wires, and then we have gates that connect the wires. That's the basic situation. You see also that these circuits are not necessarily hierarchical. They're potentially complex networks of components connected by wires. The way we're going to represent that is that we are going to have a class for wires, and then we have a model where essentially we drop a gate, a component, onto a circuit board, connecting it with the wires that are there. So essentially our idea to construct a circuit is based on side effects. You can think of it as essentially you have a circuit board, you have some wires, and then essentially you put the gates as an action onto this board and connect them with the wires. That's the mental model that we are going to pursue. So to start, we need a class wire to model wires. So wires can then be constructed as follows. We can say A equals a new wire, B is a new wire, C is a new wire. Or Scala allows you to shorten that. You can just write val ABC equals wire. That means each of these three names will get the same right-hand side, namely create a new wire. And then we need functions that create the base components as a side effect. We drop them on the board. So inverter says place an inverter between the input wire here and the output wire there. AND gate says place an AND gate between the two inputs here and the output there. And OR gate says create an OR gate with those two inputs and the output. All three methods have unit as the result type. That means they act only as a side effect by essentially connecting themselves to the wires. They don't return anything interesting. Starting with these basic elements, wires and three kinds of gates, we can construct more complex components. For instance, here's how we can define a half adder. So it says we have 4 wires, A, B, S, and C. We create some internal wires which we're going to use later. We place an OR gate between A, B, and D. So that would be an OR gate here, and that would be D. We place an AND gate between A, B, and C. So that would be my AND gate here, and that would be C. I can connect that already. We place an inverter between C and E. So that would be E now. And we place an AND gate between D, E, and S. Okay, and that's an AND gate, not an OR gate. Okay, and that's my half adder. So I define a method, which means I draw a box around it. And now I can use this thing as its separate component. So now I can start to drop half adders on my circuit board and connect them to further wires. So here's how you would do a full adder. It takes 3 input wires, 2 output wires, has 3 internal wires, and you place 2 half adders on the board, connected as you see here, and an OR gate for the 2 output carries that gives you the final Cout signal. I invite you to do that yourself, for just following these instructions and verifying that you will get the full adder that we've seen some slides ago. So here's an exercise for you. What logical function does this program describe? There's a function f, our mystery function, that takes two input wires A and B and has an output wire C. And here are its internal workings. What's the logical function that gives? Is it one of these six that you see here below? So one way to solve this puzzle is to look at these gates as describing logical formulas. For instance, this inverter here would define the signal D to be not A. Similarly, E equals not B. Then F is A and E, so F is A and not B. G is B and not A. And the final result C is F or G. So the final result is true if either A is true and B is false, or B is true and A is false. Which means to say that the final result is true if A and B are different signals. So that's the answer to our puzzle. Okay, let's proceed to an implementation of all this. So the class wire and the functions inverter, AND gate, and OR gate represent a small description language for digital circuits. We now need an implementation of this class and these methods to allow us to simulate circuits. So to be able to do this, we first have to clarify how do we do simulation? What interface do we have to run a simulation? So what we do next is develop a simple API for discrete event simulation. So a discrete event simulator performs actions that are specified by the user to be performed at a given moment. And an action is a function that doesn't take any parameters and which returns unit. So an action is really just something that lives for the action, the side effect that it performs. And the time when an action is performed is simulated. It has nothing to do with the actual time. So there's an internal timekeeping unit that essentially advances the time as the simulation progresses. So the way we'll set it up is that a concrete simulation will be inside an object that inherits from the trait simulation. And the trait simulation has the following signature of methods and members that we can use in our simulation object. So first there's the current time, which is the simulated time. So that's the current time in our simulation. Then there's a method after delay that registers an action to be performed after a certain delay relative to the current time. So we say after delay n units, run this block of statements. So what this does is it essentially stores this block to be run once the simulation has reached the time that's specified by current time plus delay. But after delay doesn't run the simulation by itself. That's done by a separate method called run. So run essentially says, well, the actions that are now stored for the simulation, they should be performed at this point. Before going into details, I want to show you the outline of the different components that we are going to assemble. So at the very top is the simulation trait, and that will be inherited by essentially our structure that defines the basic gates. Gates need simulation because it's in the end them that will be simulated. And then from gates we will have another trait called circuits that contains things like half adders, full adders, or other circuits that a user might want to define. So here we're sort of up here, that's essentially the system provides the simulation package and it provides the basic gates. When we define circuits, then maybe some of them are provided by the system and others could be provided by the user. So we could also have several classes here that essentially define different libraries of circuits. In our example, we just need a single one. And then finally we will have an object, call it simulator, which is the concrete simulation. So the concrete simulation essentially defines a test circuit that we now want to run and simulate. So we have already shown the circuits layer when we defined half adders and full adders. So that showed how to define these circuits. What we still need to do is we need to fill in the blanks for the gates class. What do inverter and AND gate, OR gate actually do and how is wire defined? And we have to fill in the simulation class to implement the API that we have defined. So let's turn next to gates. And in gates, let's turn to wire. So a wire must support three basic operations. The simulation might want to know what is the current signal on the wire. Is it true or false? It might want to set the signal of a wire as an action, so that would modify the value of the signal transported by the wire. And the third basic operation, add action, allows the simulation to customize what should happen when the signal of a wire changes. We can add an action, we can attach that to the actions of a wire, and all of these attached actions are executed at each change of the transported signal. So basically we register an action to say perform this action when the signal of the wire changes. So here's an implementation of class wire. Internally, a wire would have a signal value. Initially it's false, so no current, and that's private, so you can't access it from the outside. And the other piece of state in a wire is the list of actions that are currently attached to the wire. Initially, that's the empty list. Now here are the three methods. GetSignal simply returns the current signal value. So the setSignal operation sets the current signal value to the signal S, and it also executes all the stored actions if the signal value changes. So this line here, it's maybe a bit cryptic, so let's analyze what this is. It does a for each on all the actions, and what does it do? Well, it calls the action with the empty parameter list. So that's what that does. You could write this also a bit more expansive to say for A taken from actions, do execute the action A. That's probably a bit clearer. The last operation, add action, simply adds the given action to the list of actions on the front, and then it immediately calls the action. So why is that? Well, you can think of the circuit initially to be in an undefined state. So when I said signal value equals false, I really should have said undefined. So once we have an action, essentially we immediately execute it to essentially force the signal to be defined, namely to be the output value of that action. So once we have wires, we can now proceed to define the basic gates. So let's start with inverter. We implement an inverter by installing an action on its input wire. So we have here input add action, invert action. And what does invert action do? Well, it will sample the signal on the input wire and set the output to be the negation, the NOT of the input signal. That's what inversion means. But it will do so not immediately, but only after the inverter delay that we still have to specify. So to summarize, we've said before that in placing an inverter on the board essentially produces a side effect. What the side effect is to add the invert action to the set of actions on the input wire. If we now look at AND gate, it's implemented in a very similar way. So again, the AND gate function here has a side effect, and the side effect is to add the AND action on its two input wires in 1 and in 2. So what is AND action? Well, we get the signal from the two input wires here and here, and then we set the output signal to be the AND of the two input signals. And we do so only after a delay, namely AND gate delay. So this action will be registered in the simulation to take place at a point in time, AND gate delay from the current time that is now. And the OR gate is now implemented quite analogously. So again, it adds an action to its input wires. That's the OR action. And the OR action that simply would take the disjunction, the OR of the two input signals, and do so after OR gate delay. So here's a question to you to see whether you follow. What would happen if we compute in 1sig and in 2sig directly inside the after delay, as you see here? So I don't bother to define them as two vals in front. I just essentially inline them here and here, as you see there. Would that give us the same behavior? Or would the behavior be different, and in this case OR gate 2 would not model the OR gate faithfully? And the answer is, of course, that would be something different. So here we get the signal at the current simulated time. That's just the get signal. And then we wait OR gate delays, and then we set the output signal. Whereas in the modified program, we again wait OR gate delay units, but we set the output signal to the disjunction of the input signals at this point in the future. And of course, at this point in the future, something else might already have happened. So this is not a faithful model of an OR gate. So let's see where we are in the worksheet. So I have here my simulation trait, which is still empty. I have my gates trait, which is again empty. I just have the class wire and the 3 methods. And I have the delays that are also defined here. And finally, I have circuits, and there I've already added half adder and full adder. I just need the interface of the gates class, and that interface is provided. It's just the implementation that is still missing. So what we've done then is we have implemented the class wire, as you see here. We have implemented the inverter, as you see here. And we have implemented AND gate and OR gate. So what we have to do next is flesh out the simulation trait. So the idea is to keep in every instance of the simulation trait an agenda of actions to perform. An agenda is simply a list of events, and each event is composed of an action and the time when the action must be executed, must be produced. The time is simulated time, as we said before. The agenda is sorted in such a way that the actions to be performed first are in the beginning of the agenda. So agenda is a list of events, and here is our agenda, which is initially nil. There's also a private variable, call it current time or code time, that contains the current simulation time. An application of the after delay method with some delay and some block given inserts the task event to be produced at current time plus delay to consist of the actions in block into the agenda at the right position. So here's after delay. We produce the right event here, and we insert it into the agenda. Insertion function is straightforward, so that's essentially just what we did when we did sorting as well. So we just go through the agenda. If the time of the first item in the agenda is less or equal to the time of the item that we want to insert, then we insert in the tail of the agenda, and otherwise we put the item at the top of the agenda and follow it with the previous agenda. So once we have an agenda, we need to execute it. That's done in an event handling loop. The event handling loop removes successive elements from the agenda and performs the associated actions. So here's an implementation of the event loop. It does a pattern match on agenda. As long as the agenda is non-empty, it executes the first item on the agenda and it recursively calls itself. If the agenda is empty, it terminates. What does it mean to execute the first item of the agenda? Well, we strip off the item from the agenda, so the agenda now becomes the rest here. It sets the current time to the time stored in the first entry, and it performs the action of the first event at this time, at this simulated time. Quick check whether the loop function is tail recursive. Yes, indeed, it calls itself as last action. That's important because, of course, the agendas for simulations might become quite long. So now finally, the run method. Run method simply calls loop after it prints essentially a header. It installs a first action after delay 0 that says simulation has started and here's the current time. So it puts that at the front of the agenda and executes loop. One question for you: does every simulation terminate after a finite number of steps? At first glance it might seem so, since loop just goes through the agenda left to right until the agenda is nil. However, remember that actions that are performed here can install further actions in the agenda through after delay. And that means that, in fact, we might never finish the simulation because every action will install one or more further actions in the agenda, and the agenda could even grow without bounds if every action installs more than one action into the agenda. So time to try it out. But before we can launch the simulation, we still need a way to examine the changes of the signals on the wires. So far it's a black box. Something happens, but we don't know what. So to this end, we define another function called probe. So probe is essentially you have a wire, and then you have a pair of pliers. I'm very bad at drawing. And then an old-fashioned oscilloscope or something like that. That would tell you what goes on in these wires. So that's what a probe is. So a probe gets attached to this wire here, and it has a name because we are actually going to print out the signal of the wire just rather than showing it as a curve like here. So what we want to print is the probe action says print the name of the wire, print the current time, and print the current value of that wire. And every time the signal on the wire changes, this probe action will be executed because we have added probe action as an action to that wire. I have added all these implementations to the worksheet. Here's probe, so that's the last thing I've added here. So it's time to set up a simulation. To set up a simulation, we define an object sim, and that extends essentially the circuits that we want to simulate. Then we get an error and says, okay, so there are three things that I haven't defined yet. Indeed, those were the methods inverter delay, AND gate delay, and OR gate delay. I could define them right here, but that wouldn't be very systematic because when we define a library of gates, then we don't really want to fix these delays at this point. The delays of these gates is technology dependent. With a new generation of silicon, it might be different. So we want to define them somewhere else, further towards the actual simulation class. So what we do instead is we create a separate trait for the delays, which you see here. So essentially our simulation object extends circuits and delays, so it gets the circuits from one part and the delays from another. And here are the delays that I have defined just to do an example. So if I look at my class diagram again, I have the classes simulation, gates, circuits, and my concrete simulation, and the concrete simulation now also inherits from a trait that fixes the technology-dependent delays. So here's a sample simulation that we're going to do in the worksheet. We define 4 wires and place some probes. So 2 input wires, a sum and a carry wire, and we want to place the probes on the sum and the carry. Next, we want to define a half adder using these wires. So we place a half adder between input 1, input 2, sum and carry. Now we want to give the value true to input 1 and launch the simulation. So let's set up the simulation like this. I have the wires, I have the probes and the half adder. In order to do this without prefixing, I've just imported the simulation object, so that way I have access to everything that's defined in here. So we get the initial values of sum and carry, which are both 0. Now to do something, let's change the symbol of one of the inputs and run the simulation. So it says simulation started and not more, but if we hover over it, then we will see, okay, the sum probe gave us at time 8 a new value true. So after 8 simulated units, the sum signal went to true. What we could do now is we could also set a signal for input 2 and run again. And what we see now is that the carry and sum signals have changed. The carry signal at simulated time 11 became true, and the sum signal at simulated time 16 became false again. So that just shows that the basic of simulations work as expected. I invite you to define more circuits and have more simulation runs to play with it. So, in fact, logically speaking, we wouldn't have needed 3 gates, since, for instance, the OR gate can be defined in terms of AND or INF. So an alternative for the OR gate would be to define it as a circuit. That would then correspond to this circuit here, where we first put an inverter here and an inverter there. And then we have an AND gate of the negated symbols, and then we put a final inverter on the result wire. That's of course just a consequence of the formula that A or B is the same as not A and not B. So that's the circuit that we have drawn here. So question to you, what would change in the circuit simulation if the implementation of OR gate out that you have just seen was used for OR? Would it be nothing? The two simulations behave the same? Or would the simulations produce the same events, but the indicated times are different? Or would the times be different and OR gate out might also produce additional events? Or would the two simulations produce different events altogether? What do you think? So clearly the timings would be different in general. If we take our current example values, then an inverter delay would be 2 and an AND gate delay would be 3. So you would get a total delay of 7, whereas an OR gate delay in our example values had a delay of 5. So that would give you different times. And you might think that's it, so it would be number 2. But if you have actually tried this in the worksheet, then you will actually see something else. The times are different, and OR gate out might also produce additional events. So to demonstrate, I have plugged in the new version of the OR gate in the worksheet. And now we have the run here, where we get for the first run at time number 5 the value is true, and then at 10 the value is first false and then true again. So that looks at first really mysterious. To explain the mystery, let's have another look at this diagram again. So what we have here is essentially not a single event as in the OR gate, where essentially we have a single action to be produced, but we have multiple actions. We have the two invert actions and the AND action and then the final invert actions. So we get many more actions in our agenda that also will be executed sometimes at the same time. And when you have several items in the agenda that are executed at the same time, you can essentially get interleavings. So you can have some things that happen at some moment before something else happened. And that was essentially here what we observed, that at time 10 you got one item in the agenda that just decided that the signal should be false, and at the same time you got another item that put the signal back to true. So essentially it's the fact that you have instead of a single item in the agenda, you have multiple items which are not executed atomically as a whole. They get interspersed with each other, and that causes this fluttering behavior where you see events that you didn't see before. So to summarize, state and assignments make our mental model of computation more complicated, in particular because we lose referential transparency. On the other hand, assignments allow us to formulate certain programs in an elegant way. An example that we saw was discrete event simulation. Here a system is represented by a mutable list of actions, and the effect of actions when they're called are to change the state of objects and also to install other actions to be executed in the future. As always, the choice between functional and imperative programming must be made depending on the situation. The digital circuit simulation was a good example for a mixture of functional and imperative programming for essentially two reasons. One reason is that the non-hierarchical nature of circuit networks lends itself well to an imperative formulation where we essentially place gates and circuits between wires. The other reason is that we simulated a real-world system where things change with a system where the internal state also changes, so this is quite natural. In this final week of the course, we cover functional reactive programming. You'll find out how functional reactive programming shifts the focus from singular events to time-varying signals. This lets us express in a purely functional way event-based programs that are traditionally expressed with imperative state changes. To be sure, our implementation of functional reactive programming also uses internal state. But that state is now encapsulated, so it does not impair the reasoning one can do about the functional surface language. In this session, we're reviewing the observer pattern, which is the standard imperative way to do event handling. The observer pattern is widely used when views need to react to changes in a model. Variants of it are also called publish-subscribe or model view controller. So here we have a model, which is some stateful object or set of objects. And then we have views that show some aspect of the model, and the model typically doesn't know how views are implemented or how many they are, and the views can also change dynamically in number. So the task then is, whenever the model gets updated, all the views have to be notified so that they can update themselves as well. So a typical scheme to do this is to declare the model to be a publisher, and the views would be subscribers. So a subscriber contacts the publisher to say, I want to be notified of any updates, and when there are updates, a publisher will essentially notify all the subscribers of these updates. So here's an implementation of this principle in Scala. We have two traits, subscriber and publisher. So subscriber is the base traits of all views, and they offer a handler method that will be called by the publisher whenever there's a state change in the publisher. And then the trait publisher maintains a set of subscribers, here in this private variable. A subscribe method would add a subscriber to the set. An unsubscribe method called from a subscriber would remove the subscriber from the set. And finally, the publish method would go through all subscribers and for each subscriber call the handler method that the subscriber has defined here. And the publisher passes itself along as the publisher here. So that means the subscriber could actually subscribe to several publishers, and when handler is called, it would know what publisher pushed the change from this parameter here. Okay, so once we have that, we can make bank account a publisher. That means that one can subscribe to a bank account to be notified of any changes in that account. So bank account now extends publisher. And what else do we have to do? Well, essentially three things. First is any state change in deposit or withdraw has to call the publish method here and here. So that way all subscribers are notified. Second, when a subscriber is notified, they would like to find out what the current balance on the account is now, because it typically wasn't them to have done a deposit or withdraw method, so they don't know. So we will add another method, current balance, that just returns the current balance without depositing or withdrawing anything. That's all the changes that we needed to do. So let's use this model to define a subscriber. One example of a subscriber I call here a consolidator. Let's say you have a list of bank accounts, and we want to know at each point the balance, the total balance over all these accounts. So whenever one of these bank accounts changes, then the consolidator should be notified about the change, and it should recompute the total balance. So consolidator is a subscriber, and as part of its initialization, it will subscribe to each of the bank accounts in observed. So for each of the bank accounts, it will add itself as a subscriber. Then we have the variable total, which reflects the total balance in all the accounts in observed. That variable is initialized by the call to compute that follows immediately. Here's the definition of compute. It sets total to the sum of the current balances of all accounts in observed. Observed map current balance sum. So compute is called once when we start the consolidator, but it will also be called each time one of the accounts changes. That's done by calling compute from handler. So if one of the accounts changes, it will publish the change by calling handler, and that will recompute the total balance. And finally, the total balance method here is simply a public interface to this private variable, total. So there's one little syntax twist here. It's this equals underscore. What does that mean? Well, if I would leave out equals underscore like this, then what I would get is not an uninitialized variable, but an abstract variable. That's basically a variable that only has a way to get the variable and to store the variable, but it's not backed by a field. The variable would have to be implemented in a subclass. So to have a variable where I just say, well, I choose to not initialize the variable here because it will be initialized later, I write equals underscore. That means don't initialize total yet. So that concludes our example. Let's review what we have seen. The good thing about the observer pattern is that it manages to decouple views from state. The views are quite different from the state in the model. It allows us to have a varying numbers of views of a given state, and it was actually quite simple to set up. It's fairly easy to turn a thing like a bank account or another stateful object into a publisher. The downsides of this pattern are, first, that it forces an imperative style, since handlers are unit type, so a handler never returns anything. It can't because it's called from the publisher, so everything a handler does, it has to do with a side effect. There are quite a lot of moving parts that need to be coordinated. In particular, subscribers are fairly complex classes. A third downside is that the observer pattern, as we've seen it here, really works well only in a single-threaded model. Once we add concurrent execution, things get a lot more complicated. If I look back at the consolidator, what could happen in a concurrent execution is that several handlers will be called in parallel at the same time, maybe. And that means the consolidator has to protect itself from race conditions. Of course, that can be done. We can make it a monitor with synchronized and so on. But it's additional steps that we have to do, and those steps have additional downsides, like they might produce deadlocks or other unwanted effects in concurrency. So observers in a concurrent scenario are hairy. And the fourth downside might be that views are still tightly bound to one state, to one model, where the view update happens immediately. So these issues are actually quite relevant because the observer pattern is not a little niche thing. For instance, if we look at Adobe, which is the producer of Photoshop with which this recording was made, and also of PDF, then we learn that 1/3 of the code in their desktop applications is devoted to event handling. So 1/3 of all code of a pretty humongous code base. And furthermore, 1/2 of the bugs are found in this code. So not only is it a lot of code, but it's code that tends to be more difficult and more buggy than the rest. So can we do better? The answer is yeah, maybe. In the next sessions, we'll explore a different way, namely functional reactive programming. And that can improve on the imperative view of reactive programming that's embodied in the observer pattern. In this session, you'll learn about a functional way to do event handling called functional reactive programming. So what is functional reactive programming, or FRP, to which it is often abbreviated? Well, if you just talk about reactive programming, it's about reacting to sequences of events that happen in time. And the functional view of this is, in a nutshell, to aggregate an event sequence into a signal. So a signal is a value that changes over time. But we are no longer looking at the individual events as they fire, we're looking at the signal as a whole. So an abstract view of a signal is to say it's a function from time to the value domain. And once we have that, we can replace propagating updates to mutable state by defining new signals in terms of existing ones. So instead of having the individual events and their updates, we see the signals as a whole. So let's make this concrete with an example. Let's say you have a mouse that moves around the surface. The event-based imperative view would be that whenever the mouse moves, you get an event that says mouse moved and the new position where it is now. By contrast, the FRP view of that would be to say, well, we represent this curve as a signal from time to the current mouse position. So it's a function from time to points in a two-dimensional space that you see here. So how was this change in viewpoint invented? Well, FRP really started in 1997 with the paper Functional Reactive Animation by Connell Elliott and Paul Hudak, and they also published a library to go with it, which was called Fran. That was very influential. There have been many FRP systems since, both standalone languages and embedded libraries. Some popular examples today are Flapjacks, Elm, React.js, or also React Native. So a lot of the event propagation on JavaScript frameworks is now done in a functional reactive way using React.js, for instance. There's another branch of reactive programming, which is essentially data flow programming systems based on event streaming. An example is RX. Those are related, but the term FRP is not commonly used for them. We'll use FRP by means of a minimal class, which we define ourselves and whose implementation is explained at the end of this module. This implementation is modeled after a system called Scala React, which is described in the paper deprecating the observer pattern. So what can we do with a signal? There are two fundamental operations. The first operation is to obtain the value of the signal at the current time. So if signals are functions, then obtaining the value of a signal at a current time is function application. In our library, this is consequently expressed by just writing function application like this. So the current time is implicit. So mouse position, open parents, close parents would say the mouse position at the current time. And the second fundamental operation is to define a signal in terms of other signals. In our library, this is expressed with the signal constructor. So for instance, we could define a signal in rectangle that says is a position in the rectangle given by the lower left and upper right corners. That's a signal that gets the mouse position at this point in time, and it then asks whether the position is between LL and UR. So that can be visualized like this. So now you have, from this original signal, you have the bounding box between LL and UR. And your new signal would be a function in time that goes essentially like this. First, it's not in the bounding box, it's false. Then it's true. And then after some time, it's again false. So this would be true. This would be false. So you see, we can transform one signal into another using the signal constructor. So it's worthwhile taking a step back and see what we've done here. Here's the in rectangle function that we would define normally without functional reactive programming. So it's just the body of the signal here, and it returns a Boolean. Now, that means that every time we call in rectangle, it will tell us whether the current mouse position is between LL and UR. Contrast that with a new definition of is in rectangle that returns a signal of Boolean. That in rectangle creates a signal that at any point of time is equal to the test whether mouse position at that point in time is in the box LL or UR. So that means if we want to write, if we write, let's say val B equals in rectangle, some corners L and R, then that will give us a Boolean result B that reflects whether at the time when we evaluated this call, the current mouse position was between L and R. And the result will stay the same forever afterwards. Whereas for the signal version, if we set it up like this, val signal equals in rectangle LR, so that would give us a signal which we can query its arbitrary times in the future, and each time we query the signal, it might give us a different result, depending on the mouse position at the time when we query the signal. The signal syntax can also be used to define a signal that has always the same value, so that's a constant signal. For instance, val sig equals signal 3 is a signal that is always 3. So the idea of functional reactive programming to see signals as essentially time-varying functions is quite general. It doesn't prescribe whether signals are continuous or discrete, and also it doesn't prescribe how a signal is evaluated. We could think of several possibilities to evaluate a signal. One way would be to evaluate it on demand, to store the signal as essentially a formula, and every time its value is needed, we evaluate it. Another idea is to sample a signal that's continuous at a fixed or varying time interval at certain points and to interpolate in between. Or if the signal is discrete, we could also update it internally and propagate the updated value automatically to dependent signals. That last possibility is in a sense the functional analog to the observer pattern, and that's what we will pursue in the rest of this session. How do we define a signal that varies in time? The possibility we've seen so far was to take an externally defined signal such as mouse position and then map over them. That means define derived signals in terms of mouse position. So since mouse positions varies over time, so do the derived signals. Or we can do that internally using a signal.var. So expressions of type signal cannot be updated, but our library also defines a subclass var inside signal, so signal.var, for signals that can be changed. Signal.var provides an update operation which allows to redefine the value of a signal from the current time on. So for instance, we could set up a signal like this. It's a signal.var3. So it is at this point in the computation always 3. But at some later point we could say sig update 5. And that means from that point on the signal would return 5 instead of 3. In fact, we can make this somewhat nicer by using Scala's special update syntax. In Scala, calls to update can be written as assignments. You might have seen this already when you worked with arrays. For instance, for an array R, we can write R of I equals 0. In case you wondered what that is, it's actually translated to r.update I 0. So it's really a call of an update method on an array. This update method can be thought of as you see here. So it's in class array. The update method takes an index and a value, and it would then set the element of the array at that index to the new value. So there's a general rule in Scala that enables it. The rule is that if you have an assignment like this one here, so on the left-hand side you have something that looks like a function call and then an equals and then the right-hand side, then that's translated to an update method on the F here with all indices and then the right-hand side as arguments. And that works also if n equals 0. So if n equals 0, then that means that f open parens close parens equals e is a shorthand for f.update e. So because of that, we can also write instead of sig.update 5, sig open parens close parens equals 5. Which is quite nice because we say, okay, sig is the current value of signal, and then sig update equals 5 would mean the current value of signal after this assignment will be 5. So in both cases you can read sig open parens close parens as current value of signal sig. So now you might wonder, how does a signal var differ from a regular var? These signal variables look a bit like mutable variables, where sig open parens close parens is simply dereferencing, and that would be assignment. But there's a crucial difference. We can apply functions to signals, which gives us a relation between two signals that's maintained automatically at all future points in time. No such mechanism exists for mutable variables. We have to propagate all updates manually. So to illustrate the difference, I'm going to write down the same sequence of operations, once for regular variables and once for signal vars. So here's a list of operations. I define a variable x to be 1. I define a variable y to be x times 2. And then I set x to 3. Now I do the same thing with signal vars. So the analog here would be I define a signal, which is a signal var 1. I define another signal y, which is the signal that is x times 2. And I update the signal var to be 3. What is the value of y at the end in each case? So here we would have clearly y equals 2. And here we would have the dereferenced y is 6, because the variable x is now the signal 3, and y always maintains its relationship with that signal to be x times 2. So that nicely demonstrates the difference between regular variables and signal vars. Okay, let's do an exercise. Let's repeat the bank account example of the last session, but with signals. That means we want to add a signal balance to bank accounts, and then instead of having the consolidated subscriber, we want to define a function consolidated, which produces the sum of all balances of a given list of accounts as a signal. So the interesting question then is whether there were any savings compared to the publish subscribe implementation. So here we have entered the previous non-reactive bank account, so it's just an imperative object with a private variable myBalance, and the only thing I've done compared to the previous versions of bank accounts is that I have added a method balance that allows to inquire what the current balance is. But otherwise it's still the same as before. Deposits something into the account, returns a unit, withdraws something. Now what we want to do now is turn balance into a signal. So it should be signal int. And that means my balance would also be a signal, and it should be a variable signal. So we don't need a var here at the outside, but it will be a signal.var of int. And that's initialized to 0. So we can roll the type and the initializer into 1 and write that. Okay, so now what we have to do is that at each point when we want to know the current value of a signal like balance and myBalance, we have to dereference it. So when we inquire what is the current value of myBalance, we need the parents here. And if we update myBalance, we need the parents here. Same thing would hold here. So here's an inquiry, put the parents. Here is an update and an inquiry. And finally, we return the current value of myBalance. Okay, so let's do the next step then and define the consolidated method. Here is its signature. It takes a list of accounts and gives us back a signal int that at any point in time tells us what the total balance of the accounts is. So to implement consolidated, what we need to do is define a signal where we go through all the accounts, take the balance of each, or it would be a map, and take the sum of the results. So we can test this by setting up, let's say, 2 bank accounts and forming the consolidated bank total in the C signal and asking what the signal is. So that gives us 2 bank accounts, a signal, and that signal is initially 0 because all the bank accounts are 0. So let's deposit something into account A and ask what the signal is. So it's 10. Let's deposit something into account B. Sorry, B. So now the total is 30. Let's withdraw something from account A. And we get an error. So what does the error say? It says assertion failed, cyclic signal definition at the line 74 is when we last called it. So at this point here. So why would we get a cyclic signal definition when we write something like this? In fact, our error was that we overlooked an important difference between the variable assignments such as v equals v plus 1 and a signal update as parents equals as parents plus 1. The first makes sense, but the second doesn't. In the first case, what happens is that the new value of v becomes the old value of v plus 1. But in the second case, what we did here is we tried to define a signal s so that all points in time from this assignment on, s is 1 larger than itself. And that obviously makes no sense. It is indeed a cyclic signal definition. The definition of the signal depends on itself, and that's of course forbidden. So how do we fix this? Well, we do the same what we have already done in the deposit method. We get the value of the signal beforehand, and then we use that value in the subtraction. So what we see now, the sequence of action is, okay, let B be the signal my balance at this current point in time only, not all future points in time, and now define the next value of my balance at all following points in time to be B minus amount. So now it makes sense. Let's see what consolidated says. Yes, it gives us the right value after the withdrawal. So here's another exercise for you. Consider the two code fragments here and here. They look very similar. Are they in fact the same? In particular, do they yield the same final value for twice parents? Yes or no? Well, let's see, what are the differences? The differences are here. Num is a val, and whereas here it is a var. And furthermore, here I did a signal update. Num equals 2, and here I defined the variable number to be a new signal 2. What is the value of twice after each of these sequences? After the first sequence, the value of twice will be the value of num times 2. That's the relationship that we have established. And the value of num at this point will be 2. So we will have twice equals 4. After the second sequence, however, the value of twice will still be 2. Why? Well, because twice is linked to this first signal. What we have done in the second case is we have defined a signal var with value 1 and called it num. So num is a reference that points to the signal var. And then we have defined twice to be num times 2, so it's that signal var. So twice would be the signal var of the num signal times 2, where the num signal really points to this one here. So we said whatever that signal is, the twice signal is that signal times 2. But what we have done here in the last statement is we have now defined num to be a new signal var that is initialized to 2. So num now refers to this different signal, but the link between twice is established to the signal that num referred to previously. So twice is still 2, even though num points to a new signal which has nothing to do with what happens over here. So the answer to the question is no.